For more than a century, copper has quietly powered the modern world. Every major electrical grid, every data center, every factory, and nearly every computer has relied on copper to move electricity and information from one place to another. It became so essential that most people never stopped to question it. Copper was simply the material everything depended on. But today, something unexpected is happening. As artificial intelligence grows at an incredible pace, the technology that carried us into the digital age is beginning to show its limits. AI systems are becoming so powerful that moving data between thousands of processors has become almost as difficult as performing the calculations themselves. In many of the world's largest AI data centers, chips spend valuable time waiting for information instead of processing it. The processors are getting faster every year, but the connections between them are struggling to keep up. That has created one of the biggest engineering challenges of the AI era. Now, researchers and technology companies around the world are racing to solve it, and one country has been making an unusually large number of breakthroughs in exactly this area: China. Over the past few years, Chinese researchers have announced advances in optical networking, air-filled fiber, glass-based communication systems, photonic chips, and ultra-high-speed data transmission. While each announcement may seem unrelated on its own, together they point towards something much larger. Instead of asking how to make copper better, they're asking a completely different question. What if the future doesn't need copper at all? It sounds almost impossible. Copper has been one of civilization's most important industrial materials for generations. From power plants to smartphones, from electric vehicles to internet cables, it exists almost everywhere. Replacing it would require rethinking some of the most important technologies on Earth. Yet AI may be forcing exactly that transformation. The reason is surprisingly simple. Artificial intelligence doesn't just need faster processors. It needs those processors to communicate with each other almost instantly. Imagine trying to have a conversation with 10,000 people at the same time. Even if everyone could think incredibly fast, the discussion would still slow down if messages couldn't move quickly between them. The same thing happens inside AI supercomputers. Modern systems may contain thousands or even tens of thousands of advanced processors, working together as one enormous machine. Every second, those processors exchange enormous amounts of information. If the communication network can't keep up, the entire system becomes less efficient. For years, engineers have improved copper cables by making them faster, reducing electrical interference, and designing increasingly advanced connection technologies. But every improvement also introduces new challenges. Electrical signals generate heat. Higher speeds consume more power. Longer distances weaken the signal, requiring additional equipment to restore it before the information can continue traveling. As AI systems become larger, these problems grow exponentially. That's why many engineers now believe the next revolution won't come from faster processors alone. It will come from changing the way data moves. Instead of relying entirely on electricity flowing through copper, future systems may increasingly send information as pulses of light. Unlike electrical signals, light can travel enormous distances with extremely low loss. Optical communication also produces less heat and can carry significantly more information at the same time. For decades, fiber optic cables have already connected cities and continents using light instead of electricity. Now, researchers want to bring that same concept inside AI computers themselves. Rather than connecting processors with copper traces and electrical cables, future AI systems could increasingly use optical connections that move information using photons instead of electrons. That idea has become one of the hottest areas of research in modern computing, and this is where China's recent announcements begin to make more sense. Over the past several years, Chinese universities, telecommunications companies, and semiconductor researchers have repeatedly demonstrated new technologies involving optical communication. Some projects focused on photonic processors, others explored glass-based chips, some demonstrated record-breaking fiber transmission speeds, while others introduced entirely new networking techniques designed specifically for artificial intelligence workloads. Recently, Chinese researchers also reported transmitting data through air-filled optical fiber at extremely high speeds across long distances without traditional repeaters. While the technical details differ from project to project, the underlying direction remains remarkably consistent. Move more information, use less energy, reduce heat, eliminate bottlenecks. If these technologies continue improving, they could reshape far more than just data centers. Modern AI already influences healthcare, autonomous vehicles, robotics, scientific research, financial systems, manufacturing, logistics, and national infrastructure. Every improvement in computing efficiency has ripple effects throughout the global economy. That's why replacing even part of today's copper infrastructure would represent much more than an engineering milestone. It would represent a fundamental shift in how computers are built. Of course, this doesn't mean copper is about to disappear tomorrow. It remains one of the most reliable, affordable, and widely used industrial materials on Earth. Millions of miles of electrical wiring cannot simply be replaced overnight, but history shows that foundational technologies often remain dominant until a new generation quietly becomes good enough to solve problems the old one never could. Steam eventually gave way to electricity. Vacuum tubes gave way to transistors. Hard drives began sharing space with flash memory. And now, some engineers believe another transition may already be starting, not because copper suddenly became bad, but because artificial intelligence has created demands that copper was never originally designed to meet. If that's true, then what we're witnessing isn't simply another chip breakthrough. It may be the beginning of one of the biggest infrastructure changes the computing industry has seen in decades. And if China succeeds in leading that transition, the consequences could extend far beyond faster computers. To understand why so many researchers are looking beyond copper, it's important to understand just how dramatically artificial intelligence has changed the demands placed on modern computing. Only a few years ago, the world's largest data centers were designed primarily for cloud storage, video streaming, web applications, and online services. Those workloads certainly required fast hardware, but they were relatively predictable. Servers processed requests, sent responses, and repeated the cycle millions of times every day. Artificial intelligence changed the rules. Training a modern AI model requires thousands of processors working together as a single machine. Each processor constantly exchanges enormous amounts of information with every other processor in the system. Instead of sending occasional bursts of data, these networks operate almost continuously, moving information back and forth at incredible speeds. The challenge isn't performing the calculations anymore. The challenge is delivering the data fast enough. Imagine building the world's fastest sports car, but forcing it to drive through city traffic every day. No matter how powerful the engine becomes, the traffic limits its performance. That's essentially what's happening inside many AI clusters today. Modern processors can complete calculations at astonishing speeds, but if they have to wait for data to arrive, expensive computing power sits idle. Even a tiny delay becomes significant when multiplied across thousands of processors working simultaneously. Engineers often describe this as a communication bottleneck. It's one of the biggest reasons why building larger AI systems becomes increasingly expensive. Adding more processors doesn't automatically produce proportional performance gains. As systems grow, communication between processors becomes more complicated. More hardware means more cables. More cables mean more electrical interference. Higher data rates generate additional heat. More heat requires larger cooling systems, increasing electricity consumption and operating costs. Eventually, engineers reach a point where improving processors alone no longer delivers the expected performance. The network itself becomes the limiting factor. That's why some of the world's biggest technology companies are investing enormous resources into solving data movement instead of focusing exclusively on processing power. This is exactly where optical communication begins to stand out. Unlike traditional copper connections that transmit electrical signals, optical systems use pulses of light traveling through glass fibers or specialized photonic pathways. Light offers several important advantages. First, it can carry significantly larger amounts of information over long distances with minimal signal loss. Second, optical communication produces far less electrical interference than copper, making it easier to maintain signal quality as bandwidth increases. Third, because light doesn't generate electrical resistance in the same way as copper conductors, many optical systems can improve energy efficiency, especially when moving vast amounts of information between computing clusters. These advantages become increasingly valuable as AI infrastructure continues expanding. This helps explain why recent announcements from China have attracted so much attention. Rather than focusing only on designing faster processors, Chinese researchers have repeatedly introduced technologies aimed at improving the movement of information itself. Some projects explored advanced photonic chips capable of handling optical signals directly. Others focused on ultra-low-loss optical fibers capable of transmitting enormous amounts of information across impressive distances. Several research groups demonstrated new forms of integrated optical networking designed specifically for artificial intelligence workloads. Although these projects differ technically, they all pursue the same objective: remove communication bottlenecks before they become the biggest obstacle to AI progress. One particularly interesting direction involves bringing optical communication much closer to the processors themselves. Today, optical fibers already connect buildings, cities, and even continents. Inside computers, however, electrical copper traces still perform much of the communication between processors, memory, and networking hardware. Future systems may increasingly blur that distinction. Instead of converting information back and forth between electrical and optical signals multiple times, researchers hope to move light much deeper into computing systems. Some long-term visions even imagine optical communication operating directly between processors inside advanced AI servers. While that future remains under active development, progress is accelerating remarkably quickly. China has invested heavily in photonics research, semiconductor manufacturing, telecommunications infrastructure, and artificial intelligence over the past decade. These investments have created an ecosystem where universities, state laboratories, technology companies, and manufacturing firms often work on complementary parts of the same technological challenge. One team develops better optical materials, another improves photonic chips, another designs networking equipment, another optimizes AI software capable of taking advantage of faster communication. Together, these advances create momentum that individual breakthroughs alone cannot fully explain. This also helps explain why so many recent headlines appear connected. Glass AI chips, photonic processors, air-filled fiber, optical networking. High-speed AI interconnects. They aren't isolated inventions competing against one another. They're different pieces of a much larger puzzle. If enough of those pieces come together successfully, future AI systems could look fundamentally different from today's architectures. Instead of relying primarily on electrical pathways built around copper, much of the communication layer could gradually shift toward optical technologies. That doesn't necessarily eliminate copper completely. Power delivery will still require traditional electrical conductors. Many electronic components will continue depending on conventional circuit designs for years to come. But the role of copper in moving enormous quantities of digital information may begin changing. And that possibility has significant implications beyond engineering. Data centers consume enormous amounts of electricity. Artificial intelligence is increasing that demand every year. If faster optical communication allows AI systems to perform more work using less energy, the economic impact could be substantial. Lower operating costs, reduced cooling requirements, higher computing efficiency, better scalability. Those improvements matter not only for technology companies, but also for governments, research institutions, healthcare providers, manufacturers, financial firms, and virtually every industry beginning to adopt artificial intelligence. That's why replacing even part of today's copper infrastructure isn't simply about building faster computers. It's about enabling the next generation of AI itself. And if China's current pace of innovation continues, the country could play a major role in defining what that future looks like. The most interesting part of this story isn't that China is researching optical communication. It's that the entire technology industry is slowly reaching the same conclusion. For decades, progress in computing followed a familiar pattern. Engineers built faster processors, added more memory, improved manufacturing techniques, and shrank transistors. Each new generation delivered more performance without dramatically changing the overall architecture of computers. Artificial intelligence has disrupted that pattern. Today, simply building a faster processor is no longer enough. The real challenge is making thousands of processors behave like one giant computer. That sounds simple in theory, but it's incredibly difficult in practice. Imagine an orchestra with 10,000 musicians. Even if every musician is exceptionally talented, the performance falls apart if they can't hear the conductor or stay synchronized with one another. Timing becomes just as important as individual skill. Large AI clusters operate in much the same way. Every processor performs calculations independently, but they must constantly exchange information with the rest of the system. If synchronization slows down, overall performance drops dramatically. That's why engineers increasingly describe AI infrastructure as a communication problem rather than a computing problem. This shift is changing the priorities of the semiconductor industry. Instead of asking which company builds the fastest processor, engineers are asking a different question. Which company builds the fastest system? That's an important distinction. A complete AI system isn't just made of processors. It includes networking hardware, memory, storage, power delivery, cooling systems, advanced packaging, software, scheduling algorithms, optical communication, and increasingly, every one of those pieces must be optimized together. China appears to understand this very well. Rather than focusing exclusively on one breakthrough technology, Chinese companies and research institutions have spent years developing multiple pieces of the same ecosystem. We've already seen reports involving domestic AI accelerators designed to reduce dependence on imported hardware. We've covered memory manufacturers expanding production to challenge long-established industry leaders. There have been breakthroughs involving glass substrates capable of improving chip packaging. Chinese researchers demonstrated photonic processors that move information using light. There were advances in air-filled optical fiber capable of carrying astonishing amounts of data. And more recently, developments in AI networking technologies designed to reduce communication delays inside massive computing clusters. Individually, each story attracted attention. Together, they tell a much larger story. They're all solving different parts of the same challenge, building the infrastructure required for the next generation of artificial intelligence. That's also why many analysts believe the future AI race won't be won by whichever company builds the single fastest chip. Instead, it may be won by whoever integrates every component most efficiently. This is already becoming visible inside modern hyperscale data centers. Companies no longer purchase processors in isolation. They invest in complete platforms. Networking equipment must match processor performance. Memory bandwidth must keep pace with both. Storage systems must deliver information without delay. Power systems must support enormous energy demands. Cooling infrastructure must remove incredible amounts of heat. Software must coordinate every component with near-perfect efficiency. If even one layer falls behind, the entire system slows down. This systems-level thinking explains why optical communication has become so important. Replacing portions of copper infrastructure isn't only about transmitting data faster. It's about allowing every other component inside the AI ecosystem to perform closer to its full potential. Imagine spending hundreds of millions of dollars building one of the world's largest AI clusters, only to discover that processors spend a significant portion of their time waiting for information. That idle time represents lost performance, wasted electricity, and lower returns on enormous investments. Now imagine reducing those delays across tens of thousands of processors. Suddenly, the same hardware accomplishes more work. Training finishes sooner. Inference becomes more responsive. Operating costs decline. Energy efficiency improves. These benefits extend far beyond technology companies. Healthcare researchers could analyze larger medical datasets. Climate scientists could run more detailed simulations. Manufacturers could optimize production lines using increasingly sophisticated AI systems. Financial institutions could process larger volumes of information in real time. Autonomous vehicles could improve decision-making through more powerful training infrastructure. The ripple effects become enormous. This is one reason governments have begun treating artificial intelligence as strategic infrastructure rather than simply another software industry. Countries are investing not only in AI models, but also in the factories, supply chains, communication systems, and semiconductor technologies required to sustain long-term progress. China has been particularly active in this approach. Its investments span semiconductor manufacturing, optical communications, telecommunications equipment, artificial intelligence research, advanced materials, and industrial automation. Whether every individual project succeeds remains uncertain. And that's exactly where optical technologies could reshape the landscape. Instead of forcing electrical signals through increasingly complex copper pathways, future AI systems may rely more heavily on photons carrying enormous amounts of information with lower energy consumption and reduced heat generation. That transition won't happen overnight. Data centers represent trillions of dollars in existing infrastructure. Copper remains affordable, reliable, and deeply integrated into modern electronics. Replacing every cable, connector, and circuit would take many years. But technological transitions rarely happen all at once. They begin in specialized applications, where the advantages are greatest. Then costs fall, manufacturing improves, adoption spreads. We've seen this pattern before with solid-state storage, cloud computing, smartphones, and electric vehicles. Optical communication inside AI infrastructure may follow a remarkably similar path. If that happens, today's research announcements may be signs of one of computing's biggest architectural changes since the arrival of the internet itself. So, does this really mean copper is finished? Not even close. Despite the excitement surrounding photonic communication and optical networking, copper remains one of the most important engineering materials ever discovered. It's inexpensive, durable, highly conductive, and supported by more than a century of manufacturing experience. Nearly every power grid, industrial machine, consumer electronic device, and data center still depends on it in some way. The future isn't likely to be a world without copper. It's far more likely to be a world where copper and optical technologies each handle the jobs they perform best. Electricity will continue flowing through copper. but information may increasingly travel through light. That distinction is becoming more important every year. Inside tomorrow's AI data centers, electrical power still needs to reach processors, memory modules, storage devices, cooling systems, and networking equipment. Copper remains exceptionally well suited for delivering power efficiently. The challenge isn't electricity. The challenge is information. Artificial intelligence has created computing systems that move unimaginable amounts of data every second. Every new generation of larger AI models increases that demand even further. Some experts already compare modern AI infrastructure to building highways. When traffic was relatively light, ordinary roads worked perfectly. As cities grew, those roads became congested. Eventually, engineers built multi-lane highways, bridges, tunnels, and entirely new transportation systems. Artificial intelligence is experiencing a remarkably similar transition. The processors themselves continue improving, but the highways carrying information between those processors must improve as well. That's why networking companies have become some of the most important players in the AI industry. It's also why semiconductor companies increasingly discuss entire computing platforms instead of individual chips. The future belongs to complete systems. Systems where processors, networking, memory, storage, cooling, software, and communication all work together with extraordinary efficiency. China appears determined to compete across every one of those layers. We've already seen domestic progress in memory manufacturing, advanced packaging, optical communication, AI accelerators, photonic research, glass-based technologies, ultra-fast networking. Each announcement may appear independent, but together they reveal a much broader strategy. Rather than relying on isolated breakthroughs, China is steadily building an entire ecosystem capable of supporting increasingly advanced artificial intelligence. Whether that ecosystem ultimately becomes the world's most powerful remains impossible to predict. Technology evolves rapidly. Companies in the United States, Europe, Japan, South Korea, and Taiwan continue making remarkable advances of their own. Competition remains intense, and many of today's experimental technologies still require years of engineering before reaching widespread commercial deployment. That's why it's important to separate exciting research from immediate reality. Not every laboratory breakthrough transforms the market overnight. Engineering challenges remain. Manufacturing must scale, costs must fall, software must adapt, industry standards must evolve, customers must be willing to invest. Those transitions take time. But history shows something equally important. Major technological revolutions often begin quietly. Few people recognize the importance of the first semiconductor. Very few imagined smartphones would replace cameras, music players, GPS devices, maps, calculators, and personal computers for billions of people. Cloud computing seemed unnecessary to many businesses before becoming essential. Artificial intelligence followed a similar path. For years, it remained largely inside research laboratories. Then, suddenly, it became part of everyday life. Optical communication inside AI infrastructure could follow that same pattern. At first, only the largest research centers and hyperscale cloud providers may deploy these technologies. Over time, manufacturing improves, costs decline, reliability increases. Eventually, techniques that once seemed futuristic become ordinary engineering. If that happens, future generations may look back at today's developments the same way we now look at the early internet. Not as isolated inventions, but as the beginning of an entirely new technological foundation. Perhaps that's the most fascinating part of this story. This isn't really about copper, it's about how artificial intelligence is forcing humanity to rethink decades of engineering assumptions. For over 100 years, moving electricity and moving information often relied on many of the same materials. AI is changing that. Instead of asking how to build slightly better cables, engineers are asking whether information should travel in an entirely different way. That's an enormous shift in thinking, and if countries like China continue advancing optical networking, photonic communication, and next-generation AI infrastructure, the competition may no longer revolve around building faster processors alone. It may revolve around building smarter systems, systems that waste less energy, generate less heat, move more information, and allow artificial intelligence to scale far beyond today's limitations. Whether that future arrives in 5 years or 15, one thing already seems clear. The race is no longer only about chips, it's about everything connecting those chips together. Because in tomorrow's AI world, the fastest processor won't necessarily win. the processor that waits the least will, and if light eventually replaces copper for many of those critical connections, we may be witnessing one of the biggest infrastructure transitions in modern computing history. The age of artificial intelligence isn't simply creating faster computers, it's creating entirely new ways for computers to communicate, and that could change everything. If you enjoyed today's video, don't forget to like, subscribe, and turn on notifications. Every day we break down the biggest technology breakthroughs shaping China's future, from AI, semiconductors, photonics, robotics, energy, and advanced manufacturing to the innovations that could redefine industries around the world. Let us know in the comments. Do you think optical communication will eventually replace copper inside AI systems, or will copper remain the backbone of computing for decades to come? Thanks for watching, and we'll see you in the next video. There's a material so pure that, until a few days ago, only a tiny handful of places on the planet could make it. Not a handful of countries, a handful of facilities. It was one of those quiet, invisible bottlenecks that the rest of the world barely thinks about, yet it sits underneath one of the most important technologies of the next century. China just started mass producing it. The material is called silicon-28, and calling it pure doesn't quite capture it. It's purified to better than 99.99%, which earns it a nickname scientists actually use, the purest silicon on Earth. On June 15, 2026, China's National Nuclear Corporation announced it had achieved independent, large-scale production of this material for the first time. No headlines about a flashy new gadget, no glowing phone chip to hold up on a stage, just a slab of the quietest, cleanest silicon humanity knows how to make. And here's why that matters more than almost any product launch. This specific material is the foundation that one of the most promising paths to a working quantum computer is built on. Without it, an entire approach to quantum computing essentially can't scale. With a domestic, mass-produced supply of it, a door that was previously held shut by a few foreign suppliers just swung open for China. Now, like every story on this channel, there's important nuance here, and I'll give you all of it honestly, including why this is a foundation stone and not a finished building. But by the end of this video, you'll understand what makes this silicon so special, why noise is the great enemy of quantum computing, why only a few places on Earth could make this stuff, and why a quiet materials announcement might matter more than the loudest chip launch of the year. Let's get into it. Start with the basics, because silicon is one of those words everyone half knows. Silicon is the bedrock of the modern world. It's the second most abundant element in the Earth's crust. It's literally in sand. Purify it, slice it into wafers, etch tiny circuits onto it, and you get the chips that run your phone, your laptop, every device you own. The entire digital age is built on refined sand. We've been making ordinary electronics-grade silicon at massive scale for over half a century. That part is not new and not hard for anyone anymore. But here's the thing most people never learn. Not all silicon atoms are identical. Silicon comes in slightly different versions of itself, called isotopes, atoms with the same chemical identity, but slightly different weights. Natural silicon is a blend of three: silicon-28, which makes up about 92%, silicon-29 at roughly 5%, and silicon-30 making up the rest. For normal electronics, this blend is completely fine. Your phone's processor does not care which silicon isotopes it's made of. For 70 years, nobody needed to separate them. The mixture worked perfectly. But quantum computing is not normal electronics. And in the quantum world, that small, harmless-seeming 5% of silicon-29 turns out to be a saboteur. It's the difference between silicon that's good enough to run a supercomputer and silicon that's good enough to run a quantum computer, and those are two completely different bars. To understand why that tiny fraction matters so enormously, you have to understand the single greatest enemy of quantum computing. And that enemy has a name: noise. Here's the heart of it, and I'll keep it concrete. A regular computer thinks in bits, switches that are either on or off, 1 or 0, rock solid, dependable, binary. A quantum computer uses something far stranger and far more powerful: the qubit. A qubit can exist in a delicate blend of both states at once, and it's this fragile in-between condition that gives quantum computers their almost magical potential to solve problems that would take a normal supercomputer billions of years. But that power comes with a curse. Qubits are unbelievably fragile. They hold their delicate quantum state for only a fleeting moment before the outside world disturbs them, and the information collapses into useless randomness. Scientists call this collapse decoherence, and it is the central villain of the entire field. The whole game of building a quantum computer is, in large part, a desperate fight to keep qubits in their delicate state for as long as possible. Every extra fraction of a second of stability is hard-won. So what disturbs them? Noise. Not sound, environmental interference. Heat, stray electromagnetic fields, vibration, and, crucially, magnetic disturbance from the very material the qubit is sitting inside. This is where that 5% of silicon-29 becomes a wrecking ball. Here's the key piece of physics. Silicon-28 has a property called zero nuclear spin. In plain terms, its atomic nucleus is magnetically silent. It sits there perfectly still and quiet, generating no magnetic disturbance whatsoever. But silicon-29 is different. Its nucleus does have a spin. It acts like a tiny restless magnet, constantly flickering and wobbling. Scientists have a wonderfully descriptive name for the havoc this causes. They call it nuclear flip-flopping. Imagine you're trying to keep a single feather perfectly still and balanced on your fingertip. That's the qubit. Now imagine the room is full of tiny invisible fans randomly puffing air at it from every direction. Those puffs are the silicon-29 atoms magnetically jostling your qubit, knocking it off balance, destroying the delicate state you fought so hard to create. The more silicon-29 around your qubit, the more puffs of disturbance, and the faster your quantum information falls apart. Now the solution becomes obvious. If silicon-29 is the source of the noise, get rid of it. Strip it out. Engineer silicon that is almost pure silicon-28, magnetically silent, a calm and quiet home where a qubit can hold its delicate state in peace. Do that, and you've built what researchers describe as a solid-state vacuum, an environment so quiet the qubit can survive dramatically longer. That is exactly what the purest silicon on Earth is. And it changes everything about how stable a silicon qubit can be. So if everyone knows silicon-28 is the answer, why isn't every quantum lab swimming in it? Why was this announcement a genuine breakthrough rather than a routine purchase order? Because separating isotopes is one of the hardest things in all of industrial science. Remember, silicon-28, silicon-29, and silicon-30 are chemically identical. They behave the same in every chemical reaction. You cannot separate them with chemistry. There's no reaction that grabs one and leaves the others. The only thing that distinguishes them is a minuscule difference in weight, because each has a slightly different number of neutrons. So to purify silicon-28, you have to sort atoms by weight, one tiny mass difference at a time, until you've stripped out almost every last silicon-29 and silicon-30 atom from the mix. This is brutally difficult. It typically involves converting the silicon into a gas, then spinning that gas in sophisticated centrifuges, or using other exotic enrichment techniques to gradually concentrate the lighter silicon-28, repeating the process over and over to inch the purity higher and higher. Pushing past 99.99% purity at any meaningful quantity demands enormous technical mastery and expensive specialized infrastructure. It's closer to the world of nuclear-grade isotope enrichment than to ordinary chip making, which is precisely why China's nuclear corporation, not a traditional chip maker, is the one that cracked it. And here's the part that gives this story its strategic weight. Until now, the ability to produce ultra-pure silicon-28 at scale was concentrated in a very small group of overseas players, facilities tied to Russia, to Europe, and to US-linked supply chains. If you were a Chinese quantum lab and you needed this material, you were dependent on importing it from a handful of foreign sources. That's a choke point, a quiet, invisible one, not a banned machine or a blocked chip, but a raw material that a few outside suppliers controlled. This is the pattern that should feel familiar by now if you watch this channel. The most powerful restrictions aren't always the loud, obvious ones. Sometimes the real leverage is buried in an unglamorous material that nobody outside the field even knows exists. And China just removed that particular piece of leverage from the board by moving silicon-28 from imported from a few foreign suppliers to mass-produced at home. The achievement isn't a finished quantum computer. It's something quieter and, in the long run, possibly more important: supply chain independence in a material the future may be built on. Now, you might be wondering, there are several different ways people are trying to build quantum computers. Why does this particular path, the silicon one, matter so much that purifying its core material is a national-level achievement? Because silicon has one colossal advantage no other approach can match: the entire planet already knows how to manufacture it. Think about it. For decades, the world has poured trillions of dollars and unfathomable engineering effort into building silicon chips with billions of features etched at near-atomic precision. There are vast factories, refined techniques, and deep institutional knowledge dedicated to manipulating silicon better than any other material in human history. If you can build a quantum computer out of silicon, you can potentially tap into all of that existing manufacturing muscle to scale it up, instead of inventing an entirely new industry from scratch. That's the dream of silicon quantum computing. Other leading approaches, like the superconducting chips and trapped ion machines you may have heard of, are powerful, but require building exotic infrastructure largely from the ground up. Silicon qubits promise something seductive: the quantum future, manufactured on a foundation the world has already spent 70 years mastering. And critically, because silicon qubits can be incredibly small, this approach holds the promise of one day fitting thousands of qubits on a single chip, and potentially millions on one device, exactly the kind of scaling you'd need for a quantum computer that can actually change the world. But, and this is the catch, that entire vision rests on having silicon quiet enough to keep the qubits stable. The dream is only as good as the purity of the material underneath it, which is exactly why mass-producing the purest silicon on Earth isn't a footnote. It's the literal foundation the whole silicon quantum dream stands on. Remove the supply problem for that material, and you've cleared one of the biggest roadblocks standing between China and a scalable silicon quantum computer. Now let me be completely straight with you, because I'd rather you trust this channel than oversell you a story. Mass-producing Silicon-28 does not mean China has built a working quantum computer. It does not mean the quantum era arrived last week. What it means is that China has secured a critical ingredient, and ingredients, however essential, are not finished meals. There are real, hard problems still standing between this material and a useful quantum machine. Silicon qubits, across the whole field worldwide, are still at an early stage. Researchers have coherently controlled only a handful at a time, somewhere in the range of a few to a dozen qubits, with recent demonstrations reaching around 11. That's a long, long way from the thousands or millions you'd need for a quantum computer that can crack hard real-world problems. Getting from a dozen qubits to a million is a staggering engineering climb, and pure silicon alone does not get you there. You still need precise qubit control, error correction, packaging, wiring, and a dozen other unsolved challenges. So the honest framing is this: China has not won quantum computing. No one has. What China has done is eliminate a specific supply chain vulnerability and secure domestic control over a foundational material that its silicon quantum ambitions absolutely depend on. It's a step that's necessary but not sufficient, a cleared roadblock, not a crossed finish line. The headlines calling this the breakthrough that gives China quantum supremacy are getting ahead of reality, but the cynics waving it away as just some pure silicon, who cares, are missing the strategic point entirely. In a field where the whole game is fighting noise, controlling the quietest material on Earth is exactly the kind of unglamorous advantage that compounds over years. And there's a strategic dimension: isotope enrichment industry, turning a whole category of materials it once imported into things it now makes itself. Step back, and you'll notice this is the same shape as story after story we've covered. It's almost never the loud, obvious component that becomes the decisive battleground. It's the quiet foundational layer underneath, the substrate beneath the chip, the memory beside the processor, the cooling material that keeps it from melting, and now the ultra-pure raw silicon beneath the qubit. Over and over, the real leverage in a technology race lives in the parts most people never see, and the country that secures those invisible foundations quietly buys itself a future the headlines won't notice until much later. And the response to restriction keeps rhyming too. Faced with dependence on a handful of foreign suppliers for a critical material, China didn't shrug. It built its own production from scratch, using expertise borrowed from its nuclear industry, and removed the dependency entirely. Whether it's lithography, memory, or now isotope enrichment, the pattern holds. A choke point identified becomes a choke point engineered around. I genuinely don't think it's a coincidence anymore. It's a deliberate, systematic march to control every foundational layer of the technologies that will define the rest of this century. This particular announcement won't trend the way a flashy gadget does. There's no screen to admire, no benchmark to gawk at. But years from now, when silicon quantum computers are real and scaling, the quiet ability to manufacture the purest silicon on Earth may turn out to have been one of the foundation stones the whole thing was built on. Here's my honest opinion. I find these boring material stories more revealing than the splashy ones, precisely because almost nobody pays attention to them. It's easy to get excited about a chip you can hold up on a stage. It's much harder to get excited about a slab of ultra-pure silicon, and that's exactly why this kind of move is so telling. The companies and countries that win technology races are usually the ones quietly locking down the unglamorous foundations, while everyone else is dazzled by the product launches. Silicon 28 is the definition of an unglamorous foundation, and China just made sure it owns its supply of it. Do I think this means China is about to leap ahead in quantum computing? No, the field is too young, the qubit count's too small, the road too long for any single material to decide it. But do I think it's a meaningful, deliberate piece of a much larger strategy that's easy to underestimate? Absolutely. The whole point of this kind of move is that it doesn't look like much until, one day, it suddenly looks like everything. The quietest silicon on Earth, made to silence the noise that kills qubits, secured at home instead of bought abroad. It's a small story that's secretly a big one. And those, in my experience, are usually the ones worth paying attention to. So here's my question for you, and I genuinely want your honest take. Do you think quantum computing is going to arrive sooner than we expect and quietly transform everything? Or is it overhyped, perpetually almost here, and decades further away than the headlines suggest? Are you a quantum optimist or a quantum skeptic? Drop your real opinion in the comments. I read every single one. If you want to keep following this, the breakthroughs, the invisible foundations, the quiet moves that matter long before the world notices, subscribe to Eastern Engine and hit the notification bell. Chips, materials, quantum, the entire foundation of modern technology is being rebuilt right now, and we break it all down clearly and honestly before the mainstream catches on. Thanks for watching. I'll see you in the next one. There is a building in the city of Wuhan, China, that has its own weather. Every single morning, an artificial sun rises inside it. It climbs across a simulated sky, shifting color as the hours pass, pale blue at dawn, warm amber by midday, deep orange and violet toward evening, and then it sets. The tens of thousands of people inside, shopping, skiing, riding roller coasters, watching their children splash along an indoor lakeside beach, can glance upward and watch the whole cycle unfold in real time. This is Dream Plaza, and it is one of the most ambitious buildings operating anywhere on the planet today. The numbers alone are staggering. The complex covers nearly 800,000 square meters of floor space. The retail center by itself spans 370,000 square meters across 9 floors above ground and 4 below. But those figures only describe the shell. They tell you nothing about what was put inside it, or why, and that is the far more interesting story. Because Dream Plaza is not just big, it represents a completely different theory of what a building in the center of a modern city is even supposed to be. To understand why it exists, you first have to understand what it was built to escape. Almost every country that built shopping malls in the second half of the 20th century eventually watched them decline. The formula was always identical: a large enclosed space, anchor stores at either end, smaller shops filling the corridors between them, a food court somewhere in the middle, and a vast parking lot wrapped around the whole thing like a moat. For decades, this worked beautifully. People drove in, walked the corridors, and spent money. Then online shopping arrived, and the formula came apart. The question that broke the traditional mall was brutally simple. Why would anyone drive to a building, hunt for a parking space, walk to a store, and pay a marked up price for something they could order from their couch and have delivered the next morning? Increasingly, the answer was that they wouldn't. Foot traffic dropped. Anchor tenants packed up and left. The corridors emptied out. Across much of the West, shopping centers became half-lit monuments to a retail model the world had quietly moved beyond. Chinese developers watched this happen, and rather than simply copying the format that was already dying, they studied the failure carefully. They traced it back to its root cause. The malls had stopped offering a reason to show up that couldn't be replicated by staying home. And from that, they drew a conclusion that seems obvious in hindsight, but that most Western developers were too invested in the old model to act on. People have never primarily left their homes in order to buy things. They leave to experience things, to be somewhere specific, to feel something, to do something that requires their body to physically be present in a place. You can buy almost anything online, but you cannot ski online. You cannot take your child on a roller coaster through a screen. You cannot feel the cold of manufactured snow on your face from your living room. That single insight became the foundation of everything Dream Plaza is. The decision was locked in at the very start of the design process, and it was irreversible. This would not be a place to buy things. It would be a place to be. The building itself would be the product. Start at the bottom. The indoor theme park occupying the lower floors is not a token entertainment corner. A few arcade machines and a carousel squeezed into leftover space near the escalators. It is a full-scale attraction featuring roller coasters, high-speed rides, and multi-sensory experiences designed for adults and children alike. It runs year-round, regardless of season, regardless of weather, regardless of whatever the city outside is doing. In Wuhan, that matters enormously. Summer temperatures there routinely climb past 35 degrees Celsius, and winters arrive with real force. A venue that depends on pleasant weather might work 3 months out of the year. A fully climate-controlled one earns repeat visitors every single weekend without exception. Move upward through the building, and the temperature starts to drop before you understand why. The snow park, among the first and largest indoor ski facilities in the region when it opened, keeps its floors below freezing around the clock. Families living in a city where natural snowfall is rare and unpredictable can ski, snowboard, or simply play in manufactured powder on any Tuesday in July. That jarring transition, going from a sweltering Wuhan summer to a genuine ski slope in the time it takes to ride a few escalators, is precisely the point. Dream Plaza is selling sensory experiences the city outside its walls simply cannot offer. You want winter? Winter is on the 4th floor. The dining and retail areas are arranged unlike a standard mall. Instead of corridors lined with shops on either side, optimized purely for storefront exposure, the spaces are organized as a series of distinct atmospheric environments, each one designed to feel genuinely different from the last. The design team built the concept around the idea of time travel and the 4 seasons. Moving through Dream Plaza is meant to feel like passing through different eras and different climates. Warm golden zones that evoke high summer, cool blue-toned spaces that recall deep winter, transitional passages that shift the light and mood and texture as you walk. The atmosphere isn't background decoration. It is the architecture. It is what people came for. Beyond the enclosed floors, the complex spills outward into curated open-air areas, a lifestyle and leisure zone designed for adults, and a children's lakeside precinct built around water, open-ended play equipment, and natural shapes. In a dense urban district where green space and real outdoor room for kids is scarce, this isn't a luxury add-on. For families living in surrounding high-rise apartments, it's what turns the building into part of their weekly routine rather than an occasional outing. Now, the sky. The centerpiece of Dream Plaza's central atrium is one of the boldest single design decisions in any commercial building currently operating on Earth. The building doesn't simply provide artificial lighting the way every other indoor space does, fixed overhead sources angled to flatter products and keep shoppers comfortable enough to linger. It provides an artificial sky. A dynamic overhead display system spans the full width of the atrium, simulating the complete arc of a day. It moves from pale early morning blue, through warm midday amber, into the deep orange and violet of late afternoon, and finally into a simulated night sky as the building's evening hours begin. The sun that crosses the interior isn't a spotlight. It is a calibrated system designed to reproduce the quality and character of natural daylight, the specific kind of light human biology uses to track time, regulate mood, and maintain the circadian rhythm that governs energy, sleep, and even appetite. This matters more than it first appears. Every large enclosed building, every shopping center, every airport, every windowless venue is quietly fighting the same biological reality. Human beings are profoundly sensitive to their light environment. When that environment stops signaling what time it is, people's relationship with the space starts to break down. They tire faster. They become subtly disoriented. They want to leave. The artificial sky is engineered to prevent exactly that. It gives the building a pulse, a rhythm, a sense of time genuinely passing, which makes spending hours inside feel less like confinement and more like inhabiting a real place. It's worth pausing on how counterintuitive this is. Casino designers famously stripped windows and clocks from gambling floors, deliberately severing guests from any sense of time to keep them inside longer. Dream Plaza did the precise opposite. It introduced a complete simulated day-night cycle into a building where every door opens onto another interior room. One approach traps you by making time vanish. The other holds you by making time feel real. Both work, but only one of them also earned an international award for Best Retail Interior Design. Wuhan deserves a closer look because it is far more significant a city than most people outside China realize. With a population of around 12 million, Wuhan is one of the largest urban centers in China's interior. It sits at the meeting point of the Han and Yangtze rivers, a geographic position that made it a critical trading hub for centuries and continues to make it one of China's most important logistics nodes today. Dozens of universities are based here. A major industrial and manufacturing base operates here. A fast-growing technology sector has taken root here. This is not a secondary city playing catch-up. It is a city that has spent decades building the infrastructure and institutional weight to compete at the very top of China's urban hierarchy. The Eastern District where Dream Plaza was built is the densest and most historically significant of Wuhan's three main urban cores. Dropping a building of this scale into that district was not the speculative gamble that defines so many Chinese megaprojects, where enormous structures rise on the urban fringe and then wait years for the surrounding population to catch up. Dream Plaza opened in an already dense, already commercially active neighborhood, surrounded by millions of existing residents with disposable income and a clear appetite for experiential spending. When it opened in November 2022, the response was immediate. Opening day crowds were enormous. The experiential attractions reported wait times stretching for weeks. The building gave a major city a genuine reason to celebrate something extraordinary, and people showed up in force to do exactly that. Dream Plaza earned its design award for a specific reason. It breaks with conventional mall logic, not just in what it contains, but in how it expects people to move through it. Standard commercial architecture is built on one overriding principle: maximize exposure. Every shopper who enters should pass as many storefronts as possible. Corridors are kept straight so sightlines stretch further. Escalators are positioned to pull foot traffic through peripheral zones. Floor plans are arranged so the route to the supermarket or cinema runs through 3 departments you never intended to visit. Every decision is optimized to ensure the path to wherever you're going routes you past as many things you weren't planning to buy as possible. This is effective retail science, and it has driven billions in unplanned purchases for 60 years. But it is also, increasingly, the wrong approach for a generation that grew up in information-saturated environments and has become highly skilled at recognizing and resisting the feeling of being managed. Dream Plaza's internal geometry is curved, branching, and deliberately non-linear. There are no long straight corridors. Routes turn unexpectedly into plazas, open into soaring double-height atriums, narrow into intimate passages, then expand again. Navigation isn't optimized for efficiency, it's optimized for surprise. The underlying assumption is no longer that you came to reach a specific destination. The assumption is that you came to see what happens next. The building rewards wandering. It withholds its best moments until you've earned them by moving through something else first. Here, the journey genuinely is the destination, in the most literal architectural sense. The four-season atmospheric concept pushes this even further. Stepping from a warm, gold-toned environment into a cool, wintry blue one acts as a sensory reset, a way of making an 800,000 square meter building feel like it holds multiple distinct worlds, rather than one endless commercial space. It's the difference between a building that is merely enormous and one that somehow feels larger than its own floor plan. Dream Plaza is extraordinary, but it is also, in ways its designers haven't fully resolved, a set of open questions wearing the clothing of a solution, and the same features that make it remarkable also make it, in certain respects, genuinely fragile. That fragility doesn't show up in the steel frame or the foundations, it shows up in the assumptions the entire project rests on. The first is environmental. Keeping a snow park below freezing in a city where summers exceed 35 degrees is an enormous continuous energy commitment. Running a dynamic artificial sky, a full-scale theme park, a cinema, climate-controlled retail across 13 floors, and an outdoor lakeside precinct, all at once represents an energy demand that would be striking even before you account for the tens of thousands of daily visitors, adding to the heating, cooling, and ventilation load on every system in the building. Detailed energy consumption figures haven't been published, so the true environmental math is genuinely unknown. It may turn out to be more efficient per visitor than a city full of smaller, scattered venues. It may not. For now, no one can say for certain. The second question is economic. The experiences that make Dream Plaza feel exceptional today were new in 2022. The ski slope was novel, the artificial sky was astonishing, the indoor roller coasters were reason enough to cross the city and spend a Saturday. But what are they in 2030? In 2035? The history of experiential venues is full of attractions that felt revolutionary at opening and felt tired within a decade. Keeping genuinely novel experiences alive isn't only a financial cost, it's a creative one. Dream Plaza will have to keep reinventing itself, keep adding fresh reasons to return, or risk the same slow attrition that killed the conventional mall it was designed to replace. The artificial sun will keep rising. The real question is whether people keep finding a reason to come watch it. The third question is the most thought-provoking, and it's one cities everywhere should probably be asking more openly. Dream Plaza is, among other things, a machine for not leaving. Everything a family might want for an entire day. Exercise, entertainment, food, play, shopping, spectacle, outdoor space sits inside a single set of walls. The incentive to engage with the rest of the city is reduced by exactly the degree to which Dream Plaza succeeds at replacing it. Cities aren't just collections of services and amenities. They're systems where people encounter one another in unplanned ways, where public space generates the kind of spontaneous social friction that builds community over time. A building that substitutes for the city, rather than serving it, raises a question urban planners haven't yet answered. What happens to the street when the building beside it becomes more appealing than the street itself? Here is the honest version of what Dream Plaza is. It is not a mall. It is not a theme park. It is not a hotel complex or a civic center or an entertainment district. It is the first generation of a new kind of building that doesn't yet have a widely agreed upon name, a type that will very likely define how the world's most ambitious cities approach their downtown cores for the next several decades. Every major city on Earth is wrestling with the same fundamental question. What do you build at the heart of a dense urban district when buying things online is easier than going to a store? When entertainment competes directly with the device in everyone's pocket? When the bar for what counts as a good enough reason to leave the house has risen to a level no urban planner 50 years ago would even recognize? The answer most Western cities have offered is to wait and see, to rezone incrementally and hope that coffee shops, farmers markets, and creative offices fill the void left by departing retailers. That answer largely isn't working. Dream Plaza's answer is the opposite. Build something a screen cannot replace. Build an environment so deliberately physical, so sensory, so committed to the idea that being somewhere specific genuinely matters, that simply being inside becomes its own justification. Give it a ski slope that defies the weather outside. Give it roller coasters that make adults feel like kids again. Give it a beach and an atrium so tall it needs its own sky. And then give that sky a sun that rises, moves, and sets on a schedule, reminding everyone inside that time is passing, that this moment will end, and that there's nowhere else they'd rather spend it. Whether that answer holds for a generation is something 12 million people in Wuhan will decide with their feet, weekend after weekend, for years to come. For now, the artificial sun inside Dream Plaza rises every morning. And for now, people keep coming to stand beneath it. A normal solid-state drive has one job: store data. It receives files from the computer, places them inside flash memory cells, and returns them when requested. The controller organizes the traffic, corrects errors, and tries to keep the drive alive as thousands of writes gradually wear down the NAND. But a Chinese memory company believes the SSD should do much more than move data from one place to another. Longsys has introduced a 5-nanometer chip called the WM8500. The company describes it as an SPU, a storage processing unit. And according to Longsys, this chip can compress data inside the drive in real time, without requiring the host processor to handle the work. Across text, source code, databases, and similar workloads, the company reports an average compression ratio of approximately 2:1. That creates an extraordinary possibility. A drive containing 128 terabytes of physical flash could provide as much as 256 terabytes of effective storage. No additional NAND package, no second SSD, no magical new memory cell. The same physical drive simply stores certain data more efficiently. But capacity doubling is only the beginning. Longsys says the SPU can also move selected AI data out of expensive DRAM and into high-speed storage, reducing memory requirements by nearly 40% in one tested scenario. The company has even demonstrated a system built around AMD's Ryzen AI Max Plus 395, running a 397 billion parameter model locally. That sounds almost impossible for a compact machine. Yet the idea behind it is surprisingly simple. Instead of treating storage as a passive warehouse, Longsys wants the SSD to become an active participant in computing. The drive does not merely hold the data, it compresses it, sorts it, predicts when it will be needed, and in some cases, acts as an extension of system memory. If the technology works as described, the future SSD may not be measured only by how many terabytes it contains. It may be measured by how intelligently it uses every byte. The storage problem. AI created. For years, computer performance was discussed mainly in terms of processors. Faster CPU, faster GPU, more cores, higher clock speeds. But artificial intelligence has exposed a different bottleneck: memory. A large AI model may contain billions or hundreds of billions of parameters. Each parameter represents a numerical value learned during training. To run the model, those values must be stored somewhere and moved repeatedly into the processor. The calculations can be fast. Moving the data is often slower. Imagine owning a factory with thousands of extremely powerful machines. The machines can assemble products at incredible speed, but every component is stored in a warehouse several kilometers away. The machines spend less time working than waiting for deliveries. That is the AI memory problem. High-end data centers attack it with massive amounts of high-bandwidth memory, large pools of conventional DRAM, and extremely expensive storage systems. An ordinary PC cannot do that. Even a powerful workstation may have 64, 128, or 256 gigabytes of memory. A large model may require far more. So developers use a technique called offloading. Part of the model remains in fast DRAM. The rest is stored on an SSD and loaded only when needed. This makes larger models possible, but it introduces another problem. SSDs are much slower than DRAM. If the wrong data is requested at the wrong moment, the processor must wait. Longsys is trying to reduce that delay by making the drive itself more intelligent. From SSD controller to storage processor. Every SSD already contains a controller. The controller translates commands from the computer, decides where data should be written, manages bad memory cells, and performs error correction. Without it, NAND flash would be difficult to use reliably. But the traditional controller is largely a traffic manager. It moves data. The WM8500 is designed to process data too. Longsys says the SPU combines a conventional storage control engine with an intelligent processing engine on the same chip. That distinction matters. A normal controller asks, where should this file be placed? The SPU can ask additional questions. Can this file be compressed? Is it used frequently? Should it remain close to the processor? Can part of it be moved into a cheaper region of the drive? Will the system need it again soon? The company calls the software layer controlling these decisions ISA, or Intelligence Storage Agent. The SPU is the muscle. The ISA is the planner. Together, they turn the drive from a passive destination into something closer to a data assistant. The idea resembles what happened to graphics cards. A GPU was once a specialized component responsible mainly for drawing images. Over time, it became a general computing engine used for science, simulation, and artificial intelligence. Longsys is suggesting that storage controllers may follow a similar path, not by replacing CPUs or GPUs, by performing the data management work those processors should not have to do. How 128 terabytes becomes 256 terabytes? The headline number comes from lossless compression. Lossless means the original data can be reconstructed perfectly. Nothing is thrown away, nothing is blurred, nothing is approximated. A photograph saved as a low-quality image may use lossy compression, where some visual information is permanently removed. That can reduce file size dramatically, but the original cannot be recovered exactly. Lossless compression works differently. It searches for repeated patterns and replaces them with shorter instructions. Suppose a document contains the word semiconductor 10,000 times. Instead of storing every letter 10,000 times, a compression system can store the word once and then record where it repeats. The file becomes smaller. When it is read, the system reconstructs the full version. Longsys says the WM8500 performs this process directly inside the storage device. The computer sends data to the SSD. The SPU analyzes it. Compressible data is reduced before being written to flash. When requested, the SPU decompresses it before returning it to the host. To the operating system, the process can appear transparent. The user does not need to place files inside an archive manually. The drive handles it automatically. With an average 2-to-1 ratio on suitable workloads, 1 physical terabyte can store approximately 2 terabytes of original information. That is how 128 terabytes can provide up to 256 terabytes of effective capacity. But the phrase suitable workloads is essential. Not all data compresses equally. The files that refuse to shrink. Text compresses extremely well because language contains repetition. Source code also contains repeated words, structures, commands, and symbols. Databases may contain recurring values, empty fields, and predictable patterns. These are the kinds of workloads Longsys highlights. Video is different. Modern video files are already heavily compressed. A movie encoded with an efficient codec has already had most of its obvious redundancy removed. Trying to compress it again may save almost nothing. The same applies to JPEG photographs, compressed archives, and many encrypted files. Encryption deliberately makes data appear random. Random-looking data contains fewer predictable patterns for a compression engine to exploit. So a 128 terabytes drive will not always behave like a 256 terabytes drive. One user may see close to the full 2-to-1 benefit. Another may see only a small improvement. A data center filled with text logs, program code, and database records could benefit greatly. A media archive filled with compressed movies may not. This is not a flaw unique to Longsys. It is a basic limit of compression. You cannot repeatedly squeeze information forever. Eventually, the obvious repetition disappears. That is why the most honest description is not, Longsys created a physical 256 terabytes SSD. It created a 128 terabyte storage platform that may hold as much as 256 terabytes of uncompressed source data under favorable conditions. Still impressive, just not magic. Why put compression inside the drive? Computers have compressed files for decades. Operating systems can compress folders. Databases use compression. Servers use software tools to reduce storage needs. So why build dedicated compression hardware inside an SSD controller? Because compression requires computation. If the CPU performs it, processor time is consumed. Data must move through system memory, power is used. Other programs may slow down. A dedicated engine can perform the same task more efficiently. Think of a restaurant kitchen. The head chef can wash every plate personally. But that is probably not the best use of the most valuable worker in the building. A dedicated dishwasher handles the repetitive task while the chef focuses on cooking. The SPU attempts to do the same for data. The CPU and GPU focus on applications and AI calculations. The storage processor handles compression, caching, and movement. Longsys claims the process introduces no meaningful performance penalty. But that is one of the areas where independent testing will be important. Compression always requires work. The real question is whether the 5-nanometer engine can perform that work fast enough that the user barely notices. If the drive can compress at full interface speed, the savings could be substantial. If compression slows sustained writes or increases latency, the value becomes more complicated. Capacity is not useful if access becomes painfully slow. The 5nm chip at the center, the WM8500, is manufactured using a 5-nanometer process. That does not automatically make it revolutionary. Process node names are not direct measurements, and a smaller node does not guarantee better architecture. But 5-nanometer manufacturing provides a practical advantage. More processing logic can fit inside a compact controller while keeping power consumption manageable. Traditional SSD controllers already perform difficult tasks. They manage multiple NAND channels, calculate error correction codes, track wear, translate logical addresses, maintain caches, encrypt data, support PCI Express communication. Now add hardware compression, workload classification, predictive prefetching, and AI data scheduling. That requires more transistors, more processing, more memory, and careful power control. A storage controller cannot behave like a desktop CPU, consuming 100 watts. It lives inside a drive where heat can reduce performance and shorten flash memory life. The 5-nanometer process gives Longsys room to add intelligence without turning the SSD into a small oven. The WM8500 also supports PCI Express 5.0, allowing high-speed communication with the host system. That bandwidth matters because the entire concept depends on moving model data quickly enough to hide the difference between SSD and DRAM. The drive does not need to become as fast as DRAM. It needs to become fast and predictable, enough that software can plan around it. The second trick, using SSD as slower memory. Compression creates the headline. HLC may create the bigger long-term impact. Longsys calls it high-level cache. The idea is to use the SSD as an extension of DRAM. Computers already use virtual memory. When physical RAM becomes full, the operating system moves some data to storage. Historically, this was painful. Hard drives were so slow that a computer using large amounts of virtual memory could become nearly unusable. Modern SSDs are much faster. They are still far slower than DRAM, but the gap can be managed more intelligently. Not all data needs immediate access. Some information is hot. The processor uses it constantly. Some is warm. It may be needed soon. Some is cold. It exists in memory but is rarely touched. HLC attempts to identify those categories. Hot data remains in DRAM. Warm and cold data moves to the SSD. If the system predicts correctly, the processor sees little delay because required data is fetched before it is needed. This resembles organizing a workshop. The tools used every minute remain on the table. Tools needed occasionally sit in a nearby drawer. Tools rarely used go into storage. A badly organized workshop forces the worker to walk across the building constantly. A well-organized one keeps the right objects close at the right time. Longsys says HLC can reduce required DRAM capacity by nearly 40% in a tested 256,000 token scenario involving a 122 billion parameter workload. That does not mean every computer can remove 40% of its RAM. It means this particular architecture reportedly achieved that reduction under a specific AI workload. The 397 billion parameter demonstration. The most eye-catching demonstration involved AMD hardware. Longsys says it jointly optimized an intelligent agent system built around the Ryzen AI Max Plus 395 processor. That AMD chip is designed for powerful local AI systems, combining CPU cores, graphics resources, and a large unified memory architecture. Using the SPU and ISA system, Longsys reports that the machine successfully deployed a 397 billion parameter model locally. That figure requires context. Deployed does not necessarily mean the model ran at cloud data center speed. It does not tell us the exact precision used for the weights. It does not reveal the token generation rate. It does not tell us how much of the model remained in memory and how much was streamed from storage. But it demonstrates the direction. A model too large to fit entirely inside conventional system memory can still run if inactive sections remain on the SSD and are loaded intelligently. Many modern models use a mixture of experts architecture. An MOE model may contain hundreds of billions of total parameters, but only a fraction activates for each token. Imagine a company employing hundreds of specialists. One question requires a lawyer, another requires an engineer, a third requires an accountant. The company does not need every employee in the meeting room simultaneously. The ISA system attempts to keep currently active experts in fast memory while storing inactive experts on the SPU-equipped SSD. When the system predicts that a different expert will be needed, it begins loading that expert early. If the prediction is accurate, the data arrives before the model asks for it. The delay becomes less visible. That is intelligent prefetching. The KV cache problem. Large language models face another memory burden, called the KV cache. As a model processes a conversation, it stores information about previous tokens, so it does not need to recalculate everything repeatedly. The longer the conversation, the larger the cache grows. A short prompt may be manageable. A document containing hundreds of thousands of tokens can consume enormous amounts of memory. Longsys says its system can move older or less active portions of the KV cache onto the SSD while keeping important sections in DRAM. Compression may reduce the space required further. Again, timing is everything. If the model suddenly needs an old section and the data has not been prefetched, inference can pause. The SSD becomes a bottleneck. If the scheduler correctly predicts future needs, the storage delay can overlap with computation. The model continues working while the next data block arrives. This is why the ISA software may matter as much as the WM8500 hardware. A fast drive with poor scheduling is still slow at the wrong moment. An intelligent scheduler can make slower storage feel faster by requesting data before the wait begins. Can this replace DRAM? No, at least not in performance-sensitive roles. DRAM operates with latency measured in tens of nanoseconds. NVMe SSD latency is usually measured in microseconds. A microsecond is 1,000 nanoseconds. That difference is enormous. Even a highly advanced SSD cannot become genuine system memory simply through clever software. It can, however, reduce the amount of expensive DRAM required. This distinction is important. The SPU does not replace the workbench. It makes the storage room more useful. The most frequently used tools remain on the workbench. The rest can move to an automated shelf that delivers them when requested. For AI systems, that can change economics. DRAM is expensive. High-capacity memory configurations increase device cost and power consumption. If a manufacturer can build a system with 96 gigabytes of DRAM that behaves like a larger memory machine under selected workloads, the savings could be meaningful. But the user experience depends on the workload. Interactive applications may be sensitive to small delays. Batch processing may tolerate them. Models with predictable expert activation may work well. Other architectures may not. One benchmark cannot answer every case. Could smart SSDs replace hard drives? Longsys also presents the SPU as a possible alternative to large-capacity hard drives. HDDs remain popular because they provide huge capacity at low cost. SSDs are faster, quieter, and more efficient, but large enterprise SSDs can be extremely expensive. Compression changes that calculation. If a 128 terabytes flash drive stores the same amount of suitable data as 256 terabytes of conventional capacity, its effective cost per stored terabyte falls. It may still cost more than hard drives, but total ownership includes more than purchase price. Hard drives use mechanical parts. They require more physical space. They consume energy. They produce vibration. They need cooling. They may fail differently. An SSD with intelligent compression could become attractive in environments where space, power, and access speed matter more than the lowest possible purchase price. However, flash endurance remains important. Compression may actually help by reducing the amount of data physically written to NAND. If 2 terabytes of original data compress to 1 terabyte, fewer flash cells need to be programmed. That could extend drive life. But only independent endurance testing can show how the complete system behaves under sustained heavy use. The SPU itself also creates new complexity. More intelligence means more firmware. More firmware means more opportunities for bugs. Storage errors are unforgiving. A graphics glitch is annoying. A corrupted database can be catastrophic. The questions Longsys still needs to answer. The company's claims are fascinating. They are not the same as a full independent review. We still need to know the sustained compression speed. Can the controller maintain performance when writing hundreds of gigabytes continuously? How does latency change when compression is active? What happens with data that compresses poorly? How much power does the SPU consume? How hot does the controller become? How consistent is the 2-to-1 ratio across real enterprise workloads? How does the system protect data if power fails during a compressed write? How many drives can operate together in a server? What is the cost compared with a conventional enterprise SSD? And perhaps most importantly, when can customers actually buy one at scale? A technology demonstration can show possibility. A commercial product must show reliability, support, firmware stability, and manufacturing volume. Storage buyers are conservative for a reason. They are trusting the drive with information that may be more valuable than the hardware itself. My take. My view is that the most important part of the WM8500 is not the headline capacity doubling. Compression is useful, but it depends heavily on the data. Some users may approach 2-to-1. Others may see far less. The deeper shift is architectural. Longsys is treating storage as a computing layer. For decades, the hierarchy was simple. The CPU computes. DRAM feeds the CPU. Storage waits. AI is breaking that arrangement because model sizes are growing faster than affordable memory capacity. The SPU offers another approach. Let the storage device perform part of the data work. Compress information before it consumes flash. Keep inactive model experts outside DRAM. Predict which data will be needed next. Move old KV cache entries into a lower-cost tier. None of those ideas individually eliminates the memory bottleneck. Together, they may make local AI systems far more capable. The risk is that intelligent storage becomes complicated storage. Prediction errors create delays, compression adds processing, firmware bugs create new failure modes, and company demonstrations may look better than mixed real-world workloads. Still, the direction makes sense. We are approaching a point where adding more raw storage and more raw DRAM cannot be the only solution. Efficiency must improve too. A 128 terabytes drive should not merely be a bigger bucket. It should understand how the bucket is being used. That is what the WM8500 is trying to become. Not just an SSD controller, a storage processor, a chip that turns capacity into something flexible, a chip that lets flash behave partly like memory, and under the right conditions, a chip that allows 128 physical terabytes to hold 256 terabytes of original data. The achievement is not that Longsys created storage from nothing. It is that the company may have found a better way to use what was already there. So what do you think? Would you trust a smart SSD that automatically compresses your files and manages part of your AI memory? Or would you prefer a simpler drive with predictable physical capacity and fewer layers of processing? Let me know your view in the comments. And if you want more grounded breakdowns of the chips, memory systems, and hidden hardware reshaping computing, subscribe to Eastern Engine, because the next storage revolution may not come from adding more flash. It may come from teaching the drive what to do with it. Imagine you go to sleep on a Monday night, and there is an empty plot of land outside your window. Cleared ground, maybe some foundation work, nothing else. You wake up Friday morning and there is a 16-story residential building standing there. 150 fully finished apartments, tiles on every floor, toilets installed, lights working, hot water running, move-in ready. That sentence does not describe a hypothetical. It describes something that physically happened in Abu Dhabi in late 2025. A building called Earth Tower went from first crane lift to completed structure in 96 hours, And the company that built it is not a startup with a flashy pitch deck. It is a Chinese manufacturer that has been quietly perfecting this process for 15 years while the rest of the construction world told them it could not be done at scale. The company is called Broad Group, and what they have built is not just a faster way to construct apartments. It is a fundamental reimagining of what construction actually is. To understand where Broad is today, you need to go back to where they started. Because the gap between then and now tells you everything about how seriously to take what they are doing. In 2011, Broad assembled a 30-story hotel in 15 days. The building went up in Changsha, in central China, using prefabricated sections that were manufactured off-site, transported to the location, and bolted together with a precision that looked, on video, like someone had hit fast forward on the whole process. The interior was not a shell waiting to be fitted out. Insulation was already in the walls, plumbing was already run, air conditioning was already installed. The finishing work had been done in the factory, not on the site. The global construction industry watched the time-lapse footage and reached for familiar responses. It was called a publicity stunt. Questions were raised about structural integrity. People argued that speed and quality were fundamentally incompatible in construction, that cutting timelines that dramatically meant cutting corners somewhere. Broad kept building. 3 years after the 30-story hotel, they completed Mini Sky City, a 57-story tower standing over 200 meters tall, assembled in 19 days at a rate of roughly 3 floors per day, 800 apartments. Working space for several thousand people. The same modular system, simply applied at greater height. At that point, the conversation shifted from whether the buildings could go up quickly to whether they were actually safe to live in. Broad had anticipated this. Their structural system uses a steel frame architecture with a tolerance for seismic activity that meets and in some specifications exceeds conventional high-rise construction standards. The speed was not achieved by weakening the structure. It was achieved by moving as much work as possible off the construction site and into a controlled factory environment where consistency is higher and quality control is easier to maintain. Then came the number that started to genuinely unsettle people. A 10-story apartment building, assembled in 28 hours and 45 minutes, not days, hours, 3 cranes, 1 continuous working period, and a building that would have occupied a conventional construction crew for 6 to 8 months was standing before the second day was done. The industry did not really have a framework for processing that figure. It sat outside the range of what the existing mental model of construction could accommodate. Here is the thing that most coverage of Broad gets wrong by omission. The speed you see on the construction site is not where the innovation lives. The construction site is almost beside the point. The actual work happens in Broad's manufacturing facility in central China, and it operates nothing like a construction company. It operates like a car factory. Each module that goes into a Broad building is produced on a robotic assembly line. The module itself is roughly the dimensions of a standard shipping container, a self-contained segment of a finished apartment. By the time it reaches the end of the production line, it is approximately 90% complete. The floor tiles are laid, the bathroom fixtures are installed, the electrical wiring is run through conduits, the plumbing connections are made, the insulation is fitted, the walls are painted, the windows are in. Everything that takes months on a conventional construction site has already been completed in the factory under controlled conditions, with robotic systems maintaining tolerances that human workers in outdoor environments cannot consistently match. When those modules arrive at a construction site, the process that follows is not construction in any traditional sense. It is assembly. Cranes lift each module into its designated position. Workers make the structural connections between modules, bolting the steel frame elements together according to specifications. Crews connect the interface points where plumbing, electrical, and mechanical systems from adjacent modules meet. Then the next module goes up. The construction site becomes a logistics operation rather than a manufacturing operation. And logistics can be optimized for speed in ways that on-site construction fundamentally cannot. Broad's factory currently produces an output equivalent to roughly 84,000 housing units per year. A single facility. That figure is not about individual impressive projects, it is about what happens when you treat housing the way the automotive industry treats vehicles. You design a system, build a factory around the system, and the output scales with production capacity rather than with the availability of skilled construction labor at a specific location. Everything Broad had demonstrated in China up to 2024 could be, and was, filed away by much of the international construction industry as locally specific. A Chinese company doing impressive things in China, within Chinese regulatory frameworks, using Chinese labor, for Chinese clients. Interesting. not necessarily transferable. Earth Tower ended that argument. Eagle Hills, a property development company connected to Emaar, the group responsible for building the Burj Khalifa, sent executives to Broad's factory in central China. They walked the production floor. They watched the robotic assembly lines produce finished apartment modules. They reviewed the structural specifications. Then they placed a commercial order for 259 modules, comprising 150 residential units across multiple apartment configurations. This was not a pilot program or a research collaboration. It was a transaction. One of the most credentialed property development organizations in the world, with the technical knowledge to evaluate what they were looking at, decided the technology was ready for the Gulf market and wrote a purchase order. The modules were manufactured in September 2025. Broad's production team completed the entire order in 30 days. The units were loaded onto cargo ships in October and transported 6,000 kilometers across the ocean to the UAE. They arrived in Abu Dhabi later that month. From the moment the first crane lifted the first module on site, the clock ran for 96 hours. When it stopped, Earth Tower was standing. 16 stories, 150 apartments, 168,000 square feet of residential space. Every unit finished and operational. The project carried a value of 125 million RMB and became the first Chinese prefabricated residential building delivered into the Middle Eastern market. At CES 2026, it received the Speed Award for Smart Living, a prize that had never previously gone to a construction project, because construction projects had never previously moved at a pace that warranted the category. That last detail is worth sitting with. An industry award typically given to consumer electronics went to a building. The implication is that what Broad is doing has more in common with product manufacturing than with construction as the industry has historically understood it. Broad's next move is more significant than any single building they have assembled. The company is working toward establishing full manufacturing facilities in the UAE, not shipping modules from China, but replicating the production system itself on the ground in the Middle East. The distinction matters enormously. Shipping finished modules across oceans works, as Earth Tower demonstrated, but it adds freight cost and transit time that a local production facility eliminates entirely. If you can manufacture the modules where the demand is, you remove the ocean from the equation and the economics improve substantially. Broad's stated production target is 70 manufacturing facilities operating globally by 2030, with a combined annual output of 200 million square meters of buildings. That number is not presented as aspiration, it is presented as the production plan. The Abu Dhabi project was not the destination, it was the proof of concept that unlocks the expansion. Broad is not operating in isolation. The broader signal from the Chinese construction sector is consistent and pointed in the same direction. CSCEC, the China State Construction Engineering Corporation, currently the largest construction company on Earth by annual revenue, has received initial regulatory approval in Dubai for its modular construction division, operating under the brand name Homagic. The approval covers low-rise and mid-rise residential construction, and the company has set a target of 50,000 housing units per year specifically for markets connected to the Belt and Road Initiative. 50,000 units per year from a single company's modular division, deployed into markets that have been struggling to build housing fast enough using conventional methods for years. Dubai's approval of CSCEC's approach is a regulatory signal. When governments begin formally approving the framework conditions for modular construction from Chinese providers, the barrier shifts from technical capability to market access. And market access, once the regulatory pathway exists, tends to open quickly. The numbers confirm the trajectory. In 2025, China exported the equivalent of $4.34 billion worth of prefabricated building structures internationally. That figure represents a 42% increase in exports to Gulf markets compared to the previous year. The growth rate is not slowing. Both the supply side and the demand side are accelerating simultaneously. Construction has been, for most of human history, a craft industry. Buildings were made by skilled workers assembling materials on site, in variable weather, with variable quality outcomes, at timelines that have not fundamentally changed in decades despite improvements in equipment and materials. Every other major manufacturing sector has already undergone the transition from craft production to industrial production. Automobiles made the shift over a century ago. Consumer electronics made it 50 years ago. Clothing, furniture, appliances, all of them moved from hand-built to factory-built at some point in the 20th century. And in each case, the result was the same: Output increased dramatically, costs fell, and access expanded to populations that previously could not afford the product. Housing has resisted this shift longer than any other sector, partly because of the regulatory complexity of building codes, partly because of the deeply local nature of construction labor markets, and partly because the industry's culture has been slow to accept that a building can be treated as a manufactured product. Broad and CSCEC are not arguing this point anymore. They are simply doing it, at scale, in markets far outside China, with commercial clients who have evaluated the technology and decided it is ready. The 30-story hotel in 2011 was version 1 of a system that is now on perhaps version 8 or 9, deployed internationally, validated by credentialed buyers, and backed by a production infrastructure that treats housing the way Toyota treats the Corolla. What I find genuinely fascinating about this story is not the 96 hours. The headline number is striking, but the deeper point is about what happens to housing affordability when you apply industrial production logic to residential construction. If a factory can produce 84,000 housing units a year, and the economics of modular construction continue to improve as the system scales, the cost floor for residential construction drops in a way that nothing else currently on the horizon can match. That has implications for housing markets in the Gulf, in Southeast Asia, in Africa, and eventually in Western cities where construction costs have made affordable housing effectively impossible to deliver at the required pace. The construction industry has had a century of warning that this transition was coming. It is here now, and the company leading it is operating out of central China, not out of London or New York or Tokyo. Here is my question for you. If a broad-built apartment was available in your city, fully finished, structurally certified, assembled in under a week, would you buy or rent one? Or does the speed of construction make you nervous regardless of what the data says about quality? Drop your honest answer in the comments. I think the responses are going to split pretty sharply, and I want to see where people land. If you want to keep following stories like this, technology and engineering developments that are reshaping industries most people are not paying close enough attention to, subscribe to Eastern Engine and turn on notifications. We cover these shifts as they happen, with the depth they deserve. There is a lot more coming, and you do not want to be catching up later. Turn off a computer, and something strange happens. The files on the SSD remain exactly where they were, but everything held inside RAM disappears. Open documents, active calculations, temporary AI data, the precise state of every running program, all of it vanishes the moment electrical power is removed. That is the basic compromise inside nearly every modern computer. Fast memory forgets. Memory that remembers is slower. But researchers at Fudan University in Shanghai have built a device that appears to challenge that division. Their experimental flash memory stored information without continuous power, survived more than 5.5 million write cycles, and completed a programming operation in just 400 picoseconds. A picosecond is 1/trillionth of a second. At that speed, the device can theoretically complete 2.5 billion programming events in 1 second. Compared with conventional flash memory, whose programming time is often measured in tens of microseconds, the difference can approach 100,000 times. And the researchers say their device can program faster than SRAM built with the same channel length. That sounds like the beginning of universal memory. One technology combining the speed of working memory with the persistence of storage. But this is not yet a commercial RAM replacement. It is not a terabyte SSD. And the 400 picosecond result came from a tiny experimental device under carefully controlled conditions. The real breakthrough is more fundamental. For decades, engineers assumed that flash memory could not cross the 1 nanosecond barrier because its method of storing charge was simply too slow. Fudan's team crossed it. Then, months later, the same researchers integrated their two-dimensional memory technology with conventional silicon electronics and created a functional flash chip. The first experiment proved the physics. The second showed a possible path toward actual hardware. Together, they raise a much larger question. What happens if computers no longer have to choose between speed and memory that survives when the power goes out? The chalkboard and the stone tablet. A computer's memory system is not one single pool. It is a hierarchy. At the top are tiny registers inside the processor. They are extraordinarily fast, but there are very few of them. Below that is cache, followed by system RAM. These layers hold data close to the processor so calculations can happen quickly. Farther away sits persistent storage, SSDs and hard drives. Storage provides far more capacity, but the processor must wait longer to reach it. The arrangement exists because no single memory technology delivers every desirable property at once. SRAM is extremely fast, but it takes a large amount of silicon area and loses information without power. DRAM is denser and cheaper, but it must constantly refresh its electrical charge and also forgets when powered down. NAND flash stores enormous quantities of data and remembers without electricity, but writing to it is dramatically slower. Think of RAM as a chalkboard. Writing is immediate, erasing is easy, but when the lights go out and the room is cleaned, the information disappears. Flash memory is closer to carving a message into a stone tablet. The inscription remains. The problem is that carving takes time. Fudan's POX device is an attempt to write on the stone tablet at chalkboard speed. Why normal flash is slow. Flash memory stores information by trapping electrical charge inside an insulated layer. The presence or absence of that charge changes how the memory cell behaves electrically, allowing the device to represent zeros and ones. The charge must cross an energy barrier to enter the storage region. In conventional flash, this commonly happens through tunneling or hot carrier injection. Both methods work. Neither is naturally instantaneous. In Fowler-Nordheim tunneling, a strong electric field encourages electrons to pass through an insulating barrier that they would not normally cross. The effect is reliable, but moving enough charge takes time and often requires relatively high voltage. Hot carrier injection takes another route. Electrons accelerate along the memory channel. Some gain enough energy to jump into the storage layer. The faster and more efficiently those carriers are accelerated, the faster the memory can be programmed. Silicon places practical limits on that acceleration. The electric field is not distributed perfectly, and only a small percentage of carriers become energetic enough to cross the barrier. Engineers have improved flash memory for decades through better materials, thinner structures, and more sophisticated control. But the underlying mechanism remains slow compared with volatile memory. The accepted assumption was simple. Flash could become denser, it could become cheaper, it could consume less standby power. But sub-nanosecond programming was beyond its natural limit. The Fudan researchers attacked that limit by changing the channel material itself. The graphene channel. The experimental memory uses graphene as its channel. Graphene is a sheet of carbon only one atom thick. Its electrons behave differently from those moving through ordinary silicon. Under the right conditions, they can travel with very high mobility and experience unusual energy relationships associated with what physicists call a Dirac material. The important feature here is not simply that graphene is thin, it is how that thinness changes the electric field inside the device. In a conventional silicon channel, the horizontal electric field used to accelerate carriers is distributed across a thicker body. In the two-dimensional channel, the field becomes more concentrated. The carriers accelerate more effectively. More of them reach the high-energy state needed to enter the storage layer. The researchers call this two-dimensional enhanced hot carrier injection. Imagine two ramps reaching the same wall. Researchers observed in a comparable silicon system. More charge entered the storage region in less time. That is what enabled the 400 picosecond programming pulse. What 400 picoseconds means? 400 picoseconds equals 0.4 nanoseconds. Light travels only about 12 centimeters in that amount of time. A modern processor running at 5 GHz completes one clock cycle every 200 picoseconds. So the POX programming operation occurred within roughly 2 processor clock cycles at that frequency. That is an astonishing figure for non-volatile flash memory. Conventional silicon flash can require 10 to 100 microseconds to program a cell. 10 microseconds divided by 400 picoseconds is 25,000. 100 microseconds divided by 400 picoseconds is 250,000. That is why describing the breakthrough as approximately 100,000 times faster is reasonable. But it is not one fixed multiplier for every existing flash technology. The comparison depends on the specific device, operating conditions, and definition of programming time. The researchers tested a graphene device with a channel length of 0.2 micrometers and a programming voltage of around 5 volts. They repeated the short pulse measurement and observed a stable memory response. They also demonstrated a related device using tungsten diselenide, another two-dimensional material, which achieved 1 nanosecond programming through hot hole injection. This suggests the mechanism is not limited to one isolated graphene sample. Different two-dimensional materials may support different versions of the same general approach. Never forgets needs context. The device does not literally remember forever. No physical storage medium does. Never forgets means the information remains when electrical power is removed. That makes it non-volatile. SRAM and DRAM require continuous power to preserve their states. Remove the voltage and the stored information disappears almost immediately. flash traps charge inside an insulated region, allowing the state to survive. The Fudan device maintained a measurable non-volatile memory window, after programming and demonstrated endurance beyond 5.5 million cycles. That is important because speed alone would not make a useful memory. A device that writes in 400 picoseconds but fails after a few operations is a laboratory curiosity. A device that performs millions of cycles begins to look more credible. However, endurance testing on a small research device is not the same as proving reliability across billions of cells operating for years inside consumer hardware. Commercial memory must survive temperature changes, manufacturing variations, electrical noise, and repeated operation across a complete chip. The prototype established that the mechanism can be fast and repeatable. It did not complete the industrial journey. Why AI cares about this? Modern processors are becoming faster than the systems feeding them. This is known as the memory wall. An AI accelerator may contain thousands of arithmetic units capable of performing enormous numbers of calculations. But those units need model weights, activations, and intermediate results. If data arrives too slowly, the accelerator waits. The chip may be powerful enough to perform the operation. The memory system prevents it from starting. Moving data also consumes energy. In many AI workloads, transporting values between storage, DRAM, and the processor can use more energy than the calculation itself. That is why high-bandwidth memory has become so valuable. It places large amounts of fast memory extremely close to AI processors. But HBM is expensive, complicated to package, and still volatile. Every time a system starts, model data must be loaded from persistent storage into fast memory. Imagine a library that burns every book each night and reconstructs the collection every morning from a warehouse. The readers eventually receive the information. The rebuilding process wastes time and energy. A fast, non-volatile memory could preserve important data close to the processor even after shutdown. AI models might start more quickly. Edge devices could retain local model states without constantly refreshing memory. Computers could reduce the amount of data copied repeatedly between storage and working memory. This is the larger promise behind ultra-fast persistent memory. Could it replace RAM? Not today. The prototype demonstrated exceptional programming speed in an individual memory structure. A complete RAM system requires much more. Billions of cells must be arranged into dense arrays. Every cell must be selected without accidentally disturbing its neighbors. Read and write circuits must operate quickly. Manufacturing yield must be high. The chip must fit existing processor and memory interfaces. Cost per bit must compete with technologies produced in enormous factories. Latency also includes more than the programming pulse. A real computer must send an address, select the correct cell, move signals through wires, sense the stored state, correct errors, and transfer the result to the processor. A 400 picosecond device operation does not mean a future memory module will automatically deliver 400 picosecond system latency. The difference resembles a car engine capable of reaching a certain rotational speed. That number matters. But the speed of the complete vehicle also depends on the transmission, tires, aerodynamics, and road. The experimental device proved the engine. The researchers still needed to build more of the car, and that is exactly what they attempted next. The second breakthrough. Later in 2025, the Fudan team reported a full-featured two-dimensional NOR flash memory chip integrated with conventional silicon CMOS electronics. This was a major step beyond the original device demonstration. The new chip used the two-dimensional material as the memory core while mature silicon circuitry handled instruction control and system operation. The researchers called the integration method ATOM2CHIP. The chip supported random access, 8-bit instruction operations, and 32-bit parallel operation. Full chip testing produced a reported memory cell yield of 94.34%. Its integrated memory cells operated in 20 nanoseconds and consumed as little as 0.644 picojoules per bit. 20 nanoseconds is far slower than the original 400 picosecond pulse. That does not mean the later chip failed. It means integration introduces real-world overhead. The signal must pass through control circuits. Cells must be addressed. Operations must occur across an array rather than one optimized test device. The integrated chip sacrificed record-setting speed in exchange for functionality. That is often how new technology develops. The first prototype demonstrates an extreme physical result. The first system trades some of that result for reliability, control, and manufacturability. 20 nanoseconds is still fast for non-volatile flash memory. More importantly, the researchers showed that the two-dimensional memory could communicate with a conventional CMOS platform. Why integration is so difficult? Two-dimensional materials can be only one or a few atoms thick. That creates remarkable electrical properties. It also makes manufacturing difficult. A conventional silicon chip surface may look perfectly smooth to the human eye. At atomic scale, it resembles rough terrain. Different structures rise from the surface. Metal lines, insulating regions, and contacts create tiny height variations. Placing an atomically thin layer directly across that surface is like stretching plastic film over an entire city. From an airplane, the land looks flat. At street level, buildings, bridges, and towers make a smooth covering impossible. The film can wrinkle, tear, lose electrical performance, or fail to contact the correct region. The Fudan team's solution was modular. They manufactured the two-dimensional memory section and conventional CMOS control circuitry separately, then connected them through dense vertical interconnects. This allowed the new material to preserve its performance without requiring the entire silicon surface to become atomically flat. The approach also avoids rebuilding every part of the computer from experimental materials. Conventional CMOS remains excellent at logic. The two-dimensional layer performs the memory function, where its unusual physics provides the greatest advantage. This hybrid strategy may be more realistic than attempting to replace silicon completely. NOR flash versus the SSD in your computer. The integrated chip was a form of NOR flash. That distinction matters. Most large SSDs use NAND flash. NAND is optimized for extremely high density and low cost per bit. It arranges cells in long strings and reads or writes data in larger blocks. NOR flash offers direct random access and is commonly used for firmware and code storage, where rapid, precise access matters more than maximum capacity. The Fudan device therefore should not be imagined as an immediate replacement for a multi-terabyte NAND SSD. Its potential may first appear in applications requiring fast persistent access, processor boot code, AI accelerator configuration, embedded systems, automotive electronics, edge computing devices, persistent cache, memory placed close to specialized processors. These markets may tolerate higher cost per bit if the technology reduces startup time and energy consumption. Only after manufacturing improves could the concept challenge larger portions of the memory hierarchy. The dream of universal memory. Engineers have pursued universal memory for decades. The ideal technology would combine 5 properties: SRAM-like speed, DRAM-like density, flash-like persistence, low energy consumption, and nearly unlimited endurance. No existing memory provides all 5. Phase change memory retains data and can be fast, but heat and material changes create challenges. Magnetic memory offers strong endurance, but scaling and density remain difficult. Resistive memory can switch quickly, yet device-to-device variation complicates large arrays. Ferroelectric memory is promising, but integration and long-term reliability remain active engineering problems. POX adds another candidate. Its unusual advantage is that it remains a charge storage device related to flash, but changes the injection mechanism using two-dimensional materials. That connection to familiar flash principles could help engineers understand and adapt the technology. Still, universal is an extremely demanding word. A memory can be fast but too expensive, persistent but insufficiently dense, efficient but difficult to manufacture. The winner will not be determined by one record. It will be determined by which technology can survive a factory. What still has to happen? The first challenge is scale. The research team must move from small arrays to millions and eventually billions of memory cells. Yield becomes harder as the array grows. A 94% yield sounds strong for an early research chip. For mass production, even a small defective percentage can become unacceptable when billions of cells are involved. The second challenge is uniformity. Atomically thin materials must behave consistently across large wafers. A small difference in thickness, contamination, or contact resistance can change device performance. The third challenge is density. The memory must store enough bits per unit area to justify its cost. The fourth challenge is voltage. The prototype used programming voltages around 5 volts. Future systems may need lower operating voltage to reduce power and simplify integration. The fifth challenge is economics. Graphene and other two-dimensional materials must be deposited, patterned, and connected using processes compatible with high-volume semiconductor manufacturing. A technology can outperform existing memory and still lose if each chip costs 10 times more. The final challenge is time. The researchers have discussed expanding toward much larger integration within several years. That is ambitious. Even successful semiconductor technologies can require a decade or more to move from laboratory demonstration to widespread commercial use. My take. My view is that the most important result is not the 100,000 times headline. The speed is spectacular. But research laboratories produce spectacular isolated numbers regularly. What makes this story different is the sequence. First, the team demonstrated a 400 picosecond non-volatile flash device. Then it built a functional hybrid chip around the same broader two-dimensional memory concept. The system was slower than the record prototype, but it could execute instructions, perform parallel operations, and access memory randomly. That is progress in the correct direction. The first result said, the physical speed limit can be broken. The second said, the device can begin participating in a real circuit. China has not eliminated RAM. It has not produced a commercial universal memory chip. And no laptop shipping today contains POX memory. But the traditional boundary between fast volatile memory and slow persistent storage looks less permanent than it did before. For most of computing history, the rule was simple. Anything fast enough to serve the processor forgot when power disappeared. Anything that remembered was forced into a slower tier. The Fudan experiments show that this rule is not fundamental. It is a consequence of the materials and device structures we currently use. Change the material, reshape the electric field, accelerate the carriers differently, and flash memory can enter a speed range that once appeared impossible. The hardest work begins now: scaling, manufacturing, reducing voltage, improving yield, and proving that the technology can remain reliable outside a research laboratory. But every commercial memory technology began with a device that looked too small, too unusual, or too expensive to matter. The question is whether POX follows the same path or remains a brilliant record in a scientific paper. So what do you think? Could ultra-fast non-volatile memory eventually replace both RAM and flash with one universal technology? Or will manufacturing cost and scaling challenges keep the computer's memory hierarchy intact? Let me know your view in the comments. And if you want more grounded stories about the chips, materials, and hidden engineering breakthroughs reshaping computing, subscribe to Eastern Engine, because the next revolution in memory may not be a drive with more capacity, it may be a chip that refuses to forget. For years, the world's fastest supercomputers have followed one dominant formula. Start with powerful central processors. Add enormous numbers of specialized GPU accelerators. Connect everything with an ultra-fast network. Then, use those GPUs to perform the mathematical work that would overwhelm ordinary CPUs. America's El Capitan follows that model. It combines AMD server processors with AMD Instinct MI300A accelerators and delivers more than 1 quintillion calculations every second. It held the official title of the world's fastest publicly ranked supercomputer. Until now, a previously unlisted Chinese machine called Lineshine has entered the official TOP 500 ranking at number 1. Its verified performance is 2.198 exaflops. America's El Capitan recorded 1.809 exaflops. That places the Chinese system approximately 21.5% ahead on the benchmark used to determine the global ranking. But the most surprising part is not simply that China moved into first place, it is how Lineshine got there. The machine reached more than 2 exaflops of sustained double-precision computing without dedicated GPU accelerators. No NVIDIA GPUs. No AMD Instinct accelerators. No Intel data center GPUs. Instead, Lineshine uses millions of custom Chinese CPU cores, a proprietary interconnection network, and a domestic software stack. It is the first publicly ranked supercomputer to sustain more than 2 exaflops using CPUs alone. That does not automatically make it the best AI computer in the world. It does not mean GPUs are suddenly obsolete, and one benchmark can never describe every workload a machine may encounter. But this result is official. China has taken the #1 position on the TOP 500 for the first time since 2017, and it did so by rejecting the architecture used by almost every other leading exascale machine. What officially #1 actually means. The top 500 list has ranked the world's most powerful publicly disclosed supercomputers since 1993. It is updated twice each year. To determine the ranking, systems run a benchmark known as High Performance LinPack, or HPL. HPL asks the computer to solve an enormous system of dense linear equations using high-precision, 64-bit floating-point mathematics. This kind of calculation appears in scientific simulation, engineering, and numerical analysis. The benchmark measures how many floating-point operations the machine can sustain each second while solving the problem. A petaflop is 1 quadrillion operations per second. An exaflop is 1 quintillion. Lineshine sustained 2.198 exaflops. Written out, that is roughly 2.198 quintillion floating point operations every second during the benchmark. The number is not a theoretical marketing figure. Lineshine's theoretical peak is higher, at approximately 2.736 exaflops. But theoretical peak assumes every component operates perfectly. Every cycle is fully utilized and no time is lost to communication, memory access, or software overhead. Real machines never maintain theoretical peak continuously. Lineshine converted slightly more than 80% of its theoretical capability into measured HPL performance. That is one of the most important details in this story. Building millions of processor cores is difficult. Keeping them busy at the same time is much harder. A supercomputer does not become fast merely because it contains many processors. The processors must communicate, share data, synchronize, and divide a single enormous problem without spending most of their time waiting. Lineshine's 80% result suggests that its architecture is not simply large, it is highly coordinated, inside the CPU-only machine. Lineshine is installed at the National Supercomputing Center in Shenzhen. The machine was built by the Shenzhen Cloud Computing Center and is based on a custom platform called Lingkun. At its core is a Chinese processor known as the LX2. Each LX2 contains 304 CPU cores running at 1.55 GHz. The complete system contains 13,789,440 cores. Divide that total by 304, and the architecture appears to use roughly 45,360 of these processors. That is not 45,000 individual desktop computers. These processors are installed in densely packed computing nodes, surrounded by memory, cooling equipment, power distribution systems, and the network required to connect the entire machine. A modern GPU may contain thousands of smaller parallel computing units. Lineshine instead spreads its work across a vast population of general-purpose CPU cores. The individual clock frequency of 1.55 GHz may sound modest compared with a consumer desktop processor that can exceed 5 GHz. But supercomputers are not built to make one core run as fast as possible. They are designed to make millions of cores work together. A higher clock frequency increases power consumption and heat. At this scale, efficiency, parallelism, and communication matter more than winning a single core benchmark. Imagine trying to move a mountain. One extremely strong worker cannot do it. 45,000 organized teams might, but only if every team knows exactly which section to move, where to place it, and when to act. Without coordination, adding more workers can make the project slower. That is why the process connects its processors using a proprietary Chinese interconnect called Lingqi. The public technical information remains limited, but the benchmark results reveal that this network is doing serious work. HPL involves regular, predictable mathematics, making it easier to divide efficiently than many real scientific applications. However, Lineshine also ranked first on a second benchmark called HPCG. HPCG stands for High Performance Conjugate Gradients. Unlike HPL, it places greater pressure on memory access, communication, and irregular data movement. These are the parts of supercomputing that often prevent theoretical performance from becoming useful performance. Lineshine achieved approximately 22 petaflops on HPCG. El Capitan achieved around 17.4 petaflops. That places Lineshine roughly 26% ahead on this second measurement. This result is important because it weakens the simplest criticism. The machine did not merely win one highly optimized matrix calculation while collapsing on a more communication-intensive workload. It also led the benchmark intended to represent patterns found in real scientific applications more closely. HPCG is still only a benchmark. No single test can reproduce climate modeling, fluid dynamics, molecular simulation, seismic analysis, and every other scientific workload. But finishing first on both HPL and HPCG suggests that Lineshine's interconnect and memory system are not afterthoughts. The architecture appears balanced enough to keep millions of CPU cores supplied with data. Why build a supercomputer without GPUs? The obvious question is why anyone would avoid accelerators. GPUs became dominant in supercomputing for a reason. A CPU is designed to handle a broad range of instructions. It is flexible. It can manage operating systems, complicated decision-making, serial code, and workloads with unpredictable branches. A GPU is narrower but massively parallel. It excels when the same mathematical operation must be applied across enormous arrays of data. Scientific simulations and neural networks are filled with those operations. That is why America's leading machines use accelerators. El Capitan combines AMD EPYC processors with MI300A accelerated processing units. Frontier uses AMD MI250X accelerators. Aurora uses Intel GPU Max accelerators. Europe's Jupiter Booster uses NVIDIA Grace Hopper superchips. Against that field, Line Shine looks almost deliberately unconventional. One possible advantage is programming simplicity. Accelerated systems divide applications between CPUs and GPUs. Developers must decide which code runs where, move data between different memory spaces, and optimize software for specialized hardware. A CPU-heavy machine can provide a more uniform programming environment. The same processor type handles more of the workload. That does not make programming easy, especially across nearly 14 million cores, but it can reduce the architectural divide between a host processor and an accelerator. CPU-based systems may also perform well on workloads that contain complex control logic, irregular memory access, or sections that do not map cleanly onto GPUs. The disadvantage is efficiency. GPUs can perform far more parallel arithmetic per watt on suitable workloads. To compete without them, Line Shine must deploy an enormous number of CPU cores and keep those cores highly utilized. The machine is not proving that accelerators were a mistake. It is proving that accelerator-free exascale computing remains possible when processors, memory, software, and networking are designed as one system. An entirely custom computing stack. Line Shine is not only unusual because it avoids GPUs, its major layers are Chinese-developed. The processors are custom LX2 chips. The computing platform is called Ling Kun. The interconnect is Ling Qi. The operating system is Keilin. The benchmark submission also lists a customized compiler and locally adapted mathematical software. This matters because supercomputer performance depends on more than silicon. A powerful processor running poorly optimized code can waste most of its theoretical capability. The compiler must translate software into instructions that exploit the processor's architecture. The mathematical libraries must perform common operations efficiently. The operating system must coordinate resources across thousands of nodes. The communication software must move messages across the network without creating unnecessary delays. When a system achieves 80% of its theoretical peak on HPL, that usually means multiple layers have been optimized together. The hardware team cannot work in isolation. Neither can the software team. The machine behaves less like a collection of separate products and more like one enormous engineered instrument. This full-stack approach may be the real achievement. China did not simply build a processor and insert it into an existing American or European supercomputer design. It submitted a complete domestic platform capable of taking first place on two major rankings. The power bill behind the performance. There is a cost. Line Shine draws approximately 42.2 megawatts while delivering its submitted performance. That is industrial-scale power consumption. At that rate, operating continuously for 24 hours would require more than 1,000 megawatt-hours of electricity. Cooling the hardware adds another major engineering challenge. Every watt entering a processor eventually becomes heat. Thousands of high-density computing nodes must be cooled continuously, because overheating can reduce performance or damage components. Line Shine achieves an energy efficiency of approximately 52.07 gigaflops per watt. El Capitan records around 60.94 gigaflops per watt. That makes the American system roughly 17% more efficient on the reported metric. This is where the accelerator advantage becomes visible. Line Shine wins the raw HPL ranking. El Capitan produces more computation from each watt. Neither result cancels the other. The Chinese system was designed to maximize sustained high-precision CPU performance. The American system combines CPUs and specialized accelerators to improve performance across traditional simulation and mixed precision workloads. Two different architectural philosophies produce different strengths. In an era when electricity and cooling are becoming limits on both supercomputers and AI data centers, energy efficiency cannot be ignored. Winning the performance crown is impressive. Operating the machine economically for years is a separate challenge. The AI benchmark changes the story. This is the most important caveat. Line Shine is officially number 1 on HPL. It is also number 1 on HPCG. But when the benchmark shifts toward lower precision mathematics used heavily in artificial intelligence, the ranking changes. The HPL MXP benchmark measures mixed precision performance. Traditional scientific calculations often use 64-bit precision because tiny errors can accumulate and affect the final result. Many AI workloads can use 32-bit, 16-bit, 8-bit, or even lower precision numbers. Specialized accelerators are extremely fast at these operations. On HPL MXP, Line Shine achieved approximately 7.92 exaflops and ranked 4th. El Capitan achieved 16.7 exaflops and remained number 1. That means El Capitan delivered more than twice Lineshine's mixed precision result. This is why the phrase "world's fastest supercomputer" needs context. Lineshine is the fastest system on the official benchmark used to rank the top 500. That benchmark measures sustained double precision performance. It does not prove that Lineshine will train the largest AI model faster than El Capitan. It does not prove that it will outperform GPU systems on every application. For AI-style low-precision mathematics, El Capitan's accelerators provide a major advantage. The two machines are like different vehicles. Lineshine is an enormous high-precision freight engine capable of moving a massive scientific workload. El Capitan is a hybrid machine with specialized engines for different terrain. On the official straight-line test, Lineshine wins. On the mixed precision AI test, El Capitan pulls far ahead. Does no GPU mean the return of the CPU? Not exactly. GPUs are not disappearing from supercomputing. In fact, accelerator adoption continues to grow across the TOP 500. AI demand is making specialized low-precision computing more important, not less. Lineshine demonstrates a different point. There is no single correct architecture for every supercomputer. The best design depends on the workload. If a research center prioritizes high-precision scientific simulation, CPU flexibility, and a uniform programming environment, a massive CPU-based design may remain competitive. If the goal is training neural networks or running mixed precision mathematics, specialized accelerators are difficult to beat. Future systems may become even more heterogeneous. They may combine CPUs, GPUs, AI accelerators, photonic processors, and custom chips, assigning each task to the hardware that performs it most efficiently. Lineshine stands out because it moves in the opposite direction. Instead of adding more types of processors, it scales one processor architecture to an extraordinary level. That simplicity at the component level creates extreme complexity at the system level. Nearly 14 million cores must operate as one computer. The fact that they do so efficiently enough to reach 2.198 exaflops is the central engineering story. What will China use it for? The public top 500 entry identifies Lineshine as a research system at the National Supercomputing Center in Shenzhen. Supercomputers at this level can support many categories of scientific work. Possible workloads include weather forecasting, materials discovery, fluid dynamics, engineering simulation, molecular modeling, and large-scale numerical research. However, the precise workload mix and access policies for Lineshine have not been fully disclosed publicly. That lack of detail matters. Benchmark numbers tell us what the machine achieved during controlled tests. They do not tell us how much useful scientific work it completes each week, how easy it is to program, or how reliably it operates under sustained demand. A supercomputer becomes valuable when researchers can use it efficiently. Applications must be rewritten or optimized for the architecture. Scientific teams need access. Storage systems must feed enormous datasets into the machine. The system must remain stable, while millions of components operate simultaneously. China has demonstrated the hardware platform. The next evidence will come from published scientific results produced using it. Why this changes the global supercomputing picture. Before Lineshine entered the ranking, the top positions were dominated by American accelerated systems. El Capitan was first, Frontier was second, Aurora was third. The United States had established a clear lead in publicly ranked exascale computing. Lineshine did not slowly climb from 10th place to 5th and eventually first. It appeared directly at the top. That creates two important changes. First, the official performance lead has moved back to China for the first time since 2017. Second, the machine expands the definition of what an exascale system can look like. The industry had been moving toward the belief that accelerators were practically mandatory at this scale. Lineshine proves that a CPU-only approach can still win the traditional performance crown. Whether that approach becomes widely copied is another question. The power demand is substantial. Its AI performance is weaker than El Capitan's, and the public technical details are not yet deep enough for outside experts to evaluate every design decision. But the result cannot simply be dismissed. Top 500 accepted the submission. The measured numbers place Lineshine first, and its HPCG result strengthens the claim that this is more than a narrowly optimized demonstration. The honest catch. There are four major caveats. First, Lineshine is number one on specific benchmarks, not automatically on every real application. Second, its lack of dedicated, low-precision accelerators limits its advantage in modern AI computing. Third, it consumes more power per unit of reported performance than El Capitan. Fourth, many architectural details remain proprietary or publicly unexplained. We know the processor core count, clock frequency, system platform, interconnect, operating system, and benchmark results. We know much less about the internal design of the LX2 core, its memory hierarchy, vector capabilities, manufacturing process, packaging, and the exact topology of the Lingqi network. Those details would help explain how China reached this level without GPUs. Until more information or scientific performance results appear, some questions must remain open. But uncertainty around the details does not erase the verified result. Lineshin sustained more than 2 exaflops of high-precision performance and displaced El Capitan from the top of the official list. My take is that the #1 ranking is important, but the architectural divergence is even more important. China did not win by building a slightly larger copy of El Capitan. It chose a different route. America concentrated enormous parallel performance inside advanced accelerators. China distributed the work across nearly 14 million custom CPU cores and built a network powerful enough to keep them synchronized. The American design is more efficient and much stronger on mixed precision AI mathematics. The Chinese design is now faster on the traditional HPL benchmark and also leads HPCG. This is not a simple story of one country possessing better technology in every category. It is a story of 2 systems optimized around different strengths. Lineshin shows what can happen when processor design, networking, software, and system architecture are developed together around one objective. It also shows that mature technologies can still produce surprising results. The CPU was supposed to become a supporting actor in the exascale era. Lineshin put millions of CPUs at the center of the machine and reached #1. The question now is whether this is a one-time engineering achievement or the beginning of a broader CPU-first supercomputing strategy. Will China continue scaling the Lincoln platform? Will future LX processors improve energy efficiency and mixed precision performance? Will Lineshin produce scientific results that justify its enormous size and power demand? And will American laboratories respond with even larger accelerated systems? The supercomputer race has not ended. It has become more interesting because the leading machines are no longer following the same blueprint. So what matters more to you? Should Lineshin be considered the world's most powerful supercomputer because it officially ranks first on HPL and HPCG? Or does El Capitan's stronger efficiency and AI-oriented performance make it the more capable overall machine? Let me know your view in the comments. And subscribe to Eastern Engine for more grounded coverage of the chips, materials, and computing systems changing the global technology industry. Because China did not take the supercomputer crown by copying the dominant design. It took the crown by proving there was another road to exascale. Picture the emptiest place you can imagine. No buildings, no roads worth mentioning, just cracked earth, howling wind, and a sky that goes on forever. Now drop the single largest wheeled crane ever constructed right in the middle of it. A machine so absurdly oversized that engineers around the world genuinely questioned whether building it was even worth attempting. This is not a concept. This is not a prototype sitting in a lab. This machine was built, transported over 2,000 kilometers, assembled from scratch in the desert, and then put to work doing something no crane had ever done before on wheels. And when the job was finished, the construction industry had to rewrite what it thought was possible. Before we talk about the crane itself, we need to talk about why it exists at all, because this machine was not built to set records. Records were just a side effect. China has a massive energy challenge. The country needs enormous amounts of electricity, and it has been pushing hard toward wind power as a way to meet that demand without burning more fossil fuels. The Gobi Desert in northwest China turns out to be one of the best wind corridors on the planet. The air moves fast out there, consistently, predictably, across hundreds of kilometers of open terrain. If you can tap into that energy, you can power entire cities. So China has been doing exactly that, building wind farms across the Gobi on a scale that is almost difficult to visualize. Hundreds of turbines, then thousands, more going up every year. But here's the problem that nobody talks about when they show you footage of a wind farm looking serene and picturesque. The turbines keep getting bigger. Engineers discovered that a taller turbine with longer blades catches dramatically more wind than a shorter one. The math is not subtle. Go bigger, generate far more power per structure. So the turbines grew, and then grew some more. The latest generation of turbines being installed in the Gobi now stand over 170 meters tall. That puts them in the same height range as major skyscrapers. At the very top of that tower sits a component called the nacelle. a massive enclosed unit that houses the generator, the gearbox, and the control systems. On these newer models, that nacelle weighs north of 150 tons. And then you have the blades. 3 of them, each stretching 108 meters from root to tip. Longer than a regulation American football field, end to end. You have to lift all 3 of them, one at a time, up to the top of a structure taller than most buildings in the world and pin them into place precisely. Regular cranes top out well below this challenge. The best heavy lift cranes used in urban construction can handle around 900 tons. Impressive, until you realize that this operation required something that could manage 4,000 tons, more than 4 times greater, at heights that city cranes never need to reach. That gap between what existed and what was needed is why the Zoomlion ZADET 40000 was born. Zoomlion is a heavy machinery company based in Changsha in China's Hunan province. They already had a strong reputation in the crane world. But when the wind energy sector started demanding lifts at heights and weights that no existing equipment could handle, their engineers got to work on something genuinely unprecedented. The ZADET 40000 is technically classified as an all-terrain crane, meaning it rides on wheels and can be driven to a job site rather than being built in place. That distinction matters enormously because building a crane that stays in one location permanently is a totally different engineering challenge from building one that has to travel across highways, get disassembled and reassembled, and function reliably in extreme desert conditions. The numbers on this machine are staggering in every direction. Its main lifting boom, once fully assembled, reaches a working height of over 186 meters. That figure alone, roughly 60 stories straight up, would be the headline on almost any other crane. Here it is just the starting point. The counterweight system, which is what keeps a crane from toppling forward when it lifts heavy loads, uses 2 large outrigger arms called superlift wings that spread out behind the crane's body. For the wind turbine installation, the crew loaded 260 tons of counterweight onto those wings. And here is the detail that really lands. That was not even close to the crane's maximum counterweight capacity. It had significant additional headroom for heavier jobs. Individual components of this crane are themselves enormous. The rotating base platform that allows the crane to swing its boom in any direction weighs 65 tons on its own. Each of the 2 main boom base sections weighs 66 tons. The hydraulic cylinders that drive the crane's mechanical systems come in at 32 tons each. When you start adding up all the pieces, the total weight of the assembled crane is simply difficult to hold in your head as a real number. Here is where the story picks up a challenge that the crane's specs alone don't convey. Getting this machine to northwest China was its own logistical operation. The crane does not travel assembled. It travels as hundreds of individual components loaded across a convoy of 28 specialized transport vehicles. When that convoy rolls down the highway, it does not look like a single piece of equipment being delivered. It looks like an entire industrial district changing neighborhoods. The journey from Changsha to the job site in the Gobi covered more than 2,000 kilometers. Route planning for a convoy like this requires months of advance work. Bridge weight limits, tunnel clearances, road curvature, overhead power line heights, every single kilometer has to be assessed in advance. Some sections require escort vehicles. Some require nighttime travel to avoid disrupting daytime traffic. Some require temporary road reinforcements so the heaviest pieces don't crack the pavement. After all of that, the convoy arrived at the desert site and the team immediately began the next challenge, putting the machine together from nothing, outdoors, in one of the most inhospitable environments in China. Assembling the world's largest mobile crane in the middle of the Gobi Desert is not a weekend job. It requires multiple support cranes working in coordination, teams of engineers monitoring every measurement and connection, and the kind of patience that comes with knowing that one misaligned component early in the process can cascade into days of rework. The process started with the slewing platform, that 65-ton rotating ring at the base. Support cranes lifted it into position while the main crane chassis was brought into precise alignment beneath it. The connection requires hydraulic locking pins to seat perfectly. A centimeter of misalignment at this stage affects every lift that follows. Then came the outrigger installation. These are the thick hydraulic legs that extend outward from the crane's body to provide a stable base during lifts. Once deployed, they extend so far out that they essentially bury the crane's tires from view. On top of each outrigger foot, the crew installed large ground pads, wide flat plates that distribute the crane's concentrated weight across a broader footprint of desert floor. Without them, the outriggers would punch straight down into the earth. The boom assembly came next. 7 sections, connected in sequence, each one added using hydraulic pin systems rather than the old-fashioned hammer and brute force method. As each section locked into place, the crew ran alignment measurements from the lifting hook's center point all the way back to the crane's rotational axis. That single measurement, accurate to within centimeters, determined whether the machine could operate safely at full capacity. When the superlift wings finally spread open and the full counterweight was loaded, the assembled machine transformed. From a distance, it stops looking like a piece of construction equipment. It looks more like something from a different era of engineering, something built to move a mountain rather than lift a component. The actual turbine installation required 3 cranes working in stages, each one handling the section of the tower within its capacity range before handing the job off to the next. A 900-ton crane started the work, placing the foundation ring and the lower tower sections. A 1,800-ton crane took over for the middle portion of the tower, stacking each heavy segment as the structure climbed. By the time those 2 machines had done their work, the tower was already taller than anything around it for hundreds of kilometers. Then the ZAT 40000 hour took over. The final tower sections went up first, bringing the structure to its full height of over 170 meters. Then came the nacelle lift, 150 tons of machinery swinging at the end of a cable higher above the ground than almost anything in the region. The crew attached guide ropes to all 4 corners of the nacelle before it left the ground. As the crane lifted it skyward, ground teams kept constant tension on those ropes, preventing the wind from catching the nacelle and spinning it into the tower. At that height, an uncontrolled rotation does not result in a minor problem. It results in a catastrophic structural failure. So the teams held on, adjusting and compensating, while the crane lifted steadily upward until the nacelle seated onto the tower and the bolts could be driven home. The nacelle was the heaviest single lift. The blades were the most complicated. Each blade is 108 meters long and weighs 30 tons. Transporting something that size from a manufacturing facility to a desert mountain site is a puzzle with no clean solution. Blade transport vehicles are purpose-built for this job, with extendable frames that can spread the axles far apart to carry the blade in a stable, balanced configuration. On open highway stretches, this works well. But the final approach to the turbine site ran through mountain roads with tight switchbacks and steep grades that an extended transport configuration simply cannot negotiate. So the crew switched to a shorter vehicle configuration for the mountain section. This immediately created a new problem. With the blade hanging off the front of a shorter vehicle, the weight distribution becomes dangerously unbalanced. The rear lifts, the front digs in, and control is compromised. The fix required adding enough total vehicle weight, ballast, equipment, and support machinery to bring the total up to 160 tons, heavy enough to keep the rear wheels planted and the blade level throughout every curve. 3 additional blade-handling vehicles shadowed each transport around the clock, ready to intervene if the load shifted. After all of that, the first blade arrived at the site and could not be installed. Wind. The gusts were too strong. A 108-meter blade in wind behaves like a sail the size of a stadium. The crane cable twists, directional control over the blade disappears, and the risk of impact with the tower becomes unacceptably high. So the team unloaded the blade and waited. They waited through the afternoon, through the evening, through most of the night. Workers sat on the desert floor under a sky full of stars, watching the wind indicators, drinking tea, and waiting for a window. Just before sunrise, the air went calm. The lift began within minutes. By the time dawn broke fully over the Gobi, the first blade was locked into position. The second followed without incident. A convoy of 3 loaders hauled the third blade up the mountain road together, and it went up on the first attempt. The turbine was complete. A 6.25 megawatt wind turbine. Fully assembled, fully installed, 170 meters tall with blades spanning over 200 meters tip to tip, now stands in the Gobi Desert, generating clean electricity. At full output, this single structure produces enough power to supply hundreds of homes every hour. Multiply that across the hundreds of turbines visible from that same hilltop, and across the thousands planned for the broader wind corridor, and the scale of what is being built starts to come into focus. The Zoomlion ZAT 40000 hour made it possible. Not because it is the most automated machine ever designed. The assembly and operation still depend heavily on experienced workers making judgment calls in difficult conditions. Not because it removed the human element. Teams spent a full night on that desert floor waiting for the wind to cooperate. It made it possible because it extended the physical limit of what a wheeled crane can reach and lift, pushing that ceiling high enough to meet the demands of the next generation of wind energy infrastructure. Behind that crane, if you look out across the Gobi horizon, white towers stretch in every direction as far as you can see. Each one was once a pile of components on a truck. Each one now turns wind into electricity for communities hundreds of kilometers away. This machine was not built to sit in a showroom. It was built to go somewhere difficult and do something that had never been done. It did exactly that, on wheels. For decades, 3 companies have controlled almost the entire global market for computer memory: Samsung, SK hynix, and Micron. Their chips sit inside smartphones, laptops, gaming computers, servers, and artificial intelligence data centers. Now, a Chinese manufacturer founded only 10 years ago is preparing an expansion that could change that balance. Changxin Memory Technologies, better known as CXMT, is expected to add roughly 85,000 wafer starts per month of new DRAM manufacturing capacity during 2026. Samsung is expected to add around 15,000. That means CXMT could install more than 5 times as much new wafer capacity as Samsung this year, not 5 times as much total production. Samsung remains far larger, but in terms of new capacity being added during 2026, China's leading DRAM producer is moving faster, and CXMT is preparing to raise another 29.5 billion yuan, approximately $4.3 billion, through one of the largest technology IPOs ever attempted on Shanghai's star market. The money is expected to support production expansion, research, and the development of more advanced DRAM, including memory designed for artificial intelligence. This is arriving at an extraordinary moment. AI data centers are consuming memory faster than manufacturers can comfortably supply it. Memory prices have risen. Samsung, SK hynix, and Micron are earning enormous profits, and CXMT's revenue reportedly increased more than 7-fold in the first quarter of 2026. But rapid expansion does not automatically make CXMT a technological equal to Samsung. The Chinese company is still behind in advanced high-bandwidth memory. Its manufacturing efficiency, product mix, and total output remain smaller, and increasing wafer capacity during a memory shortage can be highly profitable, or extremely dangerous if demand weakens before the new factories are ready. So is CXMT becoming a genuine 4th global memory giant, or is it expanding at the most expensive point in a historically unstable industry? Why memory has become the new AI bottleneck? When people discuss artificial intelligence, most attention goes to processors. NVIDIA GPUs, custom accelerators, massive clusters filled with computing power. But a processor is useful only when it can receive data quickly enough. Every AI accelerator needs memory to hold model weights, temporary calculations, instructions, and the information moving between layers of a neural network. If memory cannot deliver that data fast enough, the expensive processor waits. That waiting time is one reason memory bandwidth has become so important. Traditional DRAM serves as the working memory inside computers. It stores information that processors need immediately. Unlike an SSD, DRAM is extremely fast, but it loses its contents when power is removed. A modern server may contain hundreds of gigabytes or several terabytes of DRAM. An AI cluster can contain thousands of servers. Multiply that memory across an entire data center, and demand becomes enormous. AI is also increasing demand for a specialized form of DRAM called high bandwidth memory, or HBM. HBM stacks multiple memory dies vertically and places them close to an AI processor. Thousands of tiny connections move data between the layers and the processor at extremely high speed. But HBM is difficult to manufacture. It requires advanced DRAM dies, precise stacking, specialized packaging, and strong control over heat and yield. Producing more HBM can also consume manufacturing capacity that could otherwise make conventional server, smartphone, or computer memory. This creates pressure across the entire market. As the established manufacturers redirect advanced production toward profitable AI products, supplies of standard DRAM can tighten. That is the opening CXMT is trying to exploit. The Chinese company that appeared almost from nowhere. CXMT was established in 2016. That makes it extremely young compared with its major competitors. Samsung has manufactured semiconductors for decades. SK hynix traces its history through several older Korean memory companies. Micron was founded in the 1970s. DRAM is one of the hardest semiconductor markets to enter. Each memory cell must store a reliable electrical charge while occupying as little silicon as possible. Factories must produce enormous volumes because memory is usually sold as a standardized product. A small difference in manufacturing yield can determine whether a company makes money or loses billions. CXMT initially focused on providing China with a domestic source of conventional DRAM. Its early products trailed the leading manufacturers in density, power efficiency, and process technology. But the company continued expanding. It introduced newer generations of DDR memory for computers and servers. It moved into low-power LPDD, our products used in mobile devices. And it gradually increased production inside large 300mm wafer fabrication plants. By the fourth quarter of 2025, estimates placed CXMT at nearly 8% of global DRAM revenue. In the first quarter of 2026, Counterpoint estimated its share at approximately 8%. Samsung remained the leader with around 38%. SK Hynix held close to 29%, while Micron remained another major supplier. CXMT was still far behind the top three, but it had clearly separated itself from the industry's smaller manufacturers and established itself as the world's fourth largest DRAM supplier. The gap remains large. The direction is what matters. What 85,000 wafers per month really means. Semiconductor manufacturing capacity is often measured in wafer starts per month. A wafer start occurs when a blank silicon wafer begins its journey through the fabrication process. Each wafer passes through hundreds or sometimes thousands of manufacturing steps. Thin films are deposited, patterns are printed, materials are etched away, ions are implanted, connections are formed, the wafer is cleaned, measured, and inspected repeatedly. Depending on the chip and process, completing one wafer can take several months. After fabrication, the wafer contains many individual dies. Those dies are tested, cut apart, and packaged into usable memory chips. When analysts say CXMT may add approximately 85,000 wafer starts per month during 2026, they do not mean the company will manufacture only 85,000 wafers during the year. They mean its factories may gain the ability to begin processing roughly 85,000 additional wafers every month once that capacity is operational. That could represent hundreds of millions of additional memory dies over time, depending on die size, process technology, and manufacturing yield. Samsung's estimated addition of around 15,000 wafer starts per month is much smaller, but the comparison needs context. Samsung already operates an enormous installed manufacturing base. It does not need to add as much conventional DRAM capacity to remain larger than CXMT. Samsung is also spending heavily on process upgrades, HBM, advanced packaging, and new facilities whose full capacity may arrive in later years. A company can increase memory output without adding an equal number of wafers. Moving to a more advanced process can place more memory bits on each wafer. Improving yield allows more usable chips to leave the same production line. Changing the product mix can also dramatically alter revenue. So CXMT's 85,000 versus 15,000 comparison is powerful, but it is not a complete measurement of who will produce the most memory. It shows aggression, it does not yet show leadership. Why CXMT is expanding right now? Memory manufacturers have lived through repeated cycles of shortage and oversupply. When demand rises, prices increase. Manufacturers earn large profits and build new capacity. But semiconductor factories take years to construct and equip. By the time production begins, demand may have weakened. Several manufacturers can then bring new supply online at the same time. Prices collapse, profits disappear, investment slows. Then demand eventually recovers and the cycle begins again. AI is making the current cycle unusual. Memory suppliers believe demand from data centers may remain strong for longer than previous consumer electronics booms. Large cloud companies are building enormous AI clusters. Each new generation of accelerator uses more memory. Models are becoming larger. Inference workloads are spreading into more services. Micron has said it expects tight memory supplies to continue through at least 2027. Major manufacturers are signing longer-term agreements with customers that include deposits, minimum purchases, and pricing protections. CXMT is entering this market while prices are high and supply is limited. Its first quarter 2026 revenue reached approximately 50.8 billion yuan, representing a year-over-year increase of more than 700%. The company moved from losses into substantial profitability. Part of that improvement came from increased shipments, part came from better products, but a major factor was the sharp rise in global memory prices. That financial improvement makes an IPO much easier to sell. Investors are no longer being asked to fund only a long-term semiconductor ambition. They are being shown a company generating large revenue during one of the strongest memory markets in history. What the $4.3 billion IPO could fund CXMT plans to raise 29.5 billion yuan through its Shanghai listing. That equals roughly $4.3 billion. The offering would be the largest mainland Chinese IPO of 2026 and the second largest listing in the history of Shanghai's technology-focused STAR market. For a semiconductor company, $4.3 billion is significant, but it is not unlimited. A modern memory fabrication plant can cost tens of billions of dollars when buildings, cleanrooms, lithography systems, deposition tools, etching equipment, testing systems, and supporting infrastructure are included. CXMT is therefore not building its entire expansion with IPO money alone. The company already has factories, investors, financing, and other sources of capital. The IPO adds another pool of funding. According to its listing plans, the proceeds are intended for manufacturing upgrades, research and development, process improvement, and product expansion. That last category may be the most important. Standard DDR and LPDDR products helped CXMT establish volume. HBM could determine whether it becomes strategically important to the AI market. The HBM gap. CXMT's biggest weakness is not basic DRAM capacity. It is advanced memory. Samsung, SK Hynix, and Micron are already producing high-bandwidth memory for leading AI accelerators. SK Hynix became especially successful by investing early in HBM and building a strong relationship with NVIDIA. HBM carries higher margins than ordinary memory, but it also demands better technology. The DRAM dies must be manufactured efficiently. The dies must be thinned. Tiny vertical connections called through-silicon vias must pass signals through the stack. Multiple dies must be aligned and bonded. The final package must remain reliable while transferring enormous amounts of data and operating beside a hot AI processor. One defective die can damage the value of an entire stack. CXMT is investing in an HBM packaging facility in Shanghai and has targeted production by the end of 2026. But starting production is not the same as reaching high-volume manufacturing. It must demonstrate acceptable yields. It must qualify its products with accelerator designers. It must prove long-term reliability. And it must catch competitors that are already moving toward newer HBM generations. This means CXMT's immediate expansion will probably have a larger impact on standard DRAM than on the most advanced AI memory. It may pressure prices in consumer, mobile, and server memory before it seriously threatens SK Hynix in premium HBM. Could CXMT actually hurt Samsung? Samsung is not facing an immediate collapse. It remains the largest DRAM supplier by revenue. It has far more manufacturing experience. It operates advanced process technology, major research facilities, and a global customer network. It also produces NAND flash, processors, image sensors, displays, and complete electronic products. CXMT is much more concentrated, but that concentration can become an advantage. CXMT can focus capital and engineering effort on DRAM. It can compete aggressively in the Chinese market, and it can supply domestic computer, smartphone, server, and accelerator manufacturers that want alternatives to foreign memory. CXMT does not need to defeat Samsung worldwide to create pressure. It only needs to capture enough volume to affect industry supply. Memory products are highly sensitive to small differences between demand and production. If the world needs 100 units of DRAM and manufacturers produce 98, prices can rise quickly. If they produce 105, prices can collapse. An extra few percentage points of supply can change profitability for every company in the market. Semi-analysis expects the DRAM market to remain undersupplied even after accounting for CXMT's expansion. But the expected shortage does not last forever. Capacity being installed now may influence prices in 2027 and 2028. If AI demand continues rising, the new supply could be absorbed. If AI investment slows, CXMT's expansion could arrive just as the market becomes oversupplied. What this could mean for consumers. For buyers of computers, servers, and smartphones, more competition is generally positive. Additional supply can reduce shortages. It can provide device manufacturers with more negotiating power. It may eventually lower the price of DDR5 modules, laptop memory, and server DRAM. CXMT manufactured chips have already appeared in memory products sold under recognizable international brands. That does not necessarily mean those brands have committed to CXMT for every model or every market. Memory module manufacturers frequently source chips from different suppliers depending on price, availability, and qualification. But it shows that CXMT is no longer restricted to experimental or purely domestic products. Its chips can enter commercial supply chains when they meet the required specifications. The question is whether the company can maintain performance and reliability while rapidly increasing output. Expanding too quickly can create yield problems. New production lines require trained workers. Equipment must be calibrated. Processes must remain consistent across multiple factories. A chip that works in one small production run must continue working when millions are produced every week. Scale exposes weaknesses that laboratory demonstrations can hide. The biggest risks. CXMT faces three major risks. The first is technology. Adding wafer capacity is valuable only if the products are competitive. A less advanced process may produce fewer memory bits per wafer and consume more power. That can make apparently large manufacturing capacity less productive than a smaller but more advanced factory. The second risk is the market cycle. CXMT is investing during a period of exceptional memory prices. Those prices helped create its recent profits. If supply catches demand and pricing falls, the financial picture could change rapidly. The third risk is execution. Semiconductor expansion is not simply a construction project. Factories need complex tools, materials, software, replacement parts, and skilled engineers. Any bottleneck can delay production, and advanced DRAM requires constant process improvement. Samsung, SK Hynix, and Micron will not remain still while CXMT expands. They are investing in denser DRAM, more efficient manufacturing, and newer generations of HBM. CXMT is chasing moving targets. My take is that the 5x number is not proof that CXMT has overtaken Samsung, but it may be evidence of something more important. China is no longer treating domestic DRAM as a small backup industry. It is building for global scale. CXMT already holds a meaningful share of the market. Its revenue has accelerated. Its factories are expanding. Its IPO could provide another $4.3 billion for manufacturing and research, and it is beginning the difficult move from conventional memory toward HBM. Samsung remains larger. SK Hynix remains stronger in high-end AI memory. Micron remains deeply connected to major American technology companies, but the memory industry may no longer be a permanent three-company market. CXMT is becoming a fourth participant capable of influencing supply, prices, and investment decisions. The most important test will not be how much money the IPO raises. It will be what comes out of the factories afterward. Can CXMT convert 85,000 additional monthly wafer starts into reliable, competitive memory? Can it improve yields while increasing volume? Can it manufacture HBM at scale? And can it remain profitable when today's memory shortage eventually ends? If the answers are yes, Samsung, SK Hynix, and Micron will face a competitor with domestic scale, strong financial backing, and one of the fastest capacity expansions in the industry. If the answers are no, CXMT could discover the same lesson that has punished memory manufacturers for decades. Building capacity is easy compared with filling it profitably. So what do you think? Is CXMT on its way to becoming the world's fourth true memory giant? Or is it expanding too aggressively during a temporary AI-driven shortage? Let me know your view in the comments, and subscribe to Eastern Engine for more grounded coverage of the chips, factories, and engineering breakthroughs changing the technology industry. Because China is not adding 5 times Samsung's total memory production, but it may be adding more than 5 times as much new wafer capacity this year. And in an industry where a small shift in supply can move the entire market, that difference could matter far more than it first appears. For the last 3 years, one company has held the entire world of artificial intelligence in the palm of its hand. Not Google, not OpenAI, not Microsoft. A chip company, NVIDIA. Because every major AI model you've ever heard of, every chatbot, every image generator, every breakthrough that made headlines, was trained and run on NVIDIA's chips. The company became so essential, so unavoidable, that it briefly became the most valuable company on planet Earth. If you wanted to build serious AI, you went through NVIDIA. There was no other door. And it wasn't just the chips. NVIDIA's real fortress was something most people have never heard of. A piece of software called CUDA, the invisible layer that every AI developer on Earth has been building on for over a decade. People in the industry have a name for this trap. They call it the CUDA moat. A castle wall so wide and so deep that even if a rival built a faster chip tomorrow, no one could use it, because the entire world's AI software was written for NVIDIA and NVIDIA alone. That was the situation. That was the lock on the door. And a few weeks ago, a Chinese AI company called DeepSeek did something that was supposed to be nearly impossible. It built a brand new frontier-class AI model that runs from top to bottom without a single piece of NVIDIA software anywhere in its stack. No CUDA. Running instead on chips made by Huawei, a company the United States sanctioned years ago specifically to keep it away from this exact moment. Now, and you know this is coming, there's crucial nuance here, and parts of this story cut against the hype in ways that are genuinely fascinating. I'm going to give you all of it, honestly. But by the end of this video, you'll understand what just happened, why NVIDIA's own CEO publicly admitted he's losing China, why the CUDA moat suddenly looks less like a wall and more like a dam with a crack in it, and why this might be remembered as one of the most important moments in the AI race. Let's get into it. To understand why this is such a big deal, you have to understand how complete NVIDIA's grip really was. And it came down to two things working together. The first is the chips themselves. Training a modern AI model requires a staggering amount of raw mathematical horsepower, and NVIDIA's chips, originally designed to render video game graphics, turned out to be almost perfectly suited to the kind of massively parallel math that AI demands. For years, they were simply the best on Earth at it, by a wide margin. If you wanted to train a serious model, you needed NVIDIA silicon. Full stop. But the chips were only half the fortress. The other half, the part that really locked everyone in, was the software. CUDA is NVIDIA's programming platform, the bridge that lets AI code actually talk to the chips. And here's the thing, the entire global AI community has been building on CUDA for more than a decade. Every framework, every tool, every tutorial, every trick built for CUDA. An entire generation of engineers grew up speaking it. That's the moat. Imagine a country where every road, every gas station, every mechanic, and every driving school was built for exactly one brand of car. Even if a competitor released a better vehicle, who would buy it? You couldn't fuel it, fix it, or find anyone trained to drive it. That's what NVIDIA built. Not just a better car, but the entire road system everyone else was forced to drive on. Switching away wasn't just hard. For most companies, it was unthinkable because it meant abandoning every tool and rebuilding from scratch. So when the United States wanted to slow China's AI progress, the strategy seemed obvious and airtight. Cut China off from NVIDIA's most powerful chips. No advanced NVIDIA silicon. No frontier AI. The leash was the chip, and the lock was the software. And for a while, that logic held, until a cornered company decided the only way out was to build its own road system from scratch. The company at the center of this is DeepSeek, a Chinese AI lab that already shocked the world once. Back in early 2025, when its earlier model launched, it was so unexpectedly capable and so cheap to run that it wiped out hundreds of billions of dollars from NVIDIA's market value in a single day. Investors suddenly panicking that maybe the future of AI wouldn't need quite so many expensive NVIDIA chips after all. Now DeepSeek is back with its new generation, V4, a genuinely frontier-class model, a colossal system with 1.6 trillion parameters, competitive on serious benchmarks with the best models from American labs. On certain coding and reasoning tests, it ranks at or near the very top, trading blows with the flagship models from the biggest names in Western AI. But the benchmarks aren't the real story. The real story is what's underneath. According to multiple reports, V4 is the first DeepSeek model with no NVIDIA CUDA dependency anywhere in its core stack. Instead, it was natively built to run on Huawei's Ascend chips, using Huawei's own software framework, called CNN, as the replacement for CUDA. Think of CNN as Huawei's homegrown version of that road system, its own bridge between AI code and its own chips. And the engineering effort this took is staggering, which is actually why V4 was so delayed. For months, the model kept slipping past its expected release dates, and there was a single reason. Migrating a system this enormous off of CUDA and onto Huawei's completely different software framework, essentially from scratch, is brutally hard. There's even a detail that perfectly captures the difficulty. The team developed its own specialized programming language, called Tilelang, so the model's core operations wouldn't be permanently chained to any one company's chips. Months of delay weren't a failure, they were the price of independence. Here's the detail that drives the point home like nothing else. DeepSeek reportedly gave Huawei weeks of exclusive early access to optimize the model for its chips, a courtesy it pointedly refused to give NVIDIA and AMD. The Chinese company put its own domestic chip maker first and made the American giants wait. A few years ago, that would have been unthinkable. If you want a single piece of evidence for how serious this is, you don't have to take China's word for it. You can take NVIDIA's. NVIDIA's CEO, Jensen Huang, one of the most powerful figures in all of technology, publicly admitted that his company has largely conceded China's advanced AI chip market to Huawei. Let that sink in. the head of the most dominant chip company on Earth, openly acknowledging that in the world's second-largest economy, he's handing the field to his Chinese rival. CEOs do not say things like that lightly. That is not spin. That is a man reading the board and admitting he's losing a piece of it. And the market is moving on exactly that belief. Reports indicate that China's three internet giants, Alibaba, ByteDance, and Tencent, have collectively pre-ordered hundreds of thousands of Huawei's new AI chips, positioning themselves to run models like V4 at massive scale. Pre-orders on that scale don't happen on a hunch. They happen when the biggest players in a market have decided which way the wind is blowing. Huawei is now bracing for something like $12 billion in AI chip revenue, with reports that Chinese fabs can barely keep up with demand, while Nvidia's share of that same market quietly craters. The picture is unmistakable. A model the world's developers actually want to use, running on Chinese chips, bought in enormous volume by China's biggest companies, with Nvidia's own CEO conceding the territory. The lock on the door didn't just loosen. Someone built an entirely new door. But, and this is where I have to be honest with you, because the truth here is more interesting than the clean headline. The door isn't quite as wide open as it first appears. Here's the nuance that separates this channel from the breathless headlines. Because there are three big caveats, and you deserve every one of them. First, and most important, V4 was still trained mostly on Nvidia. Building an AI model has two phases: training, the immensely expensive process of creating the model's intelligence, and inference, the cheaper process of actually running it for users. The Nvidia free achievement is strongest on the inference side. For the hardest part, frontier training, Chinese firms, including DeepSeek, have still largely leaned on Nvidia hardware, because Huawei's chips and software aren't yet reliable enough for that brutal workload. In fact, DeepSeek reportedly couldn't complete a clean training run for an earlier model on Huawei chips even with Huawei's own engineers on site. So cut Nvidia out completely is true for running the model, but the deepest, hardest layer of AI still has Nvidia footprint. Second, DeepSeek deliberately kept V4 compatible with Nvidia too. Buried in the technical details, V4 was validated on both Huawei and Nvidia platforms. Why? Because if the model only ran on Huawei chips, the global community of developers, who overwhelmingly own Nvidia hardware, couldn't use it. And an open-source model that nobody outside China can run is just a political statement, not a living technology. So DeepSeek is playing a clever double game. Prove independence is possible, while keeping global compatibility so the model stays relevant everywhere. That's not weakness, it's strategy. But it means the total break is more nuanced than it sounds. Third, Huawei's KNA software still trails Nvidia's CUDA by a wide margin, by something like an order of magnitude in ecosystem maturity. A decade of global development doesn't get matched in a year. KN works because DeepSeek controls its own full stack and tuned everything by hand. For the average developer worldwide, CUDA is still the default and will be for a long time. So here's the fair summary, the one the hype skips. China has not matched Nvidia. Huawei has not caught up. KN has not equaled CUDA. What actually happened is subtler and honestly more important than any of those simple claims. For the first time, a frontier-class AI model exists that was built from chip to model, with no American software at its core. Proving the thing everyone said was years away is possible right now. The wall isn't gone, but everyone just watched someone climb over it. So if China hasn't fully caught up, why is this such a big deal? Because of what it starts, not what it finishes. The real significance is something experts call a learning loop, and it's the thing Nvidia should actually fear. Here's how it works. DeepSeek optimizes its model for Huawei's chips. Huawei gets a serious, real-world, world-class workload to learn from. Its canned software gets battle-tested and improves. Cloud providers gain experience running it. Other Chinese AI labs see it working and start building for Huawei too. And the next model becomes easier to run on Chinese chips than the last one. Round and round, each loop making the domestic alternative a little stronger. That's how an ecosystem is born. Not in one dramatic leap, but through exactly this kind of repeated, workload-driven improvement. Nvidia's moat was never really just the chips. It was the ecosystem, the decade of everyone building on CUDA. And the only way to challenge an ecosystem is to start a rival one and let it compound. V4 is the starting gun for precisely that. It gives the Chinese stack its first true frontier-class workload to organize around. And the strategic ripple effects are already spreading. Because V4 is open source and dramatically cheaper to run than Western alternatives, reportedly by a huge margin, it becomes attractive far beyond China. Governments and institutions in countries that can't or won't rely on American cloud infrastructure can now run a top-tier AI model entirely on a non-American stack. That's a genuinely new option in the world, and it didn't exist a year ago. Step back and the pattern is the one we keep seeing on this channel. A restriction was designed to lock China out. Instead, it forced China to build the one thing the restriction was meant to prevent: a complete, independent, domestic alternative. The export controls didn't stop the parallel ecosystem. They may have been the very thing that created it. Cut off from the road system everyone else uses, China started paving its own. Here's my honest opinion. I think the two loudest reactions to this are both wrong, and the truth is more interesting than either. The people shouting China just destroyed NVIDIA and won the AI war are flatly ahead of the facts. Frontier training still leans on NVIDIA, Cana still trails CUDA badly, and DeepSeek itself kept NVIDIA compatibility on purpose. Anyone selling you NVIDIA is finished is selling a fantasy. But the people waving this away, it's nothing, they still need NVIDIA, ignore it, are making the bigger mistake, the same one that's been made at every stage of this story, because they're fixated on the fact that the wall still stands, and missing that someone just proved it can be climbed. The single most important word in this entire story is not chip or model, it's possible. For 3 years, the iron assumption was that you simply could not build frontier AI without the American stack. That assumption is now dead. Not weakened, dead. And once something is proven possible, it almost always gets better, cheaper, and more common from there. What strikes me most is that NVIDIA's own CEO seems to understand this better than the cheerleaders on either side. He didn't dismiss it, he conceded ground. That tells you the person with the most to lose and the best view of the board is taking it seriously. Maybe the rest of us should too. The CUDA moat was the widest, deepest competitive wall in modern technology. It still stands, but for the first time, there's a crack in the dam, and water has a way of finding every crack and slowly, relentlessly making it bigger. So here's my question for you, and I genuinely want your honest answer. Did the chip restrictions backfire? By forcing China to build a complete, independent AI ecosystem it might never have bothered to build otherwise? Or were they still worth it, because they've kept China a step behind and burning enormous resources to catch up? Did cutting the cord set China free, or just slow it down? Drop your real take in the comments. I read every single one, and this is exactly the debate I love seeing down there. If you want to keep following this, the breakthroughs, the workarounds, the shifts the rest of the world keeps underestimating until they can't, subscribe to Eastern Engine and hit the notification bell. Chips, AI, computing, the entire foundation of the modern world is being rewritten right now, and we break it all down clearly and honestly before the mainstream catches on. Thanks for watching. I'll see you in the next one. China's largest electric vehicle company has spent years proving that it can build batteries, motors, power electronics, and complete cars at enormous scale. Now BYD is moving deeper into the part of the vehicle that may matter most next decade, the computer that controls intelligent driving. The company has unveiled its Xuanji A3 processor. BYD describes it as China's first domestically designed 4nm chip built specifically for advanced driving systems. One chip delivers around 700 trillion operations per second. A 3-chip configuration exceeds 2,100 TOPS, and BYD says the processor has already entered chip-level mass production. A Chinese automaker is no longer satisfied with buying batteries, sensors, software, and processors from separate suppliers. BYD wants to control the complete stack. But the headline needs an important qualification. The Xuanji A3 has not yet been independently proven to beat NVIDIA's best automotive platform. Mass production of the chip does not mean millions of BYD vehicles are already using it. And a 4nm design does not prove that the processor is fabricated entirely with Chinese manufacturing equipment. Still, BYD is clearly trying to turn the vehicle into a vertically integrated platform, with the processor, software, sensors, battery, motors, and architecture developed around one system. The question is whether BYD can use its scale to make those chips an industry standard. Why BYD built its own car brain? Modern vehicles are becoming computers on wheels. Cameras, radar, LiDAR, ultrasonic sensors, navigation systems, battery controls, entertainment displays, and driver assistance software all generate enormous amounts of data. That information must be processed quickly enough for the vehicle to recognize lanes, detect pedestrians, predict nearby traffic, and decide when to brake or change direction. Traditional vehicles divided these tasks among many separate control units. Advanced driving requires tighter coordination, larger neural networks, millisecond decisions, and safe operation even when one component fails. This is why automotive computing is moving towards centralized platforms. Instead of dozens of isolated control units, more functions are combined inside a smaller number of powerful computers. The Xuanji A3 is designed for that transition. It is the centerpiece of a compact central computing platform, intended to connect intelligent driving, the digital cockpit, and core vehicle control functions. That gives BYD more control over how information moves through the car. It also allows the company to optimize the processor around its own vehicles, instead of adapting every design to a general-purpose chip from another supplier. What 700 TOPS really means. The number attached to the Xuanji A3 is 700 TOPS. TOPS means trillions of operations per second. It is commonly used to describe the peak performance of artificial intelligence accelerators. A higher number can support more camera feeds, larger neural networks, or several models at once. But TOPS should not be treated like horsepower. Two chips with the same advertised number may deliver very different real-world performance. The result depends on numerical precision, memory bandwidth, software efficiency, thermal limits, and how much of the processor can actually be used by the workload. BYD says the Xuanji A3 includes a 16-core CPU and around 273 gigabytes per second of memory bandwidth. One chip provides roughly 700 TOPS, while three working together exceed 2,100 TOPS. That is an enormous figure for a passenger vehicle. However, three chips do not automatically behave like one perfectly unified processor. The system must distribute work efficiently, move data between chips, avoid duplication, and manage power and heat. The important question is not only how much peak performance exists, it is how much useful performance the software can extract in real traffic. BYD says combining the chip with its own algorithms improves computing utilization. That is one reason vertical integration matters. The company can design models around the exact structure of the processor, then adjust the hardware around the software's needs. Why three chips? Most vehicles will not require 2,100 TOPS. A basic assisted driving system can operate with far less. Premium vehicles, however, may run cameras, LiDAR, radar, perception models, parking, driver monitoring, and cockpit intelligence simultaneously. Three chips give BYD room to divide workloads and create redundancy, with separate processors potentially handling perception, planning, cockpit functions, or backup capacity. Level 3 and Level 4 systems require more than speed. Level 3 automation can allow the vehicle to control itself under limited conditions, but the human driver may still need to take over. Level 4 systems are designed to operate without human control inside defined areas or situations. Supporting those levels requires fail operational design. If one component stops working, the system must remain safe. Extra processors, independent power paths, redundant sensors, and multiple communication networks can all contribute. BYD says the Xuanji A3 is designed to support future Level 3 and Level 4 systems. That does not mean every vehicle carrying the chip will immediately become autonomous. Regulation, software validation, sensors, mapping, and road conditions still determine what the car is legally and technically allowed to do. The NVIDIA comparison. NVIDIA has spent years building one of the strongest automotive computing ecosystems in the world. Its drive platform combines processors, networking, development tools, simulation software, and artificial intelligence models. Automakers do not simply purchase a chip. They purchase access to an established software platform with global engineering support. That is hard to replace. BYD's advantage is different. It does not need to sell the Xuanji A3 to every automaker in the world to make the project successful. BYD can deploy the chip across its own enormous vehicle portfolio. That creates a guaranteed internal customer. Each vehicle can generate data, receive software improvements, and reuse parts of the same architecture. NVIDIA must support many brands, while BYD can optimize around its own sensors, batteries, motors, networks, and factories. This does not prove BYD has beaten NVIDIA. NVIDIA still has deeper experience in AI software, simulation, developer tools, and advanced computing. But BYD may not need to win a direct benchmark battle. It may only need a processor that is powerful, efficient, reliable, and cheap enough for its own cars. The mass production claim. BYD says the Xuanji A3 has entered mass production. That claim must be interpreted carefully. Chip-level mass production means the processor has moved beyond a small laboratory sample. It suggests that the design has completed major validation steps and is being manufactured in meaningful quantities. But it does not necessarily mean the chip is already installed across BYD's current vehicle range. Automotive deployment moves slowly because chips must survive vibration, humidity, voltage changes, extreme temperatures, and long service periods. The full system also needs software validation, sensor integration, cybersecurity testing, and safety approval. Reports indicate that the first major vehicle deployments may arrive later, potentially beginning with premium BYD brands before spreading into higher volume models. So the breakthrough is real, but the rollout should not be exaggerated. The Xuanji A3 is entering the production phase. Its true impact will become visible when BYD reveals which vehicles use it, how many chips are installed, and what driving functions are activated. Who actually manufacturs it? Another major question is fabrication. BYD designed the Xuanji A3, but designing a chip and manufacturing it are different businesses. A 4-nanometer processor requires advanced lithography, materials, process control, packaging, and testing. BYD has extensive semiconductor operations, especially in automotive power electronics and mature node components. But there is no clear evidence that BYD manufactures this particular processor entirely inside its own factories. Chinese automakers and chip designers still depend heavily on outside foundries for leading-edge production, including manufacturers in Taiwan and South Korea. That means the Xuanji A3 is a major step toward design independence, but not necessarily complete supply chain independence. A company can control the architecture, software, and roadmap while still relying on foreign fabrication. That is strategically valuable, but trade restrictions or supply disruptions could still affect production. BYD's long-term challenge is larger than designing one successful chip. It must secure fabrication capacity, advanced packaging, memory, and automotive-grade testing at the scale required for millions of vehicles. BYD's vertical integration advantage. BYD began as a battery company. It later expanded into vehicles, electric motors, power electronics, semiconductors, energy storage, and manufacturing equipment. This vertical integration has helped BYD lower costs and react when supply chains become unstable. The Xuanji A3 extends that strategy into advanced computing, connecting its batteries, electric drive systems, vehicle platforms, and assisted driving software. The driving system could share information more directly with braking, steering, suspension, battery management, navigation, and the cockpit. That could reduce latency and simplify software updates. It may also lower cost. A processor designed for BYD's exact requirements may avoid features the company does not need. Once production reaches sufficient scale, BYD can spread development costs across a very large number of vehicles. This is where BYD may have an advantage over smaller automakers. Designing an advanced chip costs an enormous amount of money. The investment only makes sense if the company can deploy enough units to recover the expense. BYD has the scale to use the same architecture across several brands, vehicle classes, and price categories. The Chinese chip race. BD is not alone. Chinese automakers are rapidly developing their own intelligent driving processors or working with domestic semiconductor companies. NIO has introduced its own driving chip. XPeng has developed the Turing processor. Li Auto is working on its Mach series hardware. Geely, Huawei, Horizon Robotics, and other companies are also building automotive computing platforms. This competition shows how important the car chip has become. Automakers once differentiated themselves through engines, transmissions, and chassis tuning. In the electric vehicle era, batteries and manufacturing became central. The next competitive layer may be computing. A company that controls the processor can decide how quickly features are added, how data is handled, and how dependent the vehicle remains on suppliers. But fragmentation creates risk. Separate tools and operating systems increase costs and make every platform harder to support. Some automakers may eventually discover that designing chips is too expensive. BYD is better positioned than most because of its scale and its ability to connect the chip directly to its own vehicles. The real economic impact. The biggest opportunity may not be the most expensive autonomous vehicle. It may be bringing advanced computing into affordable cars. BYD has already pushed driver assistance features deeper into mass market segments. If the company controls the processor, it can reduce the amount paid to foreign suppliers and decide how aggressively to spread intelligent driving hardware across its lineup. That could pressure competitors. A feature that begins in a premium vehicle can move into mid-range models once production scales, just as Chinese automakers did with batteries, fast charging, displays, and electric drivetrains. If BYD installs its own chip across hundreds of thousands of vehicles, it gains an enormous data and software advantage. More vehicles create more data, better models, more useful hardware, and a stronger platform. That feedback loop matters far beyond the TOPS number. What remains unproven? Several important questions remain unanswered. We do not yet have independent benchmarks showing how the Xuanji A3 performs against NVIDIA Drive Thor, Huawei's automotive platforms, or rival Chinese chips under identical conditions. We do not know the final production cost, real-world power use, manufacturing yield, or volume of secure foundry capacity available to BYD. And we do not know how quickly the chip will move from premium vehicles into mass-market models. The real test will happen on the road. Can the system recognize unusual objects? Can it handle rain, glare, construction zones, and unpredictable drivers? Can it fail safely? Can BYD maintain the software for years? A large TOPS number cannot answer those questions. My take is that the Xuanji A3 is not important because BYD has already defeated NVIDIA. It is important because BYD is removing another external dependency from the vehicle. The company already controls batteries, motors, power electronics, and much of its manufacturing. Now it is attempting to control the computing architecture that will define intelligent cars. A single chip delivering around 700 TOPS is significant. A 3-chip system exceeding 2,100 TOPS is visually impressive, but the real advantage is integration. BYD can design the processor, algorithms, sensors, vehicle controls, and production process as one system. That is difficult for a traditional automaker coordinating outside suppliers. Limits remain. The chip may rely on foreign fabrication. Mass production does not equal mass deployment. Level 3 and Level 4 support does not mean fully autonomous. BYD cars are already operating everywhere, and NVIDIA remains a much stronger global computing platform. But BYD does not need to replace NVIDIA worldwide. It needs to make outside processors less necessary inside its own vehicles. If it succeeds, the company will not simply be an electric car manufacturer. It will become a large-scale automotive computing company with millions of vehicles serving as the deployment platform. That could reshape global competition. So what do you think? Can BYD turn the Xuanji A3 into a genuine alternative to NVIDIA's automotive processors? Or will manufacturing limits and software complexity prevent the chip from reaching its full potential? Let me know your view in the comments. And subscribe to Eastern Engine for more grounded coverage of the chips, factories, and engineering decisions reshaping the global economy. Because BYD built its rise on batteries, but its next advantage may come from the computer controlling the car. Have you ever wondered why NVIDIA keeps building faster and faster AI chips, yet the biggest AI companies still complain their systems are waiting around instead of actually computing? It turns out the biggest problem isn't always the GPU anymore. Sometimes, it's what connects them. And now China says it has built an AI network that moves information so quickly it could remove one of the largest bottlenecks in modern artificial intelligence. If that's true, it changes far more than benchmark scores. It changes how future AI supercomputers are designed, how much they cost to build, and who can compete in the global AI race. Today, we're breaking down why this network matters, why NVIDIA has spent years trying to solve the same problem, and why China's latest breakthrough has the entire semiconductor industry paying attention. When most people hear about AI hardware, they immediately think about GPUs. NVIDIA has become almost synonymous with artificial intelligence because its graphics processors train and run many of the world's largest language models. Every headline talks about faster chips, more memory, more tensor cores, and larger AI clusters. But here's something many people don't realize. The bigger an AI system becomes, the less important the individual chip is compared to the speed at which thousands of chips communicate with each other. Imagine you own the fastest sports car in the world. It can reach incredible speeds in seconds, but then you place that car in the middle of a traffic jam where every road is clogged. Suddenly, it doesn't matter how powerful the engine is because it spends most of its time waiting. That's exactly what happens inside massive AI data centers. Thousands of incredibly powerful processors constantly need to exchange enormous amounts of information. If those connections become congested, the expensive GPUs sit idle waiting for data instead of performing calculations. That waiting time is incredibly expensive. Some of today's largest AI clusters cost hundreds of millions, sometimes even billions of dollars to build. Every second a GPU isn't fully utilized represents wasted money, wasted electricity, and slower AI development. This has become one of the biggest engineering challenges in modern computing. For years, NVIDIA has been attacking this problem with technologies like NVLink and InfiniBand. These aren't GPUs themselves, they're the highways connecting those GPUs together. The faster the highway, the more efficiently every processor can work. Building these high-speed connections has become almost as important as designing the chips themselves. Now China appears determined to solve this challenge from another direction. Rather than simply building faster processors, Chinese researchers and technology companies have been investing heavily in networking technologies specifically designed for artificial intelligence workloads. Their goal isn't just faster downloads or faster internet. Their goal is dramatically reducing the time it takes for thousands of AI accelerators to exchange data while training enormous neural networks. That sounds simple until you realize just how much information modern AI systems move every second. Training a cutting-edge language model isn't like downloading a movie. Imagine thousands of processors all solving different pieces of the same giant puzzle simultaneously. After each step, every processor needs to share what it learned with thousands of others before moving to the next calculation. This exchange happens millions of times during training. If even one part of that communication slows down, the entire system becomes less efficient. That's why networking has quietly become one of the most valuable technologies in artificial intelligence. The interesting part is that networking has traditionally received far less public attention than GPUs themselves. Headlines celebrate trillion-parameter models and record-breaking chips, but the infrastructure connecting everything together usually stays behind the scenes. Yet many engineers argue these connections are becoming just as important as compute power itself. China clearly recognizes this trend. Over the last several years, enormous investments have gone into domestic networking equipment, optical communication systems, advanced switching technologies, silicon photonics research, and ultra-fast data center architectures. Instead of relying entirely on imported networking ecosystems, Chinese companies have increasingly focused on building their own complete AI infrastructure stack. That strategy mirrors what we've already seen happen across semiconductors. First came investments in domestic chip manufacturing, then memory, then advanced packaging, then AI accelerators. More recently, optical communication and photonic technologies began receiving massive attention because engineers realized future AI systems would eventually hit limits not inside processors, but between them. This is exactly where the latest reports become so interesting. Instead of asking how to make a single GPU faster, researchers are asking something much bigger. What if every GPU could spend dramatically less time waiting? Even a relatively modest improvement in communication efficiency can produce surprisingly large improvements across enormous AI clusters. Think about a warehouse filled with thousands of workers. If every employee loses only 10 seconds, wait, competition won't simply revolve around who builds the fastest processor. Instead, it may depend on who builds the fastest complete system. That's a major difference. A complete AI system includes processors, memory, networking, storage, cooling, software, power management, manufacturing capability, and increasingly, optical communication. Whoever optimizes every layer gains advantages that individual component improvements alone can't match. China appears increasingly focused on this systems approach. Rather than chasing one spectacular headline after another, many recent projects fit together like pieces of a much larger strategy. You've probably noticed this pattern if you've watched several videos on this channel. First, there were domestic AI accelerators, then high-speed memory developments, then glass-based technologies, then advanced packaging, then ultra-fast optical fibers, then AI servers, then CPU breakthroughs, now networking. Individually, each story seems impressive. Together, they begin forming an ecosystem. That's important because AI isn't powered by isolated inventions anymore. It's powered by entire infrastructures. This also explains why many governments have started viewing artificial intelligence less like traditional software and more like national infrastructure. Countries aren't simply competing to build chatbots. They're competing to build entire computing ecosystems capable of supporting future industries. Healthcare, autonomous transportation, scientific research, drug discovery, manufacturing, defense applications, climate modeling, financial systems. Every one of these increasingly depends on artificial intelligence processing massive data sets at extraordinary speeds. And every one of those workloads depends on communication. The challenge becomes even greater as AI models continue growing. A decade ago, training systems containing millions of parameters seemed impressive. Today, billions have become common. Trillions are already appearing. Future systems may become even larger. As models expand, communication requirements grow dramatically. Moving that information efficiently becomes one of the defining engineering challenges of modern computing. That's why networking engineers have suddenly become some of the most valuable specialists in artificial intelligence. They're building invisible technologies that determine whether tomorrow's AI systems spend their time calculating or waiting. This is where optical communication enters the conversation. Traditional electrical connections eventually face physical limitations involving heat generation, signal degradation, and energy consumption. Optical communication offers an alternative by transmitting enormous amounts of information using light rather than conventional electrical signaling. China has invested heavily in this area. Recent announcements involving air-filled optical fibers, photonic devices, advanced optical switching, and integrated communication technologies all point toward one long-term objective: move vastly more information while consuming less energy. If successful, that combination becomes extremely attractive for AI infrastructure. Energy consumption has quietly become one of artificial intelligence's biggest challenges. Every new generation of larger AI clusters requires enormous amounts of electricity. Data centers already consume significant power. Future AI facilities may require even more. Improving communication efficiency doesn't only accelerate computation, it can also reduce wasted energy by allowing expensive processors to spend less time idle. That creates a double benefit: higher performance, lower operational cost. Those economics matter enormously. The largest technology companies now spend billions constructing AI infrastructure. Even relatively small percentage improvements can translate into hundreds of millions of dollars over time. This explains why networking technologies have become strategic assets rather than supporting components. The companies that master them may gain advantages extending far beyond raw processor performance. And according to recent developments, China clearly wants to compete at every layer of that stack. So what exactly makes this reported AI network different from the traditional approach? Instead of treating networking as an accessory to AI hardware, the latest Chinese developments suggest networking is becoming the foundation around which future AI systems are designed. The objective isn't simply increasing raw bandwidth. Engineers are trying to reduce latency, improve synchronization between thousands of processors, eliminate communication bottlenecks, and make every computing node behave almost like part of one enormous machine. That distinction is incredibly important. Imagine trying to coordinate 10,000 people on a project. Communication is fairly easy. Now imagine coordinating 10,000 people who all need updated information every few milliseconds. Suddenly, communication itself becomes the biggest challenge. Modern AI clusters face exactly that problem. Every training cycle requires processors to exchange parameters, gradients, weights, and intermediate calculations. As clusters grow larger, the amount of communication grows even faster than the amount of computation. That's why networking has become one of the hottest areas in semiconductor research. Several Chinese companies have already demonstrated advanced AI servers, domestic switching equipment, optical interconnect technologies, and high-speed communication platforms. While each announcement might seem unrelated, together they point toward an effort to reduce dependence on foreign AI infrastructure. This also explains why Alibaba's recent 128-chip AI server attracted so much attention. Many people focused on the processors themselves, but the more interesting question was this: how efficiently do all 128 processors communicate? The same applies to China's no-GPU supercomputer projects, its photonic chip developments, and its advanced optical fiber demonstrations. These aren't isolated breakthroughs. They're pieces of a larger puzzle. If China successfully combines domestic processors, domestic memory, domestic networking, domestic packaging, and domestic manufacturing into one complete ecosystem, it becomes far less vulnerable to outside supply restrictions. That's a strategic advantage that extends well beyond artificial intelligence. It means researchers can continue building larger AI systems using technologies developed and manufactured within their own industrial ecosystem. For NVIDIA, however, this creates an interesting challenge. The company remains the global leader in AI hardware, and its networking technologies are among the most advanced in the world. NVIDIA doesn't simply sell GPUs anymore. It sells complete AI infrastructure, including networking, software, switches, communication libraries, and integrated systems. That's one reason NVIDIA has been so successful. Customers aren't buying individual chips, they're buying an entire AI platform. China appears to be pursuing a similar strategy, but using domestic technology wherever possible. Whether that ecosystem ultimately matches NVIDIA's performance remains an open question, but even approaching comparable performance would represent a significant achievement, especially considering how quickly China's AI hardware ecosystem has evolved over the past several years. Another reason this matters involves cost. Building one of today's frontier AI data centers requires staggering amounts of capital. GPUs represent only part of that expense. Networking equipment, optical transceivers, switches, storage systems, cooling infrastructure, electrical distribution, and physical construction account for enormous portions of the overall investment. If communication technologies become more efficient, companies may need fewer networking devices to achieve the same workload. If processors spend less time waiting, fewer processors may accomplish the same training task. If energy consumption drops, operational costs decrease year after year. Those savings compound across facilities containing tens of thousands of accelerators. Suddenly, communication improvements become financial improvements. That's exactly why investors closely watch networking announcements even when they don't generate the same headlines as new processors. Now consider another trend happening simultaneously: AI inference. Training enormous models receives most of the attention, but inference, actually running AI after it's trained, is becoming an even larger market. Billions of users interacting with AI assistants, image generators, autonomous vehicles, industrial robots, medical systems, and enterprise software require enormous infrastructure. Inference also benefits from faster communication, especially when requests must travel between multiple processors and memory systems almost instantly. Future AI won't exist inside one processor. It will exist across entire distributed computing environments. That's why networking matters for both training and deployment. There's also another technology quietly entering this discussion: silicon photonics. Instead of moving information using traditional electrical signals through copper connections, silicon photonics uses light traveling through optical pathways. Light experiences lower resistance, generates less heat, and can carry tremendous amounts of information simultaneously. Several countries are investing aggressively in this technology because many engineers believe future AI data centers will increasingly rely on optical communication rather than purely electrical connections. China has been especially active here. You've already seen stories on this channel involving glass chips, photonic manufacturing, air-filled fiber, optical communication, and integrated photonic devices. Viewed separately, each seemed like a fascinating breakthrough. Viewed together, they reveal a long-term direction. Replace communication bottlenecks with light. That doesn't happen overnight. Entire industries must adapt. Manufacturing changes, software changes, data center architecture changes. But once that transition begins, the performance gains can become substantial. It's similar to the transition from hard drives to solid-state storage. At first, only premium systems adopted SSDs. Eventually, they became standard because the performance difference was simply too significant to ignore. Networking may follow a similar path. The fastest future AI systems could increasingly rely on optical communication internally. Another fascinating aspect of China's strategy is diversification. Rather than betting everything on one technology, Chinese companies appear to be exploring multiple complementary directions simultaneously. Photonics, advanced packaging, novel memory, glass substrates, three-dimensional integration, domestic AI accelerators, optical networking, ultra-fast fiber. Each technology strengthens the others. That's important because AI performance rarely depends on one breakthrough anymore. Progress happens when dozens of improvements arrive together. Think about Formula One racing. Winning doesn't come from having only the strongest engine. Teams optimize aerodynamics, suspension, tires, brakes, fuel efficiency, weight distribution, driver strategy. Tiny gains across every category produce enormous advantages on race day. Artificial intelligence infrastructure works the same way. Every percentage improvement compounds. Better networking improves GPU utilization, better memory reduces weighting, better packaging shortens communication distances, better cooling allows higher sustained performance, better software coordinates everything more efficiently. Eventually, the combined improvement becomes much larger than any single breakthrough. That's exactly why complete AI ecosystems matter. Looking ahead, analysts expect competition to become even more intense. The next generation of AI models will almost certainly require even larger computing clusters. That means networking requirements will continue growing. Data movement will become even more critical. Energy efficiency will matter even more. Infrastructure spending will likely continue breaking records. Every company wants faster AI. Every government wants technological independence. Every cloud provider wants lower operating costs. Networking sits directly in the middle of all three goals. For viewers, the biggest takeaway isn't whether one country wins tomorrow. The real takeaway is understanding where the industry is heading. For years, headlines focused almost exclusively on processors. Now the conversation is expanding. Memory matters, packaging matters, cooling matters, optics matter, networking matters, and increasingly, the companies mastering every layer of the AI stack will likely shape the future of artificial intelligence. Whether China's latest AI networking technologies ultimately outperform competing solutions remains something the industry will continue evaluating as more systems are deployed and independently tested. Performance claims always require real-world validation across diverse workloads. But regardless of exact benchmark numbers, one conclusion is becoming increasingly difficult to ignore. The global AI race is no longer only about building faster chips. It's about building faster systems, complete systems, integrated systems, entire ecosystems capable of training, deploying, and scaling artificial intelligence more efficiently than ever before. That's why announcements involving networking may soon become just as important as announcements involving GPUs themselves. The future winners won't necessarily be those with the fastest individual processor. They may be the ones whose processors spend the least amount of time waiting. And if that's the direction artificial intelligence is heading, then today's networking breakthroughs may end up being remembered as some of the most important developments of this entire AI era. Because in the next generation of AI, speed won't just be measured inside the chip, it will be measured between them. If you enjoyed today's breakdown, don't forget to like the video, subscribe to the channel, and turn on notifications because every day we cover the biggest breakthroughs shaping China's technology race, from AI chips and memory to photonics, robotics, semiconductors, quantum computing, and everything in between. Thanks for watching, and we'll see you in the next one. What if I told you the chip everyone's been fighting over, the one NVIDIA built an empire on, the one entire nations are trying to control, the one the whole AI boom runs on, might be the wrong technology entirely, not slower, not weaker, wrong. As in, based on a fundamental approach that a team of Chinese researchers just sidestepped completely. Because while the world has been obsessed with electrons, pushing tiny electrical charges through smaller and smaller transistors, a lab in Shanghai built a chip that doesn't really use electricity to compute at all. It uses light, actual beams of light, photons, doing the calculations. And they're claiming this light-powered chip can perform certain AI tasks up to 1,000 times faster than NVIDIA's best graphics chips, while using a fraction of the power and generating almost none of the heat. 1,000 times, not 1,000%, 1,000 times. Now, before you get swept away, that number comes with serious fine print, and I'm going to give you all of it, honestly, because the real story here is more interesting than the hype. By the end of this video, you'll understand exactly how a chip can compute with light, why that's such a big deal for AI, where the 1000X claim is real, and where it falls apart, and why this might be one of the most important shifts in computing in decades, happening, once again, in a place the rest of the world wasn't watching closely enough. Let's get into it. To understand why a light-based chip matters, you first have to understand the wall that every electronic chip on Earth is slamming into. Every computer you've ever used works by moving electrons. Tiny electrical charges flow through microscopic switches called transistors, flipping on and off billions of times a second. And that dance of electricity is what we call computing. It's worked beautifully for 70 years. But it has two problems that are getting worse every single year. And no amount of clever engineering fully solves them. The first is heat. When you push electricity through a material, that material resists, and resistance creates heat. The more powerful the chip, the more electrons you're shoving through it, the hotter it gets. Modern AI data centers now spend an enormous share of their entire electricity bill not on computing, but on cooling, just trying to stop the chips from cooking themselves to death. We've covered this on the channel before. It's why diamond cooling became a billion-dollar race. Heat is the silent tax on everything. The second problem is energy. Training a single large AI model can consume as much electricity as hundreds of homes use in a year. As AI grows, its power appetite is becoming genuinely unsustainable. Companies are now talking about building dedicated nuclear plants just to feed their data centers. That is not a metaphor. That is a real plan, because electrons are hungry. So here's the question a handful of scientists started asking years ago. What if we stopped using electrons to compute? What if we used something that doesn't resist, doesn't heat up the same way, and moves at the fastest speed the universe allows? What if we computed with light? This is the part that sounds like science fiction, so let me make it concrete, because the core idea is genuinely elegant. Think about the last time light passed through a glass of water and bent, or split into a rainbow, or two ripples on a pond crossed and combined into a bigger ripple. Light naturally interacts. It bends, it combines. It interferes with itself in precise, predictable, mathematical ways. And here's the insight that took decades to turn into hardware. Those natural interactions are math. When two beams of light combine, the universe is, in a sense, performing a calculation, instantly, at the speed of light, using no transistors at all. A photonic chip is built to harness exactly that. Instead of wires carrying electrons, it has microscopic channels, waveguides, that carry beams of light. By splitting those beams, shifting them, and recombining them in carefully designed patterns, the chip performs the kind of mathematical operations that sit at the absolute heart of artificial intelligence. The multiplication of huge grids of numbers over and over, that's most of what training and running an AI actually is. And it turns out light is astonishingly good at doing that specific kind of math. Here's the analogy I find most useful. Traditional computing with electrons is like sending thousands of messengers through a crowded subway system. They bump into each other, they generate heat, they wait in line, they burn energy at every step. Photonic computing is like sending those same messages as laser beams through open air. No traffic, no friction, no heat from resistance. Just information moving at the one speed nothing in the universe can beat. That's the dream that's been chased for decades. The reason it stayed a dream so long isn't the physics, it's the manufacturing. And that's exactly the wall a Chinese institute just claims to have broken through. The chip at the center of this story comes from an institute called ChipX, working with a company called Turing Quantum, based in Shanghai. And what makes their announcement different from 20 years of photonic computing promises isn't a lab demo. It's a factory. Here's what they built. A 6-inch wafer made of a material called thin-film lithium niobate. And that material choice is the whole key, so hang on to it. Onto that wafer, they packed more than 1,000 optical components, the tiny light splitters, shifters, and channels that do the computing. Over 1,000 of them, integrated onto a single chip, all working together with light. Why does lithium niobate matter so much? Because it has an almost magical property. When light passes through it, you can precisely control that light, its phase, its intensity. Many labs could make one. Almost nobody could make them reliably in volume. ChipX says it cracked exactly that. In June, the institute launched what it describes as China's first pilot production line for these thin-film lithium niobate photonic wafers, with a capacity of around 12,000 6-inch wafers a year, each wafer yielding roughly 350 chips. Now, in raw numbers, 12,000 wafers is tiny compared to a giant silicon fab that pumps out hundreds of thousands. But for this specific cutting-edge type of photonic chip, it's a genuine industrial foothold. The difference between a science project and the early days of a real supply chain. And the developers claim these chips are already being used in the real world, in fields like aerospace and finance. So what about that headline number? Everything you do online is being watched. Your provider, advertisers, even governments. NordVPN encrypts your connection, hides your location, and unlocks the open internet from anywhere. Grab the deal, link in the description. The 1000X. Here's where I have to be completely straight with you, because this is exactly the kind of claim that gets channels in trouble when they don't read the fine print. The 1,000 times faster than NVIDIA figure is real in the sense that it was genuinely claimed by the developers and reported by serious outlets like the South China Morning Post. But it comes with 3 critical pieces of fine print that the breathless headlines leave out. And you deserve all 3. First, and most important, that speed is for specific, narrow tasks, not general computing. A photonic chip is not a drop-in replacement for your computer's processor, and it's not a drop-in replacement for an NVIDIA GPU across the board. It's spectacularly fast at one particular kind of math, the optical interference calculations it's physically built for. For those specific workloads, the speed-up is real and enormous. Ask it to do something outside that narrow lane, and the advantage vanishes. As one set of researchers put it, these chips can outperform GPUs by orders of magnitude, but only in tightly constrained domains. To use an analogy, it's like comparing a drag racing car to a regular sedan. On a perfectly straight quarter-mile track, the dragster is unbelievably, jaw-droppingly faster. But you can't drive it to the grocery store, you can't take it on the highway, and it can't turn corners. The 1000X is a drag strip number. NVIDIA's chips are the sedan you can drive anywhere. Both facts are true at once. Second, there's a separate but related breakthrough worth knowing, because it makes the story stronger, not weaker. Researchers at Shanghai Jiao Tong University and Tsinghua University, in a paper published in the prestigious journal Science, demonstrated a fully optical chip called LightGen, built with over 2 million photonic neurons that ran image and video generation tasks more than 100 times faster and more efficiently than a leading NVIDIA GPU. So this isn't a single lab making a wild claim. Multiple serious Chinese research teams are independently showing that light-based chips can crush GPUs at narrow AI tasks. The pattern is real even where any single number is debatable. Third, the honest caveats. The technology still faces real challenges. Yields are low, the long-term stability of these chips under sustained heavy use isn't fully proven, and exactly how that 1000X was measured remains a little murky. This is early-stage, frontier technology. It is not about to replace every NVIDIA chip in every data center next year. So here's the fair summary, the one you won't get from the hype videos or the dismissive ones. China has not made NVIDIA obsolete, but it has demonstrated in real silicon coming off a real pilot line that for the specific math that AI leans on most heavily, there is a fundamentally different and dramatically more efficient way to compute, and China is currently the one scaling it toward production. Here's the part of this story that I find genuinely fascinating, and it ties back to everything else happening in this race. When the world's biggest tech players thought about the future of radical new computing, most of them, especially in the West, bet heavily on a different approach: superconducting quantum computers. Incredibly powerful in theory, but with a brutal catch. They have to be cooled to nearly absolute zero, colder than deep space, inside giant, fragile, fantastically expensive refrigeration systems. It's a moonshot that requires extraordinary infrastructure. China made a different bet. It poured serious effort into room temperature photonic computing, chips that use light and work at normal temperatures, no exotic cooling required. And here's why that bet is so clever and so consistent with the pattern we keep seeing. Photonic chips, unlike the most advanced electronic chips, can be manufactured using older, more mature fabrication processes, the kind that don't require the single most advanced, most restricted chip-making machines on Earth. Do you see the move? Just like the GPU-free supercomputer, just like the new approach to chip design we covered recently, being blocked from the cutting edge of electronic chip-making, pushed China to invest heavily in a different kind of computing entirely, one where the restrictions matter far less. Light doesn't need a 2-nanometer transistor. Photonic computing is a lane where the export controls lose much of their grip. The wall once again didn't stop the water. It just changed the direction it flowed. And this time, it flowed toward light. Let me zoom out, because it's easy to lose the forest for the trees here. Nobody serious is claiming silicon is dead or that NVIDIA is finished. Electronic chips are flexible, mature, and woven into everything. They are not going anywhere for a very long time. The realistic future isn't light replacing electronics, it's light joining them. Imagine a data center where the flexible, general-purpose work runs on traditional chips, but the specific, brutal, repetitive math at the heart of AI gets handed off to photonic chips that do it 100 or 1,000 times more efficiently. A hybrid, the best of both worlds. And that future matters enormously for one reason above all: energy. If even a portion of the world's exploding AI workload can be shifted onto chips that compute with light, generating less heat, sipping a fraction of the power, it could meaningfully bend the curve on AI's terrifying energy appetite. That's not just a speed story, it's a sustainability story. It might be the difference between an AI future that's possible and one that's strangled by its own power bills. And the strategic dimension is just as large. For years, the entire framework of this technology race assumed the battlefield was electronic chips. Who can make the smallest transistor? Who controls the best lithography machine? Photonic computing potentially reframes the whole contest. It's a different battlefield, with different rules, and China has quietly built one of the strongest early positions on it. Whether or not any single 1000X headline holds up, that is the development the rest of the world should be paying attention to. Here's my honest opinion. I think the smartest way to hold this story is with two ideas at the same time, refusing to collapse into either easy version. On one hand, the people shouting China just made NVIDIA obsolete with a magic light chip are running way past the evidence. The 1000X is a narrow drag strip number, the yields are low, and this is early technology with real unanswered questions. Anyone selling you that is selling hype. But on the other hand, the people rolling their eyes and saying it's just a niche lab toy, ignore it, are making the bigger mistake, and it's the same mistake people keep making in this race. Because underneath the inflated headline is something genuinely real. Multiple serious Chinese teams, publishing in journals like Science, building actual chips on an actual pilot production line, proving that light-based computing can demolish the world's best GPUs at exactly the kind of math AI needs most. That's not nothing. That's the early shape of a different future. What strikes me most is how familiar the pattern has become. Cut off from the most advanced electronic chip making, China didn't just try harder to catch up on the same road. It invested in a road that goes around the roadblock entirely. Light instead of electrons. Room temperature instead of near absolute zero. Older fabs instead of forbidden machines. Over and over, the constraint becomes the catalyst. I genuinely don't think that's luck anymore. I think it's the defining strategy of this entire era, and we're watching it play out in real time. So here's my question for you, and I really want your honest answer. Do you think the future of AI computing belongs to light, these photonic chips that sip power and run cool? Or will electronic chips like NVIDIA's stay on top because they can do everything, even if they run hot and hungry? Is light the real future, or just a brilliant specialist that'll never leave its narrow lane? Drop your honest take in the comments. I read every single one, and I have a feeling this one's going to spark a real debate. If you want to keep following this, the breakthroughs, the workarounds, the technologies the rest of the world underestimates until they suddenly can't, subscribe to Eastern Engine and hit the notification bell. Chips, light, energy, supercomputers, the entire foundation of modern technology is being rewritten right now, and we break it all down before the mainstream catches up. Thanks for watching. I'll see you in the next one. Silicon has been the foundation of the modern world for more than half a century. Every smartphone, every gaming PC, every AI server, every data center, every satellite, every electric vehicle, and nearly every advanced electronic system relies on one material more than any other. Silicon quietly became the invisible backbone of civilization. It powered the internet, fueled the smartphone revolution, and now drives the AI race that has reshaped the global economy. For decades, the assumption seemed impossible to challenge. If you wanted faster chips, you improved silicon. If you wanted smarter AI, you built more silicon. If you wanted more computing power, you invested billions into making silicon smaller, faster, and more efficient. But what if the entire industry has been chasing the wrong answer? Because while much of the world continues investing hundreds of billions of dollars into squeezing another few percentage points out of silicon, researchers in China have been quietly pursuing something far more ambitious. Instead of asking how to improve silicon, they asked a completely different question: what comes after it? That question has suddenly become one of the biggest discussions inside the semiconductor industry. Not because silicon is disappearing tomorrow, but because the physical limits that engineers have warned about for years are becoming increasingly difficult to ignore. As transistors shrink toward atomic dimensions, every new manufacturing generation becomes exponentially more expensive, more complicated, and more difficult to produce. The roadmap that carried computing for decades is beginning to slow down. And whenever one era starts slowing, another usually begins. Across China, universities, research institutes, advanced laboratories, photonics companies, material scientists, and semiconductor manufacturers are all exploring technologies that could fundamentally change how information moves through computers. Some projects focus on light instead of electricity. Others replace traditional semiconductor materials with entirely different compounds. Some abandon conventional transistor designs altogether. Individually, many of these breakthroughs seem incremental. Together, they begin to paint a picture of where computing may be heading next. That possibility is making investors, governments, and technology companies pay very close attention. Because replacing silicon wouldn't simply create another faster processor. It could reshape AI infrastructure, data centers, telecommunications, cloud computing, autonomous vehicles, defense technologies, and countless industries built on digital hardware. And unlike previous generations of chip improvements, this transition may not simply be about making today's computers faster. It could redefine what computers actually are. The reason this matters now is because artificial intelligence has changed the rules. Modern AI models require staggering amounts of computational power. Companies are building data centers consuming gigawatts of electricity. GPU clusters now contain tens of thousands of processors communicating simultaneously. Memory systems struggle to keep pace. Heat generation continues increasing. Power consumption rises year after year. Ironically, many of today's biggest AI limitations are no longer caused by software. They're caused by physics. Moving electrical signals through microscopic copper wiring generates resistance, heat, latency, and energy loss. Shrinking transistors further introduces quantum effects that engineers spent decades trying to avoid. Every new manufacturing node requires increasingly expensive lithography equipment and unprecedented engineering precision. Silicon hasn't stopped working. It's simply becoming much harder to improve. That reality has pushed scientists around the world to search for alternatives that were once considered experimental. Photonic computing, advanced glass materials, optical interconnects, wide bandgap semiconductors, two-dimensional materials, and entirely new computing architectures have all moved from academic research into serious engineering programs. China has invested heavily across nearly all of these fields. Some of those investments are beginning to produce results that have attracted attention well beyond China's borders. The conversation is no longer whether alternative technologies will exist. The real question has become which country commercializes them first, because history shows something remarkably consistent. The companies that dominate one generation of computing rarely dominate the next without adapting. Mainframes gave way to personal computers. Desktop computing gave way to smartphones. Traditional CPUs were joined by GPUs. AI accelerators emerged alongside them. Every technological transition created new leaders, while forcing established giants to reinvent themselves. The next transition may prove even larger. If silicon eventually stops being the default foundation for advanced computing, entire supply chains could shift. Manufacturing priorities would change. Equipment vendors would adapt. Software developers would optimize for different hardware. Data centers could be redesigned from the ground up. That doesn't mean silicon suddenly disappears. Far from it. Silicon will almost certainly remain essential for years, perhaps decades. But the industry's focus may gradually move toward hybrid systems where silicon works alongside entirely new technologies rather than carrying the entire workload alone. And that's where China's latest research becomes especially interesting. Because instead of trying to replace every silicon chip overnight, many of its projects focus on replacing only the components where silicon performs worst. Communication between chips, high-speed data transfer, AI memory bottlenecks, heat generation, optical computing, advanced materials, one breakthrough at a time. Individually, none of these developments may seem revolutionary. Combined, they could represent the early stages of something much bigger, a transition away from an era that has defined computing for more than 50 years. And if that transition accelerates faster than expected, the biggest question won't simply be whether silicon has reached its limits. It will be who built what comes next. To understand why researchers are searching beyond silicon, you first have to understand how extraordinary its success has been. Silicon didn't become the world's dominant semiconductor by accident. It offered an almost perfect combination of affordability, stability, electrical performance, and manufacturability. As fabrication techniques improved, engineers discovered they could place more transistors onto a single chip while reducing cost per calculation. That simple trend became the engine behind modern computing for decades. Every 2 or 3 years, processors became faster, smartphones became smarter, video games became more realistic, cloud computing became practical. Artificial intelligence evolved from science fiction into everyday reality. Silicon made all of it possible, but every technology eventually reaches a point where improvement becomes increasingly difficult. For silicon, that challenge arrives at the atomic scale. Modern transistors are now measured in just a few nanometers. At these dimensions, engineers aren't simply designing electronic circuits anymore. They're designing around the strange behavior of quantum mechanics. Electrons begin leaking through barriers they were never supposed to cross. Heat becomes increasingly difficult to remove. Manufacturing tolerances shrink to astonishing levels. A tiny defect invisible to the human eye can ruin an entire wafer worth millions of dollars. This is one reason semiconductor fabrication has become one of the most expensive industries on Earth. Building a leading-edge fabrication plant now costs tens of billions of dollars. Every new manufacturing generation requires increasingly sophisticated equipment. Extreme ultraviolet lithography, atomic layer deposition, advanced packaging, high-precision metrology. Each improvement demands more investment while delivering smaller performance gains. Engineers sometimes describe this as the easy progress coming to an end. For decades, shrinking transistors solved nearly every problem. Today, shrinking them further solves fewer problems while creating entirely new ones. Artificial intelligence has made those limitations impossible to ignore. Modern AI models no longer rely on a single processor performing calculations independently. Instead, thousands of processors work together simultaneously. Each processor constantly exchanges enormous amounts of information with every other processor. That communication consumes time. It consumes electricity. it generates heat, and increasingly, it limits overall system performance. Ironically, some of the world's most powerful AI processors now spend part of their time waiting. Not because they're too slow, because information can't reach them quickly enough. That's a remarkable reversal. For years, processors represented the bottleneck. Now the bottleneck often exists between the processors. Moving data has become almost as important as processing data. This shift explains why researchers are exploring technologies that don't simply improve silicon. They're trying to redesign the entire architecture surrounding it. China has become particularly active in this area. Over the past several years, we've seen Chinese researchers publish advances involving photonic chips capable of transmitting information using light rather than electrical signals. Glass-based packaging technologies designed to improve chip communication. Air-filled optical fibers capable of transmitting enormous amounts of data across impressive distances. Novel semiconductor materials intended to reduce energy loss. Optical interconnects designed specifically for AI infrastructure. Advanced chip packaging that shortens communication pathways. Viewed separately, each breakthrough appears highly specialized. Viewed together, they reveal a consistent strategy. Instead of asking how to build a slightly faster processor, researchers are asking how to eliminate the limitations surrounding today's processors altogether. That's an important difference. Imagine upgrading the engine inside a race car while leaving narrow tires, weak brakes, and poor suspension unchanged. The engine becomes more powerful. The car doesn't necessarily become much faster. Modern AI faces a similar challenge. Processors have advanced rapidly. Memory has improved. Storage has become dramatically faster. But communication between all those components hasn't improved at the same pace. That imbalance has created entirely new engineering priorities. This helps explain why many semiconductor conferences today focus as much on packaging, networking, photonics, and material science as they do on transistor density. The future isn't being defined by one component. It's being defined by how every component works together. China's semiconductor strategy appears increasingly aligned with that philosophy, rather than concentrating and reduce dependence on silicon doing everything alone. That's why the title of this video isn't suggesting silicon suddenly disappears tomorrow. It suggests something arguably more significant. Silicon may no longer be the only foundation capable of supporting next-generation computing. Future AI systems may rely on entirely new combinations of technologies working alongside traditional semiconductor designs. Processors optimized for specific workloads, photonic communication replacing electrical signaling, advanced packaging reducing communication distances, novel materials handling specialized calculations, silicon remaining where it performs best. This hybrid approach could extend computing far beyond what conventional transistor scaling alone can achieve. Some researchers even argue that the future of computing won't belong to a single revolutionary material. Instead, it will belong to ecosystems capable of combining multiple technologies into one highly efficient platform. That possibility is attracting enormous investment worldwide, because whoever successfully builds that platform may define the next era of computing, not by making silicon slightly better, but by making the entire system fundamentally smarter. If silicon is approaching practical limits, the obvious question becomes surprisingly simple. What exactly replaces it? The answer is more complicated than many headlines suggest. There probably won't be a single material that suddenly takes over the semiconductor industry overnight. Instead, engineers increasingly believe the next generation of computing will emerge from several technologies working together, each solving a different problem that silicon struggles to handle. In many ways, the future of computing may look less like a replacement and more like an evolution. That's where China's recent research becomes particularly interesting. Rather than betting everything on one breakthrough, Chinese laboratories have been exploring multiple paths simultaneously. One of the most promising involves photonic computing. Traditional processors move information using electrons flowing through microscopic circuits. Photonic systems replace some of those electrical signals with light. At first glance, that may not sound revolutionary, but light behaves very differently from electricity. Photons travel at incredible speeds. They generate far less heat while transmitting information. They experience minimal electrical interference. And perhaps most importantly, they can carry enormous amounts of data simultaneously through optical pathways. These advantages become especially valuable inside artificial intelligence infrastructure. Modern AI isn't limited by mathematical calculations alone. It's limited by communication. Thousands of processors constantly exchange data. Memory modules feed enormous datasets into GPU clusters. Networking hardware moves information between racks. Storage systems continuously deliver new training data. Every delay reduces efficiency. If light can move that information faster than electricity, AI systems become more productive without necessarily building faster processors. That's one reason photonic technologies have become one of the semiconductor industry's hottest research areas. China isn't alone in pursuing this vision. Companies and research institutions across the United States, Europe, Japan, South Korea, and Taiwan are investing heavily in optical computing as well. But China's pace of announcements has accelerated noticeably over the past few years. We've covered breakthroughs involving photonic processors, glass-based chip packaging, air-filled fiber capable of record-breaking transmission speeds, optical interconnects, integrated AI networking. Each project addresses a different communication challenge. Together, they point toward a future where electrical signaling no longer carries every piece of information inside advanced computers. Another promising direction involves entirely new semiconductor materials. For decades, silicon dominated because it balanced cost, reliability, and manufacturing simplicity. But other materials possess electrical properties that outperform silicon in specific applications. Gallium nitride allows higher power efficiency. Silicon carbide excels in electric vehicles and industrial power electronics. Two-dimensional materials measured only atoms thick are being explored for future transistor designs. Researchers are investigating carbon-based structures with remarkable electrical behavior. None of these materials completely replaces silicon today. Instead, each one solves particular problems where silicon reaches its limits. That's an important distinction. The semiconductor industry rarely abandons successful technology immediately. It gradually introduces specialized alternatives where the benefits justify the cost. We've already seen this happen in memory. Traditional hard drives still exist. Solid-state storage expanded alongside them. Cloud storage joined both. Each technology found its own role. The same pattern may emerge with computing materials. Silicon remains excellent for general-purpose processing. Photonics may dominate communication. Wide bandgap materials may power electric infrastructure. Advanced packaging may reduce communication delays. Novel memory technologies may eliminate existing bottlenecks. Instead of replacing silicon entirely, future computers may simply rely on silicon much less than they do today. That shift could prove just as significant. China's strategy appears designed around exactly this kind of diversification. Rather than concentrating every research dollar on one revolutionary invention, investments span nearly every layer of modern computing. Semiconductor manufacturing, memory technology, advanced packaging, optical communication, artificial intelligence hardware, materials science, telecommunications, industrial automation. This creates something more valuable than isolated breakthroughs. It creates an ecosystem where improvements in one field immediately benefit another. Faster networking improves AI clusters. Better packaging enhances processor performance. Advanced materials reduce energy consumption. Optical communication eliminates bottlenecks. Each improvement strengthens the others. That's why many analysts increasingly evaluate semiconductor competition differently than they did 10 years ago. The question isn't simply who builds the fastest chip. It's who builds the strongest ecosystem around that chip. Because artificial intelligence has fundamentally changed what high-performance computing requires. Success no longer depends on processor speed alone. It depends on communication, power efficiency, heat management, memory bandwidth, packaging technology, networking architecture, manufacturing capability, software optimization, supply chains. The winners of tomorrow's computing industry will likely master all of them. That's why replacing silicon isn't really about one material defeating another. It's about building an entirely new generation of computing infrastructure. And if China's current strategy succeeds, the biggest breakthrough may not be a single revolutionary processor. It may be something much larger, a computing platform where silicon is no longer the star of the show. Instead, it becomes just one component inside a far more advanced technological ecosystem. Whether silicon is truly nearing the end of its dominance remains an open question. Predicting the future of technology has never been easy, especially in an industry that has repeatedly surprised even its own experts. Every few years, a breakthrough emerges that changes expectations, reshapes investment, and forces companies to rethink their long-term strategies. What's different today is the scale of that transformation. Artificial intelligence has accelerated demand for computing faster than almost anyone anticipated. Data centers continue growing larger. AI models require exponentially more processing power. Energy consumption keeps climbing. At the same time, the physical limits of traditional chip design are becoming increasingly difficult and expensive to overcome. That reality is pushing the entire industry to think differently. Instead of relying on one material to solve every problem, researchers are building systems where multiple technologies work together. Silicon may continue handling general-purpose computing, while photonics speeds up communication, advanced materials improve efficiency, and new packaging techniques reduce delays between components. In many ways, the future may not belong to a single revolutionary invention. It may belong to whoever integrates these technologies into one seamless platform first. China appears determined to compete in exactly that race. Over the past several years, we've seen growing investment across semiconductor manufacturing, AI hardware, optical networking, advanced materials, memory technologies, and chip packaging. Each announcement on its own may seem incremental, but together they suggest a broader strategy, one focused on shaping the next era of computing rather than simply catching up to the last one. Of course, none of this means silicon suddenly becomes obsolete tomorrow. Billions of devices around the world will continue relying on silicon for many years to come. The semiconductor industry doesn't replace foundational technology overnight. It evolves step by step, generation by generation. But history shows that every technological era eventually reaches a turning point. Vacuum tubes gave way to transistors. Mainframes gave way to personal computers. CPUs were joined by GPUs. Now, the industry is searching for what comes after today's AI hardware. Whether the next breakthrough comes from photonics, new semiconductor materials, hybrid architectures, or an approach nobody has imagined yet, one thing is becoming increasingly clear. The future of computing will likely look very different from the systems we've relied on for the past 50 years. And if that future arrives sooner than expected, today's biggest advantage may not belong to the company with the fastest silicon chip. It may belong to the country that successfully builds what comes next. If you enjoyed this video, don't forget to like, subscribe, and turn on notifications so you never miss our latest deep dives into AI, semiconductors, and the technologies shaping the future. Thanks for watching, and I'll see you in the next one. For more than 50 years, nearly every major advance in computing has followed the same basic strategy. Make silicon transistors smaller, place more of them on one chip, then use those extra transistors to increase performance, reduce power consumption, and add new capabilities. That formula transformed computers that once filled entire rooms into processors small enough to fit inside phones, watches, and medical sensors. But silicon cannot shrink forever. As transistor channels become extremely thin, electrical current becomes harder to control. Leakage increases. Heat becomes more difficult to manage. And the material begins behaving in ways that make conventional scaling less effective. Researchers around the world are therefore searching for something that could eventually work alongside silicon, or possibly replace it in specific parts of future chips. A team at Fudan University in China has now demonstrated one of the most advanced alternatives yet. They built a functioning 32-bit RISC-V processor using 5,931 transistors made from molybdenum disulfide. The active semiconductor inside each transistor consists of one layer of molybdenum atoms placed between two layers of sulfur atoms. 3 atomic planes in total. The processor is called RV32WUGI. It can execute standard 32-bit instructions, perform arithmetic, and operate as a programmable microprocessor, rather than a single isolated laboratory transistor. It is not fast. It runs at approximately 1 kHz, millions of times slower than a modern desktop or smartphone processor. Its 5,931 transistors are almost nothing compared with the billions found in commercial chips. But speed was not the purpose of this experiment. The breakthrough was proving that thousands of atomically thin transistors could be manufactured consistently, connected into reusable logic cells, and assembled into a complete processor architecture. Researchers did not simply create one transistor that worked under perfect laboratory conditions. They created a system. And that may be the step two-dimensional semiconductor technology needed most. Why silicon becomes difficult to shrink. A transistor is essentially a tiny electrical switch. One terminal controls whether current can travel through a semiconductor channel between two other terminals. When the switch is on, current flows. When it is off, the channel should block that current. Billions of these switches combine to create logic gates, registers, memory interfaces, and processor cores. For decades, reducing transistor dimensions improved nearly everything. Smaller transistors switched faster, they required less energy, and manufacturers could place more computing power inside the same area. But when a conventional semiconductor channel becomes extremely thin, the electric field controlling it can lose authority over the charge inside. Current may leak even when the transistor is supposed to be off. Interfaces between the semiconductor and surrounding materials can interfere with electron movement. The difference between the transistor's on and off states can become less distinct. Engineers have extended silicon scaling through advanced structures such as FinFETs and gate-all-around transistors. Instead of controlling the channel from only one side, the gate wraps around more of it. That improves electrostatic control. But even these designs face limits. The thinner the silicon becomes, the more its electrical properties can degrade. This is why two-dimensional semiconductors are so interesting. They are naturally atomically thin. Researchers do not need to carve a thick block of material down until only a fragile channel remains. The crystal itself is built in layers. What molybdenum disulfide actually is, molybdenum disulfide, usually written as MoS2, is made from molybdenum and sulfur. In its single-layer form, one sheet of molybdenum atoms sits between two sheets of sulfur atoms. This structure is extremely thin, but it still behaves as a semiconductor. That distinction matters. Graphene is probably the most famous two-dimensional material. It is strong, thin, and highly conductive. But ordinary graphene lacks a natural band gap. That makes it difficult to switch completely off, which is a serious problem for digital logic. A processor needs a clear difference between 0 and 1. MoS2 has a band gap, allowing a transistor to control current much more effectively. Its atomically thin body also gives the transistor gate strong electrical control over the complete channel. In theory, that could help engineers continue shrinking devices after conventional silicon becomes increasingly difficult. But producing one excellent MoS2 transistor is not the same as building a processor. A transistor may work beautifully when a researcher selects one perfect location on a small sample. A processor requires thousands, millions, or eventually billions of devices to behave predictably at the same time. A small variation that seems unimportant in one transistor can ruin an entire logic circuit when repeated across a wafer. That is the challenge the Fudan team tried to solve. From one transistor to 5,931. Before RV32WUGI, researchers had created many promising two-dimensional transistors. They had also built small logic circuits. But integration remained limited to only a few hundred devices. UGI increased that complexity dramatically. The finished processor contained exactly 5,931 months two transistors on a die measuring approximately 6 mm by 6 mm. Researchers fabricated multiple dies on a 4-inch sapphire wafer. Sapphire was used as an insulating base that helped electrically isolate the devices. The important achievement was not density. A 6 mm modern silicon chip could hold millions or even billions of transistors, depending on the manufacturing process. WUGI's devices were physically large. Their transistor channels were approximately 3 micrometers long. That is thousands of times larger than the smallest features inside advanced commercial processors. But the researchers were working with university-level fabrication equipment rather than one of the world's most advanced semiconductor factories. They prioritized reliability over density. Before shrinking the system, they needed to prove that the material could support a complete processing architecture. Building a library of logic processor designers do not normally draw every transistor individually. They use collections of verified building blocks called standard cells. A standard cell library may include inverters, AND gates, OR gates, multiplexers, registers, and more complex combinations. Design software connects these cells to create larger circuits. The Fudan team developed a complete library containing 25 types of logic units made from its two-dimensional transistor technology. This was essential. A single transistor is only a switch. Useful computation begins when switches are combined into logic. An inverter changes a 1 into a 0 or a 0 into a 1. An AND gate produces an output only when multiple conditions are true. Registers store temporary values. Adders combine binary numbers. Once these blocks behave consistently, engineers can reuse them throughout the processor. This is where WUGI moved beyond many earlier demonstrations. The project was not only material science. It combined material growth, transistor fabrication, circuit design, standard cell development, and processor architecture. The team co-optimized the manufacturing process and the chip design. Instead of assuming that tools created for mature silicon would transfer perfectly to MoS2, researchers adjusted both sides together. The circuits were designed around what the new devices could manufacture reliably. The manufacturing process was improved according to what the processor needed. Why machine learning was used? Wafer-scale two-dimensional materials contain many possible sources of variation. The film may not grow identically across every location. Contacts between metal and the semiconductor can vary. Residue defects and microscopic contamination can affect device behavior. Threshold voltage may shift from one transistor to another. When thousands of devices are connected, these small variations can accumulate. The researchers used machine learning methods to help optimize fabrication steps and improve consistency. This does not mean artificial intelligence designed the complete processor by itself. Machine learning helped researchers analyze manufacturing data, identify relationships between process conditions and device performance, and refine the production flow. The team reported a manufacturing yield of approximately 99.77%. That level of consistency was critical. A processor containing almost 6,000 transistors cannot function if large numbers of devices fail randomly. High yield allowed the team to move from individual test structures to a complete programmable circuit. Why they chose RISC-V. The processor uses the RISC-V instruction set architecture. An instruction set defines the commands a processor understands. Instructions may tell it to add numbers, move data, compare values, or jump to another part of a program. RISC-V is open and modular. Companies and researchers can design processors around it without paying for a proprietary instruction set license. That makes it especially useful for experimental hardware. The researchers did not need to create an entirely new software language simply because they were using a new semiconductor. They could implement a recognized 32-bit architecture and test whether the MIOS-2 processor executed standard instructions correctly. UGI demonstrated arithmetic, including addition and subtraction, as well as movement of data through its registers and control logic. That may sound basic, but basic arithmetic is built from multiple coordinated steps. It also contains fewer than 6,000 transistors, while advanced commercial chips contain tens of billions. During arithmetic operation, the prototype consumed approximately 0.43 milliwatts. That sounds impressive, but it would be misleading to compare the number directly with a high-performance laptop processor. UGI is performing far less computation. Its low total power partly reflects its limited size and very low speed. The researchers are not claiming that this prototype can replace an Intel, AMD, Apple, or Qualcomm processor. The accurate comparison is with previous two-dimensional circuits. From that perspective, UGI represents a major jump from small collections of laboratory devices towards system-level integration. The Wright brothers' first aircraft was not useful as a modern passenger jet. Its importance was proving controlled powered flight. UGI plays a similar role for atomically thin logic. It proves the material can do more than switch one signal in a laboratory. It can form a programmable processing system. Why atomic thickness could matter later. One possible advantage of two-dimensional materials is better control at extremely small dimensions. Another is vertical integration. Modern chips are increasingly stacking components. Memory dies are stacked to create high-bandwidth memory. Chiplets are combined inside advanced packages. Manufacturers are exploring ways to place logic layers above other circuits. The problem is temperature. Traditional transistor fabrication often involves processes hot enough to damage circuitry already built underneath. Some two-dimensional materials may be deposited or integrated at lower temperatures. That could eventually allow engineers to add new logic or sensing layers above completed silicon circuits. A future chip might use silicon for high-performance processor cores, while atomically thin devices handle sensors, local processing, or additional logic in layers above them. Two-dimensional semiconductors may therefore complement silicon before they replace it. They could also be useful in low-power edge devices. A smart sensor may not need billions of transistors or gigahertz performance. It may need a small amount of computation close to where information is collected. Thin materials could potentially combine sensing and processing in compact devices with unusual shapes or strict power limits. What still has to be solved? The road from WuJi to commercial production remains long. The transistor channels must become much shorter. The researchers' current 3-micrometer devices are enormous by modern standards. Better lithography could increase density and improve speed. Contacts between metal and MIOS-2 must also become more reliable and lower in resistance. Manufacturing must scale from small research wafers to large industrial wafers with consistent material quality. The design will need complementary transistor types comparable to the efficient CMOS logic used in modern silicon chips. Packaging, long-term reliability, temperature stability, and manufacturing cost must all be tested. And every improvement must occur without destroying the properties that make the material attractive. A working prototype is evidence of possibility. It is not evidence that mass production will be easy. Shanghai has announced an engineering demonstration line intended to move related two-dimensional chip technology beyond the university laboratory. But ambitious production targets should remain separate from what has already been scientifically demonstrated. The verified achievement today is the processor itself. My take is that the 3-atom headline is impressive, but the most important number is 5,931. Researchers have produced atomically thin transistors for years. The problem was making thousands of them behave consistently enough to create a processor. Wujuji demonstrates that the challenge is no longer limited to proving the material can switch current. The conversation can now move toward design libraries, yield, integration, and manufacturing. That is a more difficult stage, but also a more meaningful one. This processor will not compete with commercial silicon. It was never intended to. Its purpose was to cross the gap between an experimental transistor and a functional computing architecture. The team crossed that gap with a 32-bit RISC-V system, 25 types of logic cells, and nearly 6,000 MOS2 transistors. The processor is slow, it is physically large, and it remains a laboratory prototype. But every semiconductor platform begins with devices that look uncompetitive next to the mature technology they hope to challenge. Silicon has received decades of investment, factory development, and design optimization. Two-dimensional semiconductors are only beginning to build that ecosystem. So what do you think? Will atomically thin materials eventually become a serious successor to silicon, or will they remain specialized layers used only in sensors and low-power edge devices? Let me know your view in the comments. And subscribe to Eastern Engine for more grounded coverage of the chips, materials, and manufacturing breakthroughs shaping the future of computing. Because China has not built a 3-atom thick replacement for today's fastest processors, but it has proved that transistors only 3 atomic planes thick can work together as a real programmable CPU. And that is where a laboratory material begins becoming a computing technology.
So Apple looking for relief from the chip crunch behind this week's Mac and iPad price hikes. And I'm told by a person briefed on the discussions, that includes asking the administration for more flexibility to work with Chinese memory suppliers. And of course follows CEO Tim Cook telling the Journal just last week that all vendor options are back on the table. Now, the two key names in question are YMTC and CXMT, China's heavily state-backed domestic memory players. YMTC makes NAND flash storage, CXMT makes DRAM, the working memory.
China's largest memory chip maker has reportedly secured a deal worth nearly $3 billion from Tencent, one of the biggest technology companies in the country. Just days after reports said Apple was asking Washington for political clearance to buy memory from the same Chinese supplier, Changshin Memory Technologies, better known as CXMT, has landed what may be the strongest commercial endorsement in its history. The reported agreement covers more than 20 billion yuan, or roughly $2.94 billion, in DRAM chips for Tencent servers over several years. That memory will support cloud computing, databases, and artificial intelligence workloads. CXMT is no longer being treated only as a protected domestic challenger. It is becoming a supplier that major Chinese technology companies may be willing to depend on at enormous scale. If Tencent is prepared to commit billions of dollars to CXMT, could Apple be next? It is a story about how the global memory shortage, the AI infrastructure boom, and political pressure are rewriting the semiconductor supply chain. For decades, the DRAM market has been dominated by 3 companies. Samsung Electronics, SK Hynix, and Micron control most global production. That concentration gave them enormous influence over pricing, technology, and supply. When demand rises faster than new factories can respond, there are very few alternative suppliers capable of filling the gap. AI data centers are consuming huge amounts of advanced memory. Large models need memory close to processors so data can move quickly enough to keep expensive computing systems busy. Cloud companies also require conventional server DRAM for databases, virtualization, storage systems, and general computing. High bandwidth memory receives most of the attention because it sits beside advanced AI accelerators. And when the biggest technology companies build infrastructure at the same time, demand spreads across the entire market. According to the latest reporting, DRAM contract prices rose roughly 95% quarter-over-quarter during the first quarter of 2026.
Used in iPhones, PCs, and servers. Both are young companies compared with Samsung, SK Hynix, and Micron, which built their businesses decades ago. But they are gaining share quickly. Counterpoint says YMTC now has 13% of the global NAND market, while CXMT has 8% of DRAM. CXMT also gaining ground fast, preparing for what could be mainland China's largest IPO in years. And Counterpoint is hearing from stakeholders in the supply chain that these Chinese memory names can
Large cloud companies do not want to enter every quarter uncertain about price, availability, or delivery. And in some cases, they are willing to provide prepayments or commit years in advance to secure supply. The reported CXMT agreement may run for 3 years, while another source suggested it could extend as long as 5. That means Tencent is not simply making a spot purchase to cover a temporary shortage. DRAM is one of the most difficult semiconductor businesses to enter. The product may look simple compared with a central processor or graphics chip, but manufacturing it profitably requires extraordinary precision. A memory producer must create billions of microscopic cells that store data reliably. Those cells must work at high speed, consume little power, survive repeated use, and maintain consistency across huge production volumes. That increases cost and makes it difficult to compete with established companies that have spent decades refining their processes. Its early products were aimed mainly at China's domestic market, and many international customers had little reason to take the company seriously. A company does not need to be the global technology leader to become strategically important. It only needs to offer acceptable products, meaningful capacity, and a willingness to sign contracts when other suppliers are constrained. The company reportedly held about 7.7% of the global DRAM market in 2025, making it the 4th largest producer. In a tight market, even a single-digit share can influence prices and customer negotiations. It currently operates major 12-inch DRAM fabrication plants in Hefei and Beijing, with combined output estimated at around 300,000 wafers per month. New facilities and additional expansion could eventually double that figure to approximately 600,000 wafers per month. The company is also developing operations in Shanghai, including DRAM production and high-bandwidth memory packaging. But Tencent's reported commitment gives CXMT something extremely valuable: demand visibility. It can help a manufacturer plan equipment purchases, staffing, material supply, and future process development. CXMT received approval in May for an initial public offering on Shanghai's Star Market. The company reportedly aims to raise 29.5 billion yuan. Investors want proof that growth is not based only on policy support or optimistic forecasts, and they want evidence that the company's products are important enough for large buyers to sign long-term commitments. Major Chinese technology companies are trying to reduce their exposure to foreign supply restrictions. Tencent, Alibaba, ByteDance, Lenovo, Xiaomi, and other firms all depend on semiconductors produced or controlled by companies outside mainland China. Export controls have already restricted China's access to advanced AI accelerators and semiconductor manufacturing equipment.
Undercut incumbent suppliers by up to 30% depending on the contract. Now, Apple, it's been here before. 4 years ago, the company explored using YMTC chips in China-sold iPhones, then retreated under pressure from Washington. But the shortage is more severe now, and Apple has a lot less leverage with its traditional suppliers. That's why more tech companies are looking for alternatives. HP and Lenovo are both reportedly pursuing Chinese memory as a way to diversify supply. But this is not a quick swap.
A cloud company cannot expand infrastructure if it cannot secure enough components. So Chinese technology firms have strong reasons to support a domestic supplier, even if that supplier remains behind the global leaders. This does not mean they will accept any product at any price. Large data center operators care about performance, failure rates, power consumption, compatibility, and total operating cost. Server memory must run continuously under heavy workloads. A defective module can create outages, corrupted data, or expensive maintenance. Tencent therefore has to believe that CXMT can meet a meaningful standard. That is why the reported agreement is more important than a symbolic government order. Tencent is not buying memory for a demonstration project. It needs chips for real servers supporting real customers. The contract could therefore become one of the strongest tests of CXMT's manufacturing discipline. Success would generate more than revenue. It would create operational data. Every shipment provides information about defect rates, system compatibility, thermal behavior, and long-term reliability. That feedback can help CXMT improve future products. Higher production volumes also allow engineers to identify recurring process problems and improve yield. Semiconductor manufacturing becomes more competitive through repetition. The more wafers a company processes, the more opportunities it has to learn. This is one reason large customers can accelerate a supplier's development. Tencent may be buying memory because it needs supply today, but the partnership could help create a stronger competitor tomorrow. That is where Samsung, SK Hynix, and Micron should pay attention. CXMT is not about to replace them. The established leaders remain ahead in manufacturing technology, scale, customer trust, and advanced products. They also dominate high-bandwidth memory, which currently delivers some of the strongest margins in the industry. CXMT still faces serious challenges. One reported problem is low yield on next-generation DDR5 products. That matters because DDR5 is increasingly important for modern servers and personal computers. A company can announce impressive specifications, but customers ultimately care about how many reliable chips can be produced at acceptable cost. If yield remains weak, expansion alone will not solve the problem. More factory capacity can simply produce more expensive defective wafers. CXMT must therefore improve technology while expanding volume. That is difficult, but the Tencent deal provides time and money. And if CXMT can use this period of high prices to improve yield, the competitive landscape could change. The memory industry is cyclical. Shortages produce high prices and heavy investment. High prices encourage companies to build more capacity. Eventually, supply catches up. Prices fall. Weak producers then struggle because memory becomes a commodity again. CXMT's challenge is to use the current upcycle to become efficient before the market turns. The company's recent financial performance shows how powerful the upcycle has been. Its first quarter revenue reportedly reached 50.8 billion yuan, an increase of about 700% from a year earlier. It also recorded a net profit of 25 billion yuan after reporting a loss in the previous year. Those numbers are extraordinary, but they should be interpreted carefully. A booming memory market can make almost every producer look stronger. The real test comes when prices normalize. Can CXMT still compete when buyers have more options? Can it maintain margins? Can it continue investing? And can it keep customers when Samsung, SK hynix, and Micron have available capacity again? Tencent's long-term agreement may protect CXMT from some of that uncertainty. Now we come to Apple. Reports say Apple has been lobbying the United States government for clearance to purchase memory chips from CXMT. The request does not mean a contract has been signed. It does not mean CXMT memory is already inside MacBooks or iPads. And it does not mean Apple plans to abandon its current suppliers. Apple still depends on Samsung, SK hynix, and Micron. But the company recently raised prices on several Mac and iPad models after memory and storage costs rose sharply.
Qualifying a new supplier can take months to as long as 2 years with device testing, reliability checks, factory audits, and technical sharing. And it's especially complicated with YMTC. It's been on the Commerce Entity List since 2022, meaning that U.S. companies need approval to share their blueprints and other proprietary details with them.
That makes another supplier extremely attractive. Apple does not need CXMT to replace the market leaders. It only needs CXMT to provide qualified products at meaningful volume. Even a limited supply agreement could strengthen Apple's negotiating position. It could reduce dependence on 3 dominant producers. And it could help Apple avoid even larger price increases if the shortage continues. The Tencent agreement may make CXMT easier for Apple to evaluate. A multi-billion-dollar server contract gives the company commercial credibility. It shows that another major technology buyer is willing to make a long-term commitment. But Apple's standards are different. For laptops and tablets, power consumption is critical. Memory affects battery life, heat, system stability, and product reliability. Apple also demands consistency across millions of devices. A supplier must deliver the same quality from one production batch to the next. It must support product launches, regional demand changes, and strict delivery schedules. So Tencent's approval would not automatically lead to Apple qualification. Server DRAM and low-power mobile memory serve different needs. Apple would still need extensive testing, audits, traceability, and supply guarantees. The political barrier may be even harder. CXMT is included on a Pentagon list of companies alleged to have links to China's military. That listing does not create a simple universal ban on every commercial transaction, but it creates serious political and reputational risk. American lawmakers may argue that allowing Apple to purchase from CXMT would strengthen a strategic Chinese semiconductor producer. They may also warn that Apple could become dependent on a supplier that Washington later restricts. Apple wants confidence before spending months qualifying products and redesigning logistics. A deal that is legal today could become impossible tomorrow. That uncertainty explains why Apple reportedly approached the government before moving forward. The White House has not publicly approved the request. Apple has not announced a supply agreement, and CXMT has not confirmed that it will supply Apple. So the title, Apple May Be Next, must remain a possibility, not a conclusion. Still, the Tencent deal changes the context. Before this agreement, CXMT could be described as a rising Chinese memory producer, seeking credibility. After a $3 billion commitment, it begins to look like a strategic supplier with major customers, rapid growth, expanding capacity, and access to capital. That does not guarantee Apple will follow, but it makes the possibility more believable. My take is that the most important part of this story is not the dollar amount. It is the speed at which CXMT's position is changing. A global shortage has turned capacity into leverage. AI demand has pushed memory from a commodity component into a strategic resource. Chinese technology companies are locking in domestic supply, and Apple is reportedly considering a supplier that would have seemed politically unrealistic only a short time ago. The old memory market was built around 3 dominant companies and predictable customer relationships. The new market is becoming more fragmented, more political, and more expensive. Tencent wants supply security. CXMT wants scale and validation. China wants semiconductor independence. Apple wants lower costs and another negotiating option. Washington wants to limit the growth of strategic Chinese technology. Those goals are now colliding inside one of the most basic components in modern computing. A small memory chip has become part of a much larger contest over AI, industrial power, and national security. The Tencent contract may prove evidence of long-term American supply chain security. Let me know your view in the comments. And subscribe to Eastern Engine for more grounded coverage of the chips, factories, and engineering decisions reshaping the global economy. Because CXMT did not just win a $3 billion order. It may have won the credibility needed to compete for something even bigger. Here's a sentence that should not make sense. China just claims to have built one of the fastest supercomputers on Earth, a machine capable of 2 quintillion calculations every second. And it did it without using a single one of the chips the entire world believes you absolutely need to get there. No NVIDIA. No AMD graphics chips. No accelerators of any kind. Not one GPU anywhere inside the machine. If you follow technology even casually, you know how strange that is. The global AI boom. The race for the most powerful computers on the planet. The reason a company called NVIDIA became one of the most valuable businesses in human history. All of it runs on GPUs. Graphics processing units are the beating heart of modern high-performance computing. The idea of building a world-class supercomputer without them is a little like claiming you built the world's fastest race car without an engine. And yet, that's exactly what China says it has done. The machine is called Lineshine. And whether you walk away from this convinced it's a genuine breakthrough or a clever bit of national theater, the story behind why China built it this way is one of the most revealing in modern technology. Because this isn't really a story about a computer. It's a story about what happens when you take someone's favorite tool away, and they decide to win without it anyway. By the end of this, you'll understand exactly what Lineshine is, why the GPU-free design is the whole point, why some experts are deeply skeptical, and what it really tells us about where this race is heading. Let's get into it. Let's start simple, because the scale here is almost impossible to picture. A supercomputer isn't one giant computer. It's thousands of computers, wired together so tightly that they behave like a single colossal brain, all working on one problem at once. We measure their power in flops, floating point operations per second, basically how many calculations the machine can do in a single tick of the clock. The most powerful machines today operate at the exascale. 1 exaflop is a billion calculations per second. To put that in human terms, if every person on Earth did 1 calculation per second, by hand it would take roughly 4 years to do what one of these machines does in a single second. Lineshine is targeting 2 exaflops. The numbers stop meaning anything at this point. They're just big. These machines aren't built to play games or browse the web. They're the engines behind the hardest problems humanity works on, simulating nuclear reactions, modeling the climate decades into the future, designing new medicines molecule by molecule, training the largest AI systems. Supercomputing leadership isn't a vanity trophy. It's a genuine marker of which nations can tackle the biggest scientific and strategic challenges. Whoever owns the fastest machines has a real edge in science, defense, and AI. And for the last few years, the undisputed champion has been an American machine, which is exactly the record China is now trying to break, with a design philosophy nobody else would have chosen. To understand why Lineshine is so unusual, you need to meet the machine it's trying to beat. The current world record holder is called El Capitan, housed at the Lawrence Livermore National Laboratory in California. It's an extraordinary piece of engineering, and it has a measured, proven performance of about 1.8 exaflops. That word, proven, is going to matter a lot in a few minutes, so hold on to it. But here's the detail that frames this entire story. El Capitan reaches that performance using roughly 44,500 specialized chips that fuse CPU and GPU technology together on a single package. GPUs are at the core of it, and that's not unusual, it's the rule. Nearly every champion-tier supercomputer in the world leans heavily on GPU accelerators, because GPUs have a magical property. They can perform thousands of similar calculations simultaneously, in parallel, which is exactly what these massive scientific simulations and AI workloads demand. This is why NVIDIA became a titan. The entire modern computing world organized itself around the idea that for serious horsepower, you need GPUs. They are, supposedly, non-negotiable. So when China announced a machine targeting more than El Capitan's proven score, 2 exaflops, the obvious assumption was that it would use even more GPUs. Instead, China said something that made engineers around the world do a double take. No GPUs, none. Just central processors, CPUs, the same general-purpose chips that run your laptop, only 47,000 of them. And the reason for that bizarre-sounding choice is the actual heart of this story. Here's the question every expert asked immediately. Why would anyone deliberately handicap themselves like this? CPUs and GPUs are good at different things. Think of it this way. A GPU is like an army of 10,000 school children who can each only do simple arithmetic, but all at once. Perfect for crunching enormous batches of similar, simple calculations. A CPU is more like a small team of brilliant professors who can each handle complex, varied reasoning, but there are far fewer of them. For the kind of massively parallel number crunching that supercomputers do, the army of school children, the GPU approach, is usually far more efficient. That's why everyone uses it. So choosing CPUs only, on purpose, sounds like choosing the slower path. Why do it? One word: restrictions. China has been cut off from the most advanced GPUs on Earth. The very NVIDIA chips that power machines like El Capitan are precisely the ones China cannot freely buy, because of export controls. So China faced a choice. It could keep trying to get its hands on banned foreign GPUs and stay perpetually one step behind, or it could ask a heretical question: do we actually need them? Can we reach the summit using chips we can build entirely ourselves? Lineshine is the answer to that question. The chief designer, Lu Yutong of the National Supercomputing Center in Shenzhen, made the goal explicit. The machine is meant to be, in his words, fully independently controllable. Every layer, the processors, the storage, the networking, the software, domestic. No foreign components anywhere in the stack. The pilot phase reportedly runs on 100 Huawei Kunpeng servers built on homegrown processors, and the full system is designed to scale to those 47,000 CPUs across 92 cabinets, knit together by a 1 million port interconnect, moving 10 terabytes of data every second. In other words, the GPU-free design isn't a weakness China is hiding. It's the entire point. The constraint became the strategy. If you can't buy the engine everyone else uses, you prove you can win the race with an engine you built yourself. And just like the chip stories before it, the wall meant to hold China back became the exact thing that forced a different path. Now, you can't simply bolt 47,000 ordinary CPUs together and expect a world record. If it were that easy, everyone would do it. So how do you make a CPU-only machine competitive with the GPU giants? This is where the engineering gets genuinely interesting, and where China appears to have done real work. Everything you do online is being watched. Your provider, advertisers, even governments. NordVPN encrypts your connection, hides your location, and unlocks the open internet from anywhere. Grab the deal, link in the description. First, the CPUs aren't ordinary. They reportedly use on-chip high-bandwidth memory, placing fast memory directly onto the processor itself, which attacks one of the biggest bottlenecks in computing: the time wasted shuttling data back and forth between the chip and distant memory. Sound familiar? It's the same reduce the distance, reduce the delay philosophy at the heart of China's other recent chip moves. Second, the system uses something described as 3D floating orthogonal computing, an architecture designed to keep tens of thousands of processors talking to each other efficiently, so the machine scales without choking on its own internal communication. The bigger a supercomputer gets, the harder it is to stop the processors from spending all their time just waiting for each other. Solving that coordination problem at this scale is a serious achievement in itself. And third, full liquid cooling. 47,000 processors generate staggering amounts of heat, and air cooling simply can't cope. Liquid carries that heat away and lets the chips run hard without melting. Put it together, and you have a coherent, thoughtful design. This is not a random pile of laptop chips. It's a deliberate attempt to prove that a different architecture, one China can build end-to-end with no foreign parts, can reach the very top tier. Which raises the obvious question, did it actually work? And here I have to be completely straight with you, because here's where a hype video would stop, and where an honest one keeps going. There are real, serious reasons to be cautious about the headline claim, and you deserve to hear them. First, and most important, that 2 exaflop figure is a target, not a proven result. Remember the word I told you to hold on to. El Capitan's 1.8 exaflops is a measured score, verified by a standard industry benchmark called LinPack. Lineshine has no such verified benchmark for the simple reason that the full machine reportedly hasn't even been completed yet. Comparing a finished, tested machine to a not yet built target is not a fair fight. It's comparing a race already run to a race someone says they'll win. Second, the comparison gets even murkier when you look at theoretical peaks. While Lineshine targets 2 exaflops, El Capitan's theoretical peak is actually higher, around 2.79 exaflops. So the claim of building the world's fastest is, at minimum, heavily disputed by the numbers themselves. Several technology outlets have openly called the framing dubious. Third, there are questions about the chips. China's domestic high-performance processor options are still relatively limited, and whether 47,000 of them can be produced, deployed, and coordinated to actually hit the target, possibly years from now, is far from certain. So let me give you the honest framing, the one you won't get from the headline. China has not definitively built the fastest supercomputer in the world today. That specific claim doesn't hold up to scrutiny. What China has done is something more nuanced, but in my view, more interesting. It has demonstrated a credible, fully domestic, GPU-free path toward the absolute top tier of computing, a path nobody else is seriously pursuing, built entirely from components it controls. The "We beat the record" headline is shaky. The "We found a completely different road to the summit" story is real. So if the world record claim is questionable, why does this matter at all? Because the record was never the important part. Step back and look at the pattern, because by now it should feel familiar. Glass chips, diamond cooling, a new law to replace Moore's law, and now a supercomputer that refuses to use the one component everyone insisted was essential. Every single one of these stories has the same shape, a restriction designed to stop China from getting something, and a response that sidesteps the restriction entirely by building a different path. That's the real headline here, and it's bigger than any one machine. The export controls on advanced GPUs were meant to cap how powerful China's computers could become. Lineshine is a statement that says, we will reach the top tier without your chips at all. Whether this specific machine hits 2 exaflops next year or in 5 years almost doesn't matter. The strategic message is that the chokehold everyone assumed was decisive might simply be routed around. And there's a deeper point about resilience. A computing stack built entirely from domestic parts, chips, storage, networking, software, cannot be switched off by anyone else's export policy. It's slower to build and harder in the short term. But once it exists, it's immune to the very pressure that was supposed to contain it. That's a profound long-term shift, and it's happening across the entire Chinese technology landscape at once. The GPU was supposed to be the leash. Lineshine is China saying it would rather build its own animal than wear anyone's collar. Here's my honest opinion. I think both extreme reactions to this story are wrong. The people declaring China just crushed America and built the fastest supercomputer ever are getting way ahead of the evidence. The headline claim is genuinely shaky, the benchmark doesn't exist yet, and the machine may not even be finished. But the people waving it away as pure propaganda ignore it, are making the opposite mistake, and it's the more dangerous one. Because they're focused on the disputed record and completely missing the real story. China is methodically proving it can reach the frontier of computing without a single component the West controls. That's the thing that should make people pay attention. Not the number, the independence. A restriction was placed to create dependence and leverage, and the response was to engineer that leverage out of existence entirely. Even if Lineshine itself underdelivers, the approach, fully domestic, GPU-free, immune to export controls, is the template. And templates outlive any single machine. I keep coming back to the same realization across all these stories. We're watching, in real time, what happens when you corner a determined, well-funded technological power. You don't stop it, you just change the direction it grows in. And sometimes it grows in a direction you can't reach at all. So here's my question for you, and I want your real answer. Were the GPU export restrictions a smart way to slow China down? Or did they just force China to build an entire independent computing stack that no future restriction can ever touch again? In other words, did the leash work, or did it teach the animal to live without one? Drop your honest take in the comments. I read every single one, and this is exactly the kind of debate I love seeing down there. If you want to keep following this, the breakthroughs, the workarounds, the moves the rest of the world underestimates until it's too late, subscribe to Eastern Engine and hit the notification bell. Chips, supercomputers, energy, the entire foundation of modern technology is being rebuilt right now, and we break it all down before the mainstream catches on. Thanks for watching. I'll see you in the next one.
Qualcomm also set to acquire AI startup Modular as it makes its AI software push.
Every AI accelerator has the same hidden weakness: memory. The processor may contain thousands of computing units, but those units are useless if model data cannot reach them fast enough. That is why NVIDIA, AMD, and other AI chip companies rely on high bandwidth memory, or HBM. HBM stacks multiple memory dies beside the processor and connects them through extremely wide interfaces. It delivers enormous bandwidth, but it is expensive, difficult to package, and increasingly scarce. Qualcomm now says it has another answer. The company is preparing China-compliant versions of its new Dragonfly data center products, including AI accelerators, server CPUs, custom chips, and connectivity hardware. The first major accelerator in that roadmap is the AI 250.
We announced a complete portfolio of technologies that are going to be where the data center is going. An agentic AI CPU, an accelerator with a new memory architecture. Memory is very hot these days, and we don't require HBM. And we talk about connectivity and custom ASIC, and we put a projection about Qualcomm is going to be a player in the data center.
And instead of relying on conventional HBM, Qualcomm is introducing something it calls High Bandwidth Compute, or HBC. The basic idea sounds almost backwards. Use lower-cost memory related to the LPDDR technology found in phones and laptops, then place computing much closer to that memory, so the system does not need to move every piece of data all the way back to the main processor. Qualcomm claims this architecture can deliver dramatically higher effective memory bandwidth while using less power. But the AI 250 is not shipping yet. The China-specific versions have not been fully detailed, and the most dramatic performance numbers come from Qualcomm's own projections, not independent testing. So is this truly an HBM replacement, or is Qualcomm finding a clever way to enter China's AI market without following NVIDIA's architecture? Why AI chips are becoming memory machines? Artificial intelligence is often described as a computing problem. For training, that is largely true. Large models require enormous numbers of mathematical operations, but inference creates a different challenge. Inference is what happens after a model has been trained. A user asks a question, and the system generates an answer token by token. During this process, the accelerator repeatedly reads model weights from memory. The mathematics for each step may be relatively simple. The difficult part is moving enough data quickly enough. This creates what engineers call the memory wall. The processor can calculate faster than memory can feed it. Adding more computing units does not solve the problem if those units spend time waiting. HBM became the industry's answer because it offers far more bandwidth than ordinary server memory. But HBM comes with trade-offs. It requires advanced packaging. The memory stacks must sit close to the accelerator. The package becomes larger, more complicated, and more expensive. Capacity is also limited compared with ordinary DRAM. As models grow, data centers need both more bandwidth and more memory capacity. Qualcomm believes the answer is not simply a larger HBM stack. It wants to change where the computation happens. What high-bandwidth compute actually does. Qualcomm's HBC architecture fuses memory and compute dies inside the same package. Instead of sending every operation through the full path from the memory array to the central accelerator, certain calculations happen beside the memory. This is called near-memory computing. Imagine a warehouse containing millions of boxes. In a conventional system, every box must be carried to one central worker, opened, inspected, and returned. HBC places smaller workers inside the warehouse aisles. They process simple tasks near the stored data and send only the useful results to the main processor. That reduces data movement. And data movement is one of the largest energy costs in modern computing. The memory itself is not magically as fast as HBM. The advantage comes from avoiding some of the movement that makes lower bandwidth memory appear slow. Qualcomm therefore uses the phrase effective memory bandwidth. It measures how much useful data the architecture can process when computation occurs close to memory. For the AI 250 with first-generation HBC, Qualcomm claims 18 times the effective memory bandwidth of its earlier AI200 platform. At rack scale, the company lists 7.4 petabytes per second of effective bandwidth and 43 terabytes of memory capacity. That is a huge claim, but it must be interpreted carefully. Effective bandwidth is not identical to the raw physical bandwidth printed on a conventional memory specification. The number depends on the workloads, how much computation can be performed near memory, and how Qualcomm measures avoided data movement. Independent tests will be necessary. Why phone memory is not as ridiculous as it sounds. LPDR was developed for mobile devices. The letters stand for low-power double data rate memory. It is designed to provide useful performance without draining a phone battery. Compared with HBM, one LPDR chip offers much less bandwidth. But LPDR is mature, widely manufactured, and available in large capacities. Qualcomm already understands this technology extremely well because it has spent decades designing smartphone platforms. Its earlier AI200 rack is listed with 43 terabytes of LPDDR5X memory. HPC extends the strategy by placing additional processing closer to the memory. This does not mean Qualcomm is taking ordinary phone memory modules and plugging them into a data center accelerator. The packaging, interfaces, and compute dies are designed for a specialized server product. Phone memory is a useful comparison because it explains the memory family, not the final physical product. The potential economic advantage is obvious. HBM is one of the most expensive and supply-constrained components in AI hardware. A system that uses more conventional low-power DRAM could offer greater capacity at lower cost. That matters for inference, where large models may need to remain loaded in memory for long periods. The 133 terabyte per second claim. Some coverage describes the AI250 as reaching roughly 133 terabytes per second per card. That figure is derived from Qualcomm's effective bandwidth roadmap rather than a conventional raw memory bus measurement. The safer way to understand the claim is this. Qualcomm says near-memory processing allows one card to behave as though far more data were moving through the central accelerator than the physical memory interface alone would permit. The company also estimates 6 times higher memory bandwidth per watt than HBM-based systems, and it claims up to 8 times better token performance per watt than selected GPU-based systems. Again, these are Qualcomm estimates. The company has not yet placed production AI250 hardware into the hands of independent reviewers. The comparisons also depend on selected models and inference conditions. A system can look excellent during token generation, but perform differently during model loading, prompt processing, or workloads that require more arithmetic. Qualcomm is optimizing specifically for inference. It is not claiming one architecture will dominate every AI task. Why China matters. Qualcomm's chief executive has said the company intends to offer versions of all 4 Dragonfly product categories in China while remaining within US export rules. That includes accelerators, CPUs, custom silicon, and connectivity products. China is already extremely important to Qualcomm's smartphone business. The company has long relationships with Chinese device makers and automotive companies. It now wants to extend those relationships into data centers. But selling advanced AI hardware in China has become extremely complicated. US export controls limit the performance and connectivity of chips that American companies can ship there. Manufacturers may need to create reduced performance versions specifically for the Chinese market. Qualcomm has not disclosed the final specifications of its China-compliant AI250. That means the full global product and the Chinese version may not deliver identical performance. The HPC concept may remain the same, but accelerator throughput, interconnect capability, or other features could be adjusted. The title HBM-free AI chips for China describes the planned architecture and market direction. It does not mean Chinese customers can order the finished product today. Qualcomm is entering a hostile market. Export compliance is only one obstacle. China is increasingly supporting domestic AI chip suppliers. Huawei's Ascend processors and Cambricon's accelerators are becoming more important inside Chinese data centers. Some state-supported projects have been pushed toward locally made hardware. That creates a difficult situation for Qualcomm. It is an American supplier entering a market where American chips face restrictions from Washington and political pressure from Beijing. NVIDIA already learned how difficult this can become. It created export-compliant products for China, only to face changing rules and weakening access to major customers. Qualcomm believes it has advantages NVIDIA did not have. Its mobile business created deep commercial relationships across China. Its architecture may also avoid HBM, a component that is expensive and tightly connected to the most advanced AI accelerators. But relationships do not guarantee adoption. Chinese cloud companies must decide whether Qualcomm's software, performance, and long-term roadmap justify using another foreign platform. Microsoft and Meta give the roadmap credibility. Qualcomm is not entering the data center market with China as its only target. Microsoft has agreed to use Qualcomm's HPC products for AI workloads. Meta plans to use the Dragonfly C1000 server CPU in future systems. Qualcomm also says it has custom chip agreements with 2 unnamed hyperscale customers. These commitments matter because large cloud companies do not select hardware based only on a presentation slide. They evaluate software, reliability, supply, power consumption, and long-term support. Microsoft's involvement suggests that HPC is being taken seriously before commercial deployment, but it still does not prove Qualcomm's performance claims. Large customers often test multiple architectures. The real verdict will come when production systems run large models under real data center conditions. The software problem. NVIDIA's greatest advantage is not only its hardware, it is CUDA. Developers have spent years building tools, libraries, and models around NVIDIA's software platform. Qualcomm must persuade customers that existing AI workloads can move to Dragonfly without enormous engineering effort. The company offers its AI inference suite and Cloud AI SDK. It is also expanding its broader software capabilities. But hardware efficiency means little if customers struggle to deploy their models. Near-memory computing adds another challenge. The system must decide which operations should happen close to memory and which belong on the central accelerator. Good software can hide this complexity. Poor software can erase the architectural advantage. Qualcomm must therefore sell an entire platform, not just a clever memory package. The honest catch. There are 4 major reasons to remain cautious. First, the AI 250 is a future product. Second, Qualcomm's bandwidth and efficiency numbers are internal estimates. Third, the exact China compliance specifications remain unknown. Fourth, HPC is optimized for workloads with low arithmetic intensity, where moving data is more difficult than performing the calculation. Some AI tasks fit that description extremely well. Others may still favor conventional GPUs with enormous raw computing power and mature software. There is also a terminology problem. HBM-free does not mean memory is no longer important. It means Qualcomm is replacing the conventional HBM-centered design with lower power memory and near-memory processing. The entire product is still built around solving the memory bottleneck. My take is that Qualcomm's most interesting decision is not using cheaper memory. It is refusing to accept that every byte must travel to one central processor. For years, the AI industry increased performance by adding larger accelerators and faster HBM. Qualcomm is asking whether some of that work can move into the memory package instead. If HPC works as promised, it could make large model inference cheaper, more energy efficient, and less dependent on scarce HBM. That could be especially useful in China, where access to the most advanced accelerators is restricted, and data centers need alternative architectures. But Qualcomm is entering late. NVIDIA has the software ecosystem. Huawei has domestic momentum. Other cloud companies are building their own custom chips. And the AI 250 still must prove itself outside company presentations. So what do you think? Can near-memory computing replace conventional HBM for large-scale AI inference? Or will Qualcomm discover that raw GPU performance and software support still matter more than cheaper memory? Let me know your view in the comments. And subscribe to Eastern Engine for more grounded coverage of the chips, materials, and engineering ideas reshaping computing. Because Qualcomm is not trying to build another NVIDIA-style accelerator. It is betting that the next AI breakthrough will happen inside the memory itself.
China made history this year when it became the first nation to land a spacecraft on the far side of the moon, the Chang'e 4.
Over the past decade and a half, one country has quietly sent more spacecraft to the moon than any other nation on the planet. Not a single flagship mission. Not a one-off publicity launch. We are talking about a sustained campaign. Orbiters, landers, rovers, a robot designed to leap into the darkest craters imaginable, and a spacecraft that retrieved rock samples from a region no human has ever set foot on and carried them all the way back to Earth. And that is only the surface of it. Here's what makes this story genuinely gripping. China is not pursuing this because it wants to win a sprint to plant a flag. It is pursuing this because the moon may be holding something that could fundamentally reshape how humanity explores the entire solar system. Something frozen, something ancient, something that has been sitting in permanent darkness for billions of years, waiting to be discovered. By the end of this video, you are going to understand exactly why China keeps returning to the moon, what they are actually searching for, and why whoever cracks this problem first could end up shaping the future of space travel for generations. Let's get into it. Most nations that set their sights on the moon try to land on it as quickly as possible. China took a deliberately different path. Back in the early 2000s, Chinese space planners sat down and designed a roadmap intended to unfold over decades. This was not because they lacked the capability to move faster. It was a strategic choice. Every mission was engineered to teach them something specific they would need for the next one. Nothing was wasted. Nothing was rushed for the sake of headlines. The plan rested on 4 phases. First, orbit the moon and study it in detail. Second, land on it. Third, retrieve samples and bring them home. Each phase had to succeed completely before the next one began. It is the same logic you would use building a skyscraper. You do not install the glass before the steel frame is up, and you certainly do not start on the roof before the foundation is poured. The first mission launched in 2007, Chang'e 1, named after a moon goddess from Chinese mythology. The spacecraft orbited the moon for over a year and produced some of the most detailed lunar surface maps available at the time. There was no dramatic landing, no human drama, just clean, precise data that scientists and engineers could analyze for years and slowly convert into a workable plan. 3 years later, Chang'e 1-2 refined those maps even further. Researchers could now zoom into craters, ridges, and mountain ranges to determine exactly where a spacecraft could safely touch down without tipping over or sinking into loose soil. These missions never grabbed front-page attention the way a crude rocket launch would, but behind the scenes, they were building the blueprint that would guide everything to follow. And what followed genuinely changed what scientists thought they understood about the moon. In 2013, China made its first major leap. Chang'e 3 became the first spacecraft to perform a soft landing on the moon since the 1970s. Consider that for a moment. Nearly 4 decades had passed without a single controlled landing on the lunar surface. Then, quietly and precisely, China did it. The lander carried a small rover named U2, meaning Jade Rabbit. It rolled off onto the gray, dusty terrain and immediately got to work. Within days, U2 found something unexpected in the rocks. For decades, virtually everything science knew about moon rocks came from the Apollo missions. A small group of astronauts had walked the lunar surface and returned with samples, and researchers had been studying those same specimens ever since. An entire understanding of the moon's composition had been built on that foundation. Textbooks were written, models were constructed, a complete scientific narrative was assembled. That narrative, it turned out, was incomplete. U2's instruments analyzed the soil and surrounding rocks and identified a type of volcanic rock that matched nothing in the Apollo collection. The chemical signature was different. The mineral arrangement was different. It was like discovering a completely unfamiliar recipe in a cookbook you assumed you had read cover to cover. Not a variation on a known dish, but something entirely new. The implications were significant. The moon is not a single uniform body. It is geologically complex, with regions that formed through different processes across different eras. There had been volcanic activity in areas no previous mission had ever examined. The regions Apollo had explored were just a small cluster of points on a vast map stretching across millions of square kilometers. The moon people thought they knew was only a fragment of the real picture, and the rest had never been studied up close at all, which raised an obvious question. If the areas already explored were still producing surprises, what might be hiding in the places no one had ever looked? The moon always shows Earth the same face. This is not coincidence. The moon rotates at exactly the rate that keeps one side perpetually facing us, while the far side points constantly away into deep space. You could observe the moon every night for your entire life and never glimpse the other side, not even with the most powerful telescope ever built. Landing on the far side was long considered nearly impossible. The instant a spacecraft touches down there, it loses all direct contact with Earth. No line of sight, no way to send commands, no way to receive data, no way to know if something has gone wrong. It would be like trying to communicate with someone sealed inside a soundproof room with no signal and no door to knock on. China solved this with remarkable elegance. Before launching the lander, they positioned a relay satellite in a carefully selected orbit beyond the moon, where it could maintain a view of both Earth and the lunar far side simultaneously. Signals could then bounce between the lander and Earth through this satellite, like a reliable messenger relaying messages between two parties who cannot see one another. Simple in concept, extraordinarily difficult to execute. In 2019, Chang'e 4 touched down inside the South Pole Aitken Basin. one of the largest impact craters in the entire solar system. It spans more than 2,500 kilometers across, roughly the size of Western Europe. Scientists believe it is so deep and so ancient that the original impact may have punched through the moon's outer crust, exposing material from deep within the lunar interior that had been buried since the moon first formed. Then in 2024, Chang'e 6 accomplished something even more astonishing. It did not merely land on the far side. It landed, collected roughly 2 kilograms of ancient rock and soil, sealed the material inside a container, launched a small rocket off the lunar surface into orbit, docked with a waiting spacecraft, transferred the cargo, and returned it all the way to Earth. Every single step had to function flawlessly, and none of them had ever been attempted from the far side before. The return samples were around 2.8 billion years old, and showed clear evidence of volcanic activity occurring far later than anyone had predicted. The moon's geological story did not go quiet as early as scientists had assumed. It ran longer and stranger than the textbooks ever captured. And yet, as extraordinary as all of this was, it still was not the main objective. The real prize sits at a completely different part of the moon. Step outside on a clear night and look at the moon. Now picture its very bottom, the South Pole. On Earth, the poles are frozen and ice-covered. On the moon, the South Pole is something far stranger. Because the moon barely tilts on its axis, sunlight strikes the South Pole at an extremely low angle, skimming across the surface almost sideways. Some craters near the pole are so deep that their walls block every ray of sunlight entirely. Not for a day, not for a season, but for over 1 billion years. No light has reached their floors since long before any life existed on Earth. Inside these craters, temperatures plunge to around -200 degrees Celsius, colder than the surface of Pluto, and among the coldest natural environments anywhere in the solar system. But that extreme cold is exactly what makes these craters so exciting. Scientists believe those permanently shadowed crater floors may be storing frozen water ice. Over billions of years, comets and asteroids carrying water repeatedly struck the moon. Most of that water evaporated or drifted off into space. But in these permanently dark craters, the water had nowhere to go. It simply stayed, frozen solid, perfectly preserved, like food left in the back of a freezer no one ever opens. Now consider what water actually represents in space. Water is made of oxygen and hydrogen. Oxygen is what astronauts breathe. Hydrogen is one of the most powerful rocket fuels ever developed. If you can extract that ice, split it into its components, and convert it into breathable air and usable fuel, the moon stops being just a destination. It becomes a supply depot, a fueling hub sitting right next to Earth, capable of sending spacecraft deeper into the solar system without hauling all that heavy, expensive fuel up from Earth's surface. Launching anything off Earth costs an enormous amount because our planet's gravity is so strong. The moon's gravity is only about 1/6 of Earth's, which means launching fuel from the moon would cost a fraction of what it costs from home. Future missions to Mars, to the moons of Jupiter, or beyond could stop at the moon, refuel, and continue onward. The moon could become humanity's first off-world supply station, and whoever builds it first gains a substantial head start on everything that comes after. This is why the South Pole matters so much, and why China keeps returning, mission after mission, year after year. To actually find and confirm that water ice, you cannot simply orbit overhead and make educated guesses. You have to enter those dark craters directly. But conventional rovers run on solar power, and no sunlight means no energy. Worse, wheels struggle on the sharp, jagged, unpredictable terrain inside a crater that has sat undisturbed for 1 billion years. China's solution is Chang'e 7, currently planned for launch in 2026. It is the most technically ambitious lunar mission the country has ever designed, and it includes something never used before in lunar exploration: a small robot capable of jumping. Rather than slowly rolling across the surface, this hopping probe can leap directly into permanently shadowed craters. It carries instruments designed to detect water molecules, identify hydrogen signatures, and analyze frozen deposits embedded in the ground. It enters, performs its work, and exits places that would disable a standard rover within minutes. Picture sending a nimble frog into a dark cave instead of trying to drive a car down into it. The full Chang'e 7 mission also includes an orbiter mapping the South Pole region from above and relaying signals, a lander touching down on stable terrain near the pole, and a rover studying soil composition and scouting targets for the hopping probe. All 4 components operate as a coordinated team, continuously sharing information with each other and with scientists on Earth. If Chang'e 7 returns with clear confirmation of substantial water ice deposits in those ancient craters, It would rank among the most important discoveries in the history of space exploration. Not only scientifically thrilling, but practically transformative, because it would demonstrate that much of what humanity needs to begin living and working beyond Earth is already there, waiting. Finding a resource and actually using it are two very different challenges. You cannot simply scoop up ice and declare a base established. You need technology that can survive with no oxygen, extreme temperature swings, constant radiation, and fine abrasive dust that works its way into every gap in every machine. You need systems that can operate for months or years without human intervention. Essentially, you need to learn how to build on the moon using the moon itself. That is the central goal of Chang'e 8, planned for around 2029. This mission focuses on what engineers call in situ resource utilization, using what is already present rather than shipping everything from Earth across hundreds of thousands of kilometers of empty space. One set of experiments will attempt to heat and compress lunar soil into solid building blocks. Think of it as baking bricks, except instead of clay from a riverbank, you are using the gray dust that blankets the lunar surface. Those bricks could form landing pads. The process can break those bonds and release it. Some designs under consideration involve robotic 3D printers that use lunar soil as raw material to construct structures layer by layer. The same principle as a home 3D printer, but on a far larger and more serious scale. Autonomous machines could print walls, floors, and protective domes long before any human crew arrives. If these technologies prove themselves in the actual lunar environment, rather than just a laboratory, the entire economics of space construction shifts. The moon would effectively help build itself. Everything described so far feeds into one final objective: a permanent research station at the lunar South Pole. China calls it the International Lunar Research Station, or ILRS, and it ranks among the most ambitious space infrastructure projects any nation has seriously proposed. Construction is set to begin in the early 2036. Robotic missions will arrive first, delivering power units, communication systems, and laboratory modules. Machines will handle the difficult, dangerous early construction work long before any astronaut boards a rocket. Over several years, the station is intended to grow module by module until it can support human crews for extended stays. China has also invited other nations to participate, and the response has been notable, with numerous countries expressing interest in contributing experiments, technology, or personnel. This would not be a single nation's outpost, but a shared facility on another world. On the crewed side, China has been methodically testing the systems needed to land astronauts on the lunar surface before the end of this decade. The Long March 10 rocket, capable of lifting roughly 27,000 kilograms into lunar orbit, completed a key low-altitude test flight in early 2026. The Mengzhou crewed spacecraft passed a critical emergency abort test around the same time, demonstrating it can protect astronauts even if something goes wrong during launch. Each crewed lunar mission will require 2 rockets, one carrying the crew, the other carrying the lander. They rendezvous in lunar orbit, dock, and then 2 astronauts descend to the surface. The first visits will likely last only a few days, serving as proof of concept rather than the final destination. Once humanity confirms it can place people on the moon safely and return them home, the path opens toward progressively longer stays. The moon's low gravity makes launches cheaper, its potential for fuel production makes it a strategic launch pad, its far side offers radio silence ideal for astronomy, and its position makes it a natural first stop for missions heading deeper into space. The first group to build lasting infrastructure there will not simply win a competition, they may set the terms for how future missions beyond Earth are planned and executed for decades. And right now, mission by mission, rover by rover, China is laying that foundation on a surface that once seemed like a closed chapter in human history. The moon was never a finished story. It turns out it was only the introduction. Apple wants China's RAM after a 98% price surge. MacBooks already cost more. Apple has spent decades building one of the strongest supply chains in technology. But this time, even Apple could not absorb the pressure. MacBook and iPad prices have already increased after the cost of memory and storage chips surged across the industry. Now Apple is reportedly asking Washington for political clearance to purchase DRAM from Changshin Memory Technologies, better known as CXMT, China's largest memory chip producer. The reported request does not mean a deal has been signed. It does not mean Chinese RAM is already inside new MacBooks. And it does not mean CXMT has replaced Samsung, SK Hynix, or Micron. But the fact that Apple is even considering this option reveals how extreme the memory shortage has become. DRAM prices reportedly rose by as much as 98% during the first quarter of 2026, with another sharp increase expected during the second quarter. The AI boom is consuming advanced memory, manufacturing capacity, packaging resources, and capital at a pace the consumer electronics industry did not expect. Why Apple raised prices? Apple normally avoids sudden price changes during a product cycle. The company prefers predictable pricing because customers compare models, retailers plan inventory, and the entire product lineup is carefully positioned around specific price points. That strategy changed when memory and storage costs climbed too quickly. The entry MacBook Neo rose from $599 to $699. A 512GB MacBook Air increased from $1,099 to $1,999. The 128GB iPad Air moved from $599 to $749. Other Mac, iPad, HomePod, and Apple TV products also became more expensive. Apple said the increases were unavoidable because the company could no longer protect customers from the speed and scale of the component cost surge. If Apple cannot fully contain memory inflation, smaller computer and smartphone manufacturers are likely facing even greater pressure. How AI created a memory shock. An AI accelerator is only as useful as the memory feeding it. Large models require enormous quantities of data to remain close to the processor. Training needs high bandwidth memory to keep thousands of computing units active. Inference also consumes memory because model weights must be read repeatedly while each new token is generated. This has made HBM one of the most valuable products in the semiconductor industry. Samsung, SK Hynix, and Micron are investing heavily in high bandwidth memory because it earns stronger margins than many conventional products. It uses DRAM manufacturing technology, advanced packaging, engineering talent, capital, and factory time that might otherwise support ordinary server, laptop, or mobile memory. When capacity is limited, they prioritize the customers and products offering the highest return. AI companies can justify paying more because a single accelerator system may cost tens or hundreds of thousands of dollars. A laptop maker cannot increase component costs indefinitely without damaging demand. Prices rise. Apple's new prices are one of the clearest signs that the AI memory shortage has moved beyond server rooms. Why CXMT suddenly matters. CXMT was founded in 2016. DRAM is one of the hardest semiconductor markets to enter because success depends on scale, yield, process control, reliability, and relentless cost reduction. A small process variation can reduce the number of usable chips produced from every wafer. CXMT began by supplying more conventional DRAM products for China's domestic market. Its early technology lagged the global leaders, but it continued expanding capacity, improving processes, and introducing newer generations of DDR and low-power memory. The company is now widely regarded as the world's fourth largest DRAM supplier, although it remains far smaller than the top three. Apple does not need CXMT to be larger than Samsung. It needs another supplier capable of producing qualified memory at meaningful volume. Even a modest additional source can strengthen Apple's negotiating position and reduce dependence on a tightly concentrated supplier base. The shortage has transformed CXMT from a distant challenger into a potentially useful option. What Apple is reportedly asking for. According to reports, Apple has been lobbying the United States government for clearance to buy memory chips from CXMT. The company reportedly approached officials because CXMT appears on a Pentagon list of companies alleged to have links to China's military. That listing does not automatically create a universal legal ban on every commercial purchase. However, it creates political, reputational, and regulatory risk. A supplier that is permitted today could face tighter restrictions later. Apple could spend months qualifying a product, redesigning logistics, and negotiating contracts only to see new rules block the arrangement. That is why political clearance matters even if the transaction is not currently prohibited in the simplest legal sense. Apple wants confidence that it will not build part of its supply chain around a supplier that Washington later prevents it from using. The administration has not publicly approved the request. Apple and CXMT have not announced a supply agreement. For now, this is an attempt to create an option, not proof that the option will be used. Apple's qualification process. Supplying Apple is not as simple as offering a low price. Memory must meet strict requirements for performance, power consumption, heat, reliability, packaging, and long-term consistency. A chip may pass one laboratory test and still fail to qualify for mass production. Apple needs components that behave predictably across millions of devices. The supplier must maintain quality from one production batch to the next. It must provide enough volume on schedule. It must support Apple through product launches, regional demand changes, and unexpected factory disruptions. For MacBooks and iPads, power efficiency is especially important. Poor memory efficiency reduces battery life and creates additional heat. Reliability is equally important because defective memory can cause crashes, data corruption, or complete device failure. CXMT would need to prove that its products satisfy Apple's technical standards and that its factories can maintain those standards at scale. Apple may also require extensive audits, traceability, security controls, and contingency plans. Political permission would only open the door. Technical qualification would decide whether CXMT could walk through it. Why Samsung, SK Hynix, and Micron should pay attention. The established suppliers still dominate global DRAM. They possess larger factories, more advanced products, stronger customer relationships, and decades of manufacturing experience. CXMT does not threaten to replace them overnight. But Apple's interest would still carry major symbolic weight. Apple is one of the most demanding and visible electronics companies in the world. If CXMT qualified for even part of Apple's memory supply, other manufacturers would pay attention. A successful Apple contract could validate CXMT's reliability and production discipline. It could also give Apple more leverage during negotiations with current suppliers. Memory is a cyclical commodity business. Small changes in supply and demand can produce large price movements. Adding another credible supplier does not need to eliminate Samsung or Micron to affect the market. It only needs to weaken the assumption that buyers have no alternative. The possibility of CXMT entering Apple's supply chain could therefore influence pricing even before large shipments begin. Why China could benefit? For China, an Apple contract would be more than a commercial sale. It would demonstrate that a domestic memory producer had reached standards acceptable to one of the world's most influential device makers. That could strengthen confidence among Chinese computer, smartphone, server, and automotive companies. It could support CXMT's expansion and help the company improve through larger production volumes. Semiconductor manufacturing often becomes more competitive through repetition. Higher volume generates more process data. More data helps engineers find defects, improve yield, and lower cost. A major customer can therefore accelerate a supplier's development, but the relationship would also create dependence. CXMT would need to satisfy Apple's requirements, absorb pricing pressure, and invest heavily to support future products. Apple is famous for demanding lower costs while maintaining strict quality. Winning the business would be prestigious. Keeping it profitable would be another challenge. Could Chinese RAM lower MacBook prices? Possibly, but not immediately. Adding a supplier can improve competition and reduce procurement risk. If CXMT offers qualified memory at a lower price, Apple could reduce some of the pressure created by the shortage. However, Apple has already raised retail prices. Companies rarely reverse broad price increases quickly unless market conditions change dramatically. The memory market also remains tight. One supplier cannot instantly replace capacity across the industry. CXMT must serve domestic customers while expanding production and improving technology. Any Apple agreement would likely begin with limited volumes or selected products rather than the entire Mac lineup. There is also no guarantee that lower component costs would be fully passed to consumers. Apple could use savings to protect margins, invest in supply security, or avoid additional price increases. The most realistic short-term benefit would be preventing the situation from becoming worse. CXMT could give Apple another source of supply while the company waits for global memory capacity to catch up with AI demand. The political problem. This is where the technology story becomes complicated. Some American lawmakers are likely to oppose any arrangement with CXMT because of national security concerns and broader efforts to reduce dependence on Chinese technology. They may argue that allowing Apple to become a major customer would strengthen a strategic Chinese semiconductor company. Others may focus on supply chain resilience and consumer prices. Blocking an available supplier during a severe shortage could increase costs for American companies and customers. Apple must navigate both arguments. The company sells heavily in China, manufactures much of its hardware through Asian supply chains, and depends on global suppliers. At the same time, it is one of the most prominent American corporations and faces intense political scrutiny. A memory contract that looks economically sensible could still become politically impossible. That uncertainty may be the greatest obstacle. The honest catch. The headline is powerful, but several facts must remain separate. Apple reportedly wants clearance to buy from CXMT. Apple has not confirmed a signed contract. CXMT memory is not confirmed inside current MacBooks. The reported 98% increase refers to market pricing during a specific period, not the exact cost increase of every memory chip Apple buys. MacBook and iPad prices rose for multiple configurations, but iPhone prices had not yet increased at the time of the announcement. CXMT also remains behind the leading suppliers in advanced memory technology and total production scale. The story is not that Apple has abandoned Samsung, SK Hynix and Micron. The story is that the shortage has become severe enough for Apple to explore a politically risky supplier it previously did not rely on. My take is that Apple's reported request is one of the clearest signs that AI has changed the value of memory. For years, DRAM was treated as a replaceable commodity purchased from a small group of established suppliers. Now memory is becoming strategic. AI companies are absorbing supply. Prices are rising fast enough to change retail products, and a Chinese manufacturer that once looked peripheral suddenly has leverage because it can add capacity. Apple may never complete the deal. Political pressure could stop it. CXMT could fail qualification. The shortage could ease before large shipments begin. But the request itself matters. It shows that supply security can become more important than old assumptions about which companies are acceptable suppliers. It also shows how AI infrastructure costs are spreading through the wider economy. Consumers buying laptops are now paying for competition happening inside data centers. So what do you think? Should Apple be allowed to buy memory from CXMT if the chips meet its technical standards? Or would the long-term strategic risk outweigh any short-term reduction in cost? Let me know your view in the comments. And subscribe to Eastern Engine for more grounded coverage of the chips, factories, and engineering decisions reshaping technology. Because Apple is not turning to Chinese memory out of curiosity. It is considering it because a 98% price surge has made the old supply chain too expensive to ignore. For years, the world's biggest technology race has been about artificial intelligence. Every week, headlines focused on faster chips, more powerful AI models, and trillion-dollar companies competing for dominance. But something much bigger is quietly happening behind the scenes. Artificial intelligence is no longer staying inside computers. It's getting a body, and nowhere is that happening faster than China. While much of the world is still debating whether humanoid robots are decades away, Chinese factories are already preparing to deploy them at an unprecedented scale. Hundreds of robotics companies have emerged almost overnight. Entire industrial zones are being redesigned around automation. Robot manufacturers are slashing prices, improving performance, and producing machines at a speed that has surprised even industry experts. This isn't just another technology trend. It could become one of the biggest industrial shifts since the invention of the assembly line. What's making headlines isn't just the number of robots China is building, it's how quickly the economics are changing. Only a few years ago, humanoid robots cost hundreds of thousands of dollars and were mostly research projects or expensive demonstrations. Today, several Chinese companies are racing to bring prices down to levels that many manufacturers can actually afford, opening the door for much wider adoption over the coming years. And that changes everything. Because once a humanoid robot becomes cheaper than employing a human worker for several years, the conversation stops being about science fiction and starts becoming a business decision. Factories don't ask whether a robot is impressive, they ask whether it saves money. For decades, China built its economy on one simple advantage: an enormous workforce capable of manufacturing almost anything at scale. From smartphones and laptops to household appliances and electric vehicles, millions of workers powered the country's rise into the world's manufacturing giant. But China is facing a challenge that many people outside the country rarely discuss. Its population is aging. Birth rates have fallen dramatically over the past decade, while younger generations are becoming less interested in repetitive factory jobs. At the same time, wages have steadily increased as China's economy developed. Companies now face growing labor costs while also competing against manufacturers in other countries. For Beijing, automation isn't simply about showing off advanced technology. It's becoming an economic necessity. If factories cannot easily hire enough workers in the future, machines will have to fill the gap. That's one reason the Chinese government has identified robotics as a strategic industry. Local governments, research institutes, universities, and private companies have all invested heavily in developing the technologies needed to make humanoid robots commercially viable. The results are beginning to show. Chinese companies now account for a significant share of the global humanoid robotics supply chain. Many key components, including electric actuators, motors, sensors, cameras, batteries, and precision manufacturing systems, are already produced domestically. That gives Chinese manufacturers an advantage similar to what happened in electric vehicles. Once the supply chain becomes local and highly competitive, costs begin falling much faster than many analysts expect. Another reason this industry is accelerating is artificial intelligence itself. Building a robot capable of walking has never been the hardest problem. Teaching that robot to understand its surroundings, recognize objects, follow instructions, and adapt to unexpected situations has always been far more difficult. Modern AI changes that equation. Large language models and vision systems now allow robots to interpret spoken commands, identify tools, navigate unfamiliar environments, and improve through continuous training. Instead of programming every movement individually, developers can increasingly teach robots through demonstrations and massive amounts of data. That dramatically speeds up development. Several Chinese robotics companies are now combining advanced AI models with rapidly improving hardware, creating humanoid robots that can perform increasingly complex tasks inside real factories, not just carefully controlled laboratories. And that's why investors, manufacturers, and governments around the world are paying close attention. Because this race is no longer about building the smartest chatbot. It's about building millions of physical workers that never get tired, don't require breaks, and can potentially operate around the clock. If that vision becomes reality, the impact won't be limited to China. It could reshape global manufacturing, supply chains, labor markets, and the competitive balance between the world's largest economies. And the companies leading this transformation may not be the names most people expect. To understand why China has become the center of the humanoid robot revolution, you have to look beyond the robots themselves. The real story begins with manufacturing. For more than 20 years, China has built the world's largest industrial ecosystem. Nearly every major product, from smartphones and batteries to electric vehicles and consumer electronics, depends on factories that either operate inside China or rely heavily on Chinese suppliers. Over time, that manufacturing base created something incredibly valuable: an unmatched supply chain. A humanoid robot may look futuristic, but underneath the sleek exterior, it's built from components that China already manufactures in enormous quantities: electric motors, gearboxes, lithium batteries, high-resolution cameras, LiDAR sensors, AI processors, precision machined metal parts, advanced wiring. Every year, Chinese factories produce millions of these components for other industries. That means robotics companies don't have to build an entirely new supply chain from scratch. They can source many parts locally, reducing costs and speeding up production. This is exactly what happened in China's electric vehicle industry. At first, many Western analysts believed Chinese EV companies would remain years behind established automakers. Instead, fierce domestic competition created a massive manufacturing ecosystem where hundreds of suppliers competed to improve quality while driving prices lower. The result was simple: better products, lower costs, faster innovation. Now, many experts believe humanoid robotics is entering a similar phase. Instead of a handful of companies dominating the industry, dozens of Chinese startups are competing aggressively to build better robots faster than their rivals. Every improvement forces competitors to respond, creating a cycle of rapid innovation. One company attracting enormous attention is Unitree Robotics. Originally known for its agile four-legged robot dogs, Unitree has expanded aggressively into humanoid robotics. Videos of its robots walking, running, balancing, dancing, and performing complex movements have spread across social media, giving millions of people their first glimpse of just how quickly the technology is improving. But impressive demonstrations are only part of the story. The real goal isn't making robots dance, it's making robots work. Factories are interested in repetitive tasks that humans often find exhausting, dangerous, or difficult to staff. Moving heavy boxes, transporting materials, sorting components, loading machines, performing inspections, operating around the clock. Unlike industrial robotic arms, which are fixed in one location, humanoid robots can move through environments originally designed for humans. That matters because replacing an entire factory with custom automation is incredibly expensive. Replacing a worker with a robot that can simply walk to the same workstation is often much cheaper. Another rapidly growing player is Agibot, which is focused heavily on combining artificial intelligence with physical robotics. The company's vision extends beyond hardware. It aims to create robots capable of learning new tasks through AI, rather than requiring extensive reprogramming every time the environment changes. This flexibility could become one of the biggest breakthroughs in modern manufacturing. Imagine buying one robot today. Next month, instead of purchasing another specialized machine, You simply download new software that teaches it a completely different job. That's a radically different business model. Software updates become productivity upgrades. The same machine becomes more valuable over time. Chinese companies are also benefiting from another advantage that often goes unnoticed: speed. In many Western countries, scaling advanced manufacturing can take years due to permitting, labor shortages, and fragmented supply chains. China operates differently. When a promising technology emerges, suppliers, manufacturers, universities, investors, and local governments often move simultaneously. New factories are built quickly. Component suppliers expand production. Engineering talent shifts toward growing industries. Entire industrial clusters emerge within a remarkably short period. That ability to scale rapidly has become one of China's biggest competitive strengths, and it's one reason many analysts believe the country could dominate the first generation of commercially successful humanoid robots. Of course, competition isn't standing still. Tesla continues developing Optimus, while companies across the United States, Europe, Japan, and South Korea are investing billions into robotics research. But China's advantage isn't necessarily having the single most advanced prototype. It's having the ability to manufacture thousands, and eventually hundreds of thousands, of robots at prices that competitors may struggle to match. History has shown that manufacturing scale often becomes just as important as technological breakthroughs. The smartphone industry proved it. The solar industry proved it. Electric vehicles proved it. Now many believe humanoid robots could be next. And if that happens, the biggest winners may not simply be the companies building robots. They could be the nations capable of producing them faster, cheaper, and at a scale the rest of the world cannot easily replicate. If all of this sounds familiar, that's because we've seen this pattern before. A new technology appears. Most people dismiss it as expensive, impractical, or years away from widespread adoption. Then costs collapse, production scales, and suddenly, an industry transforms almost overnight. That's exactly what happened with solar panels. It happened with lithium-ion batteries. It happened with electric vehicles. And many experts believe humanoid robots are approaching the same tipping point. The biggest reason is cost. Only a few years ago, a capable humanoid robot could easily cost hundreds of thousands of dollars. At that price, only research labs and large corporations could justify buying one. But today, Chinese robotics companies are racing to reduce costs through mass production, domestic supply chains, and standardized components. As more manufacturers enter the market, competition is accelerating price reductions while improving performance at the same time. For factory owners, that changes the entire equation. Imagine a manufacturing plant that employs hundreds of workers to perform repetitive tasks around the clock. Every employee requires wages, training, insurance, safety measures, vacations, shift scheduling, and replacement when someone leaves. A robot doesn't eliminate every one of those costs, but it changes the economics dramatically. It doesn't call in sick. It doesn't need overtime pay. It doesn't require years of experience before becoming productive. And unlike traditional industrial machinery, a humanoid robot can potentially perform multiple different jobs depending on how it's trained. That's a huge advantage. Instead of buying 5 specialized machines, a factory could eventually deploy one fleet of adaptable robots capable of handling different tasks throughout the day. The return on investment suddenly becomes much easier to justify. This is one reason manufacturers around the world are watching China's robotics industry so closely. Even companies that don't plan to buy Chinese robots immediately know that increased competition usually benefits everyone. Prices fall, capabilities improve, innovation speeds up. At the same time, artificial intelligence is making these machines far more useful than previous generations of industrial robots. Traditional factory automation works best in predictable environments. If every object arrives in exactly the same position every single time, robotic arms can perform incredibly precise tasks. But real factories are rarely perfect. Boxes move, parts shift, tools end up in unexpected places, workers change workflows. Unexpected problems happen every day. Humanoid robots powered by modern AI are being designed to handle those situations much better than earlier machines. Instead of stopping every time something changes, they can increasingly recognize objects, adjust their movements, understand spoken instructions, and adapt to new environments with far less human intervention. That flexibility could become one of the industry's biggest competitive advantages. And China isn't just building robots, it's generating enormous amounts of data to train them. Every successful movement, every failed attempt, every object picked up, every task completed, all of that information can be used to improve future software models. Just like chatbots became smarter by processing billions of words, humanoid robots become more capable by collecting billions of real-world interactions. The more robots operating in factories, the more data they generate. The more data they generate, the smarter future robots become. It's a feedback loop that's incredibly difficult for competitors to ignore. This is also where China's manufacturing scale becomes a strategic advantage. Deploying thousands of robots means collecting millions of hours of operational data far faster than companies with only small pilot programs. That data can improve navigation, dexterity, balance, object recognition, decision-making, and overall reliability. Over time, the gap between companies with massive real-world deployment and those relying mostly on laboratory testing could become increasingly significant. That's why many analysts believe the real competition isn't simply about who builds the best humanoid robot today. It's about who deploys the most robots first, because whoever collects the most operational data may improve the fastest. And if China succeeds in scaling humanoid robots the same way it scaled electric vehicles, batteries, and solar manufacturing, this industry could evolve much faster than many people currently expect. Which brings us to perhaps the biggest question of all. If millions of intelligent robots begin entering factories over the next decade, what happens to the people currently doing those jobs? The idea of humanoid robots replacing people makes for dramatic headlines, but reality will almost certainly be more complicated. History shows that automation rarely eliminates work altogether. Instead, it changes the kind of work people do. When tractors replaced horses, millions of farming jobs disappeared, but entirely new industries emerged. The same happened during the Industrial Revolution, with computers, and later with the internet. Every major technological leap disrupted existing jobs, while creating opportunities that didn't exist before. Humanoid robots are likely to follow a similar pattern. Some repetitive factory positions may gradually disappear, especially where labor shortages already exist. But demand for robot technicians, AI engineers, maintenance specialists, software developers, and manufacturing operators is expected to grow alongside the industry. The transition won't happen overnight. Factories don't replace thousands of workers in a single week. New technology has to prove itself. Companies test small deployments, measure productivity, calculate costs, and only then expand. Even if humanoid robots become significantly cheaper, adoption will take years as businesses evaluate where they actually deliver value. But one thing is becoming increasingly clear. This is no longer a question of if humanoid robots become part of manufacturing. It's a question of who leads the industry. And right now, China has built a formidable lead. The country combines massive manufacturing capacity, one of the world's deepest electronic supply chains, rapidly improving artificial intelligence, and strong investment into robotics. That combination allows companies to move from prototype to production faster than many competitors. At the same time, rivals aren't standing still. Tesla continues developing Optimus with the goal of creating a general-purpose humanoid robot. Companies in Japan and South Korea remain global leaders in industrial automation. European firms continue pushing advanced robotics for specialized applications. The United States is investing heavily in AI software that could eventually power the next generation of intelligent machines. In other words, this isn't a race that's already over. It's a race that's accelerating. And the next few years could determine who builds the operating system for the physical AI era. Because that's what humanoid robots really represent. For decades, AI mostly lived inside screens. Now it's stepping into warehouses, factories, construction sites, hospitals, retail stores, and eventually, perhaps even homes. That shift could become every bit as significant as the arrival of smartphones or the internet itself. The winners won't simply sell robots. They'll build ecosystems of hardware, software, AI models, cloud services, maintenance platforms, and manufacturing networks that reinforce each other over time. China understands that. That's why it's investing across the entire value chain, instead of focusing on a single company. Whether China ultimately dominates the humanoid robot market or faces stronger competition than many expect, one fact is difficult to ignore. The pace of progress has accelerated dramatically. Just a few years ago, humanoid robots were mostly technology demonstrations that struggled to walk across a room. Today, they're lifting boxes, moving materials, operating in factories, and becoming more capable with every new generation of AI. That transformation is happening faster than many analysts predicted. And if costs continue falling while performance continues improving, the conversation may soon shift from whether businesses should adopt humanoid robots to whether they can afford not to. The AI race is no longer confined to data centers and computer chips. It's moving into the physical world. And the country that masters both artificial intelligence and advanced manufacturing could shape the next era of the global economy. The question isn't whether robots are coming. They're already here. The real question is whether the rest of the world can keep up with the speed at which China is turning science fiction into industrial reality. If you enjoyed this deep dive, don't forget to like the video, subscribe to Eastern Engine, and let me know your thoughts in the comments. Are humanoid robots going to create more opportunities than they replace? Or are we witnessing the biggest transformation of the global workforce since the Industrial Revolution? Thanks for watching, and I'll see you in the next one. For years, the entire world agreed on one thing. If you want to build the most advanced computer chips on Earth, the tiny, mind-bendingly complex processors that power your phone, your laptop, the AI everyone's talking about, you need one specific machine, a single machine built by a single company in a single country. Without it, the experts said, you simply cannot cross a certain line. You'd be stuck, permanently. That machine was deliberately kept out of China's hands. The logic was airtight. No machine, no advanced chips, no way forward. China would hit a wall at a certain level of technology and stop there, frozen, while everyone else raced ahead. Except China just walked straight through that wall. A Chinese company called SMIC has now started mass-producing a 5-nanometer class chip, a genuinely advanced processor, a full generation ahead of what most analysts swore was China's ceiling. And it did it without the machine it was banned from buying. The chip is real. It's already inside a phone you can hold in your hand, and its existence is quietly rewriting one of the core assumptions of the entire global technology war. Now, like every story on this channel, there's important fine print, and I'm going to give you all of it, honestly, because the truth here is more interesting than the hype on either side. By the end of this video, you'll understand exactly what SMIC built, why everyone said it was impossible, the brutal trick they used to pull it off, what it cost them, and why this single chip has people in boardrooms around the world genuinely rattled. Let's get into it. To understand why this is such a big deal, you need to understand the machine. Because this isn't just a machine. It might be the single most complex object humanity has ever manufactured. It's called an EUV lithography system, extreme ultraviolet. And making chips is, at its heart, a printing process. You're printing unimaginably tiny patterns onto a wafer of silicon, patterns so small they're measured in nanometers, billionths of a meter. The smaller and finer you can print those patterns, the more transistors you cram onto a chip, and the more powerful it becomes. That's been the engine of all computing progress for decades. To print the very finest patterns, the cutting edge, 5 nanometers and below, you need light with an extremely short wavelength. And generating that specific kind of extreme ultraviolet light is so monstrously difficult that only one company on the entire planet can build a machine to do it, a Dutch firm called ASML. Just one, nowhere else. How hard is it? Each EUV machine costs around $200 million. It weighs as much as 2 loaded buses. To create the light, the machine fires a high-powered laser at microscopic droplets of molten tin 50,000 times per second. It contains the flattest mirrors ever manufactured by human beings. It is a genuine marvel, and there is exactly one source for it on Earth. So here's what happened. The United States, wanting to slow China's technological rise, pressured the Netherlands to block the sale of these EUV machines to China. The reasoning was simple and on paper, devastating. EUV is the only known way to make chips at 5 nanometers and below. China can't buy EUV. Therefore, China is locked out of advanced chips, stuck at an older level called 7 nanometers, unable to go further. That was the plan. The entire strategy rested on one belief, that EUV was absolutely, non-negotiably required to break past 7 nanometers. China just proved that belief wrong. The company at the center of this is SMIC, Semiconductor Manufacturing International Corporation, China's largest chipmaker. And in late 2025, something showed up that analysts immediately pounced on. Huawei released a new phone with a processor inside it called the Kirin 9030. And when the respected analysis firm Tech Insights physically tore that chip apart to examine it, which is exactly what these firms do, they literally dissect chips under powerful microscopes. They confirmed something remarkable. The Kirin 9030 was built on a brand new SMIC process called N+3, a 5 nanometer class node, China's most advanced chip ever made, in volume production, sitting inside a consumer phone. And critically, made without a single EUV machine. Let that land for a second. This is a full generation jump. SMIC's previous best was a 7 nanometer class process called N+2. That's what powered Huawei's earlier AI chips. Jumping from 7 nanometer to 5 nanometer class is not a small step. It's the kind of leap the entire industry insisted was impossible without EUV. SMIC didn't just inch forward, it leapfrogged an entire generation, using only the older machines it's actually allowed to have. So the obvious question is, how? If EUV is the only way to print patterns that fine, and China doesn't have EUV, how is there a 5 nanometer chip sitting inside a phone right now? The answer is one of the most impressive, and most punishing, feats of engineering in the modern chip industry. And once you understand it, you'll understand both why it's brilliant and why it comes at a brutal price. Here's the workaround, and I'm going to make it simple. The machine China is allowed to have is the previous generation tool, called DUV, Deep Ultraviolet. It uses light with a longer wavelength than EUV. Think of it this way. EUV is like a fine-tipped pen that can draw an incredibly thin, crisp line in a single stroke. DUV is like a fat marker. With one stroke of a fat marker, you simply cannot draw a line as thin as the fine pen can. So how do you draw an ultra-thin line with a fat marker? You cheat. You don't draw the line directly, you draw around it. You a wall. The fine-tipped airbrush, EUV, does it in one clean pass. You don't have the airbrush. So instead, you paint the wall, then mask part of it, and paint again, then mask and paint again, and again, 4 separate, perfectly aligned passes, slowly sculpting a level of detail the fat brush could never achieve in one go. Done perfectly, the final result rivals what the airbrush would have produced. That is, essentially, what SMIC did. They used brute force, engineering brilliance and sheer stubbornness to squeeze a 5 nanometer class result out of machines that were never designed to reach it. Where EUV does the job in one elegant exposure, SMIC stacks pass after pass after pass, each one demanding flawless precision, to mimic what the forbidden machine does naturally. It's a genuinely stunning achievement. It proves that the wall everyone thought was solid had a way around it after all. But, and this is the part the hype videos skip, painting the same wall 4 times instead of once is not free. It costs you, badly. And that cost is the whole reason this story has a second, more sober half. Here's where I have to be completely straight with you, because this is exactly the kind of story that gets twisted in both directions online. Every single one of those extra patterning passes is another chance for something to go wrong. Each pass has to line up with the previous one with almost supernatural precision. If the alignment drifts even slightly across 4 stacked passes, the tiny features blur, defects creep in, and the chip fails. So the more passes you add, the more chips come out broken. This is the central problem, and the industry has a word for it: yield. Yield is the percentage of chips on a wafer that actually come out working. With EUV's clean single pass, yields are high. With SMIC's 4-pass brute force method, yields are reportedly much lower, meaning a larger share of every batch is wasted. Analysts at Tech Insights specifically flagged yield as the key challenge. More broken chips per batch means each working chip is dramatically more expensive to produce. There are 2 more honest caveats you deserve to hear. First, even though SMIC reached a 5 nanometer class node, experts note its actual transistor density still falls short of the true 5 nanometer chips that companies like TSMC and Samsung made years ago. It's 5 nanometer class, a major achievement, but not a perfect match for the global leaders. Some analysts argue it sits closer to a souped-up 6 nanometer in real-world terms. And second, the most important nuance of all, while SMIC did this without EUV, it most likely still used advanced DUV machines that were originally imported from ASML before the tightest restrictions hit. So this isn't yet a 100% homegrown miracle. The achievement is doing it without EUV, not yet doing it without any foreign tools at all. That fully independent version is what China is racing toward next, and there are already reports of domestic Chinese DUV scanners and even an EUV prototype in testing. But we're not there yet, and I won't pretend we are. So here's the fair summary. SMIC has not matched TSMC, and it's not doing this cheaply or with perfect independence. What SMIC has done is shatter the belief that 5 nanometer class chips were flat out impossible without EUV. The "it can't be done" wall is gone. What remains is an "it's expensive and hard" wall, and that is a completely different and far more survivable kind of problem. So if it's expensive, lower yield, and not quite TSMC level, why are people genuinely rattled by this? Why does a single phone chip matter so much? Because of what it proves about the direction of the entire strategy. The export controls were built on a specific bet, that cutting off EUV would stop China cold at 7 nanometers. Not slow it, stop it. The whole point was a hard ceiling. SMIC just demonstrated that the ceiling isn't a ceiling at all. It's a speed bump, a painful, expensive, yield-crushing speed bump, but China drove right over it anyway. The wall meant to halt China's progress turned out to be something China could climb, slowly and at great cost, but climb nonetheless. And here's the deeper pattern, the one we keep seeing on this channel across story after story. Cut off from EUV, China didn't give up. It poured everything into mastering DUV multi-patterning to a degree nobody thought commercially viable. The restriction didn't kill the ambition. It redirected it, and forced a kind of engineering creativity that might never have happened otherwise. The same shape as the light chips, the GPU-free supercomputer, the new approach to Moore's law. A wall goes up, the water finds another way around it. There's also a brutal economic irony buried in here. Those same restrictions that blocked Nvidia's top chips from China handed Huawei an enormous captive domestic market with no foreign competition, which gave Huawei and SMIC both the motivation and the guaranteed customers to justify pushing through these insanely difficult, expensive processes. In trying to choke the supply, the restrictions may have supercharged the demand for a homegrown alternative. The pressure designed to weaken the domestic industry instead gave it a reason to grow up fast. None of this means China has won the chip war. It hasn't. TSMC is still ahead. The cost and yield problems are real and serious. But the core assumption that a single banned machine could permanently cap China's progress, that assumption is now visibly, demonstrably cracked. And rewriting a foundational assumption like that is exactly the kind of thing that keeps strategists up at night. Let me zoom out because the trajectory matters more than this one chip. Right now, SMIC's path forward splits into two races. The first is improving yield, taking this expensive, difficult 4-pass process and grinding it down, batch after batch, into something cheaper and more reliable. That's the unglamorous, year-after-year factory work that turns a breakthrough into a business. History shows that yields, once a process exists at all, tend to climb steadily as engineers learn the quirks of their own line. Painful today doesn't mean painful forever. The second race is independence, replacing those imported DUV machines with fully domestic Chinese ones, so the entire process, top to bottom, can be done with no foreign parts at all. That's the holy grail Beijing is openly chasing, and there are already early reports of domestic immersion DUV scanners in testing, and even a homegrown EUV prototype reportedly undergoing trials. If, and it's still an if, China eventually cracks its own EUV machine, the entire export control strategy could lose much of its remaining grip. The honest near-term reality is that China is still a step behind the absolute frontier, and it's paying more to be there. But the gap between permanently locked out and a step behind and catching up is the difference between two completely different futures. SMIC just moved China from the first category into the second, and in a race like this, the direction you're moving matters far more than exactly where you stand today. Here's my honest opinion. I think the two loudest reactions to this are both wrong, and the truth sits in the uncomfortable middle. The people shouting China has caught up and beaten the sanctions are way ahead of the facts. The yields are poor, the costs are high. It's not true TSMC grade 5 nanometer, and it probably still leans on imported tools. Anyone selling you China 1 is selling a fantasy. But the people insisting, this is nothing, it's expensive and low yield, ignore it, are making the bigger and more common mistake. Because they're focused on the cost and missing the proof. The entire export control strategy was built on the word impossible. EUV is required, full stop, no workaround. SMIC just turned impossible into expensive, and in engineering, those are not remotely the same thing. Impossible is a wall, expensive is a to-do list. You can grind down expensive over time. You cannot grind down impossible. What strikes me most, yet again, is the pattern. Every time a barrier goes up to contain China's technology, the response isn't surrender. It's a workaround that nobody thought was viable, forced into existence by the pressure itself. Light instead of electrons, CPUs instead of GPUs, and now 4-pass DUV instead of the one machine they were denied. I genuinely don't think that's coincidence anymore. Necessity isn't just the mother of invention here, it's becoming the entire engine of an industry. So here's my question for you, and I want your honest answer, because this is the real debate. Did the export controls fail by proving they can be engineered around, or did they actually succeed by forcing China to spend enormous money and effort on a slower, more expensive path it otherwise wouldn't have needed? In other words, is making your rival's progress expensive a win, even if you couldn't make it impossible? Drop your real take in the comments. I read every single one, and this one genuinely splits smart people down the middle. If you want to keep following this, the workarounds, the breakthroughs, the moves the rest of the world keeps underestimating until they can't, subscribe to Eastern Engine and hit the notification bell. Chips, light, energy, the whole foundation of modern technology is being rewritten right now, and we break it all down before the mainstream catches on. Thanks for watching. I'll see you in the next one. Artificial intelligence has spent years solving one problem by buying more hardware, more GPUs, more memory, more power, larger data centers, faster networking, and increasingly expensive cooling systems. But Chinese researchers at Peking University say they have demonstrated another path. Instead of making one processor dramatically more powerful, they connected several modest processors with light and redesigned the neural network so every chip could work at the same time. The result was extraordinary. Their hybrid optical system completed a distributed artificial intelligence inference task nearly 149 times faster than a commercial GPU. Even though the combined processors provided only about 1/9 of the GPU's theoretical computing capacity. The system processed 1,000 images in 105.16 microseconds. The GPU needed 15.643 milliseconds for the same workload. The Chinese system was not powered by a magical all-optical processor. It did not train a giant language model, and it did not replace NVIDIA's most advanced accelerator. The computing was still performed electronically on 5 programmable FPGA chips. What changed was the connection between them. Each processor was linked through custom silicon photonic transceivers capable of 400 gigabits per second and a 16 by 16 optical switch that routed information using light instead of conventional electronic switching. That allowed the 5 stages of a neural network to operate like an assembly line. While one chip processed the first layer of a new image, the next chip processed the second layer of an earlier image, and the remaining chips worked on later stages simultaneously. The processors stopped waiting for one another. They stopped repeatedly moving intermediate data into distant memory, and nearly all of their available computing capacity was finally used. The question is not whether China has built a chip that is simply 100 times more powerful than every NVIDIA GPU. It has not. The real question is more important. What happens if the biggest limitation in artificial intelligence is no longer calculation but the time and energy wasted moving data between calculations? Because if light can remove that bottleneck, the future of AI may depend less on purchasing more GPUs and more on connecting the chips we already have far more intelligently. The bottleneck nobody sees. A modern AI accelerator can perform trillions of mathematical operations every second, but raw arithmetic is only one part of the job. Before a processor can calculate, it needs data. It needs model weights, input information, intermediate feature maps, instructions, and results produced by earlier stages. All of that information must move between memory, processors, network devices, and sometimes separate servers. The physical movement of data creates delay. It also consumes energy. A processor may be capable of an enormous theoretical performance, yet achieve only a fraction of that performance if its computing units spend time waiting for information. This is often described as the memory wall or communication wall. The industry's normal response is to build faster memory and wider electrical connections. High bandwidth memory places stacked DRAM beside an accelerator. Advanced packaging shortens the distance between chiplets. NVLink, InfiniBand, Ethernet, and other systems connect processors inside and between servers. These technologies are powerful, but they cannot completely escape the physical limits of electrical signaling. As data rates increase, electrical links lose more energy, generate heat, become harder to route, and require additional circuitry to recover and correct signals. The problem becomes even more difficult when an AI workload is divided among several processors. One processor may finish its assigned calculation and then wait while data travels to the next processor. If every stage operates sequentially, adding more chips may increase theoretical capacity without producing an equivalent increase in real performance. The Peking University team attacked this problem from 3 directions at once. They changed the interconnect, they changed the processing architecture, and they changed how the neural network algorithm was divided across the hardware. That combination is why the result matters. What the researchers built. The experimental system contains 3 main pieces. The first pieces are 5 field programmable gate arrays, commonly called FPGAs. An FPGA is a chip whose internal logic can be reconfigured after manufacturing. Unlike a fixed processor designed for one permanent architecture, an FPGA allows engineers to create custom data paths, processing units, buffers, and interfaces for a specific task. FPGAs are widely used in telecommunications, industrial systems, autonomous vehicles, aerospace equipment, data centers, and hardware prototypes. They are not automatically faster than GPUs. Their advantage is flexibility. Engineers can organize the hardware around one workload instead of forcing that workload through a general architecture. In this experiment, each FPGA handled one layer of a 5-layer convolutional neural network. The second component is a custom silicon photonic transceiver attached to each processing chip. The FPGA produces electrical data. The transceiver converts that data into optical signals, sends it through the network, receives incoming light, and converts it back into electrical form for the next processor. Each transceiver provided a 400 gigabit per second optical input and output interface. The third component is a non-blocking 16 by 16 optical switch. A non-blocking switch can connect available inputs to outputs without forcing one route to interfere with another. The device was manufactured on a silicon planar lightwave circuit platform. It operated around a wavelength of 1,300 nanometers and produced total optical loss of no more than 5 decibels across a broad spectral range. The network transmitted data at 400 gigabits per second, without errors and without optical amplification during the test. Together, these parts formed a reconfigurable optical fabric, capable of connecting as many as 16 processing chips. The researchers used 5 processors for the demonstrated AI workload, but the central switch provides room for a larger system. In theory, 16 400 gigabit links would provide up to 6.4 terabits per second of aggregate switching bandwidth, although the actual system remains limited by the input and output capabilities of the attached processors. How the optical pipeline works. The most important innovation is not simply replacing a copper cable with fiber. The researchers created what they call optical pipeline parallelism. Imagine a factory assembling a product in 5 stages. If one worker completes every stage alone, the next product cannot begin until the previous product is finished. Adding 5 workers does not help if all 5 still wait for the same product and work one after another. A pipeline changes the process. The first worker completes stage 1 and passes the product to the second worker. The first worker immediately begins stage 1 on the next product. Soon, all 5 workers are active simultaneously, each handling a different stage of a different product. After the pipeline fills, completed products emerge continuously. The Chinese system applied this idea to neural network inference. The 5-layer image denoising network was divided across 5 FPGAs. The first FPGA performed the first convolutional encoder stage. Intermediate feature maps moved directly from one FPGA to the next through the optical network. Each processor used local on-chip memory to buffer incoming data and digital signal processing units to execute its assigned convolution. Because each layer remained permanently deployed on its own FPGA, the system did not need to repeatedly load new kernels, store every intermediate result in external memory, and then retrieve that result for the next layer. Once the pipeline was filled, all 5 processors worked concurrently. This is where the enormous latency advantage came from. The optical link provided enough throughput to keep the pipeline moving, while the specialized hardware mapping prevented the processors from becoming idle. The demonstration. The researchers tested the architecture using a 5-layer convolutional neural network trained to remove noise from images in the Fashion MNIST dataset. Fashion MNIST contains simple grayscale images of clothing items. For the experiment, each image had a resolution of 32 by 32 pixels. Every pixel was represented using 32-bit floating point precision, giving 32,768 bits per image. Each network layer used a 5x5 convolutional kernel, followed by a rectified linear unit activation. The feature maps were reduced to 28 by 28 pixels during convolution and then padded back to 32 by 32. The model was trained offline before being deployed onto the FPGAs. That distinction is important. The optical system demonstrated inference, meaning it used an already trained model to process new inputs. It did not perform the much more demanding process of training the model from the beginning. The researchers sent 1,000 images through the completed pipeline in batches of 10. The total measured latency was 105.16 microseconds. The 5 FPGAs used a combined total of 5,040 digital signal processing units running at 390.625 MHz. Their estimated peak FP32 computing rate was about 1.969 teraflops. For the 1,000 image workload, the network required about 196 million floating point operations. Under perfect utilization, the calculation should have taken approximately 99.6 microseconds. The measured result of 105.16 microseconds means the computing hardware achieved 94.7% utilization. That number may be more significant than the headline speedup. The system did not win because it contained more arithmetic power. It won because almost all of its smaller arithmetic capacity remained busy. The GPU comparison. For comparison, the researchers ran the same workload using 32-bit floating-point precision on a commercial GPU. The paper describes that GPU as containing 3072 CUDA cores operating at 2.76 GHz, with a theoretical FP32 performance of approximately 16.96 teraflops. On paper, the GPU provided more than 8 times the raw computing capacity of the 5 FPGA system, yet it required 15.643 milliseconds to process the images. That made the optical pipeline nearly 149 times faster while using only 11.6% of the GPU's theoretical computing resources. This sounds impossible until we separate peak performance from workload efficiency. The GPU handled the 5 network layers sequentially. Adding layers and accessing memory consumed far more time than the arithmetic itself. The FPGA system was purpose-built for the network. Every layer had dedicated hardware. Data streamed continuously between those layers. The optical pipeline removed much of the waiting. This is a valid comparison for the demonstrated task, but it is not proof that 5 FPGAs will beat every GPU by 149 times on every AI model. A larger GPU batch, a better optimized implementation, a different network, or a heavier workload could produce a very different result. Modern GPUs are designed to handle enormous parallel workloads, and they become more efficient when enough computation is available to fill their cores. The experiment instead reveals how badly a powerful general processor can perform when communication and scheduling dominate a relatively small latency-sensitive task. Why light changes the equation? Light offers several advantages for chip-to-chip communication. Different wavelengths can travel through the same waveguide or fiber simultaneously. This allows wavelength division multiplexing, where several independent data channels share one physical path. Optical signals can also travel across longer distances with lower loss than extremely high-speed electrical signals. They do not create the same electromagnetic interference, and a passive optical switch does not need to inspect, buffer, schedule, and retransmit every packet like a conventional electronic switch. In the Peking University system, the switch acted as a physical routing fabric. The researchers removed much of the overhead associated with a full Ethernet networking stack. They retained essential encoding and error correction functions, but the optical switch itself performed no packet queuing or buffering. That helped keep latency extremely low. However, the system was not completely optical. The FPGAs still calculated electronically. The transceivers still converted between electricity and light. Memory remained electronic. Control logic remained electronic. The correct description is hybrid optoelectronic computing. Light handled high-speed communication, while electronic processors handled the neural network mathematics. This hybrid approach may be more practical than trying to replace every transistor with a photonic device. Why this matters for AI data centers? The AI industry is currently building larger clusters because individual chips cannot contain the largest models or serve every user alone. Thousands of accelerators must communicate during training and inference. The faster processors become, the more damaging communication delays become. A GPU that finishes its work quickly may simply spend more time waiting for another GPU, memory bank, or network switch. This creates a paradox. Companies purchase more computing power, but a growing portion of that power can be lost to coordination. Optical interconnects could help at several levels. The Peking University demonstration focuses on a tightly coordinated group of processing chips executing a pipeline. It shows that co-designing the algorithm and the interconnect can produce far more useful performance from modest hardware. That idea is especially relevant for inference. Many inference applications care about latency more than total throughput. An autonomous vehicle, industrial robot, medical instrument, communication system, or edge device may need an answer immediately. Waiting several milliseconds can matter. A specialized optical pipeline could process a fixed model with very low delay while using less expensive computing hardware. Large cloud systems could also divide frequently used models into permanent pipeline stages, although real commercial workloads are far more complicated than the demonstrated denoising network. What the headline does not mean, the phrase 100 times faster without more GPUs, is accurate only within the context of this experiment. China has not created a universal processor that makes NVIDIA obsolete. The system did not outperform a current flagship accelerator across large language models, generative video, scientific simulation, and model training. It processed a small 5-layer convolutional network on 1032 by 32 images. The comparison used one commercial GPU with 3072 CUDA cores, not an entire modern AI cluster. The model was already trained. The researchers did not publish a complete commercial power comparison showing that the entire optical system used 1/9 of the energy. They reported 1/9 of the theoretical computing resources. The transceivers, optical switch, FPGA boards, control systems, and supporting equipment still consume power. The system also used 5 separate processing boards to defeat one GPU on a workload specifically mapped to those boards. That does not invalidate the result. It defines what the result actually proves. The experiment proves that communication architecture and algorithm mapping can matter more than peak teraflops for some workloads. It proves that an optical network can transmit 400 gigabit data streams without errors while connecting multiple computing nodes. It proves that a carefully designed pipeline can keep modest processors operating near their theoretical limit. And it proves that buying a larger processor is not always the most efficient answer. The scaling challenge. The researchers acknowledge that the demonstration remains small compared with modern AI workloads. 5x5 convolution kernels and a 5-layer network are not comparable to a large transformer containing billions or trillions of parameters. Scaling the architecture would require more processors, more memory, more optical channels, more sophisticated scheduling, and support for many different computational operations. The current system's remaining bottleneck was not the optical transceiver. It was the input and output capability of the FPGAs. The paper notes that the photonic technology can already support 200 gigabits per second on each wavelength and aggregated transceiver capacities up to 1.6 terabits per second. Future processing chips would need more high-speed channels to exploit that bandwidth. The optical switch can theoretically connect 16 processors, but larger AI systems may require hundreds or thousands of nodes. Engineers would need multi-stage optical networks, fault tolerance, calibration, monitoring, and software capable of placing models across changing hardware. Programmability is another challenge. The demonstrated network benefited from a simple model with clear layers. Real AI services run different models, variable input sizes, dynamic workloads, attention mechanisms, sparse operations, and unpredictable user demand. A fixed pipeline may become inefficient when the workload changes. The system must retain enough flexibility to justify its infrastructure. China's strategic advantage. This research fits China's broader effort to improve computing performance despite restrictions on access to the most advanced foreign AI chips and manufacturing equipment. If the best individual processors are difficult to obtain, connecting available processors more efficiently becomes strategically valuable. An architecture that extracts more real work from modest chips can reduce dependence on brute force scaling. China also has growing capabilities in silicon photonics, optical communications, FPGA development, packaging, and data center infrastructure. Combining those fields could create systems that compete at the architectural level, even when individual chips remain behind the leading edge. But this should not be framed as China defeating NVIDIA overnight. NVIDIA's advantage includes hardware, memory systems, networking, software libraries, developer tools, and a massive installed ecosystem. The company is also investing heavily in optical networking and faster interconnects. The global industry already understands that communication is becoming the next major bottleneck. The race is not between China using light and the West ignoring it. The race is about who can turn photonic interconnects into reliable, programmable, manufacturable systems first. My take is that the 149 times result is real, impressive, and easy to misunderstand. The researchers did not build a processor with 149 times more computing power. They built a system that wasted far less of the computing power it already had. That may be the more important achievement. For decades, performance improvements came primarily from faster transistors, more cores, and larger chips. AI is reaching a stage where moving information can cost more time and energy than calculating with it. When that happens, architecture becomes as important as the processor. The Peking University system demonstrates a different philosophy. Divide the model across specialized chips. Keep each stage permanently ready. Stream data directly from one stage to the next. Use light to prevent communication from slowing the pipeline. And design the algorithm, processors, and network as one machine. The experiment is still far from replacing GPU clusters. Its model is small, its hardware is specialized, its commercial energy advantage remains unproven. Its scaling challenges are serious, but the result exposes a weakness in the current AI race. A system with 16.96 teraflops lost badly to a system with 1.969 teraflops because the stronger machine could not use its strength efficiently. That is the warning. The next breakthrough may not come from a GPU with twice as many cores. It may come from a network that keeps every existing core busy. China has shown that optical pipeline parallelism can deliver that advantage on one carefully chosen task. Now researchers must prove that the same principle can scale to larger models, more processors, dynamic workloads, and real products. If they succeed, AI data centers may stop being collections of isolated superchips connected by increasingly desperate wiring. They may become optical computing fabrics where many modest processors operate like one coordinated machine. So what do you think? Is optical interconnection the missing technology that will unlock the next generation of artificial intelligence? Or is this result too specialized to threaten the GPU-centered data center? Let me know your view in the comments, and subscribe to Eastern Engine for more grounded coverage of the chips, factories, and engineering decisions reshaping the global economy. Because China did not make one chip 100 times stronger. It showed that connecting chips with light can make a smaller system behave as if it were. For years, whenever people talked about the global chip race, the conversation almost always started with NVIDIA. Everyone wanted the fastest AI processors. Everyone wanted the most powerful GPUs. And for a while, it seemed like whoever controlled AI chips would control the future. But something unexpected happened. The biggest bottleneck wasn't the processor anymore. It was memory. Every AI model, every data center, every cloud server, and every supercomputer depends on enormous amounts of DRAM memory just to keep information flowing fast enough. Without it, even the world's most advanced AI chips spend valuable time waiting for data instead of processing it. In other words, the world's most expensive AI chips become dramatically less useful if they don't have enough memory beside them. And that's exactly why one Chinese company has suddenly become one of the most closely watched semiconductor companies on Earth. Its name is Changshin Memory Technologies, better known as CXMT. Until recently, most people outside China had never even heard of it. Now investors are preparing for what could become Asia's biggest IPO of 2026, raising at least 57.9 billion yuan, or roughly $8.6 billion, with the amount potentially climbing to more than 66 billion yuan if additional shares are sold. The company has already become the world's fourth largest DRAM manufacturer, reaching roughly 7.7% global market share in 2025, and plans to use the new capital to expand production and upgrade its technology. That's a remarkable rise for a company that, just a few years ago, barely registered on the global semiconductor map. Even more surprising, this isn't happening during a weak market. It's happening while demand for memory is exploding. Artificial intelligence is changing everything. Training larger AI models requires enormous amounts of memory. Running AI assistants, cloud platforms, recommendation systems, autonomous vehicles, and enterprise software requires even more. Every new AI server installed around the world needs massive quantities of DRAM, turning memory chips into one of the hottest commodities in the semiconductor industry. That surge in demand has pushed memory prices higher and created an opportunity that companies around the world are racing to capture. For decades, the global DRAM market has been controlled by just three companies: Samsung, SK Hynix, and Micron. Together, they built an industry that many believed would remain almost impossible for newcomers to enter. The costs are enormous, the technology is incredibly complex, and catching up can take years. Yet somehow, CXMT has managed to grow from a domestic Chinese project into a company that investors now believe could become one of the semiconductor industry's biggest long-term challengers. That doesn't mean it's already ahead of Samsung or Micron. It still trails the leaders in the most advanced memory technologies, particularly high-bandwidth memory used in cutting-edge AI systems. But its growth has been rapid enough that the established leaders are paying close attention. So, how did a company that almost nobody talked about become one of the biggest stories in the semiconductor world? And why are investors suddenly treating memory chips as one of the most important technologies in the entire AI revolution? Because this story isn't really about one IPO, it's about the next battlefield in the global AI race. To understand why CXMT is suddenly making headlines around the world, you first have to understand something that most people never think about. Memory isn't storage. A lot of people confuse DRAM with SSDs or hard drives, but they're completely different. Storage is where your files stay after you turn your computer off. Memory is where everything happens while your computer is actually working. Think of it like this. If your processor is the brain, then memory is the desk. The larger and faster the desk is, the more information the brain can access instantly. If the desk is too small, the brain spends most of its time reaching into filing cabinets instead of actually working. That's exactly what happens inside AI systems. When ChatGPT answers a question, when an AI generates an image, when a self-driving car recognizes a pedestrian, or when a cloud server handles millions of users, every calculation depends on enormous amounts of memory moving data back and forth at incredible speeds. In fact, today's AI servers don't just use one memory chip. They use dozens, sometimes hundreds. Without enough DRAM, even the most powerful AI processor becomes a bottleneck because it spends too much time waiting for information instead of processing it. That's why companies building AI infrastructure aren't just buying GPUs anymore. They're buying memory as fast as manufacturers can produce it. And demand has become so intense that analysts now describe memory as one of the biggest constraints on AI expansion. Prices have risen sharply, manufacturers are expanding capacity, and AI servers are consuming a growing share of global DRAM production. For decades, this wasn't much of a competition. 3 companies controlled almost everything: Samsung, SK Hynix, and Micron. Together, they built an industry so advanced that many believed nobody else could realistically catch them. Building a modern memory company isn't like opening another electronics factory. It requires billions of dollars, years of research, extremely complex manufacturing, atomic-level precision. Even tiny defects can ruin an entire wafer filled with hundreds of chips. That's why the memory industry has remained one of the most concentrated businesses in the entire technology world. For years, everyone simply assumed those 3 companies would stay on top. Then AI arrived. Almost overnight, demand exploded. Every major technology company suddenly needed more memory. Cloud providers expanded their data centers. Governments invested in AI infrastructure. Tech giants raced to build larger and larger models. And something unexpected happened. Instead of having too much memory on the market, the world suddenly didn't have enough. Rather than flooding the market with cheap chips, manufacturers found themselves trying to keep up with orders. Analysts now expect AI demand to keep memory markets tight well into the coming years, especially for server applications. That's where China saw an opportunity. For years, Beijing invested heavily in building a domestic semiconductor industry. The goal wasn't simply to manufacture more chips, it was to reduce dependence on foreign suppliers. Processors, memory, manufacturing equipment, every part of the supply chain became a strategic priority. Most of those investments happened quietly. While headlines focused on Nvidia, Apple, TSMC, or Samsung, Chinese companies kept expanding behind the scenes. One of them was CXMT. At first, almost nobody outside China paid much attention. It wasn't competing for the world's fastest AI chips. It wasn't making flashy announcements. It was focused on something much less glamorous: DRAM. But as AI transformed the semiconductor industry, that quiet strategy suddenly became incredibly valuable. Because in the AI era, it's no longer enough to build the fastest processor. You also need enough memory to feed it, and that's exactly where China's biggest memory company found its opening. In just a few years, CXMT went from being a relatively unknown domestic manufacturer to becoming the world's 4th largest DRAM supplier, a rise that surprised much of the industry and set the stage for one of the biggest technology IPOs of the year. So how does a company go from being virtually unknown to becoming one of the biggest stories in the semiconductor industry? The answer wasn't one revolutionary invention, it was years of steady expansion. CXMT was founded in 2016 with a simple but ambitious mission: build a domestic DRAM industry in China. At the time, that goal sounded almost impossible. The memory market had already been dominated for decades by Samsung, SK Hynix, and Micron. These companies had spent billions refining their manufacturing processes, shrinking transistors, improving yields, and scaling production to levels few competitors could match. Breaking into that club wasn't supposed to happen. Yet while much of the world's attention remained focused on AI processors, CXMT quietly concentrated on manufacturing. It expanded fabrication plants, hired engineers, improved production yields, introduced newer generations of DRAM, and perhaps most importantly, it kept increasing capacity. That steady approach is exactly why the company now finds itself in a position few people expected. According to Reuters, CXMT has already grown into the world's 4th largest DRAM manufacturer, holding roughly 7.7% of the global market by the end of 2025. That's still well behind the industry's biggest players, but it's a remarkable leap in less than a decade. Now the company is preparing for another massive step. its upcoming IPO isn't just about raising money, it's about accelerating growth. Reports indicate the listing could raise around 58 billion yuan, with the potential to reach more than 66 billion yuan if additional shares are sold. That would make it one of Asia's largest technology offerings this year. The funds are expected to support new production lines, manufacturing upgrades, and continued research into more advanced memory technologies. And that's happening at almost the perfect time, because the memory industry itself is changing. For years, memory chips followed a familiar cycle. Demand would rise, companies would expand production. Eventually, the market would become oversupplied. Prices would collapse. Manufacturers would cut output. Then the cycle for nearly everyone. Microsoft, Amazon, Google, Meta, Alibaba, Tencent, countless cloud providers and enterprise customers are all investing heavily in AI infrastructure. And every one of those systems needs memory, lots of it. That's one reason analysts expect DRAM demand to remain unusually strong, even as manufacturers continue expanding production. AI has become one of the industry's biggest growth drivers. But here's where the story gets even more interesting. Despite its rapid growth, CXMT isn't yet competing head-to-head with Samsung or SK Hynix in the most advanced AI memory. The highest-end AI systems rely heavily on HBM, or high-bandwidth memory. That's the ultra-fast memory sitting next to AI processors like NVIDIA's latest accelerators. HBM is one of the most difficult semiconductor products in the world to manufacture. Samsung, SK Hynix, and Micron still lead that market. CXMT's strength today is mainly in conventional DRAM, not cutting-edge HBM. So why is everyone paying attention? Because history has shown that once a semiconductor company masters one generation of technology, the next generation becomes much easier to pursue. Today's mainstream DRAM can become tomorrow's advanced memory. And if CXMT continues expanding at its current pace, the gap separating it from the industry's established leaders could become much smaller than many people expected. That possibility, not an overnight takeover, is what has investors, competitors, and governments watching so closely. But here's the question everyone is asking. If CXMT is growing this fast, should Samsung and Micron actually be worried? The answer is both yes and no. Let's start with the obvious. No company becomes the world's fourth largest DRAM manufacturer by accident. That alone is enough to make competitors pay attention. CXMT has already proven it can manufacture memory chips at scale, expand production quickly, and win customers inside one of the world's largest technology markets. And that market just happens to be China. Think about that for a moment. China isn't just building more AI. It isn't just building more data centers. It also happens to be one of the world's biggest consumers of semiconductors. Every smartphone, every laptop, every server, every electric vehicle, every AI data center, every industrial robot, they all need memory. If more of that demand can be supplied by a domestic manufacturer, that's a significant shift in itself. Instead of importing every memory chip from overseas, Chinese technology companies now have another supplier growing right at home. That doesn't mean foreign companies disappear overnight. Samsung, SK Hynix, and Micron remain among the most advanced memory manufacturers in the world. But every percentage point of market share matters in an industry worth tens of billions of dollars. Losing even a small portion of future demand can have a noticeable impact over time. And that's exactly why investors are paying so much attention to CXMT's expansion. This isn't just another semiconductor company opening another factory. It's a company increasing production during one of the strongest memory markets in years. Analysts expect AI infrastructure spending to continue driving DRAM demand, with cloud providers investing billions into larger AI clusters and new data centers. That means manufacturers capable of increasing output could benefit from sustained demand rather than a short-lived boom. But there is another reason this story matters. Competition changes everything. For years, the memory market was controlled by only a handful of companies. That limited competition, limited supply, and sometimes contributed to higher prices. If another major manufacturer continues growing, the entire industry becomes more competitive. Customers gain another option. Supply chains become more diversified. Pricing dynamics begin to change. That's why this story reaches far beyond China. It's about how the global semiconductor market itself could evolve. Of course, there are still major challenges ahead. The most profitable part of the AI memory market isn't standard DRAM. It's high-bandwidth memory, or HBM. HBM is the specialized memory used alongside the world's most powerful AI accelerators. Manufacturing it requires extremely advanced packaging technologies, precise engineering, and years of experience. That's where Samsung, SK Hynix, and Micron still hold a significant advantage. In fact, SK Hynix remains the dominant supplier of HBM for many of NVIDIA's flagship AI systems, while Samsung and Micron are also investing heavily to expand their next-generation memory production. So despite all the excitement surrounding CXMT, the company still has important technological milestones to reach before it can compete across every segment of the memory industry. But history shows that semiconductor industries rarely stand still. Today's follower can become tomorrow's challenger, and tomorrow's challenger can eventually become a market leader. Just look at how quickly China's EV industry transformed from following global manufacturers to becoming one of the world's biggest exporters. The semiconductor industry may not move quite as fast, but it's moving. And that's exactly why the world's biggest memory companies aren't ignoring CXMT anymore. Because whether it takes 5 years or 10, the race has clearly entered a new phase. The question is no longer whether China can build a memory industry. It's how big that industry can become. So, is this the beginning of a new chapter in the global semiconductor industry? It certainly looks that way. Just a few years ago, most conversations about AI focused on one thing: processors. Who had the fastest GPU? Who could build the biggest AI model? Who would dominate artificial intelligence? But today, the conversation is much bigger. Because AI isn't powered by processors alone. It needs memory, massive amounts of it. And as AI systems become larger and more powerful, memory is becoming just as important as the chips doing the calculations. That's exactly why companies like CXMT are suddenly attracting so much attention. The company hasn't replaced Samsung, it hasn't overtaken Micron, and it certainly hasn't won the memory race. But it has done something almost as important. It has proven that China is no longer just trying to participate in the global memory industry. It's becoming one of its biggest players, with billions of dollars expected from its IPO, rapidly expanding production, and demand fueled by the AI boom. CXMT is entering the next stage of its growth, at a time when the world needs more memory than ever before. Whether it eventually catches today's industry leaders remains to be seen. Samsung, SK Hynix, and Micron still have enormous technological advantages, especially in the most advanced AI memory, but competition is increasing. And history has shown that industries can change much faster than people expect. Just a decade ago, few believed Chinese electric vehicle companies would challenge the world's biggest automakers. Today, they're competing across global markets. Now, many analysts are wondering whether the memory industry could follow a similar path. One thing is already clear: the next battle in the AI revolution won't be fought only with faster processors. It will also be fought with faster, larger, and more efficient memory. And if current trends continue, CXMT may become one of the companies helping shape that future. The AI race is no longer just about who builds the smartest chip. It's also about who can keep that chip fed with enough memory to unlock its full potential. And that may end up changing the semiconductor industry in ways very few people expected. If you enjoyed this video, don't forget to like, subscribe, and let us know in the comments. Do you think China can eventually challenge Samsung and Micron in the global memory market, or will the current leaders stay on top? For decades, analog computing carried a reputation for being fast but unreliable. Digital computers won because they could repeat the same calculation with predictable precision. Every value became a sequence of zeros and ones. Analog machines worked differently. They represented numbers with continuously changing physical quantities such as voltage, current, pressure, or resistance. That allowed them to solve some equations almost instantly, but tiny errors accumulated. Components drifted. Precision collapsed as problems became larger. Researchers at Peking University now say they have solved much of that problem. Their team built a foundry-made analog matrix solver using resistive random access memory, or RRAM. The system experimentally solved 16 by 16 real-valued matrix inversion problems at 24-bit fixed-point precision, which the researchers describe as comparable to FP32 digital computing. In massive MIMO signal detection, it reached digital-level accuracy after only 3 refinement cycles. And their benchmarking suggests that, with further circuit improvements, this architecture could deliver up to 1,000 times higher throughput and nearly 100 times better energy efficiency than leading digital processors at the same precision. That does not mean this prototype can run every AI model 1,000 times faster than an NVIDIA H100. It cannot replace a general-purpose GPU. The result applies to specialized matrix equation workloads, and the largest advantage is partly projected rather than fully measured in production hardware. Analog computing has always promised extraordinary speed. The missing piece was precision. Why digital computers dominated. A digital computer treats information as discrete values. At the lowest level, a transistor is interpreted as on or off. Software then performs arithmetic through carefully sequenced logic operations. Small electrical fluctuations usually do not change a 0 into a 1. Digital systems can use error correction, repeat operations, and store exact copies of data. Analog systems trade some of that certainty for direct physical computation. Imagine solving a mathematical equation by building an electrical circuit whose voltages naturally settle into the answer. The circuit does not need to execute millions of separate instructions. The physics performs the calculation as the signals move through the hardware. But real components are imperfect. Resistance changes with temperature. Amplifiers introduce noise. Manufacturing creates small differences from one device to another. The answer may be close, but not exact enough for scientific computing, communications, or modern AI. The Peking University team attacked the problem by separating speed from accuracy. One analog circuit produces a fast, approximate answer. A second analog operation measures the remaining error and corrects it. The system repeats this process until the solution reaches the required precision. What RAM actually does. The heart of the design is resistive random access memory. An RRAM cell stores information by changing the electrical resistance of a material between two electrodes. A low resistance state may represent one value. A higher resistance state may represent another. In this experiment, each cell supported 8 stable conductance levels, equivalent to 3 bits of information. The researchers used a 1 megabit RRAM chip for high-precision matrix vector multiplication and a smaller 8x8 RRAM array for low-precision matrix inversion. Both were fabricated using a commercial 40-nanometer CMOS platform. This was not a hand-built device assembled from exotic laboratory materials. The chips were produced through a foundry-compatible process using 1 transistor, 1 resistor memory cells. An RRAM array can behave like a physical matrix. Each cell's conductance represents one matrix element. Input voltages represent a vector. When those voltages pass through the array, the resulting currents naturally combine according to Ohm's law and Kirchhoff's current law. The array performs matrix vector multiplication through its physical behavior. A digital processor would normally load data from memory, execute many multiplication and addition instructions, then write the result back. The RRAM array stores the values and performs the calculation in the same location. That reduces data movement and avoids much of the conventional von Neumann bottleneck. The matrix problem. Matrix equations appear almost everywhere in advanced computing. Wireless base stations solve them to separate overlapping signals from many antennas. Some neural network training methods also depend on matrix inversion or related linear system solving. A common form is A times X equals B. The matrix A and vector B are known. Digital methods solve this accurately, but the cost grows quickly as the matrix becomes larger. An analog circuit can produce a solution directly by placing the resistive array inside a closed feedback loop with operational amplifiers. However, the first answer is only approximate. The challenge is improving that result without handing the important calculation back to a digital processor. Earlier hybrid systems often used analog hardware for a rough estimate and digital floating point hardware for the precise correction. The Chinese team kept both major operations in the analog domain. How the two-stage solver works. The first stage performs low-precision analog inversion. Because the RRAM devices and supporting circuits are not perfectly accurate, the result contains an error. The second stage performs high-precision analog matrix vector multiplication. It calculates how far the approximate answer is from satisfying the original equation. That difference is called the residual. The solver then feeds the residual back into the low-precision inversion circuit to produce a correction. Each cycle moves the solution closer to the target. The researchers reported that precision improved by roughly 3 bits during each cycle, reflecting the 3-bit conductance levels in the RRAM cells. A 24-bit 4x4 real-valued matrix reached the maximum target precision after 9 cycles. Larger complex-valued problems generally reach the same precision within about 10 cycles. This is the central idea. The fast analog inversion does not need to be perfect. It only needs to be good enough that repeated analog correction converges toward a precise answer. The design accepts analog error, measures it, and then removes it. That is very different from pretending the hardware is naturally exact. How bit slicing builds precision. One RRAM cell stores only 3 bits, but the complete system reaches 24-bit precision. It does this through bit slicing. A high-precision matrix value is divided into several lower-precision pieces. Each piece represents a different group of bits and is mapped into a separate RRAM array. The arrays perform low-precision calculations in parallel or sequence. Their partial outputs are then shifted according to their significance and added together. It is similar to separating a large decimal number into thousands, hundreds, tens, and units. Each part is easier to represent. Combining the weighted parts reconstructs the original value. Bit slicing was already useful for analog matrix vector multiplication. The harder problem was applying high precision to matrix inversion, where the same simple distributive rules do not transfer cleanly. The researchers solved this by keeping inversion low precision, while using bit-sliced matrix vector multiplication to calculate the correction accurately. Block AMC makes the design scalable. A physical RRAM array cannot grow without limit. Large arrays suffer from wire resistance, routing complexity, stronger currents, parasitic effects, and amplified noise. The team therefore used a block-based algorithm called Block AMC. A larger matrix is divided into smaller submatrices. Different RRAM arrays store different blocks. The system performs a sequence of inversion and multiplication operations on those blocks, then combines the intermediate results. Using this approach, the researchers experimentally solved a 16 by 16 real-valued matrix inversion problem with 24-bit fixed-point precision. The relative error reached roughly 1 part in 10 million after 10 cycles. 16 by 16 may sound small compared with giant AI models, but matrix inversion is more difficult to map into analog hardware than ordinary multiplication. The point was to prove that a precise analog solver could scale beyond one tiny hardwired circuit. The block method also allows future systems to use multiple moderate-sized arrays instead of depending on one enormous analog network. The massive MIMO test. The researchers demonstrated the solver on wireless signal detection. Massive MIMO uses many antennas at a base station to communicate with several devices at once. The received signals overlap. The base station must solve matrix equations to separate the different users and recover the transmitted information. The experiment modeled systems using higher-order 256 QAM modulation, which packs 8 bits into each transmitted symbol. That demands far more precision than earlier analog demonstrations limited to simpler modulation. The researchers transmitted a binarized image of the Peking University emblem through the modeled wireless channel. Their analog solver recovered the signal with bit error performance comparable to FP32 digital processing. For a 128 by 8 system, the detector reached comparable accuracy after only 3 iterative cycles. This matters because it connects the architecture to a real workload rather than only random laboratory matrices. Wireless communication, especially future 5G advanced and 6G systems, may require repeated matrix solving with strict limits on latency and energy. Where the 1000x claim comes from, the 1000 times figure needs careful explanation. The prototype did not directly defeat an NVIDIA H100 by 1000 times in a complete application. The researchers benchmarked their analog architecture against state-of-the-art digital processors at comparable precision. Their model considered matrix size, array dimensions, converter overhead, amplifier speed, and block processing requirements. At moderate array sizes, the analog design already showed advantages for specific matrix solving tasks. For larger optimized arrays and faster operational amplifiers, the projected throughput advantage could approach 3 orders of magnitude. Energy efficiency could improve by nearly 2 orders of magnitude. The paper also notes that Block AMC reduces the advantage as matrices become larger because more stages and intermediate operations are required. Even then, the architecture remained ahead in the researchers' comparisons. The maximum result depends on better supporting circuits and dedicated integration. So the honest statement is that the demonstrated architecture could reach 1,000 times higher throughput for precise matrix equation solving. It is not evidence that an analog chip will make every CUDA workload 1,000 times faster. Why this could matter for AI? Modern AI depends heavily on matrix operations, but not every matrix operation is the same. Neural network inference is dominated by matrix multiplication. This chip focuses on matrix inversion and solving linear systems. Those operations appear in optimization, scientific machine learning, signal processing, and some second-order training methods. An analog solver could become a specialist accelerator. A conventional CPU or GPU would manage the overall program. When the workload reaches a suitable matrix equation, the system could send that task to the RAM solver. The analog hardware would produce the answer quickly and efficiently, then return it to the digital processor. This is more realistic than expecting analog computing to replace digital machines completely. Digital hardware remains better for control flow, memory management, software compatibility, and exact general-purpose operations. Analog hardware may win by handling the narrow calculations where physics offers a shortcut. The honest catch. Several engineering challenges remain. The low-precision inversion circuit still uses external components, including operational amplifiers, data converters, switches, and a microcontroller. The larger, high-precision RAM array was integrated, but the complete solver was not one compact commercial chip. Scaling the inversion array beyond the demonstrated size requires dedicated design and fabrication. Larger arrays produce stronger currents and more complicated routing. Noise, wire resistance, device defects, and temperature variation must remain controlled. The system also needs programming and verification procedures to place every RAM cell into the correct conductance state. Converters and amplifiers consume area and energy, and commercial software would need tools that identify suitable equations and map them efficiently onto the hardware. It does not prove that mass production will be easy. My take is that the breakthrough is not simply bringing analog computing back. It is making analog error part of the algorithm. The first circuit is allowed to be imperfect. The second measures that imperfection. Repeated correction turns a rough physical answer into one approaching digital precision. That is a powerful design philosophy. Future computers may not choose between analog and digital. They may combine both. Digital processors will coordinate the system and preserve programmability. Analog accelerators will solve selected equations using currents, resistance, and feedback, instead of long sequences of instructions. The 1,000 times estimate may shrink once complete commercial overhead is included, or better integration may allow the architecture to approach its projected advantage. Either way, this work moves analog matrix solving from a low-precision curiosity toward a credible specialist technology. So what do you think? Will analog accelerators become essential for AI, science, and 6G? Or will manufacturing variation and software complexity keep GPUs in control? Let me know your view in the comments. And subscribe to Eastern Engine for more grounded coverage of the chips, materials, and engineering breakthroughs reshaping computing. Because China has not built a universal NVIDIA replacement, but it may have solved the precision problem that kept analog computing out of the modern chip era. For 60 years, the entire technology industry has obeyed a single rule. It was never a law of government, never a law of physics really. It was a prediction made by a man named Gordon Moore in 1965 that quietly became the heartbeat of the modern world. Every smartphone, every laptop, every data center, every AI model you've ever touched exists because of it. The rule was simple. Every 2 years, you make the transistors on a chip smaller, you pack twice as many of them onto the same sliver of silicon, and everything gets faster, smaller, smaller. For 6 decades, that one word drove a $1 trillion industry forward. And on May 25, 2026, on a stage in Shanghai, a woman the Chinese tech world calls the chip queen stood up and told a room full of the world's leading engineers that the rule is finished, done, that the future of computing would not be won by making things smaller, and that her company had spent the last 6 years quietly proving it, building 381 chips in total secrecy to back up the claim. Her name is He-Ting Bo. The company is Huawei, and what she proposed isn't a new chip, it's a new rule to replace the one that's governed all of technology since before the moon landing. Now, is this a genuine breakthrough, or a desperate company spinning a limitation into a headline? That's the real question. And by the end of this video, you'll be able to answer it yourself. Let's get into it. To understand why this matters, you have to understand why Moore's law was running out of road in the first place. Because this part isn't propaganda, it's physics and the whole industry agrees on it. Picture a transistor as a tiny switch. Moore's law was the promise that engineers would keep shrinking that switch, year after year, fitting more and more of them into the same space. In 1971, a leading chip had a few thousand transistors. Today's most advanced processors have tens of billions. That staggering journey is Moore's law in action. But here's the problem. Transistors are now so small, they're measured in nanometers. And a few nanometers is a span of just a handful of atoms. You cannot shrink something forever. Eventually, you hit a wall where the switch is so tiny that electrons start leaking through it even when it's supposed to be off, where heat becomes unmanageable, and where the machines needed to etch these features cost hundreds of millions of dollars each. The closer you get to the size of individual atoms, the more every further step costs, and the less you get back. The returns don't just shrink, they collapse. The entire industry has known this reckoning was coming for years. Even Moore's own law was, in a sense, always going to expire. You can't keep having your way down to nothing. The question was never whether the smaller is better era would end. The question was what comes after it, and who would define the rule that replaced it. That's the door Huawei just walked through, and the reason Huawei walked through it first has a lot to do with something that was supposed to cripple them. Here's the twist that makes this story genuinely fascinating. Huawei didn't develop this new approach purely out of scientific curiosity. They developed it because they had no choice. For years, Huawei has been cut off from the most advanced chip-making machines on Earth. Specifically, the extreme ultraviolet lithography systems built by a single Dutch company, the only tools capable of etching the very smallest transistors. Those machines are the engine of Moore's law. No access to the machine, no way to keep shrinking. So while the rest of the industry kept racing down the shrinking path, the path that requires those banned machines, Huawei was locked out of the race entirely. Most observers assumed that meant Huawei would simply fall further and further behind, permanently. Instead, being locked out forced a different question. If you can't win by making transistors smaller, can you win some other way? Can you get more performance out of chips you're already able to build, without needing the forbidden machine at all? That question is the seed of everything. Huawei's chairman has even pointedly thanked the export restrictions for supercharging China's semiconductor industry. And as strange as that sounds, this is exactly what he meant. The wall didn't stop them. It redirected them down a road nobody else was seriously exploring, because nobody else was desperate enough to need it. And what they found at the end of that road is a genuinely different way of thinking about what a chip even is. So what actually is this new rule? Let me explain it in a way that sticks, because the core idea is beautiful in its simplicity. Huawei calls it the Tau scaling law. Tau, written as the Greek letter tau, is a symbol engineers use to represent time. Specifically, the time it takes for a signal to travel from one part of a chip to another, and that single shift, from measuring size to measuring time, is the whole revolution. Think of a chip as a city. Moore's law was obsessed with one thing: making the buildings smaller so you could cram more of them into the city. Huawei's Tau scaling law asks a completely different question. Forget the size of the buildings. How fast can a message get from one side of the city to the other? Because here's the secret the industry doesn't advertise. In a modern chip, a huge amount of time and energy isn't spent on the transistors switching. It's spent on signals traveling, crawling down long wires from one part of the chip to another. Shrinking transistors does nothing to fix that. You can have the smallest, fastest switches in the world, but if the messages between them have to travel a long way, the whole system waits. Huawei's insight: stop fixating on the switches, start attacking the distance. Make the signals travel less, arrive faster, and the entire chip speeds up, without shrinking a single transistor, and without ever touching the banned machine. That's the rule. Not smaller, faster. And to make it real, they built something that sounds like science fiction, but is already rolling off production lines. The technology that turns this idea into reality is called logic folding, and the name is the perfect description of what it does. Imagine a city again, but this one is flat. Everything spread out across the ground, connected by long roads. Everything you do online is being watched. Your provider, advertisers, even governments. NordVPN encrypts your connection, hides your location, and unlocks the open internet from anywhere. Grab the deal, link in the description. Now imagine you could fold that city upward, stacking neighborhoods directly on top of each other, so the journey between them shrinks from miles to inches. That's logic folding. Instead of laying circuits out flat across a single layer of silicon, Huawei folds them into vertically stacked active layers, building up instead of out. The payoff is enormous. By stacking circuits vertically, the wires connecting them get dramatically shorter. Signals travel less distance, so they arrive faster. That's the time, the tau, being compressed. And as a bonus, folding the circuits upward also lets you pack more of them into the same footprint. Huawei claims this approach can deliver up to 55% higher transistor density and significantly better power efficiency, all at the same manufacturing process, with no need for the smaller, forbidden node. Read that again, because it's the heart of why this matters. More density, more performance, without shrinking the transistors, and without the machine they're banned from buying. If it works the way Huawei claims, it's a way to keep advancing chips that completely sidesteps the chokehold the restrictions were designed to create. And here's the detail that makes this more than a slideshow promise. Huawei says this isn't theoretical. Over the past 6 years, the company quietly designed and mass-produced 381 chips built on these principles, across smartphones, AI processors, and more. The first chips to fully adopt the logic folding architecture will be Huawei's new flagship Kirin processors, launching in the autumn of 2026. This isn't a lab demo. It's a production reality that the rest of the industry only just learned existed. Now, here's the claim that made headlines around the world, and the part where I need to be straight with you. Huawei says that by 2031, chips designed with this approach could reach a transistor density equivalent to a 1.4 nanometer process. To understand why that's a bombshell, the most advanced chips being mass-produced today by the world's leading foundry sit at the 2 nanometer level. A 1.4 nanometer class density would put Huawei's designs ahead of where the global frontier is right now, achieved without the machines everyone assumed were absolutely required to get there. If that lands, it doesn't just close China's chip gap, it potentially erases it. But, and this is the honest catch you won't get from a hype video, there are real reasons for skepticism, and you should hold both things in your head at once. First, 1.4 nanometer equivalent is a claim about density equivalence, not the same thing as actually manufacturing a true 1.4 nanometer chip. It's a clever reframing, and critics argue it blurs an important line. Second, Huawei did not release independent performance data to back the headline numbers. We largely have the company's word. And third, stacking circuits vertically creates its own brutal problems, especially heat. When you fold a city upward, you also concentrate all its heat into a smaller space, and managing that is genuinely hard. So is this a real breakthrough, or a desperate company dressing up a limitation? The most honest answer is probably both. It's clearly born of necessity. Huawei built this because it was cornered. But born of necessity and genuine breakthrough are not opposites. Some of the most important leaps in history came from exactly that pressure. The 6 years of work and 381 real, shipped chips suggest there's substance here, not just a press release. The grand 2031 target is the part to watch with healthy skepticism. Step back, and here's what makes this a genuine turning point, rather than just another product announcement. For 60 years, the rule that governed chips was written by the West, followed by the West, and led by the West. Moore worked at the company that became Intel. The entire framework of progress, smaller, 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 was an American idea that the whole world adopted. Whoever defines the rules of a technology tends to lead that technology. What Huawei just attempted is not merely to catch up within the old rules, it's to rewrite the rules themselves, to propose a new definition of progress that happens to play directly to China's strengths and around its weaknesses. He Tingbo framed it not as a Huawei product but as a new guiding principle for the entire industry, openly inviting engineers worldwide to build on it. That's not the language of a company selling a chip. That's the language of a company trying to set the agenda for everyone else. And whether or not the 2031 target is hit precisely, the deeper shift is already real. The era where progress meant one thing, shrinking, is genuinely ending, for everyone, by the laws of physics. Something has to come next. And for the first time in the history of computing, one of the most serious proposals for what comes next was written in Shanghai, not Silicon Valley. There's one more detail worth sitting with. He Tingbo ended her keynote with a quiet promise. Before winter 2026, we will bring the surprise, a big leap ahead. Whatever that surprise is, the industry is now watching China to find out. And that, more than any single number, is the real story. The watching has reversed direction. Here's my honest opinion. I think the smartest way to see this is to refuse both of the easy takes. The people screaming, Huawei just destroyed Moore's Law and humiliated the West, are getting ahead of the evidence. The headline numbers are unverified, the 2031 target is far off, and the heat problems are real. But the people waving it away as just propaganda from a cornered company are missing something just as important. 6 years of secret work and 381 mass-produced chips is not a press release. It's a track record. What genuinely fascinates me is the pattern. Glass substrates, diamond cooling, and now a wholesale attempt to redefine the rule of chip progress. Over and over, the same story repeats. A restriction designed to stop China instead forces China down a road no one else was exploring, and sometimes that road leads somewhere new. The wall meant to contain them keeps functioning as a map. I don't think that's a coincidence anymore. I think it's becoming the defining dynamic of this entire era of technology. Moore's Law was always going to end. The only real question was who would write the sentence that comes after it. The fact that Huawei is even in the running to write that sentence, that's the thing nobody saw coming 5 years ago. Here's my question for you, and I want your honest answer, because this one genuinely splits people. When you cut a competitor off from your best technology, are you protecting your lead, or are you forcing them to invent something better that you'll eventually have to compete with? Huawei's own chairman thanked the restrictions for making his company stronger. Was cutting China off a brilliant move, or the biggest strategic mistake of the decade? Drop your real take in the comments. I read them all. If you want to keep following this, the breakthroughs, the rule changes, the moves nobody saw coming until it was too late, subscribe to Eastern Engine and turn on notifications. Chips, materials, energy, the whole foundation of modern technology is being rewritten right now, and we break it down before the rest of the world catches up. Thanks for watching. I'll see you in the next one. Picture the most valuable company in the history of the world being told it's no longer welcome in the largest technology market on Earth. Not fined, not warned. Shown the door. That's what just happened to NVIDIA in China, the company whose chips power virtually every artificial intelligence system on the planet. The company that became worth more than the entire economies of most countries has just been pushed out of China by the Chinese government itself. Beijing has effectively told its biggest technology giants, the Alibabas and ByteDances and Tencents of the world, to stop buying NVIDIA. Cancel the orders, sell off whatever inventory is left, and from now on, you buy Chinese. And here's the part that makes this almost poetic. For 3 years, the story was the exact reverse. It was the United States slamming doors on China, banning the sale of the best NVIDIA chips, trying to choke off China's access to the silicon that powers modern AI. The whole world watched America wield NVIDIA like a weapon. And now, in a twist almost nobody saw coming, China has taken that same weapon, turned it around, and pointed it the other way. We don't want them anymore, Beijing is essentially saying. We'll build our own. It is one of the most dramatic reversals in the entire technology war. And this is exactly the kind of story where the headline and the reality pull in different directions. The truth underneath is far stranger and more interesting than China bans NVIDIA at the end. There's a secret dependency Beijing isn't advertising. There's a question of whether this is confidence or a calculated bluff. And there's a real chance this backfires spectacularly. I'm going to walk you through all of it. By the end, you'll understand what actually happened, why China would reject the best chips on Earth, who's stepping in to replace them, and whether this is a masterstroke or a massive gamble. Let's get into it. To feel how strange this moment is, you have to rewind and remember how we got here. Because the whole thing reads like a story with a twist ending. Act 1 belonged entirely to America. Worried that advanced AI could hand China a military and economic edge, the United States rolled out wave after wave of export controls. The crown jewels of NVIDIA's lineup, the chips that train the world's most powerful AI, were forbidden from sale to Chinese buyers. Washington even leaned on NVIDIA to create deliberately weakened, China-only versions of its chips, throttled down to stay just inside the legal lines. The message was unmistakable. You may buy our scraps, not our best. For a while, China took it. Chinese companies bought the watered-down chips because something was better than nothing. They grumbled, they stockpiled, they waited for the politics to shift. Everyone assumed that the moment America loosened the rules, Chinese firms would come sprinting back to NVIDIA with open wallets. Then came the twist. In a surprise move, the US actually approved the export of a more capable NVIDIA chip, the H200, to China. The door cracked back open. And this is the moment everyone expected China to pour through it. Instead, Beijing slammed it shut from its own side. China's government turned around and told its companies, don't buy them. Don't buy the H200. Don't buy the consumer cards either. We're not interested. According to reporting from the Financial Times, Chinese firms that had even placed orders were told they couldn't follow through. American officials confirmed the bizarre situation out loud. The US Commerce Secretary publicly acknowledged that NVIDIA still hadn't sold the chips because China itself was blocking the imports. Let that sink in. America spent years trying to stop China from buying these chips. Now America is willing to sell, and China is refusing to buy. The jailer unlocked the cell and the prisoner said, "No thanks, I built my own door." That is the reversal. And it raises the obvious, almost dizzying question. Why on earth would China reject the very technology it spent years fighting to get? It sounds insane at first. Turning down the most advanced AI chips on the market is like a thirsty traveler refusing a glass of water. But once you understand Beijing's reasoning, it stops looking crazy and starts looking like cold, deliberate strategy. There are three forces driving it, and they stack on top of each other. The first is the hard lesson of dependence. China learned something painful over the last few years. Relying on a foreign supplier for a critical technology is a leash. and the other end of that leash is held by your rival. One day, the chips flow. The next day, a politician in Washington signs a paper and they stop. You can't build the future of your entire economy on a supply line someone else can cut whenever they please. From Beijing's view, every NVIDIA chip bought is a vote of dependence, and every Chinese chip bought instead is a step toward never being strangled again. Even if the domestic chip is worse today, it's yours. Nobody can take it away. The second force is more cold-blooded: leverage. By refusing to buy even the chips America is now willing to sell, China sends a loud, deliberate signal. We don't need you. Whether or suddenly removed. Imagine being a young company trying to sell soda in a country where Coca-Cola has just been ordered to leave. Overnight, every thirsty customer is yours. That's what China just did for its domestic chip industry. It didn't just block a rival, it gifted its own companies the single largest AI market on the planet, with no NVIDIA in the room. 3 motives: security, leverage, and protectionism, pointing in the same direction. But a strategy is only as good as the alternative behind it. Kicking out NVIDIA only makes sense if someone at home can actually fill the hole. So who's stepping up? This is where the story gets genuinely interesting, because China isn't betting on one savior. It's unleashing an entire roster of domestic challengers, each circling the space NVIDIA left behind. At the front of the pack, unmistakably, is Huawei. If you've watched this channel, you know Huawei has become the central character in China's chip saga. The company America sanctioned hardest, which somehow keeps clawing its way forward. Its Ascend line of AI chips is now positioned as the literal backbone of China's state-backed AI ambitions. And Huawei has a clever answer to a real weakness. Individually, its chips still can't match NVIDIA's best one-on-one. So instead of fighting that battle, Huawei changed the rules. It built what it calls supernodes, systems that lash thousands of its own chips together into a single massive cluster. The logic is blunt but effective. If one of your chips is weaker, use far more of them, wired together so tightly they act as one brain. Huawei's deputy chairman openly admitted a single Ascend can't beat a single NVIDIA chip, then claimed its supernode clusters are the most powerful in the world anyway. Brute force, engineered cleverly to turn a weakness into a non-issue. But Huawei is far from alone, and that's the part most coverage misses. There's a whole ecosystem rising behind it. Cambricon, a Chinese AI chip specialist, posted a revenue surge of over 4,000% in a recent period. Not a typo, 4,000, as orders flooded in from companies scrambling for NVIDIA alternatives. Baidu has its own Kunlun chips, already powering a training system built from tens of thousands of processors. Alibaba's chip division, T-Head, is designing its own silicon. So is Tencent. The giants that used to be NVIDIA's biggest Chinese customers are now, one by one, becoming NVIDIA's replacements, building in-house the very thing they used to import. And there's a deeper layer still, one that hints at how far China's ambitions really reach. Some of these companies, like Alibaba's T-Head, are building their chips on something called RISC-V, an open, free chip architecture that anyone can use, completely outside the control of any single Western company. It's a quiet but profound move. It's not just about replacing NVIDIA's chips. It's about escaping the foundations those chips are built on entirely, owning not just the engine, but the very blueprint of the engine. China isn't trying to swap one dependency for another. It's trying to own the whole stack, top to bottom. So the replacements are real, numerous, and backed by the full weight of the state, which makes it sound like a done deal. It is not. And this is where I have to be completely honest with you. Here's the part the triumphant headlines leave out. And it's the most important section in this whole video, so stay with me. Despite the ban, despite the bravado, despite the "we don't need you" messaging, China's AI industry is still, right now, deeply and quietly dependent on NVIDIA. Not a little, enormously. Look past the announcements at the actual numbers. By credible estimates, somewhere around 75% of the chips training AI models inside Chinese data centers still run on NVIDIA's technology. 3 out of every 4. The company has shipped more than 1 million of its export-compliant chips into China since late 2024, reportedly outpacing its closest domestic rival's shipments by something like 5-to-1. So even as Beijing publicly shoves NVIDIA out the front door, an enormous amount of NVIDIA silicon is already humming away inside the country, doing the heaviest lifting in Chinese AI. And there's a crucial technical reason for this, one we've touched on before. There are 2 halves to building an AI: training, the brutally demanding process of creating the model's intelligence, and inference, the lighter job of running it for users. China's homegrown chips have become genuinely competitive at inference. but for the hardest, most punishing work, frontier training, they still lag. As one analyst put it bluntly, Chinese companies can keep the lights on with domestic chips, but they can only sustain truly frontier-level progress with continued access to NVIDIA hardware. The domestic chips can run the house, they can't yet build the mansion. So the honest picture is full of tension. China is banning the very chips it secretly still leans on. It's projecting total independence, while 3/4 of its most important AI work quietly depends on the rival it's pushing out. That's not a contradiction born of confusion. It's a high-stakes bet. Beijing is essentially saying, we will force ourselves to need you less by cutting you off now, and trust that the pressure makes our own industry strong enough, fast enough, to survive the gap. It's ripping off the band-aid before the wound has fully healed, gambling that the shock accelerates the cure. That's a bold, genuinely risky move, and it might just work, because, strangely enough, it's worked before. Here's the thing that should make anyone betting against China pause. We have seen this exact movie several times already, and it keeps ending the same way. Think back over the stories that keep surfacing in this space. Cut off from the world's best chip-making machines, China was told it could never make advanced chips, then it found a way to manufacture them anyway, using older equipment and sheer engineering stubbornness. Told it couldn't build a frontier AI model without American software, a Chinese lab went and built one that runs without it. Told its supercomputers would stall without forbidden processors, China built a world-class one on entirely different chips. Over and over, the same shape. A wall goes up to contain China, and instead of stopping, China is forced to build the very thing the wall was meant to deny it, and sometimes ends up with an independent capability it would never have bothered to create if the wall had never existed. This is the deep irony at the center of the entire technology war, and it's worth saying plainly. Restrictions meant to keep China dependent have, again and again, become the exact pressure that forced China toward independence. The leash, pulled too hard, taught the animal to live without one. Necessity didn't just inspire invention here, it practically mandated it, funded it, and gave it a guaranteed market. The NVIDIA ban is simply the boldest version of this pattern yet. Instead of waiting for America to cut the cord, China is cutting it itself, on its own timeline, deliberately, to force its domestic industry to grow up faster. It's a country betting that self-inflicted pressure now is better than foreign-controlled vulnerability later. And given the track record, given how many times the impossible wall has turned into a merely expensive speed bump, betting confidently against China's ability to adapt has been a losing position for a while now. But, and I promised you honesty, confidence based on a pattern is not the same as certainty. This bet is bigger than the others, and the ways it could go wrong are real. Let me give you the other side, because no honest analysis skips it. The most obvious danger is the training gap. If Chinese chips genuinely can't handle frontier-level AI training yet, and the evidence says they largely can't, then cutting off NVIDIA too aggressively could leave Chinese AI labs starved of the horsepower they need to keep pace with the absolute cutting edge in America. While a US lab trains its next giant model on a mountain of NVIDIA's best, a Chinese lab might be stuck doing the same job slower, more expensively, on chips that aren't quite there. In a race measured in months, a self-imposed handicap is a serious risk. China could win independence and lose the speed race at the same time. The second danger is that this is partly a bluff that could get called. If a big slice of the motivation here is negotiating leverage, projecting we don't need you to win a better trade deal, then it only works as long as the bluff holds. If China's domestic chips stumble, if the supernodes can't scale, if the training gap widens instead of closing, then the we don't need NVIDIA posture collapses, and Beijing is left having rejected chips it actually needed purely for a power play that didn't pay off. And there's a quieter problem. Even China's homegrown champions still aren't fully homegrown. Some of the most advanced domestic chips still rely, somewhere in the supply chain, on manufacturing tools and processes that trace back to foreign technology China doesn't yet fully control. True, total independence, every layer, every machine, every line of code domestic, is still a goal, not a finished reality. Declaring independence and achieving independence are different things, and the gap between them is where this bet could unravel. So this is genuinely a gamble. A bold, calculated, pattern-backed gamble, but a gamble all the same. It could accelerate China's chip industry by years, or it could leave it exposed at the worst possible moment. Probably, the truth will land somewhere in between, and we'll spend the next 2 years watching which way it tips. Here's my honest opinion. I think both of the easy reactions to this miss the point, and the interesting truth lives in the friction between them. The triumphant take, China just crushed Nvidia and declared total independence, is getting way ahead of reality, because 3/4 of China's serious AI work still quietly runs on Nvidia, and the hardest training problems remain unsolved at home. Anyone telling you Nvidia is finished in China is ignoring the silicon already humming inside Chinese data centers right now. But the dismissive take, "It's just posturing, China still needs Nvidia, ignore it," is the bigger mistake, and it's the one that's been wrong over and over, because it focuses on the gap that exists today and ignores the direction everything is moving. The single most revealing fact in this entire story isn't a chip spec or a market share number. It's this: when America finally offered to sell, China chose to refuse. That choice tells you Beijing has decided, at the highest level, that the future is worth a painful present, that it would rather struggle now on its own chips than stay comfortable on someone else's. Countries don't make that choice from weakness. They make it from a cold, long-term confidence that the gap is closable. And that's what makes this the most fascinating move in the whole technology war so far. It's not a country reacting to a wall someone built around it. It's a country building its own wall, on purpose, to force itself to become the thing it wants to be. That's either visionary or reckless, and honestly it might be both at once. The pattern says don't bet against it. Common sense says the risk is real. The only thing I'm certain of is that we're watching one of the boldest industrial gambles of our lifetime play out in real time. So here's my question for you, and I really want your honest answer. Was banning Nvidia a brilliant power move, forcing China's industry to grow up fast and breaking its dependence for good, or a reckless gamble that could leave Chinese AI stuck in the slow lane right when the race is at its most intense? Did China just free itself, or just shoot itself in the foot? Drop your real take in the comments. I read every single one, and I have a feeling this one is going to spark a serious debate down there. If you want to keep following this, the bans, the breakthroughs, the bold gambles the rest of the world keeps underestimating until it's too late, subscribe to Eastern Engine and hit the notification bell. Chips, AI, the entire foundation of the modern world is being rewritten right now, and we break it all down clearly and honestly before the mainstream catches on. Thanks for watching. I'll see you in the next one. For nearly 50 years, there was a number that every fusion scientist on Earth treated as a law of nature. It wasn't written into the universe like gravity or the speed of light. It was a wall discovered by experiment, a hard ceiling that showed up again and again, in reactor after reactor, country after country. Push your fusion fuel past this particular density, and the whole thing falls apart. The superheated plasma, the star stuff you're trying to control, destabilizes, tears itself apart, and the reaction collapses, every time. Scientists gave it a name, the green-walled limit, and it was one of the great frustrating barriers standing between humanity and the dream of limitless clean energy. Because to make fusion actually produce more power than it consumes, you need that fuel, dense and hot and stable all at once, and the green-walled limit said you couldn't have all three. Then, on the first day of 2026, a team of Chinese scientists running a reactor they nicknamed the Artificial Sun did something the textbooks said shouldn't be possible. They blew straight past that limit, not by a little, but by as much as 65%, and the plasma didn't collapse. It stayed stable. It held. A wall that stood for nearly half a century just developed a door. Now, and you know this is coming if you watch this channel, there is crucial context here, and I'm going to give you all of it, honestly, including why this is not the free energy by next year miracle some headlines are selling. But the real story, the true one, is arguably more important than the hype. By the end of this video, you'll understand what fusion actually is, why this specific limit terrified scientists for 50 years, exactly how China broke it, and what it really means for the future of energy on this planet. Let's get into it. Let's start with the basics, because the nickname is doing a lot of work, and it's worth understanding why it's earned. Look up at the sun. Every bit of warmth and light pouring off it comes from one process: fusion. Deep in the sun's core, under crushing pressure and unimaginable heat, hydrogen atoms are smashed together so hard that they merge, they fuse into helium. And every time they do, a tiny bit of mass gets converted into an enormous burst of energy. That's it. That's what powers every star in the sky. It is, quite literally, the engine of the universe. Now imagine bottling that. Imagine building a machine on Earth that recreates the heart of a star, that fuses atoms the same way the sun does, and harnesses the energy that pours out. That's the dream of fusion power, and the prize is almost too good to believe. The fuel is essentially a form of hydrogen you can pull from seawater, It produces no carbon emissions. It can't melt down like a conventional nuclear plant. It generates only tiny amounts of short-lived waste compared to the fission reactors we use today. A single glass of fusion fuel could, in theory, hold the energy of barrels and barrels of oil. Clean, safe, and very nearly limitless. That's why nations have poured tens of billions of dollars into chasing it for over half a century. It's arguably the most valuable engineering goal in human history. The machine China uses to chase it is called EAST, the Experimental Advanced Superconducting Tokamak, located in Hefei. A tokamak is a specific design, a giant donut-shaped chamber wrapped in incredibly powerful magnets. Here's the central problem it solves. To make atoms fuse on Earth, you have to heat your hydrogen fuel to insane temperatures. EAST runs its plasma well beyond 100 million degrees Celsius, which is several times hotter than the core of the actual sun. And here's the obvious question. What do you build a container out of that can hold something hotter than the center of a star? The answer is nothing. No material on Earth can touch it. So the tokamak doesn't use a physical container for the hot part. It uses a cage made of pure magnetic force, suspending that star-hot plasma in midair so it never touches the walls. That is the artificial sun, a man-made knot of magnetic fields holding a sliver of star, glowing at 100 million degrees in the middle of a steel donut in eastern China. And the limit they just broke is all about how much fuel you're allowed to pack into that magnetic cage. Here's where we get to the heart of it, the Greenwald limit, and why it haunted fusion for so long. To get useful power out of fusion, three things have to be true at once. Your fuel has to be hot enough, it has to be held together long enough, and it has to be dense enough, meaning you've packed enough fuel particles into the space for them to actually collide and fuse in large numbers. Temperature, time, and density. Crank up all three together, and you approach the holy grail. Ignition, the point where the reaction produces more energy than you put in and becomes self-sustaining, like a fire that keeps itself burning. The problem was density. Back in the 1980s, a physicist named Martin Greenwald noticed a stubborn pattern across fusion experiments. Every tokamak seemed to hit a density ceiling, try to pack in more fuel beyond a certain point, and the plasma would suddenly become violently unstable. It would develop disruptions, lose its confinement, and the reaction would crash. It happened so consistently that it became an empirical law of the field. The Greenwald limit, a line you simply did not cross, and it was a genuine roadblock to the entire dream. Because if you can't increase density past this line, you're capped on how much fusion power a reactor of a given size can produce. It forced designs to be bigger, more expensive, more conservative. For decades, fusion scientists essentially had to build around this wall, accepting it as a fixed fact of nature. Here's the part that makes the new result so striking. For nearly 50 years, most people assumed the Greenwald limit was something close to fundamental, a hard rule baked into how plasmas behave. But a newer theory suggested something more hopeful, that the limit wasn't a law of physics at all. It was a consequence, a side effect of how the plasma interacts with the walls of the reactor as it forms. And if that was true, then in principle, with exactly the right conditions, you might be able to sidestep it entirely. That theory had a name: plasma wall self-organization. It was elegant, it was promising, and for years, nobody had ever proven it actually worked in a real reactor. It was a beautiful idea waiting for evidence. China's artificial sun just provided that evidence. So how do you walk through a wall that stopped everyone for 50 years? The answer is surprisingly subtle and genuinely clever. The Chinese team, led by Professor Ping Zhu and Associate Professor Ning Yan, didn't break the limit with brute force, not by simply building bigger magnets or cranking up the power. They broke it by carefully choreographing the very beginning of the reaction, the startup phase, the first moments when the plasma is being born. Here's the core idea, simplified. Normally, as you cram more fuel into the plasma, the edge of that plasma, where it meets the reactor, gets cold and dirty. Impurities build up, energy leaks away, and that cascade is what triggers the instability that crashes the whole thing at the Greenwald limit. The wall and the plasma get into a destructive relationship. The Chinese team's insight was to manage that relationship from the very first instant. They precisely controlled two things: the amount of fuel gas they started with, and a special type of heating called electron-cyclotron resonance heating, essentially using carefully tuned microwaves to energize the electrons in the plasma at exactly the right moment. By dialing in those startup conditions just so, they got the plasma and the reactor walls to settle into a balanced, self-regulating relationship, the self-organization the theory predicted. In that balanced state, something remarkable happens. The plasma stops fighting to high density. Instead of becoming unstable as you pack more fuel in, it stays calm and confined. The team sustained stable plasma at densities between 1.3 and 1.65 times the Greenwald limit. That's 30 to 65% past the line that crashed reactors for half a century, with no disruptions. And critically, this was the first time anyone had ever experimentally confirmed that the self-organization theory actually works in a real tokamak. They didn't just break a record, they proved a theory that could reshape how every future reactor is designed. It's the difference between forcing a locked door and discovering it was never truly locked. You just had to turn the handle the right way. That's what makes this more than a number. It's a new understanding of how the rules actually work. Now here's where I have to be completely straight with you, because this is exactly the kind of story that gets wildly overhyped, and I'd rather you trust this channel than mislead you. This breakthrough does not mean fusion power is arriving next year, or even this decade. It does not mean your electricity bill is about to vanish, and here are the honest reasons why. First, and most important, no fusion reactor on Earth, including East, currently produces net positive energy when you account for the entire system. Right now, these machines still consume more energy to run than they generate. Breaking the density limit is a crucial ingredient toward changing that, but it is not the same as achieving it. East is an experiment, not a power plant. It will never put a single watt into anyone's home. Second, fusion still faces brutal engineering challenges that have nothing to do with this particular limit. Building materials that can survive years of relentless neutron bombardment and star-level heat. Sustaining the reaction not for seconds or minutes, but indefinitely. Turning the heat into electricity efficiently and affordably. These are enormous, unsolved problems, and progress on the materials side has actually been slower than progress on the plasma physics side. And third, even the scientists involved are careful here. As one expert put it, this breakthrough improves confidence in future reactor designs rather than accelerating timelines. It doesn't suddenly make commercial fusion arrive sooner. It makes the eventual reactors potentially smaller, cheaper, and easier to design, because they may not need to be as enormous or as conservative about density as everyone assumed. So the honest framing is this: China did not just solve fusion. What China did is remove one of the longest-standing roadblocks on the path, and prove that a barrier everyone treated as nearly fundamental was actually beatable. That's not the finish line, but it's a genuine, verified, peer-reviewed step toward it, published in the journal Science Advances, and it matters for every fusion project on Earth, not just China's. Here's the part that makes this bigger than a single experiment in Hefei. This discovery doesn't just help China. Because it's a fundamental insight into how plasma behaves, it potentially helps everyone chasing fusion. The world's largest fusion project, ITER, a massive international collaboration in France involving dozens of countries, could potentially use this density-free regime to reach its own goals more easily. The same is true for the wave of private fusion startups that have collectively attracted billions of dollars in investment. A barrier that constrained all of their designs may have just been loosened for all of them at once. There's even a fascinating bonus buried in the data. For years, there's been a rivalry between two reactor shapes, the donut-shaped tokamaks and a twisted design called a stellarator. Each had different strengths around density. The East results suggest tokamaks can now operate in a high-density regime that was previously thought to be a stellarator's advantage, effectively giving the most common reactor design a new superpower it wasn't supposed to have. And then there's the strategic picture, which is impossible to ignore. China has now formally written controllable nuclear fusion into its national 5-year plan as a major strategic priority, with a roadmap targeting a pilot reactor around 2035 and a demonstration reactor by roughly 2045. While much of the world has treated fusion as a someday maybe science project, China is treating it as a national industrial goal with a timeline and serious funding behind it. East breaking the Greenwald limit isn't an isolated lab result. It's one milestone in a deliberate, long-term national march toward being the country that figures out how to put a star in a bottle first. And whoever does that first, whoever cracks practical, commercial fusion, doesn't just win a scientific prize. They potentially gain control over the cheapest, cleanest, most abundant energy source in human history. The country that masters fusion could reshape the entire global balance of power, because energy underlies everything, every factory, every data center, every economy. This isn't only about science, it's about who powers the next century. Here's my honest opinion. I think the right way to hold this is to resist both of the easy reactions. The breathless headlines screaming "China just solved fusion, unlimited energy is here," are flatly wrong. We're still decades from a commercial reactor, no machine yet produces net energy, and the hardest engineering problems remain unsolved. Anyone promising you a fusion-powered home by 2030 is selling fantasy. But the cynics who shrug and say fusion is always 30 years away, ignore it, are making a subtler mistake. Because the nature of the progress is changing. For 50 years, the Greenwald limit was treated as a near-permanent wall. China just demonstrated, with peer-reviewed evidence, that it was never a wall at all, just a problem waiting for the right understanding. That's not 30 years away, that's a barrier falling in real time. When the supposedly impossible limits start breaking one by one, the old joke about fusion being perpetually distant stops being quite so funny. What strikes me most is the shift in posture. Fusion used to be a graveyard of broken promises that no one wanted to bet on. Now, there's billions in private money flowing in, nations writing it into industrial plans, and reactors breaking limits that stood since the 1980s. The momentum is real, even if the finish line is still far off. And the fact that one of the biggest recent breakthroughs came out of an artificial sun in eastern China tells you something about who's taking this prize most seriously right now. So here's my question for you, and I genuinely want your honest answer. Do you think we'll see practical, commercial fusion power in our lifetimes? Or is it still the technology that's always 30 years away, no matter how many limits get broken? Are you a fusion optimist or a fusion skeptic? Drop your real take in the comments. I read everyone, and I have a feeling this splits people right down the middle. If you want to keep following this, the breakthroughs, the broken limits, the race to power the future before the rest of the world catches on, subscribe to Eastern Engine and hit the notification bell. Energy, chips, the foundations of the modern world are being rewritten right now, and we break it all down clearly and honestly. Thanks for watching. I'll see you in the next one. BYD became one of the world's most powerful electric vehicle manufacturers by mastering batteries, electric motors, electronics, and mass production. Now the Chinese company wants to use those same capabilities to build something very different: humanoid robots. BYD Executive Vice President Stella Li says her goal is to place 2 or 3 humanoid robots inside every BYD showroom. The robots could greet customers, explain vehicle features, demonstrate technology, and make the buying experience more interactive. Li believes the necessary technology could become commercially available within the next 1 or 2 years. But the showroom is only the beginning. BYD is also developing robots for factories, service industries, and eventually homes. The company is even considering highly automated factories that could operate with minimal human presence. That puts BYD on a collision course with Tesla. For years, Tesla has argued that it should not be viewed simply as a car company. Elon Musk has repeatedly presented Tesla as an artificial intelligence and robotics company that happens to manufacture vehicles. Optimus, Tesla's humanoid robot, is central to that vision. But BYD's entry changes the competition. The next major fight between Tesla and China may not be about electric cars at all. It may be about which company can turn the automobile supply chain into a robot industry. Why BYD wants robots in showrooms? A humanoid robot inside a car dealership sounds like a publicity stunt. But from BYD's perspective, a showroom is an unusually practical place to begin. The environment is controlled. Floors are flat. Products are arranged predictably. The robot does not need to navigate a crowded construction site or an unfamiliar home. It can perform a limited number of repeatable tasks. It can welcome customers, answer common questions, point toward specific vehicles, explain charging features, and guide buyers through available configurations. The robot could also operate as a moving demonstration of BYD's engineering capabilities. Customers would not only see an electric car, they would see batteries, motors, sensors, software, artificial intelligence, and robotics working together in one physical machine. Stella Li has emphasized that robots would not eliminate the need for human salespeople. Buying a vehicle involves emotion, negotiation, trust, and personal preferences. A robot may explain a feature clearly, but it cannot necessarily replace the connection between a customer and an experienced employee. The more realistic strategy is to use robots as assistants. They could handle repetitive explanations while human employees focus on questions requiring judgment and personal attention. Showrooms would also provide BYD with valuable real-world testing. Engineers could study how customers react, which questions are difficult, where the robot becomes confused, and how reliably it operates throughout the day. That information would help improve future versions before robots move into less predictable environments. Why car companies are building humanoids. At first glance, a humanoid robot appears unrelated to an electric car, but the two products share more technology than many people realize. An electric vehicle needs batteries, electric motors, power electronics, cameras, sensors, processors, software, cooling systems, and advanced manufacturing. A humanoid robot needs almost the same categories of components. Its battery stores energy. Electric actuators move its arms, legs, hands, and joints. Cameras allow it to perceive its surroundings. Processors interpret visual information and coordinate movement. Software decides how the machine should respond. The physical design is different, but much of the industrial knowledge overlaps. This gives electric vehicle companies an advantage over ordinary software startups. A robotics startup may have excellent artificial intelligence, but little experience producing complex machines at scale. A traditional automaker already understands factories, suppliers, quality control, logistics, safety testing, and cost reduction. BYD has an additional advantage because it produces many important components internally. The company began as a battery manufacturer before becoming a major vehicle producer. It developed expertise in battery chemistry, power semiconductors, electric drive systems, electronics, and automated manufacturing. Those capabilities can be redirected toward robotics. A robot must become cheaper, more reliable, and easier to manufacture before it can move from a laboratory demonstration into ordinary businesses. That transition is exactly where large industrial companies may be strongest. From car factories to dark factories. BYD's humanoid ambitions are not limited to customer-facing robots. The company also wants robots inside its manufacturing operations. Factories are one of the most obvious early markets for humanoid machines. Industrial robots already weld vehicle bodies, move components, apply paint, and perform other repetitive tasks. However, most conventional industrial robots are fixed in place and designed for one specific operation. A humanoid could theoretically move between workstations and use equipment originally designed for people. It could carry parts, inspect products, operate tools, or perform tasks that change from one production run to another. This flexibility is the central promise. Instead of rebuilding an entire production line around a specialized machine, a company could train a general-purpose robot to work inside an existing human environment. BYD has discussed the possibility of dark factories within approximately 3 to 5 years. A dark factory is an extremely automated facility that requires so few people that some areas could operate without normal lighting. The term does not necessarily mean every employee disappears. Maintenance, engineering, supervision, safety, and quality control may still require people, but the production floor could become far more automated than a conventional car plant. Humanoid robots would not be the only machines inside such a factory. They would work alongside robotic arms, automated transport vehicles, machine vision systems, and intelligent production software. The goal would be continuous manufacturing with fewer interruptions, lower labor requirements, and faster adaptation. Tesla's Optimus vision. Tesla recognized the connection between vehicles and humanoid robots earlier than most global automakers. The company revealed Optimus in 2021 and presented it as a general-purpose machine capable of performing dangerous, repetitive, or boring work. Tesla's long-term argument is that physical labor represents an enormous market. If a useful robot can perform tasks across factories, warehouses, offices, and homes, demand could eventually exceed demand for cars. Tesla believes its experience with electric vehicles gives it the necessary building blocks. The company designs batteries, motors, power systems, computer hardware, cameras, and artificial intelligence software. Its factories also provide controlled environments where robots can be tested internally before being offered to outside customers. Tesla has continued preparing production capacity for Optimus, although the timing and scale of commercial manufacturing remain uncertain. Humanoid robots are far harder to mass-produce than promotional demonstrations suggest. Walking across a stage is not the same as completing useful work for 8 hours. The robot must balance, recognize objects, manipulate tools, recover from mistakes, and operate safely around people. The hands may be the most difficult component. Human hands combine strength, sensitivity, flexibility, and extremely precise control. A useful humanoid robot must handle delicate objects without dropping or crushing them. It must also perform thousands of movements without frequent mechanical failure. Tesla may have a head start in public attention and development time, but it no longer has the field to itself. China's robotics ecosystem BYD is entering one of the most competitive robotics markets in the world. China already has a dense network of companies producing electric motors, actuators, sensors, batteries, gearboxes, cameras, and industrial robots. Many of these suppliers developed alongside the electric vehicle industry. That means Chinese humanoid manufacturers can access a large domestic component ecosystem. Companies such as Unitree and UB Tech have already gained attention with walking robots, factory trials, public demonstrations, and increasingly capable humanoid platforms. Another Chinese electric vehicle manufacturer, XPeng, is preparing to mass-produce its iron humanoid robot by the end of 2026. XPeng plans to use its robots inside retail stores before expanding into broader commercial markets. Its chief executive has personally taken control of the robotics division, showing how strategically important the project has become. XPeng also connects humanoids to a larger physical artificial intelligence strategy that includes autonomous vehicles, robotaxis, and flying cars. This is becoming a pattern. Chinese electric vehicle companies are no longer treating cars as their final product. They see the car as a platform that helped them develop batteries, motors, sensors, computing systems, factories, and artificial intelligence. Robots are the next platform. Why humanoid robots are still difficult. The investment is real, but the technology remains immature. Humanoid robots look impressive in carefully prepared demonstrations. Real commercial environments expose their weaknesses. Battery life is limited. Motors generate heat. Mechanical joints wear out. Hands struggle with unfamiliar objects. Software can become confused by unexpected movement, poor lighting, noise, or crowded spaces. A human worker can immediately adapt when a box is placed in the wrong location. A robot may stop completely. Reliability is especially important in factories. A machine that works 90% of the time may look successful during a short demonstration. On a production line, 10% failure would be unacceptable. Every interruption can delay other machines and reduce the output of the entire facility. Safety is another challenge. A humanoid robot is heavy, powerful, and designed to move near people. The software must prevent collisions and react correctly when someone suddenly steps into its path. Companies must also decide whether a humanoid is actually the most efficient design. Human-shaped robots are useful in spaces built for people, but specialized robots can be cheaper, faster, and more reliable for many tasks. A warehouse may benefit more from wheeled machines than from robots walking on two legs. A factory may prefer fixed robotic arms for repetitive assembly. Humanoids must prove that their flexibility justifies their complexity. The economics will decide the winner. The robotics race will not be won by the company producing the most impressive video. It will be won by the company that can deliver useful work at a competitive cost. Businesses will compare the robot's purchase price, maintenance cost, energy consumption, reliability, productivity, and expected lifetime. A robot that costs less than a worker but requires constant repairs may not save money. A more expensive robot could still be valuable if it operates continuously and performs several different tasks. Manufacturing scale will therefore matter enormously. Tesla and BYD both understand how to reduce costs through production volume. They negotiate with suppliers, redesign components, automate assembly, and spread development expenses across large numbers of units. China's broad manufacturing network could give BYD access to lower-cost components and faster supplier competition. Tesla may benefit from stronger artificial intelligence branding, accumulated robot development, and direct integration with its software systems. The winner may not be the company with the most human-looking machine. It may be the company that reaches acceptable performance at the lowest total cost. What this means for Tesla BYD has already challenged Tesla in electric vehicles through aggressive pricing, battery integration, rapid product development, and manufacturing scale. Humanoid robots could repeat the same pattern. Tesla creates a bold vision and attracts global attention. Chinese manufacturers then compete through faster industrialization, dense supplier networks, and lower production costs. However, BYD's success is not guaranteed. Building cars does not automatically solve robotics. The company must develop sophisticated artificial intelligence, reliable hands, safe movement, and useful software. It must also prove that showroom and factory robots create real economic value. But BYD does not need to defeat Optimus immediately. It only needs to establish a working platform, test it inside its own operations, and improve it through repetition. Its showrooms provide public testing environments. Its factories provide industrial testing environments. Its dealer network could eventually become a sales and service network for robots. That combination is powerful. My take is that BYD's showroom plan matters, because it reveals how the company intends to enter robotics gradually. It is not beginning with the impossible promise of a robot that can perform every household task. It is starting with controlled environments, where the machine can provide limited but visible value. From showrooms, the robot can move into factories. From factories, it may eventually move into services and homes. Tesla is following a similar path by testing Optimus inside its own industrial operations. The difference is that China now has an entire ecosystem trying to commercialize humanoids at the same time. BYD, XPeng, Unitree, UB Tech, and many component suppliers are competing, marketing than useful technology. Let me know your view in the comments, and subscribe to Eastern Engine for more grounded coverage of the factories, machines, batteries, and engineering decisions reshaping the global economy. Because BYD may still be known for electric cars today, but its next major product might walk into the showroom on two legs. On May 25, 2025, something quietly historic happened that most of the global media barely covered. A freight train pulled out of a station in western China, carrying 32 containers of cargo. 15 days later, that same train arrived in Iran, more than 10,000 kilometers away, having crossed 4 separate countries, 2 major mountain ranges, and some of the harshest desert terrain on the planet, without ever touching an ocean. The journey that train completed in 15 days would have taken between 30 and 40 days by sea. But the duration is not really the story. The story is the route itself. For decades, moving large volumes of goods between Asia and the Middle East has meant one thing: ships, oceans, and a small handful of narrow waterways that determine which cargo arrives where. That arrangement has shaped global trade, global politics, and the balance of economic power for generations. This railway represents something different. It is the first serious attempt in modern history to build a major commercial corridor between two continents that bypasses maritime trade routes entirely. And the implications of that, once you sit with them, are genuinely significant. In this video, we are going to walk through how this railway was built, what it means for the countries connected by it, the broader expansion plan that involves 5 additional nations, and the parallel Arctic shipping route that is developing alongside it. The full picture is more strategic and more carefully designed than any single train run can communicate on its own. To understand why this railway exists, you first have to understand a single narrow stretch of water that almost no one outside the shipping industry talks about. It is called the Strait of Malacca, and it sits between Malaysia and Indonesia. Roughly 94,000 ships pass through it every year: oil tankers, container vessels, bulk carriers, and everything in between. It is one of the most heavily trafficked maritime corridors on the planet, and it functions as the primary gateway between the Indian Ocean and the Pacific. For China, this passage is not just useful, it is structural. Approximately 80% of China's oil imports flow through this single waterway. The energy that powers Chinese factories, vehicles, power grids, and consumer products travels through one narrow corridor on its way to refineries and storage facilities across the country. Now consider what that means in practical terms. If the Strait of Malacca were to close for even a short period, the economic effects would compound rapidly. Estimates put the daily cost of a closure in the tens of millions of dollars, and a sustained disruption would begin shutting down industrial activity within weeks. The world's second largest economy depends on a single maritime passage staying open and accessible. This is where geopolitical context enters the picture. Since 2019, the United States has maintained the ability to dock its naval vessels at deepwater facilities in Singapore, which sits at the southern entrance to the Strait of Malacca. In a major conflict scenario, the U.S. Navy has the capability to severely restrict maritime traffic through this corridor on a short timeline. That is not a theoretical concern in Beijing. It is a planning assumption. There are alternative maritime routes that could in theory be used. The Lombok Strait and the Sunda Strait both connect the same broader regions, but neither has the port infrastructure, the depth profile, or the logistical capacity to absorb meaningful volume on short notice. Switching even a portion of China's energy imports to these backup routes would require years of port expansion and supply chain restructuring. The conclusion that Chinese strategic planners reached was straightforward. The vulnerability of relying on a single maritime choke point was unacceptable in the long term, and the solution was to build a way to move energy and goods that did not depend on the ocean at all. The country whose geography made that solution possible was Iran. The route itself is an engineering challenge of a kind that very few projects in modern history have attempted at this scale. Starting in western China, the corridor heads west through Kazakhstan, then south through Uzbekistan and Turkmenistan, and finally crosses into Iran, where it terminates at the apron dry port near Tehran. 10,400 kilometers of connected railway track, spanning 4 sovereign nations, traversing some of the most punishing terrain on Earth. The terrain alone tells you something about the ambition behind this project. Vast stretches of open desert where shifting sand can bury rail infrastructure between maintenance cycles. Mountain ranges located in seismically active zones where the ground beneath the track is itself unstable. Summer temperatures that warp metal and crack concrete. Winter conditions cold enough to disrupt fuel and lubrication systems. The total cost of the project exceeded $2 billion, financed through a combination of Chinese policy banks, the Asian Infrastructure Investment Bank, and bilateral loan agreements between the participating governments. One of the most technically demanding aspects of the project was solving the rail gauge problem. China and most of Central Asia use different track widths, a legacy of historical infrastructure decisions made over a century ago. Russia and the former Soviet states use a broader gauge than the Chinese network, which historically meant cargo had to be transferred manually between different carriages at each border. That added hours to every shipment and made the route impractical for time-sensitive freight. The engineering response was the construction of automated bogie exchange facilities at the key border crossings. These systems allow the same container, on the same shipping platform, to be transferred between rail systems of different gauges in under 30 minutes. The technology is not new, but its deployment at this scale and across this many borders is unprecedented. There is also a structural detail that speaks to how seriously both sides took this project's strategic importance. Sections of the Iranian portion of the railway were built underground rather than at surface level. Officially, this protects the line from extreme weather. Realistically, it also protects the infrastructure from potential aerial threats. That is not the kind of design decision you make for a routine commercial freight corridor. When the first train completed the full route in May 2025, Chinese state media described the corridor as an energy lifeline between the two countries. That framing was not exaggeration. It was a clear statement of intent. The context for understanding why this railway matters so much to Iran requires looking at the broader economic situation the country has been operating under for years. International sanctions have constrained Iranian access to global financial systems for over a decade. Major banks have been disconnected from international transaction networks. Foreign companies that pursue significant business relationships with Tehran have faced regulatory consequences in Western jurisdictions. Oil buyers have been pressured through secondary sanctions to avoid Iranian crude. The cumulative effect of these measures has been to push Iran toward economic partnerships that operate outside the dollar-denominated global trade system. China made the strategic decision to be that partner. In 2021, the two countries signed a 25-year comprehensive cooperation agreement valued at approximately $400 billion. This was not a routine trade agreement. It was a generational commitment covering energy, infrastructure development, manufacturing partnerships, and technology cooperation. The follow-through has been substantial. In 2024, China purchased the overwhelming majority of Iran's crude oil exports, representing roughly $29 billion in trade. Iran's total oil revenue for the year reached approximately $67 billion, the highest figure the country had recorded in over a decade. The official sanctions remained in place. Their practical impact on Iranian oil exports had diminished significantly. With the railway now operational, those trade flows can move along a corridor that is structurally insulated from external interference. Iranian oil can move onto trains, travel across Central Asian territory, and arrive in China without involving any Western financial institution, insurance provider, or shipping line at any point in the chain. There is also a currency dimension to this arrangement that deserves attention. Since 2012, China has been settling its Iranian oil purchases in yuan rather than US dollars. This sounds like a technical detail. It is actually one of the most quietly consequential elements of the entire relationship. The dollar's role as the default global currency for energy trading is one of the foundations of contemporary American economic influence. Every major oil transaction conducted in an alternative currency reduces that role incrementally. Russia has pursued a parallel strategy with its own energy exports since 2022. The combined volume of energy trade settling outside dollar systems has grown notably over recent years, and this railway adds further infrastructure to that broader shift. Iran's geography also gives it strategic value that extends well beyond its own borders. The country sits directly along the Strait of Hormuz, through which approximately 20% of global oil shipments pass. It also has direct land borders with several Central Asian nations that have historically struggled with limited access to ocean trade routes. For landlocked countries like Tajikistan, Kyrgyzstan, and Afghanistan, a railway network connecting through Iran to Persian Gulf ports represents a fundamental change in their economic options. China gains influence across a region that has traditionally operated within other spheres of geopolitical power. It is a development that benefits multiple parties, which is exactly the kind of arrangement that tends to grow rather than fragment. The China to Iran corridor is the foundation of a larger network that has been under development in parallel. The Five Nations Railway Corridor project connects China, Kyrgyzstan, Tajikistan, Afghanistan, and Iran in a single integrated rail network. The new track required for the project totals around 1,300 kilometers, with the largest single section running through northern Afghanistan. The initial framework agreement was signed in late 2014, and the project has continued advancing through various phases since then. A significant milestone occurred in May 2023, when the first cargo run traveled from Iran into Afghanistan, along the Kaf-Herat segment of the network. That shipment carried 655 tons of railway construction equipment, meaning the network was, in a literal sense, transporting the materials needed for its own expansion. In May 2025, senior officials from Iran, China, Kazakhstan, Uzbekistan, Turkmenistan, and Turkey met in Tehran specifically to discuss the next phase of the transcontinental rail expansion. The momentum behind the project has accelerated rather than slowed. For the landlocked nations involved, the implications are significant. These countries have operated with severe disadvantages in global trade since their independence. Moving goods to or from their territories has always required navigating multiple borders and ultimately depending on ports they did not control. A rail network connecting them to Persian Gulf shipping points changes that situation in fundamental ways. The financing structure supporting all of this is also worth understanding. China's Belt and Road Initiative has committed well over $1 trillion to infrastructure projects globally since its launch in 2013. Central Asia represents one of its most strategically concentrated investment zones. The loan structures attached to these railway projects typically feature extended repayment timelines and resource-backed arrangements, which create durable economic relationships between China and partner countries. While the overland railway is moving freight east-west, China is simultaneously developing a maritime corridor in the opposite direction, one that runs through the Arctic. The Northern Sea Route follows the northern coast of Russia through Arctic waters and represents the most direct shipping path between Asia and Europe. A journey that takes around 45 days via the Suez Canal can be completed in roughly 30 days via the Northern Sea Route. Until recently, the obstacle was simple. Most of the route was locked under ice for most of the year, leaving only a brief 88-day operational window annually. That window is expanding. Climate change has steadily increased the period during which Arctic shipping is viable, and the operational window now extends to around 90 to 100 days per year. In June 2024, Russia and China formally agreed to develop year-round container shipping along this corridor. Russia has been investing in the icebreaker fleet required to make this practical. The latest generation of Russian nuclear-powered icebreakers, including the Arktika and the Sibir, can operate continuously through ice up to several meters thick. The Arktika weighs 33,000 tons, is powered by 2 nuclear reactors, and can operate for 7 years between refueling cycles. The strategic significance of the Arctic route lies in what it bypasses. The Suez Canal, despite being administered by Egypt, operates within a broader Western economic ecosystem. Insurance, financing, and logistics for vessels using it overwhelmingly involve European and American institutions. A functioning Arctic corridor allows trade to flow without any of those touch points. What is taking shape is a pattern. One corridor cutting across Central Asia by land, another opening up through the Arctic by sea, both moving in directions that reduce dependency on the maritime routes and financial infrastructure that have defined global trade for generations. It is worth being honest about the limitations of what this railway can accomplish in the short term. A single oil supertanker carries roughly 2 million barrels of crude oil, the equivalent of hundreds of freight train shipments. Scaling rail transport to fully replace maritime shipping is simply not realistic in any near-term timeframe. The corridor also faces real operational challenges. Multiple border crossings mean coordination overhead. Desert conditions stress rail infrastructure heavily. Fixed rail lines have inherent vulnerabilities that ocean-going vessels do not share. The early operational record reflects some of these realities. Within weeks of the inaugural freight run in May 2025, regional security developments interrupted further commercial services along sections of the corridor. The launch did not progress smoothly into routine operations, but focusing only on the operational hiccups misses what this railway actually represents. It does not need to replace maritime shipping to matter. It needs to exist as a working option that gives all parties involved choices they did not previously have. When China has a functioning land route for at least a portion of its energy imports, the strategic leverage associated with maritime choke points diminishes. When Iran has a major trading partner operating through infrastructure that exists outside the reach of Western financial systems, the practical impact of sanctions weakens. When Central Asian nations have rail access to global markets, they gain leverage in choosing their economic partners. There is also a broader signaling element to consider. Every kilometer of new track in this region sends a quiet message to other countries watching from the sidelines. There are alternatives to the existing global trade and financial architecture, and the alternatives are being built in real time. What I find most interesting about this story is not really the train itself. It is what the project tells us about how infrastructure is being used as long-term strategy rather than short-term capacity. The countries building this railway are not trying to win a single contest with the West. They are constructing an alternative architecture for trade, finance, and energy that can operate in parallel to the existing system. It does not need to replace anything to be effective. It just needs to exist, function reliably, and demonstrate that other options are viable. That is a much harder thing to respond to than a single competitive challenge, because it is not really a confrontation. It is the steady, patient construction of a different way of doing things, one project at a time, across a region that has historically been at the margins of global trade. Whether this approach succeeds at the scale its architects intend will depend on factors that take decades to play out: regional stability, sustained investment, technological developments, and broader geopolitical shifts. But the work being done right now is laying foundations that will shape that future regardless of how individual events unfold. My question for you is this: do you think infrastructure projects like this railway will end up shifting the balance of global trade meaningfully over the next 20 years? Or will the existing maritime system remain dominant despite these alternatives? Drop your honest answer in the comments. I am genuinely curious which way most people are leaning on this one. If this kind of deep dive analysis on global infrastructure and engineering strategy is what you come here for, please subscribe to Eastern Engine and hit the notification bell. We cover the major projects reshaping the global economic landscape with the depth they actually deserve. There is a lot more coming on this topic. And you do not want to fall behind. China's memory crisis is spreading into a part of the semiconductor industry most people barely notice. A Chinese supplier called Giantech Semiconductor has reportedly told distributors that prices across its entire NOR flash product portfolio will rise by 25% beginning July 6th. The increase applies not only to newly signed orders, but also to outstanding orders that have not yet been delivered. That is a major move for a component that usually receives far less attention than RAM, high bandwidth memory, or solid-state drives. NOR flash is the small, reliable memory that stores firmware, boot code, configuration data, and essential instructions inside cars, routers, industrial machines, communications equipment, and countless connected devices. Without it, many electronic systems cannot even start. Contract prices for mature memory products have already surged sharply during the first half of 2026. Artificial intelligence infrastructure is absorbing investment, factory space, and customer attention. Automotive and edge AI systems are demanding larger amounts of dependable embedded memory. And now one Chinese supplier is adding another 25% to its price list. The question is whether this is a temporary adjustment from one company, or whether the global memory shortage is moving into the overlooked chips that keep the world's electronics running. What NOR flash actually does. NOR flash is not the same as the DDR5 memory inside a gaming computer. It is also different from the NAND flash used inside an SSD or smartphone storage drive. The easiest way to understand NOR flash is to think of it as instruction memory. When a device powers on, it needs a trusted place to find the first code it will execute. That code may initialize the processor, check connected hardware, load safety settings, verify security keys, and prepare the operating system. NOR flash is well suited to that job because it keeps data when power is removed and allows fast, direct access to stored instructions. A vehicle may use NOR flash inside electronic control units, infotainment systems, driver assistance computers, cameras, radar modules, telematic systems, and digital instrument clusters. A network switch may use it to store boot firmware and configuration code. An industrial robot may depend on it for control software that must survive vibration, heat, and years of continuous operation. A product containing powerful processors and expensive sensors can still become unusable if its boot memory is missing, unreliable, or delayed. Why prices are rising now? Mature memory products such as NOR flash and with the highest demand and profit. but suppliers have little incentive to build large amounts of new mature node capacity when investors and customers are focused on AI. Modern cars contain more electronic systems than ever. Digital cockpits, advanced driver assistance, connectivity, over-the-air updates, cameras, radar, battery management, and intelligent lighting all require firmware. Edge AI devices also need more local code because they process information near the user instead of sending everything to a distant cloud. As software grows more complex, manufacturers move toward higher-density NOR flash products. That creates pressure on a market where supply is already becoming less flexible. The 25% increase. According to current industry reporting, Giantech's new prices take effect on July 6th. The increase covers the company's full NOR flash portfolio and applies to both new orders and undelivered existing orders. Normally, customers may assume that an accepted order protects them from a later price adjustment. Applying the new price to outstanding shipments suggests that the supplier sees the market tightening quickly enough to reset terms immediately. It does not mean every NOR flash manufacturer has raised prices by exactly 25%. It does not mean every chip buyer will pay the same amount. Large customers may have long-term contracts, negotiated allocations, or different product mixes, and a 25% increase in one component does not mean the final price of a car, server, or router will rise by 25%. The decision signals demand strong enough and availability limited enough to raise prices across an entire category without waiting for the next pricing quarter. A broader memory shock. TrendForce says contract prices for NOR flash and SLC NAND rose by more than 100% during the first half of 2026. It expects additional increases during the second half because major new capacity is not arriving quickly. When demand suddenly rises, manufacturers can sometimes solve the problem by running existing factories harder or releasing inventory. That becomes difficult when the underlying production base is shrinking. Mature memory is not the highest growth destination for semiconductor investment. High-bandwidth memory can sell for far more than a small embedded flash chip. Enterprise SSDs are being purchased through large multi-year agreements. Advanced server memory is receiving priority because cloud companies are willing to pay to secure supply. The result is that mature products can become scarce, even when total global memory investment is rising. The industry is building more memory, but not necessarily the specific kinds every customer needs. Why cars are exposed. Automotive companies are especially vulnerable because they cannot replace a qualified memory chip overnight. A consumer gadget manufacturer may redesign a board or switch suppliers relatively quickly. A vehicle component must pass demanding validation for temperature, vibration, reliability, and long operating life. Changing one part can require new testing, software verification, documentation, and approval. Automakers also need predictable supplies for many years because vehicles remain in production and require replacement parts after sales end. This dependence gives approved suppliers more pricing power when capacity tightens. Driver assistance systems need firmware for sensors and processing units. Connected vehicles need secure boot functions and update mechanisms. Higher levels of automation can increase the number and complexity of electronic modules. A shortage of relatively inexpensive NOR flash can therefore interrupt production of a much more expensive vehicle. Factories were forced to slow or stop because one missing controller or memory device prevented an entire car from being completed. AI servers are next, but with context. The title says cars and AI servers are next. That does not mean NOR flash will replace HBM or become the largest memory cost inside an AI server. Servers, network switches, accelerators, storage controllers, power systems, and management boards all require firmware. As AI data centers expand, they install enormous numbers of devices that must boot, authenticate, communicate, and recover reliably. Every additional server rack contains many embedded systems. The amount of NOR flash per device may be modest, but the number of devices is growing rapidly. AI clusters depend on high-speed switches, optical modules, smart network cards, and management controllers. These systems use dependable code storage for startup, configuration, diagnostics, and updates. Edge AI hardware creates another source of demand. Cameras, robots, industrial computers, vehicles, and smart appliances increasingly run models locally. That requires more sophisticated firmware and often larger embedded memory capacities. So AI contributes to the shortage in two ways. It pulls investment toward premium memory such as HBM and enterprise NAND. At the same time, it increases demand for the smaller firmware chips used throughout the infrastructure. China's position. Giantech is not the largest memory company in the world. Samsung, SK Hynix, Micron, Kioxia, and other major suppliers control far larger portions of global memory production. But China has been expanding its presence in mature and embedded semiconductor categories. That matters because domestic customers want secure supplies for vehicles, communication systems, industrial equipment, and consumer electronics. Chinese technology companies are also trying to reduce dependence on foreign components where possible. A stronger domestic NOR flash industry can support that goal. Yet higher Chinese prices show that localization does not automatically mean cheap supply. Domestic manufacturers still respond to capacity, demand, equipment costs, yields, and market conditions. If Chinese automakers and electronics companies compete for the same limited output, prices can rise inside China even while production expands. The shortage could benefit suppliers through higher margins. It could also encourage investment in additional capacity. But new semiconductor output takes time. Equipment must be ordered, installed, qualified, and operated at acceptable yields. Customers must test the finished chips. The market may remain tight long before any new line reaches meaningful volume. Duchu pays the final bill. The immediate buyers are distributors, module makers, electronics manufacturers, and system suppliers. They must decide whether to absorb the higher cost or pass it onward. For an expensive vehicle or server, one NOR flash chip may represent only a small fraction of the final price. Manufacturers may instead accept lower margins. They may negotiate with suppliers, reduce inventory, delay projects, or redesign future products around alternative parts. Smaller companies have fewer options. They purchase lower volumes, possess less negotiating power, and may not have second sources already approved. They could face longer delivery times or steeper price increases. The most serious risk is not the added cost of one chip, it is interruption. A missing component can delay an entire board, controller, machine, or vehicle. Companies may therefore pay a premium simply to guarantee allocation. This behavior can make the shortage worse because customers order earlier and hold more inventory than usual. What could end the shortage? Several developments could weaken the price surge. Demand for AI hardware could slow. Automotive production could weaken. Customers could reduce memory capacity or redesign products to use alternative devices. Manufacturers could reopen older lines, improve yields, or shift capacity back toward mature products. Chinese suppliers could expand faster than expected. But each solution has limits. Redesigns take time. Automotive qualification is slow. Building capacity is expensive. And suppliers may prefer to keep production disciplined rather than create another oversupply cycle. Memory companies remember what happens when too many factories chase temporary demand. Prices collapse, inventories rise, and expensive equipment sits underused. That history encourages caution. The market may eventually balance, but buyers should not assume prices will return quickly to previous lows. What this does not prove. One supplier's notice is not proof that every electronics category faces an immediate crisis. Giantech's increase must be separated from broader claims. We do not know the exact price paid by every customer. We do not know how much inventory distributors currently hold. We do not know whether competitors will match the full increase. And we do not know how long the new pricing will remain in place. The report is best understood as evidence that pressure has reached another memory category. NOR flash was once treated as a stable, mature component. Now it is being affected by the same forces reshaping DRAM, NAND, HBM, and enterprise storage. AI demand is changing investment priorities across the entire memory supply chain. My take is that the 25% increase matters less as an isolated number than as a warning. The memory supercycle is spreading outward. It began with the obvious products: HBM for accelerators, server DRAM, and enterprise SSDs. Now pressure is reaching the smaller chips that store the code required to start cars, routers, robots, and industrial systems. These devices are not glamorous. They do not appear in benchmark charts. Most consumers will never know which company made them. But modern hardware depends on them. Giantech's decision shows that mature memory can become strategically important precisely because the industry spent years treating it as ordinary. Supply is limited, qualification is slow, demand is becoming more sophisticated, and manufacturers are focusing investment elsewhere. That combination creates pricing power. The final impact may not be a dramatic 25% increase in the price of a car or server. It may appear as delayed production, smaller margins, redesigned products, and manufacturers paying more to secure guaranteed supply. China's domestic memory industry could eventually add enough capacity to ease the pressure. But today, one of its own suppliers is signaling that the shortage remains strong. So what do you think? Is the NOR flash increase another temporary spike? Or is it proof that the AI memory crisis is reaching every layer of modern electronics? Let me know your view in the comments. And subscribe to Eastern Engine for more grounded coverage of the chips, factories, and engineering decisions reshaping the global economy. Because the next hardware bottleneck may not be the processor everyone watches. It may be the tiny memory chip that tells that processor how to start. Here's something that should bother you. Right now, somewhere in the Gobi Desert, a machine is releasing air that was frozen solid last Tuesday, and that release is powering a city through the night. In Shanghai, a factory is pulling carbon dioxide out of the sky, combining it with hydrogen split from seawater, and producing jet fuel molecule for molecule identical to what comes out of an oil well. In Shanxi province, an ammonia plant is running on nothing but nitrogen from the air and sunlight. No natural gas, no extreme heat, no fossil fuels, and it hasn't stopped for 50 days straight. 6 breakthroughs, all running right now. Not in labs, in the real world, on factory floors, with real investors writing real checks. And almost none of it is in the news. That's not an accident. The story underneath all of it is so large and so structurally threatening to how the world currently works that it's easier to report each piece individually as a curiosity than to report them all together as what they actually are: a coordinated dismantling of the energy architecture the entire modern world was built on. This is that story. And by the end, you'll understand why a Chinese oil refinery voluntarily spending 800 million yuan to stop being an oil refinery is actually the most important data point in all of it. The choke point everyone ignores. To understand why these breakthroughs matter, you need to understand what they're solving for. China manufactures more physical goods than any economy on Earth. Pick up a random product in any store in any country. There's a high probability that something inside it, a component, a material, a subassembly, started as energy consumed inside a Chinese factory. That scale of production is staggering, and it has a single, brutal vulnerability almost nobody outside military planning circles talks about. More than 70% of China's oil comes from abroad. That alone is manageable. What isn't manageable is the geography of how it arrives. Almost every drop travels by ship through the Strait of Malacca, a stretch of water between Malaysia and Indonesia that, at its narrowest point, is under 3 kilometers wide. 1 in 4 barrels of oil traded on the entire planet squeezes through that gap. Military strategists have a name for the anxiety this creates: the Malacca dilemma. At its core, it's simple. If that passage gets blocked, by conflict, by political decision, by anything, Chinese factories don't slow down, they stop. Not in weeks, days. China has spent decades trying to route around it. Pipelines through Central Asia, deepwater ports in Pakistan, underground emergency reserves. None of it solves the root problem because the oil still has to cross the ocean first. The pipeline from Pakistan helps until the oil reaching Pakistan is cut off upstream. The only solution that actually works is making the energy locally, from materials that are everywhere, that nobody can blockade. That's what these 6 breakthroughs are. Not energy innovation for its own sake. A systematic, deliberate disassembly of the Malacca dilemma, one technology at a time. Fuel made from nothing. The first piece is almost offensive in its simplicity once you understand it. A facility in Shanghai, opened January 2026, built by a company called Carbonology, is producing jet fuel from carbon dioxide and water. Not biofuel, not almost jet fuel, actual aviation fuel, chemically identical to what refineries pump out of crude oil. A plane engine cannot tell the difference. A pilot cannot tell the difference. The only way you'd know is if someone told you. The process. Machines pull CO2 from the atmosphere. Solar-powered electrolyzers split water into oxygen and hydrogen. The CO2 and hydrogen combine under controlled heat and pressure. The result is a liquid hydrocarbon, the same molecule, built from scratch, from ingredients that exist literally everywhere on Earth. Current output is 100 tons per year, a proof of concept scale. But the roadmap goes 1,000 tons, then 5,000, then a commercial facility targeting 100,000 tons annually by 2027. Sequoia China has already written a check. And here's the detail that tells you this isn't vaporware. European aviation law already mandates a minimum percentage of sustainable fuel in aircraft, growing to a much larger share by 2050. The buyers were legally required to exist before the factories finished building. That almost never happens. It means the market was created by regulation before supply could catch up, the most favorable commercial position possible. This solves the where does the fuel come from problem. But fuel requires power to produce, and power has its own problem. The night problem, solved with frozen air. Solar and wind have a flaw so obvious it almost goes unexamined. They stop when conditions change. The sun goes down. The wind dies. Even the largest battery installations in the world typically bridge gaps of 4 to 5 hours. That's enough to cover a residential suburb. It is not enough to run a continuous industrial operation through a cloudy week. In the Gobi Desert, engineers tried something so straightforward it sounds like it shouldn't work. They froze air. Take normal atmospheric air, the mixture you're breathing right now, and cool it to minus 194 degrees Celsius. At that temperature, it becomes a liquid you can pump into tanks and store like diesel. When you need the energy back, you let the liquid air warm up and expand. It expands 700 times. That expansion spins turbines. The turbines generate electricity. The facility next to a 250 megawatt solar farm uses daytime surplus power, energy that would otherwise be wasted, to freeze air instead. At night, that stored air powers a city for 10 hours, double the duration of the best battery systems available, using no lithium, no cobalt, no rare earth minerals requiring international supply chains, just air and industrial equipment that can be manufactured anywhere. The plant has been running since late 2025, not a prototype. A working facility producing roughly 180 gigawatt hours of energy per year. The night problem is solved. But there's a separate category of machine, ships, heavy industrial equipment, long-haul freight that can't run on stored electricity. Those need actual fuel, and the answer to that comes from a molecule most people associate with cleaning products. The boring chemical that could end oil shipping. Ammonia, industrial solvent, fertilizer precursor, the smell from a horse stable. Also, the most promising carrier for clean hydrogen that humanity currently has. Here's the problem ammonia solves. Hydrogen is a spectacular clean fuel. Burn it, and the only byproduct is water. But hydrogen is also the lightest element in existence, which means storing and shipping it requires either extreme compression or extreme cooling. Expensive, technically demanding, and logistically difficult at ocean freight scale. You can't casually ship hydrogen across the Pacific the way you ship crude oil. Ammonia solves this by acting as a container. Pack hydrogen into ammonia molecules, ship the ammonia as a liquid at normal industrial temperatures, unpack the hydrogen at the destination. It's a lunchbox for energy that happens to use chemistry instead of plastic. The traditional ammonia production process, Haber-Bosch, invented in 1909, requires massive heat, enormous pressure, and enormous quantities of natural gas. It also feeds roughly half the world's population through fertilizer. Stopping it isn't an option. In Shanxi province, a facility is now making ammonia at room temperature. No natural gas, no extreme pressure, nitrogen pulled from air, hydrogen made from water via solar power, combined without the energy-intensive conditions the century-old process requires. It has operated continuously for over 50 days at more than 90% efficiency. Japan and South Korea are already running ammonia-powered cargo ships on live ocean routes with real freight. If bulk shipping, which moves 90% of everything traded globally, migrates to ammonia, oil's role in maritime fuel doesn't get smaller. It becomes optional. That word, optional, is the one that should give you pause. An optional commodity is a different kind of commodity than a necessary one. The thread connecting all of it. Every technology described so far needs hydrogen. The synthetic jet fuel factory needs hydrogen to build the fuel molecule. The ammonia plant needs hydrogen as its core ingredient. The electrolyzers powering the frozen air facility run on clean electricity. Electricity that's increasingly used to produce hydrogen as an intermediate step. This isn't coincidence. Hydrogen is the connective tissue of the entire system, so the relevant question becomes, how much can one country produce? In 2019, China's clean hydrogen output was roughly 23,000 tons annually. By 2024, it was 125,000 tons. Nearly a six-fold increase in 5 years, still accelerating. One province, Guangdong, is building an offshore wind installation specifically to power water-splitting electrolyzers, targeting 80,000 tons of hydrogen per year from a single project. The more significant number, China currently manufactures approximately 65% of the world's electrolyzers, the machines that split water into hydrogen. This is the detail most coverage of this space completely ignores. They all need electrolyzers. Most of those machines will ship from one country. The end game. Every technology discussed so far still has one constraint. It needs energy input. Solar needs sun, wind needs wind. Even liquid air storage is just shifting energy in time, not creating it. There is one technology that, if it works, removes that constraint permanently. China's East Reactor. experimental advanced superconducting tokamak set a new world record this year for sustained plasma stability, surpassing what physicists call the Greenwald limit, a threshold in plasma density that defines the boundary of what a controlled fusion reaction can sustain. It held that condition longer than any machine on Earth has managed before. Fusion is not ready to power cities. Anyone claiming otherwise isn't doing analysis. They're selling something. The engineering distance between a record-breaking plasma duration and a grid-connected power plant is still measured in decades of work. But here's the honest framing that most coverage misses. Fusion doesn't need to arrive soon to matter now. The investment patterns around it are themselves a signal. When a country commits serious capital and serious scientific infrastructure to fusion research, it's communicating a planning horizon that most Western governments don't operate on. China is building for 2050 and 2070, the way it built high-speed rail for 2030 in 2005. Fusion is the long bet underneath the short bets. The honest catch: none of this is frictionless. Synthetic fuel at 100 tons per year is not synthetic fuel at 100 million tons per year. Scaling industrial chemistry is not just multiplication. Every increase in volume introduces new engineering problems. Carbonology's 2027 target of 100,000 tons is ambitious. Whether the unit economics stay favorable at that scale is unproven. Green ammonia at room temperature has run for 50 days. 50 days is not 50 years. Long-duration industrial reliability is a different test than initial proof of concept, and the transition from works in a pilot to works in a global supply chain has killed more promising technologies than most people realize. And fusion is still, realistically, not a near-term grid technology. Pouring investment into it now is rational long-term strategy, but it cannot solve an energy security problem in this decade. The honest version of this story is, the foundation is being laid with real materials, real facilities, and real operating data. It is not finished. The gap between this works and this replaced oil is still significant, and the timeline for closing it is uncertain. What isn't uncertain is the direction. My take: here's what I actually think, having looked at all of it together. The pieces aren't individually revolutionary. Synthetic fuel has been a research concept for decades. Liquid air storage has existed in various forms since the 1970s. Ammonia as an energy carrier is well understood chemistry. What's different is that all of these are now simultaneously crossing from laboratory to factory floor, at a moment when one country controls 65% of the critical manufacturing hardware, has declared hydrogen a national infrastructure priority on par with oil and gas, and has a documented track record of taking impossible manufacturing problems and systematically solving them through scale. The more revealing data point isn't any single technology. It's the refinery. One of China's largest oil refining companies posted a profit decline of more than a third in 2025. Not because people used less energy, but because alternatives started competing with it. And its response was to commit 800 million yuan to converting its oil facilities to synthetic fuel production. A company whose entire identity, infrastructure, and business model was built on oil is voluntarily rebuilding itself around something else. Companies don't do that because a trend is interesting. They do it because they've run the numbers and concluded the future is moving, whether they move with it or not. The world that ran on oil didn't announce its own ending. It just slowly started losing ground to something that was cheaper and harder to interrupt. That transition is further along than most people outside this space understand. And the country building the machines that power it, the electrolyzers, the fuel factories, the storage systems, is doing to energy what it already did to solar panels, becoming the supplier the rest of the world depends on, before the rest of the world fully understood what it was depending on. The map used to be power. Whoever sat above the oil field held the leverage. Whoever controlled the strait controlled the flow. If you can make fuel from air and water, the map stops mattering. And one country just got significantly better at making fuel from air and water. My question for you: if energy can genuinely be produced anywhere from ingredients that exist everywhere, who do you think loses the most? Which economy is most exposed when the geography of energy stops being relevant? Drop your honest take in the comments. I read every one. If you want to keep following this, the quiet moves, the overlooked technologies, the shifts that matter before the headlines catch up, subscribe to Eastern Engine and hit the notification bell. This is where the actual story is. Thanks for watching. See you in the next one. For the entire history of electrical power, almost every power plant on Earth has worked the same fundamental way. You take a heat source, burning coal, splitting atoms, concentrated sunlight, it doesn't matter which, and you use that heat to boil water. The water turns to steam. The steam, under enormous pressure, blasts through a turbine and spins it. The spinning turbine turns a generator, and the generator produces electricity. Then you cool the steam back into water and do the whole thing over again, millions of times. That cycle is so old, it predates the light bulb. The basic principle of using boiling water and steam to do mechanical work goes all the way back to the steam engines that powered the Industrial Revolution. For more than 2 centuries, through every advance in fuel and engineering and materials science, the working fluid at the heart of nearly every power plant stayed exactly the same. Water in, steam out. Spin the turbine. China just broke that 200-year tradition. In a steel plant tucked into the mountains of southwest China, engineers have switched on a power generator that doesn't use steam at all. Instead, it runs on the one substance the entire world spends enormous effort trying to get rid of. It runs on carbon dioxide, the gas we blame for climate change, the byproduct of every furnace and engine and power station, the thing scientists are racing to capture and bury underground. China has turned it into the beating heart of a power plant. And the headline number is staggering. This system is reportedly around 50% more efficient at squeezing electricity out of waste heat than the steam technology the world has relied on for generations. So how does a power plant run on a pollutant? Why did this take 200 years to figure out? And what does it actually mean for the future of energy? Let's break it all down. Before we go any further, I have to clear something up, because the way this story gets told online is genuinely misleading, and I'd rather give you the honest version. When people hear a power plant that runs on CO2, they immediately picture giant machines sucking carbon dioxide out of the sky, cleaning the atmosphere while generating electricity. A magic device that fixes climate change and powers your home at the same time. That is not what this is. I want to be completely straight with you about that. This technology does not pull CO2 out of the air, it does not reduce the amount of carbon dioxide in the atmosphere, and it does not burn CO2 as a fuel. You can't burn carbon dioxide. It's already been burned, which is what makes it CO2 in the first place. So what is actually happening here? The carbon dioxide isn't the fuel, it's the messenger. In every power plant, you need something to carry heat from your heat source to your turbine. For 200 years, that messenger has been water turned to steam. What China has done is replace the water with carbon dioxide, a fixed amount of it, sealed inside the system, used over and over in a closed loop. The CO2 never escapes. It never gets used up. It just shuttles heat back and forth, endlessly. Why does that matter? Because it turns out carbon dioxide, when you treat it the right way, is a dramatically better messenger than water ever was. And understanding why requires us to look at one of the stranger states that matter can exist in. You already know the 3 everyday states of matter: solid, liquid, gas, ice, water, steam. Carbon dioxide has the same 3 states. Frozen, it's the dry ice that fogs up a concert stage. As a gas, it's the invisible thing you exhale. But there's a 4th condition, and it's the key to this whole story. If you take carbon dioxide and crush it under enormous pressure while also heating it past a certain temperature, something bizarre happens. It stops being clearly a gas and stops being clearly a liquid. It enters a hybrid state that scientists call supercritical. In this state, the CO2 flows freely and fills its container like a gas would, but it's also dense and packed tight, carrying heat the way a liquid does. Think of it as getting the best of both worlds at once. A gas is easy to push around and compress, but it's terrible at holding heat. A liquid is fantastic at holding and moving heat, but it's heavy and hard to pump. Supercritical CO2 behaves like both simultaneously. It moves like a gas and carries heat like a liquid. That combination is exactly what you want in the messenger that carries energy through a power plant. And it gives supercritical CO2 a set of advantages over steam that are honestly difficult to overstate. First, it transfers heat far more efficiently than steam does, which means more of your precious heat energy actually ends up spinning the turbine instead of being lost along the way. Second, and this is the part engineers get genuinely excited about, supercritical CO2 is so dense and energetic that the turbine it spins can be a fraction of the size of a conventional steam turbine for the same power output. We're talking about a turbine you could potentially hold in your arms doing work that would normally require a machine the size of a bus. And third, there's a subtle but enormous efficiency win hiding in the physics. To make steam, you have to boil water, and boiling water requires a huge amount of energy just to force it through that phase change from liquid to vapor. It's a wasteful, energy-hungry step. Turning CO2 into its supercritical state takes far less energy than boiling water into steam. You skip a giant chunk of waste right at the start. Put all of that together and you get a power system that is smaller, more efficient, and able to wring electricity out of heat that older technology would have simply thrown away. Here's the obvious question. If supercritical CO2 is so much better than steam, why has the entire world been boiling water for 2 centuries instead? The answer is that this idea is not new at all. In fact, it's shockingly old. The concept of using a supercritical CO2 cycle to generate power was first seriously explored back in the 1960s. Engineers in Italy and the United States looked at the thermodynamics and realized this approach could, on paper, outperform conventional steam plants. The math worked. The theory was sound. The promise was clear. And then it sat on a shelf for 60 years. Because there was a problem, and it was a brutal one. To make this work, you have to hold carbon dioxide at extreme pressure and extreme temperature, continuously, for years on end, while it surges through your machinery. And the materials available in the 1960s, and for decades afterward, simply could not survive those conditions. The metals would corrode, the seals would fail, the turbine components would degrade under the relentless assault of hot, high-pressure CO2. The fluid that made the system so efficient was also aggressive enough to chew through the equipment meant to contain it. So the idea remained exactly that, an idea. A tantalizing concept that worked beautifully in theory and fell apart the moment you tried to build it and run it for real. For 60 years, supercritical CO2 power was the technology of the future, and it seemed like it always would be. Cracking it required advances in metallurgy, in high-pressure engineering, in turbine design, and in materials that could shrug off conditions that would destroy ordinary steel. It required someone willing to pour money and time into solving a problem the rest of the world had largely given up on. That part of the story should sound familiar if you follow Chinese engineering. It's a pattern we've seen again and again. The project is called Kaitan-1, sometimes referred to as Supercarbon Number 1, and it was developed by the Nuclear Power Institute of China, part of the China National Nuclear Corporation, working alongside industrial partners. It's located inside a working steel plant in Liupan Shui, a city in mountainous Guizhou province in southwest China. And the choice of location is not random. It's central to the whole point. Steelmaking generates staggering amounts of heat. Furnaces run at blistering temperatures, and a huge portion of that thermal energy normally just escapes into the atmosphere as waste. It does no work. It powers nothing. It simply radiates away, lost forever. Every steel plant on Earth is, in a sense, constantly throwing away energy. Kaitan-1 captures that waste heat, the heat that would otherwise have vanished, and feeds it into the supercritical CO2 system. The hot CO2 expands and drives the compact turbine. The turbine spins the generator. Electricity flows out to the grid, and the CO2 cycles back around to grab more heat and do it all again. Nothing is burned. No new emissions are created. The plant is generating genuinely useful electricity out of energy that was previously garbage. The system was built in 2 units, each producing 15 megawatts. The first unit connected to the grid on December 20, 2025, and ran stably for months. Then, on May 30, 2026, engineers brought the second unit online, bringing the total installed capacity to 30 megawatts. With both units running, China National Nuclear Corporation declared it the world's first full-scale commercial demonstration of supercritical CO2 waste heat power generation, and the largest and most advanced project of its kind anywhere on the planet. And here is where that efficiency figure comes back. According to the teams behind it, the system is roughly 50% more efficient at capturing and converting waste heat from steel production than the steam-based technology that would traditionally do this job. 50% more electricity from the same wasted heat with smaller equipment. Now you'll have noticed this was built by China's Nuclear Corporation at a steel plant, and you might be wondering where exactly the nuclear angle fits. This is where the story gets genuinely forward-looking. The waste heat steel plant is the proving ground. It's the place to demonstrate that supercritical CO2 power works reliably in the real world, in a commercial setting, day after day. But the steel plant isn't the ultimate target. The reason the Nuclear Power Institute developed this technology is that the same supercritical CO2 cycle could one day replace the steam systems inside nuclear reactors themselves. Think about what that would mean. Today's nuclear plants use their reactor heat to boil water and make steam, just like a coal plant does. They just generate the heat in a cleaner way. If you swapped that steam system for a supercritical CO2 system, a nuclear plant could become significantly more efficient and dramatically more compact. The enormous turbine halls that define conventional nuclear stations could shrink. The whole plant could get smaller, cheaper, and more powerful per square meter. And it doesn't stop at large reactors. The engineers behind this project have openly pointed toward a whole family of future uses where compact, efficient power generation matters enormously. Mobile nuclear power sources, reactors small enough to be transported and deployed where they're needed. Concentrated solar power plants, which generate heat from focused sunlight and currently rely on steam. And perhaps most strikingly, space-based power generation, where every kilogram and every cubic meter is precious, and a compact CO2 turbine could be worth its weight in gold. That's the real ambition here. The steel plant is step one. The destination is a fundamentally better way to turn heat into electricity across nuclear power, solar power, mobile generators, and even spacecraft. A 200-year-old bottleneck finally opened. Now, I don't want to oversell this, because part of why you're hopefully here is that I try to give you the real picture rather than pure hype. This is a genuine, significant achievement. The world's first commercial-scale operation of a technology that defeated 60 years of materials problems. That's real, and it deserves recognition. But it's also a demonstration project, and demonstration is not the same as proven at scale. 30 megawatts is meaningful, but it's small in the context of the global power grid. A single large conventional power plant produces dozens of times that. The big open questions now are about durability and cost. Can this equipment survive the relentless assault of high-pressure, high-temperature CO2, not just for months, but for the decades a power plant is expected to operate? Will the maintenance costs stay reasonable? Can it be scaled up and manufactured cheaply enough to compete with the steam technology it's meant to replace? Some energy analysts have raised exactly these concerns, and they're fair ones. A breakthrough that works for a few months in one steel plant still has to prove it can work everywhere, for years, at a price that makes sense. But here's the thing. Every transformative technology starts exactly like this. Small, demonstrated, surrounded by skeptics asking reasonable questions about whether it'll last. The steam turbine itself was once a fragile experiment. The question is never whether the first version is perfect. It's whether the underlying idea is sound, and whether someone is committed to refining it. On both counts, supercritical CO2 looks like the real deal. Step back for a second and consider what this actually represents. Roughly the entire planet's electricity, the power running through the device you're watching this on, is generated by spinning turbines, and the overwhelming majority of those turbines are spun by steam. We have built our entire civilization on top of a 200-year-old method of boiling water. Any improvement to that fundamental process, even a small one, ripples out across literally everything. A technology that's 50% more efficient at recovering waste heat is not a niche curiosity. The world's heavy industries, steel, cement, chemicals, glass, bleed enormous quantities of heat into the atmosphere every single day, heat that represents wasted energy and, indirectly, wasted fuel and extra emissions. If that heat can be efficiently recaptured and turned into electricity, you're getting more power out of the energy you've already spent, without burning anything extra. That's a genuine climate win, even though the system itself isn't pulling carbon from the sky. And if this technology eventually migrates into nuclear reactors, solar plants, and compact mobile power units, the efficiency gains compound across the entire energy landscape. Smaller, cheaper, more powerful generation, everywhere heat needs to become electricity. There's also a bigger pattern worth naming. This is, once again, a case of a technology invented in the West, abandoned as too difficult, and then revived and commercialized by Chinese engineers willing to grind through the hard materials problems that made everyone else give up. The supercritical CO2 cycle was dreamed up in Italian and American labs in the 1960s. The United States has continued researching it, and institutions like the Southwest Research Institute have built their own demonstrators. But it was China that put the first commercial version on the grid. That's becoming a recognizable story in energy and engineering, and it's one worth paying close attention to, regardless of how you feel about it. Here's my honest opinion, for what it's worth. What I find most compelling about this isn't the CO2 angle, even though that's what makes the headline pop. It's the willingness to attack a 200-year-old assumption that nearly everyone else treated as permanent. The entire power industry decided decades ago that steam was simply how you do this, and the supercritical CO2 idea was filed away as too hard. China didn't accept that. They spent more than a decade working the problem until the materials and engineering caught up with the theory. I think the steam plant era is genuinely going to start winding down over the next few decades, and supercritical CO2 is one of the technologies most likely to replace it. Not overnight, the durability and cost questions are real, and the first version will need years of refinement, but the physics is undeniable. And once a better method gets a commercial foothold, the rest of the industry tends to follow whether it wants to or not. The thing that makes me cautious is the same thing that makes every demonstration project uncertain. We won't truly know if this is a revolution or just an impressive experiment until it's run for 10 or 20 years at full scale. But the direction is unmistakable, and the bottleneck that stopped this for 60 years has finally been broken. So here's my question for you. Do you think supercritical CO2 will actually replace steam turbines across the world's power plants in your lifetime? Or do you think steam is too deeply entrenched to ever fully go away? Drop your honest answer in the comments. This is one of those topics where I genuinely want to know which way people are leaning. If you enjoy these deep dives into the engineering breakthroughs quietly reshaping the world, do me a favor and subscribe to Eastern Engine, and tap the notification bell so you don't miss what's next. We break down these stories clearly, without the hype, and there's a lot more coming. Thanks for watching, I'll see you in the next one. A laboratory in Oregon takes one of Huawei's newest smartphone processors and begins removing it layer by layer. The package comes apart, the memory is separated, the silicon is polished until structures invisible to the human eye become visible under powerful microscopes. And deep inside the chip, researchers find a number that appears to break the normal hierarchy of semiconductor manufacturing: 32.5 nanometers. That is the measured pitch of the lowest local metal layer inside Huawei's Kirin 9030 processor, manufactured by China's SEMIC using its N+3 process. Now compare that with Intel's newest commercial manufacturing technology. Inside Panther Lake processors built on Intel 18A, the equivalent layer is reportedly spaced at 36 nanometers. On that one measurement, China's 7-nanometer class process went smaller than the layer shipping inside Intel 18A. And it did so without EUV lithography. That sounds like SMIC somehow jumped beyond Intel. It did not. Intel's overall process remains denser, more efficient, and considerably more advanced. Intel 18A can also support a tighter metal pitch than the version used in Panther Lake. But the measurement is still remarkable because it reveals how aggressively SMIC has stretched older lithography equipment. The company did not overcome the problem with one secret machine. It attacked the chip from several directions at once: quadruple patterning, narrower cells, fewer transistor fins, contacts placed in tighter positions, and a metal network compressed almost to the practical edge of DUV manufacturing. The result is not a clean victory, it is an engineering trade. SMIC gained density, but it paid for that density with additional masks, extra processing, tighter alignment tolerances, and greater manufacturing complexity. And that trade may tell us more about the future of Chinese chipmaking than a simple benchmark ever could. Modern semiconductor names are misleading. 7 nanometers, 5 nanometers, 3 nanometers, 18 angstroms. These labels sound like direct physical measurements, as though every important feature inside a 7-nanometer chip must be 7 nanometers wide. That has not been true for years. Process names have become generational labels. They describe a package of manufacturing improvements rather than one universal dimension. Intel 18A does not mean every structure measures 18 angstroms. SMIC N+3 does not mean every feature measures 7 nanometers. Two companies can use completely different names while producing structures that overlap in certain dimensions. That is why comparing 7 nanometer with 18A by name alone creates the wrong picture. A chip contains many different measurements. There is gate pitch, fin pitch, cell height, transistor density, metal pitch, SRAM density, and the spacing between contacts and wires. Each reveals one part of the process. The new teardown focused attention on M0, the first local metal layer sitting just above the transistor structures. Think of the transistors as tiny buildings. The metal layers are the roads connecting them. M0 handles extremely short local connections inside the smallest logic cells. Higher layers gradually become wider roads carrying signals across larger regions of the chip. A tighter M0 pitch allows more local wiring to fit into a smaller area. But one narrow street does not automatically mean the whole city is better. The city also needs highways, power delivery, intersections, and enough space for traffic to move. That is where the comparison becomes complicated. The chip examined was Huawei's Kirin 9030 Pro, part of the processor family used in the Mate 80 series. It is manufactured using SMIC's third-generation 7-nanometer class process, known as N+3. Researchers measured the M0 pitch at approximately 32.5 nanometers. That is around 10% tighter than the 36-nanometer M0 configuration found in Intel's Panther Lake processors. SMIC's M1 layer measured approximately 38 nanometers, while M2 measured around 40. These dimensions show that SMIC compressed the lowest wiring layers aggressively, but the larger picture is different. The teardown estimated SMIC N+3 at roughly 113 million transistors per square millimeter using a normalized logic density metric. That places it around the level of TSMC's older N6 process. Intel 18A's high-density library remains approximately 38% denser. So how can one local layer be tighter while the overall process remains far behind? Because density is not controlled by one dimension. SMIC squeezed M0 partly because it needed to. Intel could leave more space there because it had already removed one of the largest sources of congestion: power. Traditional chips deliver both data signals and electrical power through metal layers above the transistors. Imagine trying to build a city where delivery vans, commuter traffic, power cables, and water pipes all compete for the same narrow streets. The result is congestion. Intel's power via technology changes that arrangement. Instead of routing power through the front-side metal stack, Intel brings power through the back of the silicon. Signals remain on one side. Power arrives from the other. This frees valuable routing space above the transistors and reduces resistance in the power network. With less front-side congestion, Intel does not always need to compress every local wire to the smallest possible pitch. Panther Lake uses a 36nm M0 pitch, but Intel 18A reportedly supports a 32nm option. Intel chose the looser configuration partly because Panther Lake relies heavily on higher performance cell libraries and because PowerVia gives designers more routing freedom. That is why the headline needs the phrase "in one critical layer." SMIC produced a tighter M0 pitch in this shipping Huawei chip. But Intel's process is not limited to 36 nanometers, and a wider M0 layer does not automatically represent weaker technology. Sometimes additional space is not a failure to shrink. It is a choice enabled by a better architecture. The most impressive part of SMIC N+3 is not that the company found a magical replacement for EUV. It is that engineers extracted more resolution from DUV lithography through repetition. The key method is called self-aligned quadruple patterning, or SAQP. The concept sounds almost like a geometric trick. A DUV lithography system first prints a relatively wide guide pattern called a mandrel. A thin spacer material is deposited along the sides of that guide. The original guide is removed, leaving the spacers behind. Those spacers then become guides for another deposition and removal cycle. One original line effectively becomes 4 narrower lines. Imagine drawing one thick stripe on a road. You place barriers along both edges, then remove the original stripe. Next, place smaller barriers around the barriers that remain. After several carefully controlled steps, one broad pattern has been multiplied into several narrow, evenly spaced features. The lithography machine did not directly resolve every final line. The process created them through deposition and etching. That is how SMIC could form a roughly 32nm grid using DUV equipment. But every added operation creates risk. The spacers must have nearly identical thickness. The etch must remove exactly the intended material. The new lines must remain aligned with contacts and structures created in other steps. If one stage shifts slightly, the error can propagate through the entire pattern. EUV can print finer features with fewer pattern-splitting steps. DUV can reach similar dimensions in selected layers, but the path is longer. SMIC replaced machine simplicity with process complexity. Quadruple patterning sounds clever because it is clever. It is also expensive. Each additional deposition, etch, cleaning, and inspection step consumes factory time. More steps require more equipment. More equipment means more maintenance. More masks increase cost before the first commercial wafer is even produced. Alignment becomes increasingly difficult because patterns created in separate operations must meet with extraordinary precision. A small overlay error can place one metal line too close to another, creating electrical leakage or a short circuit. Place it too far away, and the intended connection may fail. Then there is variation. If one spacer is slightly thicker than another, the final lines will not be identical. Resistance changes, timing changes. One region of the chip may behave differently from another. The teardown reportedly found that the tight M0 trenches had a more difficult profile than the looser metal layers above them. That does not mean the chip is defective. It means the manufacturing cost is visible in the structure. SMIC successfully created the feature, but the feature carries evidence of how hard it was to create. This is the central paradox of DUV scaling. The machine itself is older. The process surrounding it becomes more complicated. The metal layer was only part of the story. SMIC also used several design and manufacturing techniques to reduce the area of the basic logic cells. The first was fin depopulation. The Kirin 9030 uses FinFET transistors. In a FinFET, current flows through vertical silicon fins surrounded by the gate. More fins can provide stronger electrical drive, but more fins also consume space. SMIC N+3 uses 2 NMOS fins and 2 PMOS fins in its measured logic cells. Reducing the fin count allows cells to become narrower, but it can also limit drive strength. It is similar to replacing a wide multi-lane tunnel with a narrower one. The tunnel occupies less land. It may not move the same amount of traffic. The second technique is contact over active gate. Normally, the electrical contact connected to a gate may sit beside the active region, consuming additional space. Place that contact directly over the active gate, and the cell becomes shorter. Simple in a diagram. Difficult in production. The contact must land accurately without damaging or interfering with the transistor below it. The third technique is the single diffusion break. Logic cells need isolation between neighboring transistor regions. Older layouts often used a wider double break. A single diffusion break saves space, but it increases sensitivity to local manufacturing variations. Again, density improves. Margin becomes smaller. None of these ideas is unique to SMIC. Major foundries use similar density-enhancing techniques. What stands out is how aggressively SMIC combined them in one process generation. This is where the story moves beyond lithography. A foundry cannot simply shrink every shape and ask chip designers to continue as before. At these dimensions, the manufacturing process and the circuit layout must be developed together. This is called design technology co-optimization. The factory tells designers which shapes can be produced reliably. Designers reorganize logic cells around those restrictions. The factory then adjusts the process to support the new layouts. The result is a feedback loop. Suppose a transistor loses one fin to save area. The circuit may now switch more slowly. Designers compensate by changing the cell, adjusting the signal path, or using a stronger cell elsewhere. Suppose a metal layer becomes tighter but gains resistance. Engineers may shorten important routes or move selected connections to a higher layer. The process is no longer simply about drawing smaller transistors. It becomes a puzzle involving density, power, performance, heat, and manufacturability. SMIC N+3 appears to be a product of that puzzle. Its density did not come from one enormous leap in lithography. It came from dozens of smaller compromises that reinforce one another. Huawei used the denser N+3 process to fit more capability into a chip with a die area similar to its predecessor. The Kirin 9030 reportedly adds another middle CPU core, expands several caches, and increases GPU and neural processing resources. Individual CPU cores also became smaller. The prime core shrank despite receiving a larger private cache. The middle cores became significantly more compact. GPU compute units became smaller, allowing Huawei to increase the number of units while keeping the full graphics section within a manageable area. That is what process scaling is supposed to accomplish. The goal is not merely creating a beautiful cross-section under a microscope. The goal is using less area for existing functions, then spending the saved area on more capability. Huawei appears to have done that successfully, but performance reveals the limitation. The Kirin 9030 improved significantly over the previous generation, especially in graphics. It still trails current flagship processors from the leading mobile chip companies. Its CPU architecture and manufacturing efficiency remain behind the newest designs. The chip can contain more hardware than its predecessor. It cannot operate that hardware with the same power efficiency as a processor manufactured on a leading 3nm class process. Density matters. The voltage and frequency curve matters more. A smaller structure does not automatically switch faster. Narrower metal wires have greater electrical resistance. Smaller transistors can suffer from leakage and variability. More patterning can introduce dimensional differences across the wafer. A process must balance density with the ability to operate at useful voltage and frequency. This is where SMIC's disadvantage becomes clear. The Kirin 9030 is a credible modern smartphone processor, but it is not equal to the latest Apple, Qualcomm, or MediaTek flagship chips. Its strongest CPU core reportedly performs more like an older high-end design. Its GPU made a major generational jump, yet remains far behind current top-tier alternatives. Efficiency is the greater challenge. A processor can reach competitive performance by consuming more power, but a smartphone has strict thermal limits. The device cannot use a large cooling system. The battery must last. The surface cannot become uncomfortably hot. That means performance per watt determines how much of the chip's theoretical capability can be used continuously. SMIC compressed the layout. it has not yet matched the manufacturing characteristics of the most advanced nodes. In M0 pitch inside these two shipping products, yes, the Kirin 9030's measured 32.5 nanometer pitch is tighter than Panther Lake's 36 nanometer implementation. Across the entire manufacturing process, no. Intel 18 amps uses gate-all-around ribbon FET transistors, rather than conventional FinFETs. It includes backside power delivery. It offers substantially greater normalized logic density, and it provides a more advanced platform for performance and efficiency. Even the narrow M0 victory needs context because Intel 18A supports a tighter 32 nanometer version that was not used in Panther Lake. So the correct interpretation is not that SMIC's 7 nanometer process is better than Intel 18A. It is that process node names hide enormous complexity. A company working with older lithography can produce one dimension that looks more advanced than a dimension inside a newer process. But it may need more steps, more masks, and more compromise to get there. The number is real. The meaning is conditional. The significance lies in what SMIC proved can still be extracted from DUV. Many observers assumed that without EUV, advanced logic manufacturing would quickly reach a hard wall. The Kirin 9030 suggests the wall is not perfectly vertical. It is more like a steep mountain. Progress remains possible, but every meter becomes harder than the last. SMIC has tightened local metals, reduced cell dimensions, and incorporated multiple density boosters. It has reached roughly TSM6 class logic density, while using a more complicated manufacturing route. That is not parity with the leading edge. It is evidence of continued movement, and commercial shipment matters. This is not a research wafer designed only to demonstrate one small test structure. The process is manufacturing a complete smartphone system on chip containing CPU cores, graphics, AI processing, memory controllers, image processing, and communication hardware. Every one of those blocks must work together. A laboratory can optimize one line. A consumer processor must survive millions of interacting lines. That makes the result harder to dismiss. SMIC may still have additional scaling options. Cell height could be reduced again. Some local metal layers could be pushed into even more aggressive patterning. Gate pitch may shrink slightly. Future designs could use backside contacts or advanced three-dimensional stacking. But each option becomes more difficult. If another routing layer requires quadruple patterning, mask count rises again. If cells become shorter, designers lose wiring tracks. If contacts move to the backside, manufacturing requires wafer thinning, backside alignment, and new integration steps. None of these is impossible. Together, they become unforgiving. The danger is not that one individual step cannot work. The danger is that the combined process becomes too expensive, too slow, or too sensitive to variation. A foundry does not win by producing the world's most impressive cross-section. It wins by producing large numbers of functional chips at a competitive cost. That is why EUV remains so valuable. It does not perform magic. It reduces the number of tricks required. If shrinking the chip in 2 dimensions becomes increasingly expensive, the next option is to build upward. Huawei has discussed an approach called logic folding, which would divide parts of a logic block across multiple active silicon layers. Instead of placing every transistor beside the others on one flat surface, some functions could sit above or below their neighbors. Short vertical connections could replace longer horizontal wires. This could improve density per package area and reduce the time required for signals to travel across large blocks. The approach has its own difficulties. Stacked active logic creates heat. Bonding must be extremely precise. Testing becomes more complicated. The density comparison also changes because adding another layer increases transistors per package footprint without improving the transistor process itself. Still, the direction is logical. When the map cannot become much smaller, fold the map. SMIC N+3 may therefore represent both progress and a warning. It demonstrates how far planar DUV scaling can be pushed. It also demonstrates why the industry is looking beyond planar scaling. My view is that the 32.5 nanometer result is more interesting than the phrase "China beat Intel" suggests. A simple victory would almost be less revealing. SMIC did not create a universally superior process. It created an unusually aggressive one. The company used quadruple patterning, tighter local wiring, and several layout optimizations to achieve a dimension optimization. So no, the Kirin 9030 does not prove that China has overtaken Intel. It proves something narrower, and still significant. A 7 nanometer class chip, manufactured without EUV, can contain one local wiring layer tighter than the configuration used inside a commercial Intel 18A processor. That should not be exaggerated. It should not be ignored either, because technological progress does not always arrive as a clean leap from one machine generation to another. Sometimes it comes from taking an old tool, surrounding it with new processes, and forcing it to perform one more task that looked unreasonable. The final product may cost more. It may consume more power. It may remain behind the leader overall, but it works. And once something works in a commercial chip, the question changes. It is no longer, can this be done? It becomes, how far can they push it next? So what do you think? Is SMIC's 32.5 nanometer metal pitch evidence that DUV lithography still has meaningful life left? Or does the added cost and complexity prove that this approach is approaching its practical limit? Let me know your position in the comments. And if you want more grounded breakdowns of the machines, materials, and hidden engineering choices shaping the semiconductor industry, subscribe to Eastern Engine, because sometimes the most important part of a processor is not the feature advertised on the box. It is the wire buried at the very bottom of the chip. A camera looks at a handwritten number. A radar signal bounces off an object. A laboratory instrument measures the optical fingerprint of a pharmaceutical sample. To a normal computer, these are three different worlds. The image is made from pixels. The radar arrives as a changing radio frequency waveform. The chemical sample appears as a spectrum, different wavelengths rising and falling according to the material being measured. Each normally requires its own sensor electronics, conversion hardware, and processing pipeline. But researchers in China have built one photonic intelligence chip designed to handle all three. Instead of forcing every signal through a conventional digital processor first, the system converts images, spectra, and radio frequency signals into a common optical language, light. Those optical patterns enter the chip through a single fiber. They are separated, weighted, and processed by microscopic waveguides. The result passes through an optical neural network and reaches a classification output with a measured response time of just 1.33 nanoseconds. 1.33 billionths of a second. The chip successfully classified handwritten images, recognized pharmaceutical spectra, and distinguished radar targets, and it performed part of that computation using only 29 femtojoules per operation. A femtojoule is 1/4,000,000th of a joule. This does not mean the chip can understand every image, identify every chemical, or operate a complete autonomous vehicle by itself. It is still a research prototype. The laboratory setup includes external light sources, amplifiers, and test equipment that would need to be reduced or integrated before practical deployment. But the achievement points toward a new kind of edge intelligence. A sensor may no longer need to capture information, digitize everything, send it to a processor, and wait for a response. It may process the signal almost immediately, using the physics of light before the data ever becomes a conventional stream of digital numbers. The delay hiding between a sensor and AI. Modern sensors generate enormous quantities of analog information. A camera receives changing light intensity. A radar antenna detects reflected electromagnetic waves. A spectrometer measures how materials absorb or reflect different wavelengths. Nature produces analog signals continuously. Computers prefer digital numbers, so before a conventional AI model can process the information, the sensor output must usually pass through several steps. First, the analog signal is sampled. Then, an analog to digital converter turns it into numbers. Those numbers move into memory. The processor retrieves them. Software reorganizes the data into a format the AI model can accept. Only then does inference begin. Each step adds delay. Each conversion consumes energy, and each movement of data creates another bottleneck. This may not matter when a cloud server has several seconds to analyze a photograph. It matters enormously when a robot must avoid an obstacle, a radar system must identify an approaching object, or a medical sensor must react immediately to a changing signal. At the edge, milliseconds matter. Sometimes microseconds matter. Researchers therefore want to move intelligence closer to the sensor, not inside a distant data center, not after a long digital pipeline, directly where the signal first arrives. The Chinese team's photonic edge intelligence chip, called PEIC, was designed around that goal. One chip, three different languages. The central problem was not only speed, it was compatibility. An image is spatial. Its information is arranged across two dimensions. A chemical spectrum is spectral. Its information is distributed across wavelength. A radar signal is temporal. Its information changes through time. These data types do not naturally fit into the same computing architecture. Trying to process all three with one ordinary analog circuit would be like asking one translator to interpret a photograph, a melody, and a weather map using the same alphabet. The researchers solved this by converting every input into a broad optical spectrum. They call the process modal fusion. For image data, the system uses a scattering structure. The image passes through an optical setup that converts spatial patterns into a unique spectrum. A different image creates a different spectral fingerprint. For chemical data, the input is already spectral. A pharmaceutical sample can absorb or reflect light differently depending on its composition. For radar, the radio frequency waveform is used to modulate an optical carrier. This converts time-domain radar information into sidebands distributed around an optical frequency. 3 original formats. 1 optical representation. Once every signal becomes a spectrum, all 3 can travel into the same chip through one fiber. That is the first major innovation. The chip does not need a separate entrance for every type of sensor. It asks the sensors to speak light. Why light changes the computation? Electronic processors perform operations by moving and switching electrical charge. They are extraordinarily capable, programmable, and mature. But moving charge creates resistance and heat. Digital systems also process many tasks through sequences of clocked instructions. Light behaves differently. Multiple wavelengths can travel through one waveguide at the same time without being processed one after another. This is called wavelength parallelism. Imagine one road carrying cars of many colors. An electronic system may inspect each car separately. A photonic system can route all the colors simultaneously according to their wavelength. That makes optical computing attractive for mathematical operations that repeat across large datasets. Neural networks depend heavily on those operations. They multiply inputs by weights, combine the results, and pass them through nonlinear functions. A conventional chip performs those multiplications electronically. A photonic chip can encode values into light intensity or phase, then let interference, routing, and detection perform part of the mathematics physically. The answer emerges from how the light propagates. In the PEIC, the first major processing stage is built around an arrayed waveguide grating. It is one of the most important components in the system. The prism built inside a chip, an arrayed waveguide grating, or AWG, behaves somewhat like an advanced microscopic prism. A normal prism separates white light into colors because different wavelengths bend differently. An AWG performs a related function, using many waveguides with carefully controlled lengths. Light enters the device and splits across an array of paths. Each path is slightly longer than the previous one, but light waves accumulate different phase delays. When those paths recombine, different wavelengths interfere constructively at different output ports. One wavelength travels toward one output. Another wavelength travels somewhere else. The researchers' AWG contained 185 arrayed waveguides and occupied roughly 1.5 by 1.5 millimeters. It separated the optical spectrum into channels spaced 100 gigahertz apart, but the component did more than detect wavelengths. The team also used it as a convolution engine. Convolution is one of the fundamental operations in machine vision and signal analysis. A small pattern, called a kernel, moves across the input and measures particular features. One kernel may respond strongly to edges, another may detect curves, another may identify a repeating frequency pattern. Instead of performing those calculations sequentially in digital logic, the PEIC weights different parts of the optical spectrum and routes them through the AWG. The optical energy arriving at each output represents the convolution result. The chip is sensing and computing in the same structure. That combination avoids moving raw sensor data into a separate processor before useful features can be extracted. Why 29 femtojoules matters? The researchers estimated that the sensing and convolution stage consumed around 29 femtojoules per operation. The number is almost too small to visualize. 1 femtojoule is 0.000000000000000000000001 joules. A common household light bulb uses tens of joules every second. The energy used in one optical operation is a microscopic fraction of that. This does not mean the complete laboratory system runs on 29 femtojoules. External lasers, amplifiers, control electronics, and supporting equipment consume far more power. The number applies to the optical computation itself. That distinction matters. A chip can have an extremely efficient core while the complete system remains bulky or power-hungry. Still, core efficiency is important because edge devices live under strict limits. A drone cannot carry a data center power supply. A wearable sensor cannot become hot against the skin. A small robot cannot devote most of its battery to converting and moving sensor data. If optical pre-processing can reduce the amount of digital work required later, the entire device may become more efficient. The light does not need to solve every problem. It only needs to remove enough work from the electronic processor to justify its presence. The part that makes it a neural network. Convolution alone is not enough. Neural networks also need nonlinearity. Without a nonlinear activation function, multiple processing layers collapse mathematically into one large linear transformation. The network cannot learn complex decision boundaries. Electronic AI chips implement nonlinear functions with transistor circuits and software instructions. Optical systems find this more difficult because light propagating through ordinary waveguides is naturally linear. Double the input, and the output usually doubles. The PEIC uses a nonlinear activation layer built from photodetectors and microring modulators. The photodetector converts optical power into an electrical response. That electrical signal controls a ring-shaped optical device, producing a nonlinear change in the outgoing light. After this activation stage, a fully connected optical layer combines the extracted features and produces the final classification result. The output is physical. The researchers determine the result by identifying which output port receives the highest optical power. No additional digital post-processing is required for the final decision. That makes the system an end-to-end optical neural network, rather than just an optical filter connected to a conventional classifier. What 1.33 nanoseconds really means. The measured response time of the nonlinear activation unit was 1.33 nanoseconds. That number represents the critical response inside the optical neural network pipeline. It is not the same as saying the entire laboratory can classify 751 million completely independent images every second. The present proof-of-concept system operates in approximately the 100 MHz range. That means its practical repetition rate is closer to 100 million cycles per second. Still fast, but different from the simplest interpretation of 1.33 nanoseconds. Why the gap? A complete system includes modulation, signal preparation, optical propagation, control, and repeated operation. The nonlinear ring modulator relies on carrier injection, which limits how quickly the full architecture can reset and process the next sample. The optical input itself can carry enormous bandwidth, potentially in the terahertz range, but the current nonlinear stage limits the full system's operational rate. Think of a warehouse with an extremely wide entrance but a smaller sorting station inside. Huge amounts of material can arrive. The sorting machine determines how quickly completed packages leave. Future nonlinear optical devices could increase that rate. For now, the measured nanosecond response demonstrates extremely low latency, while the system-level rate remains around 100 MHz. Both numbers are valuable. They simply describe different parts of the machine. Test 1. Recognizing images. For image classification, the researchers used handwritten digits. These are the familiar black and white numbers often used to test machine learning systems. The image was displayed through an optical setup and projected onto a random scattering chip. The scattering structure transformed the two-dimensional image into a spectral fingerprint. A handwritten 3 produced one pattern. A handwritten 8 produced another. Those spectra traveled through the fiber and into the PEIC. The chip extracted features using the AWG-based convolution stage, passed the signal through nonlinear activation, and produced a classification output. This approach is unusual because planar photonic chips struggle with two-dimensional images. A chip waveguide naturally guides light along one direction. Routing every pixel of a large image into separate paths would create a complicated maze of connections and crosstalk. The scattering approach compresses spatial information into the spectral domain. Instead of giving every pixel its own road, it transforms the entire image into a unique combination of wavelengths. The chip then analyzes that combination. It is less like looking at the image directly, and more like identifying the echo the image leaves in light. Test 2. Reading pharmaceutical spectra. The second task involved drug spectrum recognition. Different pharmaceutical samples produce different spectral signatures. A material may absorb strongly at one wavelength and weakly at another, creating a pattern that functions like an optical fingerprint. Traditional analysis may digitize the entire spectrum and send the values into a computer. The PEIC receives the spectral data in its native optical form. No image conversion is required. No radio frequency modulation is required. The spectrum travels directly into the chip. The AWG separates the wavelengths and performs the weighted feature extraction at the same time. This is one of the clearest examples of the architecture's advantage. The sensor output and the computing medium are already compatible. Light measures the sample. Light carries the information. Light performs much of the classification. Potential future uses could include compact pharmaceutical inspection, environmental monitoring, and wearable biochemical sensing. But the experiment did not prove that the chip can identify every unknown chemical. It classified samples within a defined research dataset. General chemical analysis would require larger training sets, careful calibration, and robust handling of noise and temperature changes. Test 3. Classifying radar targets. Radar presents a completely different challenge. A radar system transmits electromagnetic waves and measures how they return after hitting an object. The returned signal contains clues about shape, distance, motion, and orientation. Traditional radar processors digitize the waveform and perform signal processing operations electronically. That can consume significant power and add latency. The researchers modeled radar returns from different target geometries. These time-varying electrical signals drove an electro-optic phase modulator. The modulator placed the radar information onto light by creating frequency sidebands around an optical carrier. A more complicated radar waveform produced a different optical spectrum. The PEIC then classified the target by analyzing those spectral features. This approach could eventually support robotics, autonomous navigation, and compact sensing platforms. A machine could receive radar data and begin extracting target information almost immediately, without first sending every sample through a large digital processing chain. Again, the current experiment was controlled. The radar signals were modeled and generated using laboratory equipment. A real outdoor environment introduces rain, interference, multiple reflections, and unexpected objects. Practical deployment would require testing under those conditions. The chip can also learn. The researchers demonstrated both supervised and unsupervised learning. Supervised learning uses labeled examples. The network sees an input and is told the correct answer. It adjusts its internal weights to reduce future errors. Unsupervised learning works without explicit labels. The system searches for structure or clusters inside the data. Supporting both approaches matters because many edge environments do not provide perfectly labeled information. A sensor may encounter patterns that were never categorized in advance. The optical chip's weights are controlled through programmable phase-shifting elements. An FPGA-based electronic framework supplies control voltages, allowing the researchers to adjust the network during inference and training. This reveals an important truth about photonic AI. The system is not purely optical. Electronics still configure the chip, calibrate components, and control its weights. The advantage comes from assigning the right task to each domain. Electronics provide flexibility and memory. Photonics provides parallelism, bandwidth, and low-latency signal processing. The future may not belong to light instead of electricity. It may belong to systems that use both where each works best. What is still outside the chip? The laboratory demonstration relied on several external components. A broadband optical source generated the light, a programmable wave shaper created controlled spectra, an optical amplifier increased signal strength, a spatial light modulator helped generate image inputs, a waveform generator and phase modulator produced radar signals. These machines are useful for research because they can simulate many sensors and inputs. They are not intended to sit beside the chip in a finished robot. In a practical system, a camera, spectrometer, or radar front end would feed signals into a smaller integrated optical interface. The researchers also note that weak real-world signals may require amplification. Their current experiment used an external erbium-doped fiber amplifier. Future versions could integrate optical gain into a silicon nitride photonic circuit, reducing the need for bulky external hardware. That path is technically plausible. It is not yet completed. The chip at the center is compact. The entire laboratory around it is not. This is common in early semiconductor research. The first transistor needed a room of test equipment. Commercial value arrives when the surrounding system shrinks. Why this could matter most at the edge. Cloud AI can tolerate before deciding whether to break. These devices need local intelligence, but local intelligence creates a trade-off. More processing increases power consumption. Lower power often means slower response. Photonic edge computing aims to weaken that compromise. Raw analog information can be converted into an optical spectrum, processed in parallel and classified with extremely low latency. Only the final result may need to reach the electronic controller. Instead of sending a complete radar waveform to the CPU, the optical front end could report a target category. Instead of digitizing every point in a chemical spectrum, it could report whether a sample matches a known pattern. The processor receives less data. The device responds faster. the battery lasts longer. That is the vision. The honest catch. The PIC does not replace a general CPU, GPU, or AI accelerator. It is specialized hardware. Its strength comes from performing a limited set of operations extremely efficiently. Changing the task requires new training and reprogrammed weights. Some applications may require different optical interfaces. The chip's demonstrated network is also far smaller than the giant models used in modern generative AI. It is designed for classification at the edge, not for writing essays or generating video. Accuracy must remain stable outside the laboratory. Photonic components can drift with temperature. Manufacturing differences can change phase and transmission. Calibration circuits can correct some variation, but they add complexity. The 1.33 nanosecond figure should also be interpreted carefully. It describes a measured component response within the network, not the entire end-to-end world-to-decision time of a finished product. And while 29 femtojoules per operation is excellent for the optical core, the complete system's energy consumption includes light generation, amplification, and control electronics. The research proves a powerful architecture. Commercial engineering must prove the product. My take. My view is that the most important part of this breakthrough is not the 1.33 nanosecond number by itself. It is the decision to unify very different sensors before computation begins. Images, spectra, and radar signals normally travel through separate pipelines. The researchers converted all three into one optical language and fed them through one photonic neural network. That could be more important than building the fastest possible chip for only one sensor. Real machines use multiple senses. A robot may need a camera in daylight, radar in fog, and chemical sensing in a hazardous environment. Today, each sensor often brings separate converters, processors, and software. A common optical intelligence layer could simplify that architecture, but the phrase "could" matters. This technology still needs integration, environmental testing, larger networks, and lower-cost packaging. The current system is not ready to appear inside a smartphone or vehicle tomorrow. Even so, the direction is convincing. Sensors naturally produce analog signals. Light naturally carries enormous parallel bandwidth. Neural networks naturally depend on repeated matrix and convolution operations. The PEIC brings those properties together. It does not wait for the world to become digital before intelligence begins. It starts computing while the information is still light. A camera image becomes a spectrum. A radar echo becomes a spectrum. A pharmaceutical sample becomes a spectrum. One fiber carries them. One chip separates them. One optical network decides what they represent. And one part of that decision responds in 1.33 nanoseconds. So what do you think? Will photonic chips become the standard front end for cameras, radar, and scientific sensors? Or will the difficulty of lasers, calibration, and packaging keep conventional electronics in control? Let me know your view in the comments. And if you want more grounded stories about the chips, materials, and hidden engineering breakthroughs reshaping computing, subscribe to Eastern Engine, because the next generation of AI may not begin by converting the world into numbers. It may begin by letting light understand the world first.
The semiconductor industry is truly the engine room of the global economy. Chips go into everything from your smartphone to your car to massive data centers. And the web of global connections is enormous. ASML in the Netherlands producing the lithography machines that are shipped to TSMC here in Taiwan that manufactures the actual chips using designs from ARM in the UK, Nvidia, and Apple. China, the biggest consumer of semiconductors.
Right now, TSMC, Samsung, and Intel are focused on something unexpected, not just smaller transistors or global trade limits, but glass. A super thin sheet of engineered glass is becoming one of the biggest changes the chip industry has seen in years. China has already invested more than $1 billion into this technology as companies race to shape the future of advanced chips. It may sound strange at first. Glass is everywhere, from phone screens to windows. But this new type of glass could completely change how powerful chips are built. That is why major tech companies and governments are paying close attention and investing heavily in it. For decades, the tech world followed one simple rule: make transistors smaller, and devices become faster and smarter. That idea helped create smartphones, cloud computing, AI systems, and modern technology as we know it. But now, in 2026, the industry is running into new limits. Today's advanced AI chips use so much power that even the best current designs are struggling to keep up. Engineers have started running into a major problem, and surprisingly, the issue is not inside the chip itself. It is underneath it. That is where advanced glass technology comes in. And once you see why companies are focusing on it so early, the whole situation makes a lot more sense. Think about a skyscraper. No matter how impressive the design looks, everything depends on the foundation underneath. If the base is weak, the entire building can run into problems. Computer chips work the same way. Every chip sits on something called a substrate, which acts like the foundation that supports everything above it.
On the planet. Just think of all the electronics that China produces, and a country that's also trying to build out its own chip industry, so it's less reliant on the West. And that has put the broader industry in the crosshairs of Washington. They have imposed export controls and tariffs to try to contain China's chip industry. They've also spent heavily to try to ensure there's production and more of it on US soil. Tariffs can only go so far. No company builds chips from the start to finish.
For years, these substrates were made from special plastic and resin materials that help move electrical signals and control heat. They have done the job well for decades, but today's powerful AI chips are pushing those older materials close to their limits. That is why companies are now turning to ultra-thin glass as a possible next step in chip design. Older substrate materials worked well when computer chips were smaller and less demanding, but today's AI processors are far more advanced. Modern AI systems now combine multiple smaller chips called chiplets into one powerful package that handles memory, processing, and communication all at the same time. This design helps companies push performance even further, but it also creates new engineering challenges. These chip packages are becoming much larger and more complex, with billions of tiny connections working at extremely high speeds while producing a huge amount of heat. That is where the substrate becomes a major factor. Traditional organic materials can bend and expand as temperatures rise during operation. As AI systems grow more powerful, keeping everything stable and efficient is becoming much harder, which is why advanced glass substrates are getting so much attention right now. As chips heat up and cool down over time, traditional substrate materials can slightly expand and shrink. These tiny changes may not seem important, but in advanced AI systems, why the industry started searching for a completely different solution, something more stable, precise, and reliable under extreme conditions. The surprising answer turned out to be advanced glass substrates. Unlike older materials, glass can stay much more stable during temperature changes, making it a strong candidate for the next generation of high-performance AI chips. At first, glass sounded like a strange choice for advanced computer chips. Many engineers thought it would be too fragile, too expensive, and too difficult to manufacture at scale. But the glass used in next-generation chip packaging is very different from everyday glass. It is a specially engineered material designed for the extreme demands of modern computing. Traditional substrate materials react to heat by expanding and shrinking over time, which can make large AI chip systems harder to keep stable. That was manageable with smaller chips, but today's powerful AI processors need much higher precision. Advanced glass substrates offer a big advantage because they stay far more stable under changing temperatures. That stability helps engineers maintain better performance, reliability, and efficiency as AI chip designs continue to grow larger and more complex. Advanced glass substrates can handle heat and mechanical stress with far greater stability than traditional materials. Even during constant heating and cooling cycles, they keep their shape with impressive precision. That allows engineers to place electrical connections much closer together without worrying about long-term alignment issues. The improvement is huge. Glass substrates may support far higher connection density than current organic materials, creating faster communication between chip components while using energy more efficiently. For AI systems, that could mean major performance gains without relying only on smaller transistors. Glass also helps with heat management, which is one of the biggest challenges in modern computing. Better cooling and thermal control allow powerful AI processors to run more efficiently for longer periods, especially inside massive data centers, where performance and energy use are critical factors. Glass substrates could help future AI chips run at higher performance levels for longer periods, without slowing down from heat buildup. They also improve signal quality, allowing data to move with less interference compared to traditional materials. At the extreme speeds modern AI systems operate, those improvements can make a major difference in overall performance. But there is a challenge. Manufacturing these advanced glass substrates is incredibly difficult. The material must be perfectly flat, and tiny pathways inside the glass have to be created with extreme precision. Even microscopic imperfections can affect reliability. Producing this technology at large scale requires years of advanced engineering and highly specialized equipment. That difficulty is one of the biggest reasons only a small number of companies are capable of competing in this space right now. That manufacturing barrier is exactly why the recent moves by China, Intel, Samsung, and TSMC are getting so much attention. While most headlines focused on advanced lithography machines, another major technology race was quietly building in the background. For years, many experts believed the future of powerful chips depended mostly on access to cutting-edge lithography systems. The idea was simple: control the most advanced manufacturing tools, and you control the future of chip production. But China and several major tech companies also focused heavily on another strategy: advanced chip packaging and substrate technology. Instead of relying only on smaller transistors, companies began investing in new ways to connect chip components together more efficiently. That includes advanced glass substrates, precision manufacturing, and material science breakthroughs that can improve performance without depending entirely on next-generation lithography tools. China has spent years investing heavily in these areas, building factories, research programs, and supply chains focused on advanced packaging technology. Now, as AI systems demand more power and efficiency, those investments are starting to attract serious global attention. BOE is one of the clearest examples of why China's strategy around glass substrates makes sense. The company is already one of the world's biggest makers of display technology, producing precision glass for smartphones, TVs, and monitors on a massive scale every year. That experience gives BOE a strong advantage, because many of the same skills used in display glass manufacturing also apply to advanced semiconductor glass substrates. The equipment, engineering knowledge, and supply chains are closely connected, making the move into chip packaging technology a natural expansion rather than a completely new business. Other Chinese companies have also been investing heavily in solving one of the toughest challenges in this field: creating tiny electrical pathways inside the glass with extremely high precision. Over the past few years, research programs, patent activity, and production plans have all shown growing momentum in this area. Several companies are now aiming for larger-scale glass substrate production between 2026 and 2027 as demand for advanced AI chip packaging continues to rise worldwide. What connects all of these efforts is the massive level of investment going into advanced chip packaging technology. Since 2023, China has directed major funding toward factories, research programs, equipment, patents, and engineering talent focused on next-generation semiconductor packaging. Much of this activity received less global attention because most headlines were centered on the race for smaller transistors and advanced lithography systems. Meanwhile, companies and government-backed programs were steadily building capabilities in packaging technology, especially around advanced glass substrates and precision manufacturing. One reason this strategy stands out is that it builds on skills China already developed through industries like display manufacturing and materials engineering. With long-term investment and large-scale production experience, the country positioned itself to compete strongly in a growing part of the semiconductor supply chain. Now, as demand for powerful AI systems keeps rising, companies in the United States, Taiwan, South Korea, and Europe are accelerating their own investments in advanced packaging and glass substrate technology to stay competitive in the next phase of the chip industry. Intel, Samsung, TSMC, and several major American materials companies have all increased their focus on glass substrate technology over the past few years. The decisions being made now could shape the future of the global semiconductor supply chain for years to come. Intel has one of the longest histories in this area, spending more than a decade researching and developing advanced glass substrate solutions. During that time, the company built a large patent portfolio and gained valuable manufacturing experience that gives it a strong position in the industry. Intel has also started working closely with partners and suppliers to expand the overall ecosystem around this technology. Samsung is also moving quickly. The company has been developing pilot production lines and investing heavily in engineers with expertise in advanced packaging and glass materials. It has also formed partnerships with materials suppliers to help secure the specialized components needed for future production. As AI systems continue growing more powerful, major semiconductor companies are racing to improve packaging technology, and glass substrates are becoming one of the most important areas of competition. Samsung's long-term plans reportedly aim for large-scale glass substrate production around 2028, which could make the company one of the first major suppliers for advanced AI chip systems. Because Samsung already plays a huge role in the global tech supply chain, its progress in this area is getting a lot of industry attention. TSMC has also increased its focus on glass substrate research in recent years. As one of the biggest leaders in advanced AI chip packaging, The company understands that future performance gains may depend just as much on packaging technology as on transistor design itself. Expanding its work on glass substrates helps TSMC stay competitive as the industry evolves. Corning is another important player in the space. The company has decades of experience producing highly specialized glass for telecommunications, displays, and scientific applications. That expertise could make Corning a key supplier as demand for advanced semiconductor glass materials continues to grow worldwide. Investments in semiconductor-grade glass production show that the supply chain for advanced glass substrates is starting to grow in the United States. That is important because future chip manufacturing depends not only on technology, but also on having strong materials suppliers and production networks in place. Right now, the race for leadership in glass substrate technology is wide open. Companies across the United States, Asia, and Europe are investing heavily as they compete to build the next generation of AI chip packaging. Over the next few years, major AI chip designers and large cloud computing companies are expected to begin selecting long-term suppliers, which could shape the market for years to come. Big technology shifts often seem small at first. They usually begin with highly technical changes that receive little public attention, then later become recognized as major turning points for an entire industry. Many experts believe advanced glass substrates could become one of those key moments for the future of computing. Of course, that was the moment everything changed. Honestly, glass substrates are starting to feel exactly like that kind of turning point. While most people focused on export rules, advanced chips, and transistor technology, a quieter race has been happening underneath it all, the race to reinvent chip packaging. The companies and countries leading this shift are not just developing a new material. They are building the foundation that could power the next generation of AI systems. Faster AI training, more efficient data centers, and stronger computing performance could all come from improvements in this hidden layer of technology. The stakes are massive because building advanced glass substrate production lines can cost hundreds of millions, sometimes even billions of dollars. The companies that scale production first could gain a huge long-term advantage through better manufacturing experience, lower costs, and stronger partnerships. In my opinion, this may end up being one of the biggest technology shifts people overlooked at first. The transistor race still matters, but the future of AI could depend just as much on packaging and materials innovation as raw chip power itself. What do you think? Will glass substrates become the next major breakthrough in AI computing, or is the industry moving too fast to predict? Drop your thoughts in the comments. And if you enjoyed this breakdown and want more deep dives into the future of AI and technology, make sure to subscribe to the channel and turn on notifications so you do not miss the next video. Imagine buying a new stick of Corsair Vengeance memory. The black heat spreader looks familiar. The specifications look ordinary. DDR5, 6,000 megatransfers per second. Support for both Intel and AMD platforms. Nothing on the packaging suggests that this particular module represents a major change inside the global semiconductor industry. But then someone opens the software that identifies the components hidden beneath that heat spreader. The manufacturer listed is not Samsung, it is not Micron, and it is not SK Hynix. Instead, the DRAM chips appear to come from Changxin Memory Technologies, better known as CXMT, a Chinese company that, only a few years ago, was barely visible outside the domestic market. That detail may sound small. After all, companies change component suppliers all the time. But memory is not a normal industry. For decades, nearly every modern computer has depended on a remarkably concentrated group of manufacturers. Whether you bought a gaming PC, a workstation, a laptop, or a server, the memory inside was overwhelmingly likely to originate from the same three companies: Samsung, SK Hynix, Micron. Now, Chinese-made DDR5 has apparently appeared inside a product carrying one of the most recognizable names in enthusiast computing. This does not mean China has suddenly defeated the established memory giants. It does not prove that CXMT has better technology, lower prices, or superior reliability. But it does suggest something more subtle, and potentially more disruptive. The door may finally be opening, and once a new supplier enters a market built around only 3 dominant producers, the first thing that changes is not necessarily technology. It is leverage. People love talking about processors. They compare the number of CPU cores, they debate graphics cards, they analyze clock speeds, cooling systems, and benchmark charts containing more colored bars than most human beings should ever be forced to examine. Memory receives far less attention. RAM usually becomes important only when there is not enough of it. Open too many browser tabs, launch a demanding game, edit a large video, or run an artificial intelligence model locally, and suddenly the computer begins hesitating. Data that should remain immediately available has to be moved elsewhere. Applications stutter. Response times stretch. The CPU may be the worker performing calculations, but RAM is the workbench. A faster worker does not help much if the workbench is too small, too slow, or constantly being cleared. Modern DRAM stores information inside billions of microscopic cells. Each cell represents a bit of data by holding a tiny electrical charge. That charge does not remain indefinitely, so the system must refresh it thousands of times every second. Dynamic random access memory. That is what the D in DRAM means. The process sounds straightforward until you remember the scale. A single memory chip must contain billions of these cells, manufacture them with extremely low defect rates, refresh them reliably, and move enormous quantities of information without corrupting the data. One weak cell can become a problem. One unstable timing margin can produce crashes that appear only under certain temperatures. One manufacturing variation can turn a fast chip into a slower one, or into scrap. Making DRAM is not simply printing a large number of identical switches. It is closer to constructing an apartment tower where every room must repeatedly switch its light on and off in perfect coordination, billions of times, while the entire building is moving. And customers expect it to work for years. That difficulty helps explain why the industry became so concentrated. Today, Samsung, SK Hynix, and Micron dominate conventional DRAM production. They did not reach that position because nobody else ever attempted to compete. The history of memory manufacturing is filled with companies that entered confidently, spent enormous sums, suffered through a downturn, and disappeared. DRAM is brutally cyclical. When demand is high, memory prices rise. Manufacturers earn strong profits and expand production. New capacity arrives. Supply increases. Prices fall. Margins collapse. Companies reduce investment or exit the business. Then demand returns. The survivors become stronger. Every cycle acts like an industrial filter, removing manufacturers that lack scale, manufacturing efficiency, or enough cash to survive the bad years. Eventually, only a handful remain. This concentration creates a strange situation. RAM modules are sold under many familiar brands: Corsair, Kingston, G-Skill, Crucial, and others, but the actual silicon beneath the heat spreaders often comes from the same small group of DRAM manufacturers. The module company selects the chips, tests them, places them on a circuit board, programs the operating profiles, adds cooling, and sells the finished product. But the microscopic memory dies themselves are the difficult part. Think of the difference between a bakery and a wheat farm. Many bakeries can package and sell bread under different names, but if almost all of them depend on only 3 farms for wheat, the apparent diversity at the store hides a concentrated foundation. CXMT is attempting to become another farm, and that is why one ordinary-looking Corsair module matters. The module in question appears to be a 16GB Corsair Vengeance DDR5 stick purchased in China. Its reported part number ends with the letters CN, indicating a model intended for the Chinese market. It operates at DDR5-6000 with CL36 timings and a voltage of 1.35 volts. Those numbers are not revolutionary. DDR5-6000 has become a widely used performance point for modern desktop computers. CL36 is respectable, although enthusiasts can purchase lower latency kits. The module is reportedly compatible with both Intel XMP and AMD eExpo memory profiles, allowing systems to apply its rated settings automatically. In other words, this is not an experimental chip sitting beneath laboratory lights. It appears to be ordinary consumer RAM. That may be the most interesting part. Industry changes are not always announced by a dramatic machine, a record-setting benchmark, or an executive standing beneath a giant screen. Sometimes the change is buried beneath a black metal heat spreader, working quietly inside a gaming computer. However, an important qualification is necessary. Corsair has not publicly confirmed the reported CXMT configuration. The evidence comes from photographs and diagnostic information shared online. It appears convincing, and several hardware publications have analyzed it, but it should not be treated as a formal company announcement. That distinction matters. Yet even with that caution, the possibility is significant. A respected international memory brand appears willing to put its name, warranty, and compatibility expectations behind a module using Chinese DRAM. For CXMT, that is more meaningful than another presentation slide. A specification tells people what a company claims it can manufacture. A retail product suggests someone may be willing to depend on it. Changxin Memory Technologies was founded in 2016. That makes it remarkably young compared with the established memory producers. Samsung's semiconductor history stretches back decades. Micron was founded in the late 1970s. SK hynix traces its origins through a long series of companies, factories, and acquisitions. CXMT entered an industry where its future competitors already possessed enormous factories, experienced engineering teams, established customer relationships, and libraries of manufacturing knowledge built through multiple generations of DRAM. It was not entering at the starting line. It was entering while the race was already moving. CXMT initially focused heavily on domestic customers and more mature forms of memory. That was sensible. A new DRAM manufacturer does not immediately begin by challenging the fastest chips available. It must first learn how to manufacture reliably at scale. Yield is everything. Suppose a factory processes a wafer containing hundreds of memory dies. If most of those dies work, the cost of the wafer can be spread across many sellable products. If a large percentage fails, every surviving chip becomes far more expensive. The drawing may be correct. The transistor may function. The first prototype may impress engineers. But until yields rise, the economics remain broken. This is the invisible mountain every new chip producer must climb. CXMT has apparently climbed far enough to offer a broad DDR5 portfolio. The company officially lists memory dies with capacities of 16 gigabits and 24 gigabits, reaching advertised speeds of up to 8,000 megabits per second. It has also displayed multiple kinds of memory modules for desktops, laptops, workstations, and servers. That does not automatically place CXMT beside the leaders. Published specifications are not the same as independent validation, and maximum speed tells only part of the story. But it shows that the company is no longer confined to yesterday's market. The 24 gigabit figure sounds technical, but it creates a practical advantage. 8 bits make 1 byte. Therefore, a 24 gigabit memory die stores 3 gigabytes of data. Place 8 of those dies on a module, and the result is a 24 gigabyte stick of RAM. That enables unusual but increasingly useful configurations. 2 modules can create a 48 gigabyte kit. 4 modules can create 96 gigabytes. For years, desktop memory capacities usually doubled in a predictable pattern: 8, 16, 32, 64, and then 128 gigabytes. 24 gigabit dies fill the large gaps between those levels. A gamer might not need 64 gigabytes, but could benefit from more than 32. A video editor may find 48 gigabytes ideal. A creator running local AI models might want 96 without paying for 128. This is not a cinematic breakthrough. No glowing reactor activates. No computer becomes 1,000 times faster. But semiconductor industries are often transformed by awkward little improvements that make products fit customers more precisely. A 24 gigabyte module is one of those improvements. Chinese brands such as Gloway and Kingbank have already presented DDR5 products using high-density domestic memory. If CXMT can provide these dies consistently, it gains a way to compete that is not based only on being cheaper. It can compete through configuration. That matters because entering an established market with an identical product is difficult. Entering with a slightly different answer to a real customer problem is easier. Why would a company like Corsair consider another supplier now? The answer may begin far away from gaming computers. Inside AI data centers, advanced accelerators depend on high bandwidth memory, or HBM. Unlike conventional desktop RAM, HBM stacks multiple memory dies vertically and places them extremely close to the processor. This architecture can move huge amounts of data while using less space and energy than a collection of ordinary modules. For artificial intelligence, that bandwidth is critical. An AI accelerator without enough memory bandwidth is like a fire engine connected to a garden hose. The processing units may be extraordinarily powerful, but they cannot remain productive if data arrives too slowly. HBM solves part of that problem. It is also extremely valuable. Memory companies can earn far more from advanced data center products than from ordinary consumer DRAM. Naturally, Samsung, SK hynix, and Micron are investing aggressively in HBM and other premium server products. But factories do not possess unlimited capacity. HBM consumes more wafer resources than conventional DDR5. Micron has explained that producing a given amount of HBM can require roughly 3 times the wafer capacity needed for the same quantity of DDR5 bits, with future generations potentially demanding even more. So the AI boom creates a paradox. The world is producing increasingly sophisticated memory, yet ordinary memory can become tighter and more expensive because manufacturing resources are moving toward the premium end of the market. The penthouse is expanding. The ground floor apartments become harder to find. For a new supplier focused on conventional DDR5, that creates an opening. CXMT does not need to outperform the best memory Samsung has ever built. It does not need to lead HBM technology tomorrow. It does not need to win every benchmark. It needs to become good enough, stable enough, and available enough that module manufacturers consider it a practical alternative. That is a very different target. In established technology markets, customers often remain with the same supplier because changing creates risk. New parts require testing. Firmware may need adjustment. Warranty behavior must be understood. Engineers must confirm that the component performs consistently across different systems and temperatures. Even a cheaper alternative may not be attractive if it introduces unpredictable failures. But shortages change the calculation. When the familiar supplier cannot provide enough chips, or when prices rise sharply, the inconvenience of testing a new source begins to look smaller. Scarcity does not merely increase prices, it lowers the walls surrounding the market. This may be the true opportunity for CXMT. The company is arriving at a moment when conventional DRAM customers are actively looking for more supply, while the established manufacturers are chasing the extraordinary economics of artificial intelligence. It is similar to a busy restaurant focusing almost entirely on expensive private events. The regular customers still need dinner. Eventually, another restaurant opens across the street. At first, people may enter only because the usual place is full. Then some discover that the alternative is acceptable. A few may even prefer it. This is where the story requires restraint. A label showing DDR5 6000 does not reveal long-term reliability. It does not tell us how consistently different modules perform. It does not reveal how much overclocking headroom exists, how the chips behave at elevated temperatures, or how efficiently CXMT can manufacture millions of identical dies. Those questions require independent testing. Memory stability can be deceptive. A system may boot normally, run everyday software and appear perfect, then produce an error after several hours under a heavy workload. That is why serious qualification takes time. Manufacturers test voltage margins, temperature ranges, signal integrity, compatibility, retention, and repeated stress cycles. Server customers can be even more demanding, because a small failure rate multiplied across thousands of machines becomes a large operational problem. Corsair's involvement, assuming the module is genuine and production-ready, provides some reassurance. A company selling performance memory has a reputation to protect, but the logo on the heat spreader cannot replace comprehensive testing. At present, the most accurate conclusion is not that CXMT has matched Samsung, Micron, or SK Hynix. It is that CXMT appears to have reached a level where its DDR5 can be considered for a mainstream branded product. That sentence is less dramatic. It is also more important. The immediate threat is not that millions of customers will suddenly reject Korean and American memory. The immediate threat is bargaining power. When only 3 suppliers can provide a critical component, customers have limited options. If one company reduces output, another encounters production problems, and the third prioritizes higher margin products, buyers must accept the available price. A credible fourth supplier changes those conversations. Corsair does not need to replace every Samsung or Micron chip with CXMT memory. The mere possibility of shifting part of its volume can influence negotiations. This is why new competition can affect a market long before it wins a large share. Imagine 3 taxi companies serving an airport. Prices remain relatively predictable because every traveler must choose one of them. Then a 4th operator arrives with enough cars to handle only 10% of passengers. It has not conquered the airport, but suddenly every existing operator knows customers have another choice. Prices, service, and availability begin to matter more. CXMT could play that role in conventional DRAM, even if its products remain concentrated in China and selected international markets. The additional capacity may reduce pressure on global supply. It may encourage module brands to diversify. It could also force established producers to think carefully before moving too much manufacturing attention away from ordinary consumer memory. Competition does not require a new company to become number one. Sometimes it only requires the company to become impossible to ignore. There is another reason the Corsair appearance matters. Trust moves through layers. Most consumers have never heard of the company that manufactured the individual DRAM dies inside their memory kit. They trust the brand printed on the outside. Corsair performs the testing, creates the product profile, provides support and handles the warranty. If the module works, customers rarely investigate further. That allows a relatively unknown semiconductor supplier to enter the market behind a familiar name. This is how industrial acceptance often spreads. First, a component appears in a limited regional product. Then it enters more models. Another brand qualifies it. A laptop manufacturer tests it. Volumes grow. Engineers collect reliability data. Manufacturing improves. Customers become less nervous. Nothing appears to happen, and then the supplier is suddenly part of the normal ecosystem. The hardest step is often not producing the chip. It is persuading the first major customer to take the risk. That is why one Corsair module can mean more than its sales volume suggests. It creates a reference point. Future customers no longer have to ask, "Has anyone used this?" They can ask, "How did it perform?" That is a much easier conversation. Samsung, Micron, and SK Hynix are not standing still. They operate some of the most advanced semiconductor facilities on Earth. They have deep relationships with server companies, computer manufacturers, and smartphone brands. Their technologies have passed years of qualification across enormous product volumes. They also lead in areas where the greatest value is currently being created. HBM is central to AI acceleration. Low-power memory is critical for mobile devices. Advanced server DRAM must combine capacity, efficiency, reliability, and bandwidth at a scale that leaves little room for error. CXMT's presence in DDR5 6000 does not erase those advantages. There is also a difference between demonstrating an 8,000 megabit per second product and shipping it profitably in massive quantities. Yield, cost, consistency, and delivery schedules decide whether a manufacturer becomes a permanent competitor. The established companies have survived multiple market crashes. They understand how to reduce cost from one generation to the next. They can combine technology leadership with enormous purchasing power and global support networks. CXMT therefore faces two races simultaneously. The first is technical, improving density, speed, efficiency, and reliability. The second is economic, producing enough working chips at a low enough cost to earn money throughout the memory cycle. Winning one race does not guarantee victory in the other. Still, the incumbents should not dismiss CXMT because its current products are behind the frontier. Semiconductor progress is cumulative. Every wafer teaches the manufacturer something. Every defective die reveals where the process failed. Every customer qualification exposes another compatibility issue. Every production increase gives engineers more data. A company can purchase equipment, hire experts, and study designs, but manufacturing intuition emerges only through repetition. The first million chips are not merely products, they are lessons. If CXMT begins supplying more module brands, it gains real-world feedback that cannot be replicated inside a laboratory. More shipments reveal failure patterns. More revenue funds better factories. Better yields reduce cost. Lower cost attracts more customers. The loop begins turning. This does not guarantee that CXMT will catch the leaders. Semiconductor history is full of expensive attempts that never closed the gap. But a supplier inside recognized commercial products has crossed a threshold. It is no longer learning only from prototypes. It is learning from the market. Samsung and Micron do not need to fear the exact chip inside today's Corsair module. They need to monitor what the company manufacturing that chip may learn over the next 5 years. Potentially, but not automatically competitive. Customers must trust the chips. The company must continue manufacturing during downturns rather than disappearing when prices fall. And the savings must reach consumers. A module company can purchase cheaper chips without reducing the retail price. The difference may simply become additional margin. There is also the possibility that new supply is absorbed immediately by growing demand. AI computers, larger software, high-resolution content, and local machine learning workloads are increasing the amount of memory used across many devices. Yesterday, 16 gigabytes felt generous. Today, 32 gigabytes is becoming ordinary for performance systems. Tomorrow, 48 or 64 may feel normal. So CXMT might not make RAM dramatically cheap. It may instead prevent prices from rising even faster. Consumers rarely notice the disaster that did not occur. But economically, avoiding a shortage can be as valuable as creating a discount. For years, the memory industry has resembled a table with 3 chairs. Samsung occupied one, SK Hynix occupied another, Micron occupied the third. Many companies sold memory modules, but nearly all eventually returned to that same table to obtain the underlying chips. CXMT is now pulling another chair toward the room. It has not been invited to the head of the table. It may not yet be trusted with the most demanding dishes. and nobody knows whether the chair will survive the next severe market downturn. But it is visible. That alone changes the atmosphere. The Corsair module is not proof that the old order has ended. It is evidence that another supplier may have reached the beginning of commercial acceptance. And beginnings are easy to underestimate because they look unimpressive. A single module, a regional model, 6,000 megatransfers per second, no world record, no dramatic reveal. Just a computer component performing the ordinary job it was designed to perform. Yet entire industries are often disrupted not when a new technology performs an impossible trick, but when it becomes boring enough to use. My view is that Samsung, Micron, and SK Hynix do not need to panic, but they absolutely need to pay attention. CXMT is not yet an equal competitor across the entire DRAM market. The established manufacturers remain far ahead in advanced memory, especially the HBM products powering the AI boom. They possess enormous technical, financial, and manufacturing advantages. But the Corsair discovery suggests that CXMT may be crossing from technical capability into commercial credibility. That is the transition that matters. A company can remain irrelevant for years while producing impressive prototypes. The moment trusted brands begin placing its components inside normal products, the equation changes. The biggest threat to the established companies may not be that CXMT builds faster memory next year. It may be that CXMT provides adequate memory at the exact moment traditional suppliers are concentrating on more profitable AI products. The leaders are moving upward. CXMT is filling the space they leave behind. And once a new manufacturer establishes volume, customers, and manufacturing experience in the mainstream market, it can begin climbing toward the premium segments later. That journey will be difficult. It could take years. It may encounter technical setbacks, weak yields, or another brutal memory downturn. But for the first time, the possibility no longer looks theoretical. A Chinese DRAM supplier appears to be hiding beneath a Corsair heat spreader. That is small enough to overlook, and perhaps too important to ignore. So what do you think? Would you buy a Corsair memory kit containing CXMT chips if it offered the same warranty and performance at a noticeably lower price? Or would you stay with memory manufactured by Samsung, Micron, or SK Hynix until Chinese DRAM has built a longer record for reliability? Let me know where you stand in the comments. And if you want to see how China's semiconductor industry is moving from laboratory announcements into real products, supply chains, and computers, subscribe to Eastern Engine. Because the next major shift in technology may not arrive inside a futuristic supercomputer. It may already be sitting inside an ordinary stick of RAM. A data center can contain the fastest AI chips ever built. Thousands of GPUs, hundreds of billions of transistors, cooling systems powerful enough to remove the heat generated by a small industrial facility. And yet the entire machine can still be slowed down by something that looks almost ordinary. A strand of glass, not a silicon wafer, not high bandwidth memory, not another advanced processor, glass. Inside modern AI data centers, microscopic pulses of light travel through optical fiber, carrying information between servers, switches, buildings, and entire campuses. These fibers have become the nervous system connecting the chips together, and demand is now increasing so quickly that some of China's largest optical fiber manufacturers reportedly have production lines operating near full capacity, with order schedules extending into early 2027. One industry executive estimates that AI-focused data centers may require approximately 36 times more fiber than traditional CPU-based racks. Corning says individual 72 GPU systems, including designs based around NVIDIA's Blackwell platform, can already need 16 times more fiber than conventional cloud switching racks. That helps explain why NVIDIA recently entered a long-term partnership with Corning to expand American optical connectivity manufacturing capacity tenfold. It also helps explain why NVIDIA committed $2 billion to optical specialist Coherent, while Meta agreed to purchase as much as $6 billion of fiber, cable, and connectivity equipment from Corning. The next AI bottleneck may not be the ability to manufacture more GPUs. It may be the ability to connect them, because an isolated AI chip is not an AI factory. It is simply a very expensive calculator waiting for data, the component hiding in plain sight. When most people picture artificial intelligence, they imagine processors, large black packages, glowing server racks, silicon wafers moving through advanced factories. Optical fiber rarely receives the same attention because the technology appears passive. A fiber does not calculate. It does not train a model. It does not store billions of parameters. It simply carries information. But that simple job has become one of the hardest problems in modern computing. Large AI models are not usually trained on one processor. The work is divided across hundreds, thousands, or even tens of thousands of accelerators. Every accelerator calculates only one part of the result. Then the machines must exchange what they learned again, and again, and again. The processors are constantly talking. If that communication slows, the expensive computing hardware waits. Imagine hiring 10,000 brilliant engineers to build one aircraft, then giving them a single narrow hallway through which every drawing, component, and instruction must pass. The engineers may be fast. The hallway determines how quickly the aircraft is completed. Optical fiber is the hallway, and AI has turned that hallway into a traffic jam. Why AI needs so much more fiber? Traditional data centers mainly handle requests moving between users and servers. Someone loads a website, a company accesses a database, a video is streamed. Information generally enters the data center, reaches the correct machine, and leaves again. AI clusters generate a different kind of traffic. Most of the communication happens inside the facility. GPU to GPU, rack to rack, switch to switch, building to building. This is called east-west traffic. During AI training, thousands of accelerators repeatedly exchange model updates. If one part of the cluster finishes its calculation early, it may still have to wait for the others before the next step begins. The network, therefore, cannot merely be fast on average. It must be consistently fast. One congested connection can hold back an entire group of processors. This is why AI networks are built with enormous numbers of redundant links. Engineers try to ensure that any GPU can communicate with many others without all the traffic being forced through one narrow route. The network begins to resemble a giant web. More processors create more possible connections. More connections require more ports. More ports require more transceivers, switches, connectors, and fibers. The growth is not always linear. Double the number of accelerators, and the communication problem may increase by far more than 2 times. That is how a data center filled with GPUs can consume dozens of times more optical fiber than a traditional server installation. Why copper cannot handle everything? Copper still plays an important role inside computing systems. It is inexpensive, it is familiar, and over short distances it can move data extremely quickly. But copper has limits. As transmission speeds increase, electrical signals weaken, interference becomes harder to control, power consumption rises because the system must work harder to preserve signal quality. A short connection inside one server can remain electrical. A connection running across a row of racks becomes more difficult. A link crossing a large building becomes harder again. At 800 gigabits per second, and especially as networks move toward 1.6 terabits, distance becomes expensive. Copper cables can also become thick and heavy. A rack containing hundreds of high-speed connections can begin to resemble a mechanical sculpture made from cables. Fiber changes the equation. Instead of pushing electrons through metal, the system converts data into pulses of light. Those pulses travel through an extremely pure glass core surrounded by material with a slightly different optical property. Light reflects internally and remains trapped inside the fiber, traveling long distances with far less signal loss than an equivalent electrical connection. The strand can be thinner than a human hair, yet it may carry extraordinary amounts of data. That is why AI infrastructure is gradually shifting from copper toward optics, not everywhere, not all at once, but closer and closer to the processor. The light is moving toward the chip. Traditional optical networks use pluggable transceivers. A cable reaches the front of a network switch. An optical module converts the incoming light into an electrical signal. The electrical data then travels across the circuit board to the switching chip. That arrangement has worked well, but as bandwidth rises, the electrical path between the optical module and the chip begins consuming more power. It also creates heat. NVIDIA's answer is co-packaged optics. Instead of keeping optical components at the outer edge of the switch, the optical engines move much closer to the networking silicon. The electrical path becomes shorter. More of the journey happens as light. NVIDIA says its photonics-based networking systems can improve power efficiency, while allowing AI clusters to scale to much larger numbers of GPUs. But this transition does not reduce the importance of glass. It increases it. More optical engines create more optical connections. More connections require more fibers, connectors, splitters, and precision components. The light may move closer to the chip. The glass follows it. This is why NVIDIA's partnerships with Corning and Coherent matter. The company is not merely buying cable. It is helping expand the manufacturing base for the optical architecture its future AI systems will depend on. What sold out until 2027 really means. The phrase sounds absolute. It is not. China has not run out of every spool of fiber. Homes will not suddenly lose internet access because AI consumed the world's glass. The real situation is more specific. Industry reports indicate that large Chinese manufacturers such as Hengtong and Fiberhome are operating at high utilization, while delivery schedules for some optical products now extend into early 2027. Other Chinese suppliers have reported overseas orders booked into the first quarter of next year. That means much of the available manufacturing capacity has already been committed. A new customer can still place an order. The customer may simply have to wait much longer than before, and the shortage is not equal across every product. Basic telecom fiber is different from the bend-resistant, high-density and low-loss fiber required inside advanced data centers. AI installations often need specialized products capable of being packed tightly into limited spaces while maintaining signal quality. Those are precisely the products experiencing the greatest pressure, so sold out is useful shorthand. The more accurate description is this: the production calendar is filling faster than factories can expand it. The demand curve turned vertical. In 2025, global demand for optical fiber and cable used in data centers reportedly increased by almost 76%. The total reached nearly 70 million core kilometers. 1 core kilometer represents 1 fiber core extending for 1 kilometer. A cable containing hundreds or thousands of individual cores therefore adds up quickly. Industry forecasts suggest demand could exceed 100 million core kilometers in 2026. That is not normal growth. That is the shape of a market being reorganized. For years, optical fiber demand was driven mainly by telecom networks, broadband expansion, and mobile infrastructure. Fiber traveled toward homes. Now, increasingly, it travels toward GPUs. One Chinese industry expert summarized the transformation clearly. Optical fiber used to be installed near households. Now it is installed beside every accelerator. The destination changed. The volumes changed with it. And manufacturers that survived years of weak pricing suddenly find themselves facing more demand than they prepared for. Why factories cannot simply make more optical fiber look simple after it is finished? The manufacturing process is not. It begins with a preform. A preform is a large, extremely pure cylinder of specially engineered glass. It contains the same basic optical structure that will exist inside the final fiber, but at a much larger scale. The center becomes the fiber core. The surrounding glass becomes the cladding. To create the preform, manufacturers deposit carefully controlled layers of glass material while adjusting chemical composition and refractive properties. Impurities must be minimized. A tiny contamination can scatter light. A slight variation can change how the signal travels. Once the preform is completed, it is placed inside a tall drawing tower. The bottom is heated until the glass softens. Gravity and precise mechanical control pull a thin strand downward. A cylinder weighing hundreds of kilograms can become thousands of kilometers of optical fiber. The strand must maintain an almost perfectly consistent diameter. Protective coatings are applied immediately. The fiber is tested, bundled, and later assembled into cables. Expanding this process is not as simple as buying another machine and turning it on. Preform factories require specialized equipment, skilled engineers, clean production environments, and significant capital. New capacity can take 18 months to 2 years to become operational. That delay explains the current mismatch. AI demand changes in months. Glass capacity changes in years. The preform is the real bottleneck. The preform is often the most valuable part of the optical fiber supply chain. It determines the quality and performance of the final strand. Manufacturers can sometimes expand cable assembly capacity relatively quickly. Producing much more high-quality preform is harder. That is where technical knowledge becomes important. The glass must be pure enough that light can travel through kilometers of fiber while losing only a small fraction of its power. The composition must remain stable from the center of the preform to its outer edge. The material must draw smoothly without creating microscopic defects. Think of stretching a highly detailed image painted on a thick cylinder until the cylinder becomes a thread. Every internal proportion must remain correct. China's major fiber companies have invested heavily in this upstream capability. Fiberhome recently displayed what it describes as the world's largest optical fiber preform, reflecting the industry's effort to extract more finished fiber from each manufacturing cycle. But even larger preforms do not instantly solve the shortage. They must be manufactured consistently. They must meet the correct specifications, and the rest of the production system must be able to draw, coat, test, and cable the resulting fiber. The chain is only as fast as its slowest operation. Why China matters? China built enormous optical fiber capacity during the expansion of broadband, mobile networks, and national communications infrastructure. That scale once contributed to oversupply and weak pricing. Factories competed aggressively. Margins narrowed. Some smaller producers left the market. Larger manufacturers became cautious about adding even more capacity. Then AI arrived. The same industry that had spent years worrying about too much fiber suddenly faced the opposite problem. Chinese manufacturers now supply domestic computing projects while receiving rising orders from overseas customers. First quarter overseas sales across parts of the Chinese fiber industry reportedly increased by more than 55% compared with the previous year. The advantage is not only low manufacturing cost, it is scale. Large preform capacity, existing draw towers, cable factories, experienced engineering teams, and supply networks already capable of delivering enormous quantities. The AI boom did not create this industrial base, it revealed how valuable it had become. The price of specialized glass is rising. Not every fiber price has moved equally, but certain high-performance categories have increased sharply. One specialized bend-resistant product used in dense installations reportedly rose from around 32 yuan to as much as 240 yuan per core kilometer over roughly 1 year. That represents an increase of several hundred%. Why would bend resistance matter? Because AI data centers are crowded. Cables must turn around tight corners. They pass through racks, trays, and densely packed connection panels. A normal fiber bent too sharply can leak light and weaken the signal. Bend-resistant fiber maintains performance in tighter spaces. That becomes valuable when thousands of connections must be installed inside a limited area. The data center does not merely need more glass. It needs better glass, and better glass is harder to produce quickly. NVIDIA's response is not small. In May 2026, NVIDIA and Corning announced a multi-year partnership to expand optical connectivity manufacturing in the United States. Corning plans to increase its American optical connectivity capacity tenfold. It also plans to raise American fiber production capacity by more than 50% and construct 3 new manufacturing facilities. That is not the response of a company expecting demand to return to normal next quarter. NVIDIA separately announced a $2 billion investment in Coherent, alongside purchase commitments and access to future optical capacity. Coherent manufactures lasers, optical components, and networking products needed to convert electrical information into light and move it through AI systems. Meta has reached its own agreement with Corning worth as much as $6 billion. The pattern is clear. Large technology companies are no longer treating fiber as a generic product they can purchase whenever needed. They are securing manufacturing capacity years in advance. They are funding expansion. They are reserving supply. That usually happens when a component moves from being a commodity to being strategically important. Can a glass shortage actually delay AI? Potentially. A company can purchase GPUs and still be unable to deploy them immediately if the rest of the infrastructure is missing. Servers need power, cooling, switches, memory, buildings, transformers, and connectivity. An AI cluster cannot simply place thousands of accelerators in one room and expect them to cooperate. The network must be installed, tested, and synchronized. If optical cables arrive late, the entire facility may open late. If designs. But each workaround has limits. At some point, physical data must move. The processors cannot calculate information they have not received. The honest catch. The 36 times figure should not be treated as a universal law. Different data centers use different architectures. A small inference facility may not resemble an enormous training cluster. Some systems use more copper, others move rapidly toward optics. The number of fibers depends on rack design, GPU count, redundancy, network topology, and transmission speed. Corning's estimate of 16 times more fiber for certain 72 GPU nodes may be more relevant to specific modern systems. The 36 times estimate describes the broader intensity of AI-focused facilities compared with traditional CPU racks. Both numbers communicate the same direction. AI networking is far more fiber-intensive than conventional computing. The exact multiplier changes. The demand problem remains. My take. My view is that this story reveals something important about every major technology boom. The public focuses on the glamorous component, the GPU, the model, the benchmark, but the limitation often appears somewhere less exciting. A transformer, a cooling pipe, a memory package, a cable. In this case, a strand of purified glass. NVIDIA can design a faster accelerator. But if thousands of those accelerators cannot exchange data quickly enough, much of the additional computing power is wasted. That is why optical fiber has moved from the background to the center of AI infrastructure planning. The most interesting part is not simply that China has large fiber factories. It is that those factories were built for one technological era and have suddenly become critical to another. Infrastructure created for telecom networks is now being redirected toward AI. Manufacturing capacity that once looked excessive now looks scarce, and the industry cannot expand quickly because the true bottleneck begins with a highly specialized cylinder of glass that may take years of factory investment to produce at a larger scale. No glass, no connection, no AI factory. So what do you think? Will optical fiber become one of the biggest hidden constraints on artificial intelligence over the next several years? Or will new networking designs, multi-core fiber, and co-packaged optics allow manufacturers to stay ahead of demand? Let me know your view in the comments. And if you want more grounded stories about the materials, machines, and overlooked components shaping the future of computing, subscribe to Eastern Engine. Because the next limit on artificial intelligence may not be hiding inside the chip. It may be the glass connecting one chip to another. His name is Dong Hui. He is 39 years old. 6 years ago, a car accident left him paralyzed from the neck down. He couldn't move his fingers. He couldn't write. Something as ordinary as holding a pen had become completely impossible, and every specialist he'd seen told him the same thing in different words: this is permanent. Then surgeons placed a coin-sized chip between his skull and his brain. 11 months later, sitting in the courtyard of his home in China's Henan province, Dong Hui picked up a pen. Slowly, carefully, deliberately, he wrote his name. Then he wrote, "Thank you." Then he wrote the date. He later told journalists he was so overwhelmed that he missed a stroke in his own name. "I couldn't believe I was able to write again. I was so excited." That chip, the one that gave Dong Hui back his hands, just became the first invasive brain-computer interface in history to receive full commercial approval anywhere on Earth. Not a trial permit, not a research exemption, a product license. Available to real patients, covered by China's national health insurance. In production right now, scaling to meet demand. And here's the part that changes the entire story. While that was happening, Elon Musk's Neuralink, the most famous, most funded, most publicized brain chip project in the world, still has 21 people in an experimental trial. No commercial approval, no product license, no insurance coverage, anywhere. The race that everyone assumed Elon Musk would win, someone just crossed the finish line. And it wasn't him. To understand what just happened, you need to understand how this competition looked from the outside for the past several years. Neuralink was the story. Full stop. Elon Musk announced it, hyped it, described a future where paralyzed people would walk again, where blind people would see again, where the entire interface between human consciousness and computing would be reinvented. He is the most followed person on the planet. Every announcement got global coverage. Every trial update was front-page news. The assumption baked into almost every article written about brain-computer interfaces was simple. Neuralink leads, everyone else follows. Meanwhile, in Shanghai, a startup called Neurical Technology was quietly doing something different. No celebrity CEO, no viral announcements, no promises about controlling computers with your thoughts or uploading your memories. Just a research team, a partnership with Tsinghua University, one of China's most prestigious technical institutions, and a singular focus on getting one specific device approved for one specific group of patients. The device was called Neo. It's roughly the size of a coin. It takes about 90 minutes to implant. It sits between the skull and the outer protective membrane of the brain, called the dura mater, with 8 sensors pressing gently against that membrane, without ever penetrating the brain tissue itself. Wireless signals travel from the implant to an external processor, which translates the brain's electrical activity into commands for a robotic glove, allowing patients with severe hand paralysis to perform basic grasping movements they hadn't been able to do in years. In March 2026, China's National Medical Products Administration gave it full commercial clearance. 36 clinical trials, 32 of them completed in a compressed window in 2025 alone. And then, approved. Not for trials, for hospitals, for patients, for production. The first invasive brain implant ever cleared for sale anywhere in the world. Here's the counterintuitive part of this story. Neo is not the most powerful brain chip ever built. It almost certainly isn't. Neuralink's N1 chip penetrates the brain's outer cortex directly, accessing neural signals closer to their source and potentially enabling finer, more precise control. Neuralink's long-term ambitions, restoring sight, enabling full-body movement, eventually merging human consciousness with computing, are technically more audacious than anything Neo currently does. So how did the less aggressive device win the regulatory race? Because less aggressive and commercially viable are not opposites. They're often the same thing. NEO's design is epidural. It sits on top of the brain's protective membrane, rather than inside the brain tissue itself. A researcher at the University of Technology, Sydney, speaking to MIT Technology Review, explained why that distinction matters enormously in a regulatory context. An epidural approach carries significantly lower risk of bleeding and lower risk of signal loss over time than electrodes that penetrate the cortex. When a regulator is evaluating a device for broad commercial use, not just in a handful of carefully selected trial participants, but in real hospitals with real patients who have varying health conditions, risk profile is everything. NEO didn't win because it outperformed Neuralink. It won because it was designed to be approvable, not just impressive. And Neuralink had something else that Neuralink doesn't: state-level strategic backing with matching urgency. China has listed brain-computer interface technology as one of 6 national strategic priorities, alongside quantum computing and humanoid robotics. That designation isn't symbolic. It comes with coordinated funding, expedited regulatory pathways, and the kind of institutional alignment between researchers, companies, and government that compresses the timeline from lab to clinic in ways that are genuinely difficult to replicate in a system where commercial interests, regulatory bodies, and research institutions operate independently. Neuralink ran 32 of its 36 trials in a matter of months in 2025. That pace of clinical validation reflects a system operating in a different gear from what Neuralink has been navigating. The facts and the regulatory milestones are important, but there's a human being at the center of this story, and he deserves more than a footnote. Everything you do online is being watched: your provider, advertisers, even governments. NordVPN encrypts your connection, hides your location, and unlocks the open internet from anywhere. Grab the deal, link in the description. Dong Hui was paralyzed in 2018, 6 years of his life spent unable to use his hands. Then he saw something on television, a news report about another paralyzed man in China who had regained some movement through a brain-computer interface trial. He signed up for Neuralink's program in October 2023, 1 month after watching that report. The implant went in. The rehabilitation process began. Slowly, painstakingly, his brain learned to communicate with the device, and the device learned to interpret his brain. 11 months later, he wrote his name in his own courtyard. He also told journalists he hadn't expected it to work. He'd spent 6 years being told his condition was permanent. The moment he picked up that pen was the moment 6 years of that certainty collapsed. This is what NEO actually is, underneath all the regulatory language and competitive framing. It is a device that gave a man back the ability to write his own name, and it is now approved for use in a country of 1.4 billion people, covered by the National Health Insurance System, with more patients entering the program as production scales. The numbers behind that aren't just impressive, they're staggering. Hundreds of thousands of people in China live with the kind of spinal cord injury NEO is designed to treat. Here's the pattern that keeps appearing in technology, and it's directly relevant to everything covered on this channel. A technology is invented, usually in a Western lab, usually by researchers with enormous resources and high ambitions. For years, everyone watches that original team. They assume the leader stays the leader. They write articles about when the technology will mature, when it will become commercial, when if everyone. It happened with diamond cooling. NVIDIA's CEO was flying to China while most of the world was still debating whether diamond was even practical. And now it's happening with brain chips. Neuralink has more press coverage than every other BCI company combined. And a startup most people have never heard of, built in Shanghai with funding from Tsinghua University and backing from China's National Technology Strategy, just became the first to put a commercially approved brain implant into a patient outside a clinical trial. The pattern isn't that the famous version is wrong or that the quiet version is always better. The pattern is that fame and leadership aren't the same thing. And in technology, the milestone that actually counts isn't who announced it first, it's who shipped it first. NEO is the first. It will not be the only. China has at least 2 more BCI devices behind NEO in the pipeline. Neuroxess and StairMed are both developing competing implants domestically. The Beijing Brain Institute's BEINA01 system is expected to reach market by 2028. Within the span of roughly 2 years, China could have multiple commercially approved brain implants operating in its healthcare system, each generation learning from the one before it, while the rest of the world is still working through regulatory trials. The advantage this creates isn't just about one device. It's about data. Every patient who receives NEO generates real-world performance data in a commercial healthcare setting. That data, how the implant performs over months and years, which patient profiles respond best, which failure modes appear and how often, is exactly the kind of evidence that makes second-generation devices better. And it is the kind of evidence that regulators in other countries will eventually require before approving anything. China now has a head start not just in commercial approval, but in the accumulation of long-term real-world safety and performance data. That compounding lead is far harder to close than a regulatory gap. It's the same dynamic as the glass substrate story, the same dynamic as the diamond chip story. Being first doesn't just mean you got there early, it means every subsequent year of operation makes you harder to catch. For Neuralink specifically, the competitive picture has shifted in a way that doesn't get fully acknowledged. Neuralink's technical ambitions remain larger. Its long-term vision, the idea of a general-purpose brain-computer interface that goes far beyond motor rehabilitation, hasn't changed, but it is now competing in a landscape where a rival has commercial approvals, insurance coverage, real patients, and accumulating real-world data, while Neuralink is still adding participants to a clinical trial. That's a different kind of pressure than it was 12 months ago. Here's what strikes me most about this story, and it's something I keep coming back to. Neuralink had everything: the money, the attention, the most famous founder in technology, a decade of runway, and Neo, a startup from Shanghai with a fraction of the profile, shipped first. Not because Neuralink is more talented than Neuralink's engineers, both teams are world-class, but because Neuralink made a device that was designed to clear regulatory hurdles rather than one designed to impress a keynote audience. They optimized for approval, not for ambition. And in the market for medical devices, approval is everything. The most powerful chip in the world is useless inside a lab. I think the Neuralink story is far from over. A device that actually penetrates the cortex and accesses finer neural signals will likely enable capabilities that Neo simply can't. But Neuralink now has to develop and prove those capabilities while a competitor is already in hospitals, already covered by insurance, already generating data, and already treating patients. That's a completely different race than the one Neuralink thought it was running. Here's my question for you, and I want your honest answer. Does this change how you think about Neuralink? Because here's the tension. Neo got to market first, but Neuralink's ambitions are larger. Is first to market in medicine the thing that matters most, or does the device with the higher ceiling eventually win regardless? Drop your actual opinion in the comments. This one I'm genuinely curious about. If you want to keep following these stories, the ones that rewrite which country leads in a technology that seems settled, subscribe to Eastern Engine and turn on notifications. Brain chips, diamond chips, glass chips, the substrate layer, the thermal layer, all of it connects. And all of it is moving faster than most people realize. Thanks for watching. See you in the next one. Just 6 months ago, the global AI industry was forced to confront an uncomfortable reality. A relatively unknown Chinese startup called DeepSeek released an open-source reasoning model that stunned Silicon Valley. Investors suddenly realized that building world-class artificial intelligence might not require endless billions of dollars or the most expensive hardware in the world. Nvidia shares plunged, semiconductor stocks sold off, and one simple question echoed across Wall Street. What if China was catching up much faster than anyone expected? Many people assumed that moment was a one-time surprise. They believed American companies would quickly regain their lead, push even further ahead, and restore confidence in the AI race. But now, it has happened again. This time, the company isn't DeepSeek, it's Moonshot AI. And instead of releasing another incremental chatbot, Moonshot has unveiled what it calls the world's largest open-weight artificial intelligence model ever created. Its name is Kimi K3, and almost immediately after its announcement, investors around the world began asking whether another major shift in the AI race had just begun. The timing couldn't have been more dramatic. This past week, semiconductor stocks suffered one of their worst performances in more than a year. The Philadelphia Semiconductor Index fell sharply, while companies like Nvidia, AMD, and Broadcom all finished the week lower. Across Asia, technology shares also came under pressure as investors tried to understand what China's latest AI breakthrough could mean for the future of the industry. Of course, markets never move because of one single event. There were already concerns about high AI valuations, massive spending by technology giants, and broader geopolitical uncertainty. But Moonshot's announcement added fuel to an already nervous market because it reminded investors of something they had hoped was behind them. The DeepSeek surprise. For the second time this year, a Chinese AI company appeared seemingly out of nowhere with technology that demanded attention from the entire world. So what exactly is Kimi K3? Why are AI researchers taking it seriously? Why did Wall Street react so quickly? And perhaps most importantly, is this another DeepSeek moment? Or is it something even bigger? To understand why this announcement matters, we first need to understand the company behind it. Unlike OpenAI, Google, or Anthropic, Moonshot AI isn't a household name outside China. In fact, many people in the United States had probably never even heard of the company before this week. Yet inside China's technology industry, Moonshot has been quietly building for years. Founded by a team of AI researchers and entrepreneurs, the company quickly became one of China's most valuable artificial intelligence startups. It attracted backing from some of the country's largest technology investors, including Alibaba, giving it access to enormous computing resources, engineering talent, and one of the fastest-growing AI ecosystems anywhere in the world. Instead of chasing headlines, Moonshot focused on building large language models capable of handling extremely long documents, complex reasoning tasks, software development, and enterprise applications. Its previous Kimi chatbot gained popularity inside China because it could process enormous amounts of text at once, far more than many competing systems at the time. But Kimi K3 is an entirely different level. According to Moonshot, the new model contains a staggering 2.8 trillion parameters, making it the largest open-weight AI model ever announced. Instead of functioning like a traditional dense neural network where every parameter is activated for every request, Kimi K3 uses what's known as a mixture of experts, or MoE, architecture. That distinction is incredibly important. Rather than activating all 2.8 trillion parameters every time someone asks a question, the model intelligently selects only the most relevant expert networks needed for each task. This dramatically reduces the amount of computing power required while still allowing the overall system to benefit from an enormous knowledge base. In simple terms, it's a bit like having thousands of specialists available inside one giant company. Instead of asking every employee to solve every problem, only the few experts who are actually needed join the conversation. The result is a system that can be both extremely large and surprisingly efficient. That efficiency is becoming one of the defining themes of China's AI industry. Rather than trying to simply build the biggest data centers or purchase the largest number of GPUs, many Chinese companies are increasingly focused on getting more performance from every unit of compute they already have. This strategy has become even more important as US export controls continue limiting China's access to NVIDIA's most advanced AI chips. Instead of slowing down innovation, those restrictions may have encouraged Chinese companies to rethink how modern AI systems should be designed in the first place. And that brings us to the most interesting part of the story. Because Kimi K3 isn't attracting attention simply because it's large, it's attracting attention because of how well it performs. In independent benchmark testing released alongside the announcement, Kimi K3 demonstrated results that immediately caught the attention of AI researchers around the world. On several demanding software engineering and coding evaluations, the model ranked among the strongest systems available, competing directly with leading American models, and even outperforming them in certain specialized tests. That doesn't mean Kimi K3 is suddenly the undisputed best AI model on Earth. Different benchmarks measure different abilities, and several leading US systems still perform exceptionally well across a wide range of tasks. But that's not really the point. The point is that another Chinese company has once again produced an AI system capable of competing at the highest levels of the industry. And for investors, that's becoming increasingly difficult to ignore. But here's where the story becomes much more interesting. When most people hear that an AI model has 2.8 trillion parameters, they naturally assume bigger automatically means better. In reality, that's not how modern artificial intelligence works anymore. Over the past few years, the AI industry has undergone a quiet but significant shift. Companies are no longer competing simply to build the largest model possible. They're competing to build the smartest, fastest, and most efficient model. And that's exactly where Kimi K3 enters the conversation. Unlike earlier generations of large language models that attempted to activate every parameter for every request, Kimi K3 uses what's called a mixture of experts, or MoE architecture. Think of it like this. Imagine you own a company with 10,000 employees. If every employee attended every meeting, the company would become painfully slow and incredibly expensive to operate. Instead, businesses assign specialists to specific problems. The legal team handles contracts, engineers solve technical issues, finance manages budgets, marketing focuses on customers. Only the people actually needed join the discussion. Modern AI is beginning to work the same way. Instead of waking up all 2.8 trillion parameters every time someone asks a question, Kimi K3 activates only a relatively small portion of the network depending on the task being performed. That means the model can deliver much of the capability of an enormous system without paying the full computational cost every single time. And that's becoming increasingly important. Training frontier AI models now costs billions of dollars. Running them can cost millions more every month. The biggest challenge in artificial intelligence is no longer simply creating smarter models. It's figuring out how to make those models affordable enough for millions of people to actually use. This is exactly why researchers across the industry are paying attention to architectures like Mixture of Experts. They represent one possible path toward making next-generation AI dramatically cheaper to operate. For China, this strategy carries even greater importance. Because of US export restrictions on advanced AI hardware, Chinese companies have spent the past several years learning how to squeeze every ounce of performance from the computing resources they already possess. Instead of assuming they can always buy more cutting-edge chips, many Chinese AI companies have focused on software optimization, distributed computing, model compression, and efficient architectures. In many ways, necessity has become a powerful driver of innovation. That doesn't mean China has solved every hardware challenge. Far from it. Companies like NVIDIA still produce many of the world's most advanced AI accelerators, and access to high-end computing remains one of the industry's biggest competitive advantages. But Kimi K3 demonstrates that algorithm design can sometimes narrow the gap faster than people expect. And that's exactly what has captured Wall Street's attention. Because investors aren't simply asking whether Moonshot built another chatbot, they're asking whether the economics of AI are beginning to change. For the past 2 years, the dominant assumption across financial markets has been relatively simple. The more advanced AI becomes, the more GPUs everyone will need. That assumption helped drive NVIDIA's extraordinary rise into one of the world's most valuable companies. Every major AI company, from OpenAI and Anthropic to Google, Meta, Microsoft, Amazon, and xAI, announced plans to spend tens or even hundreds of billions of dollars building larger data centers packed with increasingly powerful graphics processors. The belief was straightforward. More intelligence required more hardware. More hardware meant more NVIDIA chips. More NVIDIA chips meant higher revenues. But Chinese companies like DeepSeek, and now Moonshot, have introduced an uncomfortable question. What if software improvements begin arriving faster than hardware improvements? What if smarter algorithms reduce the amount of computing needed for many AI tasks? Suddenly, investors are no longer evaluating only who has the biggest GPU cluster. They're also asking who has the most efficient software. That subtle shift can have enormous financial consequences. It doesn't necessarily mean NVIDIA loses. In fact, many experts believe better AI models could ultimately increase demand for computing because cheaper intelligence encourages wider adoption across businesses, governments, healthcare, manufacturing, robotics, education, and countless other industries. History has shown this pattern many times before. When computers became cheaper, people didn't buy fewer computers, they bought more. When internet access became faster, people didn't use less bandwidth, they used dramatically more. Efficiency often expands markets rather than shrinking them. The same could eventually happen with artificial intelligence. But markets don't always think about the long term. Investors often react first and analyze later. That's one reason semiconductor shares experienced heavy volatility after Moonshot's announcement. The immediate question wasn't whether Kimi K3 would destroy NVIDIA's business. The question was whether Wall Street had underestimated how quickly Chinese AI companies were closing the gap. And this wasn't happening in isolation. Over the past year alone, China has produced a steady stream of AI announcements that have challenged long-standing assumptions. Huawei continued expanding its AI computing ecosystem despite export restrictions. DeepSeek demonstrated that frontier-level reasoning could be achieved with surprisingly efficient training methods. Alibaba introduced increasingly competitive enterprise AI systems. Baidu continued pushing foundation models into commercial deployment. Tencent accelerated AI integration across its enormous software ecosystem. Now Moonshot has added another headline. Viewed individually, each announcement may seem manageable. Viewed together, they begin telling a much larger story. Not that China has overtaken the United States, but that China's AI ecosystem is becoming far deeper, broader, and more competitive than many analysts predicted just a year ago. And that's exactly why Kimi K3 has generated headlines around the world. Because this isn't just another product launch. It's another data point suggesting that the global AI race is becoming far more competitive than anyone expected. But there's another reason Kimi K3 is making headlines, and it has nothing to do with parameter counts. It's the word open. That single word could end up being more important than all 2.8 trillion parameters combined. To understand why, imagine there are two incredibly powerful AI models. One can only be used through a company's website or paid subscription. The other can be downloaded, modified, improved, and integrated into almost any application. Which one spreads faster? History has already given us the answer. Open technologies have repeatedly transformed entire industries. Linux became the backbone of cloud computing. Android became the world's largest mobile operating system. Python became one of the most widely used programming languages on Earth. When developers are allowed to build on top of a technology instead of simply renting access to it, innovation often accelerates dramatically. That's exactly why the AI industry has become divided into two very different philosophies. On one side are companies that keep their frontier models largely closed. On the other are companies increasingly embracing open-weight systems that researchers, startups, universities, and businesses can run themselves. Moonshot has clearly chosen the second path. The company announced that Kimi K3's weights will be publicly available, allowing developers around the world to experiment with the model instead of relying exclusively on Moonshot's own servers. That decision immediately expands the potential audience far beyond China. A software company in Germany could fine-tune it for manufacturing. A university in Canada could study its architecture. A startup in Brazil could build an entirely new product on top of it. A robotics company in Japan could integrate it directly into industrial automation systems. Instead of one company creating every application, thousands of developers suddenly gain the ability to build their own. That's one reason many analysts believe open-weight models can spread much faster than traditional closed platforms. And that's exactly what happened with DeepSeek. When DeepSeek released its reasoning model earlier this year, it wasn't simply another chatbot entering the market. Developers immediately began creating optimized versions, local deployments, research projects, and enterprise applications around it. Within weeks, DeepSeek had become part of conversations taking place far beyond China's borders. Now Moonshot appears to be following a remarkably similar strategy. But this time, the model is even larger, even more capable, and arriving at a moment when businesses around the world are actively searching for alternatives in the rapidly evolving AI market. That combination explains why many observers have started calling Kimi K3 another DeepSeek moment. Not because it's identical, but because it represents another unexpected challenge to assumptions that had become deeply embedded across the technology industry. For years, many people believed only a handful of American companies could consistently build frontier AI models. OpenAI, Google, Anthropic, Meta, Microsoft, those names largely defined the conversation. Now the list is expanding. DeepSeek, Moonshot, Huawei, Alibaba, Baidu, Tencent. Each company contributes something different. Some specialize in enterprise AI, others focus on consumer applications. Some build hardware, others build foundation models. Together, however, they form something much larger than any individual announcement: an ecosystem. And ecosystems are often much harder to compete against than individual companies. Silicon Valley understands this better than anyone. Apple didn't become dominant because of the iPhone alone. It built an ecosystem. Google didn't become a trillion-dollar company simply because of search. It built an ecosystem. Amazon didn't transform global commerce by creating one successful product. It built an ecosystem. China appears to be applying the same lesson to artificial intelligence. Instead of relying on one national champion, multiple companies are advancing simultaneously. Some compete against each other, others collaborate. Universities continue producing AI research. Cloud providers expand computing infrastructure. Chip manufacturers improve domestic hardware. Software companies integrate AI into existing products. Each piece strengthens the others. That's why focusing only on one model risks missing the bigger picture. Kimi K3 isn't important solely because of what it can do today. It's important because it shows another major Chinese company reaching the frontier of AI development. And every time another company reaches that frontier, the competitive landscape becomes more crowded. For American technology companies, that doesn't necessarily represent an immediate crisis. The United States still leads in many critical areas, including semiconductor design, advanced AI hardware, venture capital, cloud infrastructure, and several of the world's most influential AI research organizations. But leadership is no longer measured simply by who arrives first. It's increasingly measured by who can continue innovating while others rapidly close the gap. That's the challenge now facing the global AI industry. Because once multiple countries begin producing world-class foundation models, competition shifts away from simply proving technical capability. It becomes a race for developers, for enterprise customers, for cloud platforms, for software ecosystems, for robotics, for manufacturing, and ultimately for global influence. Which brings us back to Wall Street, because investors aren't just pricing today's technology, they're trying to predict who will dominate the next decade. And every announcement like Kimi K3 makes that prediction a little more complicated. Whether Kimi K3 ultimately becomes the world's leading AI model is almost beside the point. The bigger story is that China has now produced yet another frontier-level AI system capable of competing with some of the industry's biggest names. Just a few months after DeepSeek surprised the world, Moonshot AI has shown that China's AI momentum wasn't a one-off event. It may be part of a much larger trend. For investors, developers, and governments alike, that's becoming impossible to ignore. The AI race is no longer about a handful of companies in Silicon Valley. It's becoming a truly global competition, with multiple Chinese firms now pushing the boundaries of what's possible. Every new breakthrough raises the stakes, accelerates innovation, and forces competitors to respond even faster. Of course, there are still plenty of questions. Can Moonshot build a thriving developer ecosystem? Will businesses around the world adopt Kimi K3? Can China continue advancing despite restrictions on advanced AI chips? And perhaps the biggest question of all, who will release the next breakthrough that changes the conversation yet again? One thing is certain, the pace of AI development isn't slowing down. If anything, it's accelerating. And if this really is another DeepSeek moment, then the next chapter of the AI race may arrive much sooner than anyone expects. If you enjoyed this video, don't forget to like, subscribe, and turn on notifications so you never miss our latest updates on China's biggest technology breakthroughs and the global AI race. Thanks for watching, and we'll see you in the next one. Most countries announce a big project, spend a decade building it, and then hold a press conference. China announces a big project, builds it in 2 years, and by the time the press conference happens, they are already halfway through the next one. What is happening in China right now is not one mega project, it is dozens of them, running simultaneously, across industries that have nothing to do with each other, all moving at a pace that is genuinely difficult to process when you lay them out side by side. Delivery infrastructure, transportation, automotive engineering, construction, healthcare, agriculture, biometric systems, humanoid robotics, each one of these sectors is being rebuilt from the ground up, and most of the world is only paying attention to one or two of them at a time. This video is about what it looks like when you zoom out and see all of it at once. Let's start somewhere familiar, food delivery, because it is a useful anchor for understanding the broader pace of change. In most countries, food delivery means a person on a motorbike navigating traffic, finding your address and knocking on your door. It works. It is slow. It has not changed much in 30 years. China's Meituan has been deploying autonomous delivery drones across urban areas, already completing hundreds of thousands of successful deliveries. The drones operate on fixed aerial corridors, deposit packages at designated collection points, and achieve delivery windows measured in minutes, rather than the half-hour guesses most people are used to. In rural areas, the challenge is different. Many villages in China sit beyond road infrastructure that supports normal logistics networks. JD.com has been addressing this with heavy-lift cargo drones capable of carrying loads up to 30 kilograms, effectively extending supply chain reach into communities that previously had no access to rapid delivery at all. Remote does not mean disconnected anymore. It just means the drone route is longer. The infrastructure being built around this is not experimental. These are operational networks with real volumes, and they are expanding. China's automotive sector is currently doing something that deserves more sustained attention than it receives in Western media. The scale of autonomous and semi-autonomous capability being deployed into consumer vehicles is genuinely without parallel anywhere else in the world. 2 out of every 3 new vehicles being sold in China this year are equipped with some level of autonomous driving hardware. That is not a projection, it is a current production reality. The number of test vehicles operating on designated autonomous driving corridors across Chinese cities now runs into the tens of thousands, spread across nearly 20 major urban areas. One vehicle that captures where this technology is heading is the Z01. It runs on a dual-chip AI computing platform, delivering over 500 trillion operations per second, feeding data from 11 high-definition cameras, 12 ultrasonic sensors, and 5 radar systems simultaneously. The vehicle's AI assistant can receive voice commands from outside the car and drive itself to the owner's location from up to 2 kilometers away. That is not a demonstration model. That is the production specification. BYD's engineering decisions in this era deserve attention on their own. Their Yangwang U8 SUV uses 4 fully independent electric motors, 1 per wheel, which enables movement modes that are simply impossible in a conventional drivetrain. The vehicle can rotate in place by running opposite wheels in opposing directions. It can move laterally by running all wheels in the same sideways direction. In flood conditions, it can enter water nearly 1.5 meters deep, remain buoyant, and propel itself by wheel spin for up to 30 minutes. This is not a limited production novelty. It is available to buy. At the performance end of BYD's lineup sits the Yangwang U9, a supercar that recently recorded a top speed of just under 500 kilometers per hour, putting it among the fastest production vehicles ever documented. Its active suspension system can raise and lower individual wheels by 75 millimeters in 40 milliseconds, giving the car the ability to absorb obstacles, adjust its stance dynamically at speed, and even execute coordinated movements that look choreographed when demonstrated at low speed. The same company building a car that can boat through floods is also building one of the fastest production vehicles on the planet. Both are electric. Both are available now. One of the persistent objections to electric vehicle adoption has been charging time. Even fast chargers at current standards require meaningful waiting, long enough to matter on a road trip, long enough to be genuinely inconvenient in daily life. BYD's latest battery and charging platform has moved the technical argument to a different place entirely. Their current generation system supports charging at 1 megawatt, 1,000 kilowatts, which delivers approximately 400 kilometers of driving range in 5 minutes of charging. That number reframes the comparison. A 5-minute stop to gain 400 kilometers of range is shorter than the average petrol station visit when you factor in paying, waiting, and moving. The argument that electric vehicles are fundamentally slower to refuel than combustion vehicles no longer holds at this charging rate. The infrastructure to support this is being built out alongside the vehicle capability. The two are developing in parallel, which is how you actually change a market rather than just announcing intentions to change it. The construction sector in China has been quietly undergoing a transformation that rarely gets the attention it deserves. A project in western China recently completed a highway section using a fleet of 100 autonomous haul trucks, each capable of carrying 85 tons of material. The trucks operated continuously, including in temperatures reaching -40 degrees Celsius, without human operators. They were supported by autonomous road rollers and automated paving equipment, guided by GPS and real-time terrain mapping. The outcome of that combination, autonomous excavation, autonomous haulage, autonomous compaction, automated paving, is a highway construction process that runs around the clock regardless of weather or shift schedules, with consistent output that does not degrade with fatigue. China's stated goal is to have several thousand autonomous haul trucks operating across major construction projects by the end of this year. Given the rate at which the pilot deployments have scaled, there is no particular reason to be skeptical of that timeline. There is something worth pausing on here. These machines are building the roads that autonomous vehicles will eventually use. The infrastructure for a robotic future is being constructed by robots. China's maglev train program has been advancing in two parallel tracks: commercial deployment and speed research, and both are producing numbers that are difficult to contextualize against anything in the existing transport landscape. Commercial maglev lines in operation currently achieve speeds well above 400 kilometers per hour, roughly comparable to the fastest conventional high-speed rail. But the research program has been testing at significantly higher velocities. Experimental runs have recorded speeds exceeding 600 kilometers per hour in controlled conditions. At those speeds, the geography of China changes. A journey between Beijing and Shanghai, currently around 5.5 hours by high-speed rail, drops below 3 hours. Distances that currently require domestic flights become competitive with ground transport for the first time. The technology eliminates rail contact entirely. No friction between wheel and track means no track degradation at high speeds, no wheel wear, and a noise profile fundamentally different from conventional rail. The engineering challenges are enormous, but China is further along in addressing them practically, as opposed to theoretically, than any other country. At more than 60 major airports across China, passengers move through security, check-in, baggage drop, and boarding gates using only their face. No ticket printed, no identification card presented, no interaction with staff required, unless the passenger initiates it. The processing speed at optimized checkpoints is approximately 12 seconds per passenger from entry to clearance. Beijing's main international airport has over 600 biometric verification points integrated across its facilities. Shanghai Hongqiao's system handles the complete journey from terminal entrance to aircraft boarding without a single document exchange. The broader facial recognition infrastructure extends beyond transport. More than 200 million cameras are currently installed across China, feeding into systems that identify individuals in real time, flag regulatory violations, and assist law enforcement in tracking specific individuals through public spaces. This is the part of China's technological development that generates the most complex conversation in the West, and understandably so. The capability is extraordinary. The applications raise questions about civil liberties, state surveillance, and the appropriate limits of biometric data collection that have no easy answers. China has moved faster on deployment than on the policy frameworks that would govern its use, which is a tension that will intensify as the technology spreads globally. WeChat Pay's palm recognition payment system is now operational in over 1,500 retail locations across China. Users register their palm, the system maps both surface lines and subcutaneous vein patterns, and then pay by holding their hand above a scanner. The registration takes seconds. The payment takes less than one. The security architecture is more robust than fingerprint recognition, primarily because vein patterns are internal and cannot be lifted from surfaces the user has touched. The error rate is below 1 in a million transactions. Students at universities, commuters on transit systems, and shoppers in regular retail stores are all using it as a primary payment method. The trajectory is toward a payment infrastructure that requires the user to carry nothing at all: no card, no phone, no physical token of any kind. China's robotics industry has moved past the industrial automation phase and into territory that is harder to categorize neatly. Unitree Robotics produces a humanoid robot designated the G1, standing just over 1.30 m, weighing 35 kilograms, with 23 articulated joints. It walks with a gait that closely mimics natural human movement, responds to voice commands, can carry objects, and can perform physical tasks in environments designed for humans rather than machines. The price point sits at $16,000, a figure that, compared to humanoid robots developed elsewhere in the world, is dramatically lower. Their quadruped robot series, four-legged machines roughly the size of a medium dog, has been deployed in actual working environments, including sporting events, police operations, and industrial inspection. The machines navigate autonomously, respond to voice commands, and carry payloads at running speeds. They were used at the Asian Games in Hangzhou to retrieve equipment on the field during competition, operating in front of large crowds without incident. XP Robots in Dalian is doing something more unsettling. They build humanoid robots designed to be visually indistinguishable from humans at conversational distance. Each unit takes approximately 1 month to produce, involves over 140 degrees of motion freedom in the face and body, and achieves a level of realism in skin texture, eye movement, and facial expression that makes extended observation increasingly uncomfortable. They are currently producing over 500 units per year, deployed in museums, hotels, educational institutions, and government facilities. Several units have been built as replicas of historical scientific figures, rendered as functioning, conversational robots that can discuss the subject's life and work. Chinese hospitals have been deploying automation across multiple points in the patient care pathway. Robotic systems now handle blood draws in some facilities, using vein mapping technology to locate and access veins with a precision rate that reduces failed attempts compared to manual techniques. Automated medication dispensing and delivery robots move pharmaceutical orders from pharmacy to ward without human handling. More significantly, telesurgery systems have been used to perform procedures on patients in remote locations with the surgeon operating from a different city. The latency requirements for surgical precision over long-distance connections are extremely demanding, and the fact that this has moved from research to clinical practice is a notable threshold. The AI diagnostic systems being piloted in some facilities are achieving accuracy rates on specific diagnostic tasks that compare favorably with specialist physicians. This is not a replacement argument. It is a capability argument. The availability of diagnostic support that performs at specialist level, in settings where specialists are not geographically accessible, changes what rural and underserved healthcare can look like. Agricultural automation in China has moved well past GPS-guided tractors. Crop spraying drones capable of carrying 100 kilograms of material cover fields at speeds and consistency that manual application cannot match, operating at night and in conditions that restrict human workers. Automated transplanting equipment covers multiple hectares of planting per day with GPS precision that eliminates the spacing inconsistencies inherent in manual planting. Specialized robotic systems for cotton cultivation can cover dozens of hectares daily at a rate many times faster than field workers performing the equivalent task. The economic logic is straightforward. Labor-intensive agricultural tasks are being transferred to machines that operate continuously, do not require rest, and maintain consistent output across an entire working day. The food supply chain that feeds 1.4 billion people is being restructured around this automation at a speed that has significant implications for agricultural labor markets across the region. What strikes me most about laying all of this out in one place is how different it looks from the way it is usually presented. Individual stories about a fast-charging battery or a robot dog are easy to absorb as novelties. The aggregate picture is something different. China is not building one impressive technology. It is building the infrastructure layer that connects all of them. Autonomous vehicles moving on roads built by autonomous machines, through cities monitored by AI systems, carrying goods delivered by drones, to people who pay with their palms, treated by robotic medical systems, and fed by automated farms. That is not a collection of cool gadgets. That is an attempt to rebuild the operating layer of a civilization. Whether every piece of it works as described, whether the social trade-offs involved are ones other societies would accept, and whether the pace is sustainable, those are all legitimate questions. But the ambition and the execution speed are real, and they deserve to be understood clearly rather than dismissed or exaggerated. My question for you is this: which one of these technologies do you think will reach your country first? The ultra-fast EV charging, the autonomous vehicles, or the humanoid robots? Tell me in the comments. I genuinely want to know what people in different parts of the world think the timeline looks like from where they are sitting. If this kind of deep dive breakdown is what you come here for, make sure you are subscribed to Eastern Engine. Hit the subscribe button and turn on notifications. We cover the engineering and technology stories that are reshaping the world, and there is a lot more coming. The pace of development right now means there is a new story worth telling almost every week. Don't miss it. Artificial intelligence has a networking problem. The world is building larger GPU clusters, larger data centers, and increasingly powerful computing systems. But all of those processors must constantly exchange enormous amounts of data. If the network connecting them is too slow, expensive, or power-hungry, even the most advanced AI chips can spend valuable time waiting. Now, China says it has completed a major test of a technology designed to attack that bottleneck. Yangtze Optical Fiber and Cable, better known as YOFC, worked with China Telecom and optical equipment company Decoli to transmit 51.3 terabits of data per second across 206.5 kilometers, or roughly 128 miles. The system reached as much as 1.2 terabits per second on a single wavelength, and it completed the entire distance without electronically regenerating the signal or using remotely pumped amplifiers along the route. But the most unusual part was the cable. Instead of sending light through a conventional solid glass core, the system used hollow core fiber. Most of the light traveled through an air-filled channel surrounded by a carefully designed glass structure. That allows optical signals to move faster and experience far less interaction with the glass itself. YOFC says its technology can reduce latency by approximately 31%, increase optical propagation speed by around 47%, and sharply reduce nonlinear distortion. The question is whether this is simply another impressive telecommunications demonstration, or whether air-filled fiber could become a critical part of the infrastructure connecting the world's largest AI systems. Why normal fiber uses glass? Modern communications depend on fiber optic cables. Internet traffic, cloud services, financial transactions, video streaming, mobile networks, and data center connections all rely on pulses of light traveling through extremely thin strands of glass. Traditional optical fiber contains a solid core made primarily from silica. That core is surrounded by another layer of glass with different optical properties. The structure keeps light confined inside the cable as it travels across long distances. This technology transformed global communications because fiber can carry vastly more information than copper while losing relatively little signal strength. But conventional fiber still has physical limitations. Light does not travel through glass at the same speed that it travels through a vacuum or through air. The refractive properties of silica slow the signal down. In ordinary fiber, optical propagation is typically around 2/3 of the speed of light in a vacuum. That delay may sound insignificant, but over hundreds or thousands of kilometers, microseconds accumulate. For ordinary video streaming, the difference may not matter. For distributed artificial intelligence clusters, financial trading, cloud infrastructure, or scientific computing, small delays can affect performance. Glass also interacts with intense optical signals. As more power and more data channels are pushed through the same fiber, nonlinear effects can distort the signal and limit how much information can be transmitted reliably. Hollow core fiber attempts to avoid those problems by moving most of the light away from solid glass. How hollow core fiber works. The name can be misleading. Hollow core fiber is not simply an empty plastic tube. It is still an advanced glass structure, manufactured with extremely precise geometry. Around the air-filled center are thin glass membranes or tubes arranged to keep light trapped inside the hollow region. The structure reflects and guides the optical signal through the air-filled core, while allowing only a small portion of the light to interact with the surrounding material. Because the light travels primarily through air, it can move significantly faster than it does through solid silica. The lower interaction with glass also reduces several types of distortion. This can allow engineers to send stronger optical signals, use more advanced modulation, and potentially increase the distance between major network equipment. The concept is not completely new. Researchers have studied hollow core fiber for decades. The problem was loss. Early designs allowed too much light to leak out of the core. A signal weakened so quickly that the lower latency was not enough to justify the technology. Conventional fiber remained cheaper, easier to manufacture, easier to connect, and more reliable over long distances. The important change is that hollow core attenuation has been falling. YOFC says its latest fiber has achieved loss as low as 0.04 decibels per kilometer under reported test conditions. That is a critical milestone because low latency only matters commercially if the signal can also survive a useful distance. What China's trial achieved: the new Chinese trial combined high capacity, long distance, and a real cable deployment. The system transmitted an aggregate 51.3 terabits per second across a 206.5 kilometer hollow core fiber span. Aggregate capacity means the total data rate across multiple wavelengths. It does not mean one optical channel carried all 51.3 terabits. The maximum reported rate for an individual wavelength was 1.2 terabits per second. Different colors, or wavelengths of light, can travel through the same fiber simultaneously. This technique is called wavelength division multiplexing. Each wavelength carries its own stream of information. When many channels are combined, the fiber can transport an enormous total volume of data. The companies used a self-developed optimization system to adjust the data rate and optical power of individual wavelengths. That matters because not every channel experiences exactly the same conditions. Rather than forcing every wavelength to operate at one fixed setting, the system could allocate resources more efficiently. The result was a very high total capacity across a long hollow core span. What without repeaters really means, some headlines have suggested that the trial required no signal boosting. That is not completely accurate. The system used conventional erbium-doped fiber amplifiers, commonly called EDFAs. These devices amplify optical signals without first converting the information into an electronic form. What the system avoided was signal regeneration along the 206.5 kilometer span. A regenerator receives a weakened optical signal, converts it into electrical data, cleans and retimes that data, and then creates a new optical signal for the next section of the journey. Regeneration can extend network reach, but it adds equipment, power consumption, cost, latency, and potential failure points. The trial also avoided remotely pumped amplifiers placed at difficult locations along the cable route. So the achievement is not that the light traveled completely unassisted. The achievement is that the companies maintained a 51.3 terabit per second connection across the full span, using optical amplification without needing intermediate electronic regeneration. That makes the result far more relevant to real long-distance networks. Why this matters for AI? An AI cluster is not just a room full of processors. It is a networked system. During model training, thousands of accelerators repeatedly exchange gradients, parameters, activations, and other information. The processors must remain synchronized. If communication takes too long, expensive hardware can sit idle while waiting for data from another machine. Inside one server, this problem is addressed through extremely fast chip-to-chip connections. Inside one rack, specialized networking connects multiple systems. But the AI industry is increasingly moving beyond individual racks and even beyond individual buildings. Power availability may force companies to divide computing infrastructure across several data centers. One location may not have enough electricity, cooling capacity, or physical space to contain an entire cluster. Distributed AI infrastructure therefore needs high-capacity connections between separate buildings or regions. This is where hollow core fiber may become valuable. Lower propagation latency could help distant data centers behave more like one coordinated computing system. Lower optical nonlinearity could allow stronger signals and more data channels. Longer spans without electronic regeneration could reduce network complexity and energy use. Hollow core fiber will not make a slow network switch faster or improve poorly designed software, but it could improve the physical layer carrying information between major computing facilities. The energy question. AI data centers are already placing enormous pressure on electrical grids. The processors consume power. Cooling systems consume power. Memory and storage consume power, and the networking equipment connecting everything also consumes power. Long-distance optical systems require amplifiers, transponders, switches, and sometimes regenerators. If hollow core fiber allows longer distances between regeneration points, operators may be able to remove some equipment from a network route. That could reduce power consumption, maintenance requirements, and physical infrastructure. However, the total savings will depend on the complete network. A faster fiber does not automatically make every attached device more efficient. Transceivers still consume energy. Switches still process traffic. Cooling is still required. Installation costs may also remain high. The strongest case for hollow core fiber may initially appear in networks where latency and capacity are more valuable than the lowest possible cable price. The global race. China is not developing hollow core fiber alone. Microsoft acquired British hollow core specialist Luminicity and has been deploying the technology in parts of its Azure infrastructure. Microsoft has also worked with manufacturing partners to expand production. Researchers associated with Luminicity and the University of Southampton have demonstrated hollow core designs with losses below some long-standing solid core fiber benchmarks. Amazon and other major cloud companies have also examined advanced fiber technologies as data center networks expand. This means the Chinese trial should not be interpreted as proof that China invented the entire field or has permanently defeated Western competitors. It shows that China is building its own manufacturing, deployment, and optical equipment ecosystem around the technology. YOFC says it has established an integrated production chain covering preform manufacturing, fiber drawing, coating, cabling, and testing. The company has also produced a continuous hollow core fiber length exceeding 90 kilometers and participated in multiple pilot or commercial projects. That manufacturing capability may become as important as laboratory performance. A fiber technology cannot transform global networks if it can only be produced in short, fragile pieces. The manufacturing challenge. Conventional fiber has decades of industrial experience behind it. Manufacturers can produce enormous quantities at low cost. Telecommunications companies understand how to install it, splice it, test it, and repair it. The supporting standards and equipment are mature. Hollow core fiber must compete with that entire ecosystem. Its internal geometry is far more complex. Small manufacturing defects can increase optical loss. Joining two hollow core sections can be difficult because the air-filled structures must remain precisely aligned. Connections with conventional fiber can also introduce additional loss. Bending, cabling, environmental stress, and long-term reliability must be effective for most communications. It is inexpensive, reliable, and widely available. Hollow core technology will probably enter the market first where its unique advantages justify the added cost. Where it could be used first. The most obvious early applications are financial networks, major cloud regions, AI data center links, scientific facilities, and telecommunications backbones. High-frequency trading companies pay large amounts of money to reduce network latency by tiny fractions of a second. Cloud providers may value faster communication between separate data centers. AI companies may need to connect clusters located near different power sources. Scientific institutions may use the fiber to transfer enormous data sets or synchronize precision instruments. Military and government networks could also value lower latency and reduced signal distortion. Consumer broadband will probably not be the first major market. Replacing the fiber entering individual homes would be expensive, and most household internet connections are limited by service plans, routers, Wi-Fi, and network congestion rather than the propagation speed of the glass itself. The technology makes more sense in the backbone of the network, where enormous quantities of data travel across long distances. My take is that this trial is important, but not because conventional fiber is suddenly obsolete. Solid core silica fiber will remain the foundation of global communications for many years. It is proven, inexpensive, and good enough for an enormous range of applications. The breakthrough is that hollow core fiber is moving out of small laboratory experiments and into longer commercial scale links. China's 51.3 terabit per second trial demonstrates that an air-filled core can support high-capacity transmission across more than 200 kilometers without electronic regeneration along the span. That is a meaningful engineering result. The technology still faces manufacturing costs, splicing challenges, standardization questions, and competition from improving conventional fiber. But AI is changing the value of network performance. When companies spend billions of dollars on processors, memory, and data centers, the cost of a better cable becomes easier to justify if that cable keeps the entire computing system operating more efficiently. The next AI bottleneck may not be the chip. It may be the connection between the chips. And China has just demonstrated a fiber designed to move that data through air instead of solid glass. So what do you think? Could hollow core fiber become the next major upgrade to global AI infrastructure? Or will manufacturing complexity keep it limited to specialized networks? Let me know your view in the comments. And subscribe to Eastern Engine for more grounded coverage of the chips, factories, and engineering decisions reshaping the global economy. Because the future of computing will not depend only on how fast processors can calculate. It will also depend on how quickly information can move between them. In 1972, an American astronaut climbed back into his lunar module, took one last look at the gray horizon, and left the moon behind. That was the last time any human stood on the surface of another world, 50-some years ago. And ever since, going back has been something the world's biggest space powers have talked about far more than they've actually done. But here's the thing, almost nobody outside the space world is paying attention to. While America's return to the moon keeps slipping, one delay, then another, China has quietly set a date, 2030, and it is hitting its checkpoints one by one, almost exactly on schedule. So the question is no longer whether humans will walk on the moon again. It's who gets there next, and whose flag is planted when they do. Today, let's look at exactly how close China really is, why NASA is genuinely nervous, and whether the country that's never sent a single person to the moon could actually beat the country that's already done it 6 times. Let's start with what China is actually saying, because it would be easy to wave this off as the kind of grand announcement countries love to make and then never follow through on. China's Manned Space Agency has stated, plainly and repeatedly, that it intends to land astronauts on the moon before the year 2030. And recently, officials doubled down, saying the program is on track and that the hardware is, in their words, progressing smoothly. Now, talk is cheap. Plenty of moon promises have come and gone. What makes this one different is that China has spent the last 2 decades building a track record that's almost boringly reliable. They say they'll do a thing, set a date, and then, more often than not, they do it. Consider what they've already pulled off. They've landed robotic missions on the far side of the moon, the side that always faces away from Earth, which no other country had ever soft landed on. They've scooped up lunar soil and flown it back to Earth. They've built and fully staffed their own space station, orbiting right now with crews rotating in and out. This is not a country fumbling towards space. This is a country that has been methodically climbing a ladder, rung by rung, and the top of that ladder is a human footprint on the moon. So what does it actually take to put people on the moon? 3 big pieces of hardware, and China is building all 3 at once. First, the rocket. It's called the Long March 10, a giant 3-stage heavy-lift rocket designed specifically to throw enough mass toward the moon to make a crewed landing possible. Building a rocket this powerful is one of the hardest things any space program can attempt, and only a handful of nations have ever managed it. To put it in perspective, getting a crew to the moon and back isn't like launching a satellite into orbit a few hundred miles up. You have to push a heavy spacecraft nearly 250,000 miles, slow it down, and then have enough power left to bring everyone home. That demands raw muscle that very few rockets in history have ever had, and China is building theirs from the ground up. What's interesting is the approach they've taken. Rather than inventing something wildly experimental, they've scaled up and refined technology they already trust, clustering proven engines together to generate enormous thrust. It's a conservative, methodical design philosophy, and in spaceflight, conservative and methodical is often exactly what gets you to the finish line in one piece. Flashy doesn't matter on the launch pad. Reliable does. Second, the crew spacecraft. It's named Mengzhou. Think of it as China's version of the capsule that carries astronauts out to the moon and safely back home. It's built in 2 parts, one section that brings the crew back to Earth, and another that provides power, propulsion, and life support along the way. It's designed to carry a crew of around 6, which is notable on its own, because more seats means more capability, more scientists, more equipment, more ambition per mission. And critically, parts of it are being designed to be reusable, which is a sign China is thinking past a single heroic landing and toward a sustained program of going back again and again. This capsule has to do something genuinely difficult too. Coming home from the moon, a spacecraft slams into Earth's atmosphere far faster than anything returning from low orbit. We're talking a fiery, high-speed re-entry that demands a heat shield and a guidance system that simply cannot fail. The fact that China is already flight testing this hardware, rather than just sketching it on paper, tells you how far along they really are. And third, the lander itself, named Lanyue, which translates beautifully to embracing the moon. This is the vehicle that would actually carry astronauts down to the surface and back up to lunar orbit. It's reportedly capable of bringing along a small rover, so the crew wouldn't just plant a flag and leave. They'd actually drive across the surface and explore. Think about what that signals. A flag and footprints mission is a photo op. A mission that brings a rover is the beginning of real exploration, covering ground, studying the terrain, scouting for resources. China isn't designing a quick visit, they're designing a foothold. Here's the part that should make you sit up. China says testing on the lander began back in 2024. The crew capsule is already going through prototype flights, and they've laid out a clear sequence: robotic test flights first, then uncrewed system tests, then a joint test mission near the end of the decade, with the crewed landing a year after that. Every piece has a slot on the calendar. They've even talked publicly about testing the emergency escape systems, the hardware that would yank a crew to safety if a launch went wrong, which is the kind of unglamorous safety-first detail that serious programs obsess over and pretenders skip. It's a staircase, and so far, they're walking up it on time. Now, let's talk about the other side of this race, because you can't understand why people are nervous without it. America's plan to return to the moon is called Artemis. And to be clear, Artemis is real, it's serious, and it has made genuine progress. NASA has flown crews around the moon for the first time in 50 years. The ambition is enormous, not just to visit, but to build a lasting presence. A stepping stone towards sending humans all the way to Mars. But Artemis has one persistent problem: delays. The timeline has slipped again and again. A mission that was once aimed at 1 year got pushed to the next, and then the next. At one point, NASA restructured the program entirely, adding an extra test flight before the actual landing, which pushed the boots on the moon moment even further out. The program has run years behind its original schedule and tens of billions of dollars over budget. And it's worth being fair about why these delays happen, because it's not simple incompetence. Part of it is that NASA holds itself to an extraordinarily high safety bar. These are human lives, and the agency carries the memory of past tragedies. Part of it is that the program depends on a web of contractors and commercial partners, each with their own timelines and technical hurdles. And part of it is politics. Budgets shift, administrations change, priorities get rewritten every few years. America's space program has to survive a gauntlet that China's, run by a single centralized state, simply doesn't face in the same way. But the reasons for the delays don't change the result of the delays. And this is where the math gets uncomfortable. On paper, America is still aiming to land first. NASA's leadership has said publicly they intend to be on the surface before China is. But on paper is doing a lot of work in that sentence. Because every time Artemis slips, the gap between America's target and China's 2030 deadline gets thinner. A program that's ahead but keeps sliding backward is, at some point, just a program that's running out of cushion. It's like watching two runners. One has a head start and far more experience, but that runner keeps stopping to retie their shoes, while the other is running at a steady, relentless pace and never breaks stride. The runner in front is still in front, for now, but anyone watching can feel which way the momentum is flowing. So why does this rattle people in Washington? Why not just shrug and say, "We've been to the moon, we'll get there again"? Because in this race, second place has consequences that go way beyond bragging rights. Members of the US Congress have openly warned that the country cannot afford to let China reach the moon first. NASA's own leadership has framed this as a great competition with a rival that has both the will and the means to challenge America in space. Those are not casual words. That's the language of a country that has realized it might actually lose something it assumed it owned. And here's the strategic twist that makes this more than a symbolic contest. Both China and America are aiming for the same destination, the moon's south pole. Why there? Because scientists believe those permanently shadowed craters hold water ice. And water on the moon is everything. You can drink it, you can split it into oxygen to breathe, and into hydrogen for rocket fuel. In other words, whoever establishes a foothold at the lunar south pole first gets first pick of the most valuable real estate off of planet Earth. This isn't about a flag and a photo. It's about who sets the rules for the next era of space, who builds the first base, who controls the best landing sites, who writes the playbook everyone else has to follow. And there's a deeper layer here that's easy to miss. The first moon race, back in the 1960s, was about proving a point. a contest of ideologies between two superpowers, settled the moment a boot hit the dust. This new race is different. It's not about a single symbolic moment, it's about staying. Both sides are talking about permanent bases, long-term presence, and using the moon as a launch pad for going even deeper into space, eventually to Mars. The moon, in this version of the story, isn't the finish line. It's the gas station, the outpost, the high ground. There's also a question of leadership that goes beyond the moon itself. Space achievement has always been a kind of global advertisement, a way of telling the rest of the world, look what our system can do. When a country lands humans on another world, it doesn't just win a scientific prize. It wins prestige, influence, and the ability to pull other nations into its orbit, sometimes literally, by inviting partners onto its missions and into its station. China has been openly courting international partners for its lunar ambitions. Every country that signs on with China is a country not signing on with America, and vice versa. The moon, in that sense, has become a stage where a much larger competition plays out. That's why a country that already won the moon race once is suddenly very, very focused on not coming in second the second time around. Now I want to show you the moment that, to me, really captures how serious China is, and most people scrolled right past it. Recently, China launched a fresh crew to its space station. Routine on the surface, but buried in the details was something remarkable. One of those crew members is expected to stay in orbit for roughly a year, the longest single human spaceflight in China's history. Why does that matter for the moon? Because going to the moon and building a presence there means keeping humans healthy in space for long, grueling stretches. Long-duration missions are how you prove your life support systems, your food, your radiation protection, your crew's bodies can take the punishment. Every long stay in orbit is a rehearsal for something bigger. And it's not just the crewed flights. Look at how often China is launching anything into orbit. They went from around 68 orbital launches in 1 year to more than 90 the next, and they're on track for more than 140 in a single year. That's the tempo of a country that has turned spaceflight into something closer to an assembly line, and a fast-moving one. When a space program is launching that often, testing that aggressively, and keeping people in orbit for a year at a time, it tells you something. They're not hoping to reach the moon. They're training for it. Let me zoom out for a second, because I think the single most important thing to understand about China's space program isn't any one rocket or capsule, it's the pattern. For decades, China's approach to space has followed the same quiet rhythm. Announce a clear goal, set a realistic date, build the pieces step by step, and let the results do the talking. No dramatic press conferences promising the impossible. No moonshots in the reckless sense of the word, just a long, patient climb. Look at how the space station came together. They didn't try to build it all at once. They launched a test lab, learned from it, then launched the real modules one at a time, until they had a fully functioning station with crews living aboard. Each step de-risked the next. By the time the hard part arrived, they'd already practiced most of it. The moon program is following that exact same template. Robotic landings came first, including on the far side, which nobody had ever done. Then sample returns, bringing actual lunar material back to Earth, proving they could get to the moon, operate on it, and come home. Now they're building the crude hardware, testing it piece by piece, with a joint rehearsal planned before the real thing. It's the same staircase, just taller. And this is what makes the 2030 target so credible. It's not a number someone picked out of the air to grab headlines. It sits at the top of a sequence that's already mostly built, with each lower step already proven. When a country tells you it'll do something in 5 years, the right question is, have they been doing the work for the last 15? In China's case, the answer is yes. That doesn't make success guaranteed, but it does mean this deadline deserves to be taken seriously, far more seriously than the West has tended to take it. All right, the big question, can China really beat America back to the moon? Let me be honest with you, because that's the whole point of this channel. Nobody knows for certain, and anyone who tells you they're 100% sure is selling something. China still has enormous work ahead. They've never flown a human anywhere near the moon. Every piece of their lunar hardware, the giant rocket, the deep space capsule, the lander, still has to be tested, flown and proven, all within a few short years. That is a brutal timeline, and spaceflight has a long history of humbling anyone who gets cocky. One serious failure could push everything back. But, and this is the part that's hard to argue with, America's biggest enemy in this race might not be China at all. It might be America's own delays. If NASA holds its current schedule, it likely still lands first. If, and that little word has been the weak point in the Artemis program from the beginning. So here's the real shape of it. America is ahead but stumbling. China is behind but sprinting at a steady, disciplined pace. And when you've got one side losing momentum and the other gaining it, the gap doesn't just shrink, it can close all at once. Here's my honest opinion. For whatever it's worth, I don't think this comes down to who has the better engineers, because both sides are extraordinary at what they do. I think it comes down to consistency. China's superpower in this race isn't a magic piece of technology. It's that they pick a date, build the staircase, and climb it without drama. America has more raw capability and more experience, but it keeps tripping over its own budgets, politics, and shifting priorities. And if I'm being straight with you, I think the safe bet is not that China definitely lands first, but that this race is going to be far, far closer than most people in the West assume. The comfortable belief that America obviously wins because it won before, that assumption is exactly what makes a country slow down, and slowing down in a race this tight is the most dangerous thing you can do. Whoever gets there first, one thing is certain, a new era on the moon is coming this decade. And for the first time since Apollo, it genuinely won't be a one-horse race. So now I want to hear from you. Do you think China actually pulls it off and lands on the moon by 2030? Or does America's experience win out in the end? And honestly, does it even matter to you who gets there first, as long as humanity goes back? Drop your answer in the comments. I read them. And the best takes sometimes become whole videos of their own. And if you want to keep up with this race, and everything else happening in China's technology, economy, and space programs as it unfolds, hit that subscribe button and ring the bell. This is Eastern Engine, where we break down the forces shaping the future, clearly and without the hype. New videos regularly, so you'll never miss what's coming next. Thanks for watching. I'll see you in the next one. On March 27, 1989, a room full of Soviet engineers on the Crimean Peninsula sat waiting for a signal that was already overdue. 400 million kilometers away, in orbit around Mars, their spacecraft had just performed what should have been a routine maneuver. It rotated to photograph one of Mars's two small moons. To aim its cameras, it had to swing its main antenna away from Earth and fall silent for a few minutes. The engineers expected that. They knew almost to the minute when the signal should return. The minute came. The signal did not. About 4 hours later, something finally arrived. But it was wrong. It was the garbled, broken kind of pulse a spacecraft sends when it is no longer pointed at anything at all, when it is tumbling helplessly through space. That faint, distorted transmission was the last thing anyone on Earth ever received from the probe. It had crossed the entire solar system to reach Mars and to slip closer to one of its moons than any machine before it. And in its final minutes, circling the red planet, it captured a photograph. What that photograph showed, and what made the spacecraft fall silent at the exact moment it turned to look, became one of the strangest and most disputed episodes in the history of spaceflight. Let's find out what was actually out there. The spacecraft was called Phobos 2, and it carries a distinction most people don't know about. It was the final interplanetary probe the Soviet Union ever designed. To understand why that matters, you have to understand how long the Soviets had been away from Mars. After a string of disappointing Mars probes in the early 1970s, the political leadership had largely lost patience with the red planet. The results weren't impressive enough to justify the enormous cost, and the funding dried up. But the scientists never stopped thinking about it. At the Space Research Institute in Moscow, known by its Russian initials IKI, a group of researchers kept turning the problem over. They knew that to return to Mars, they needed an idea compelling enough to change the leadership's mind. By the end of the 1970s, they had one. The idea was this: don't go to Mars itself. Go to its moons. Mars has two, and they are tiny. The larger is called Phobos, the smaller Deimos. What made Phobos so attractive wasn't only the science, it was the orbit. Phobos circles Mars on a path a chemically powered spacecraft could actually reach without too much difficulty. It was, in a sense, the easy door into the Martian system. And targeting a moon instead of the planet carried one more advantage that mattered enormously in 1980s geopolitics. It let the Soviets do something the Americans hadn't done, rather than repeating something they already had. In early 1985, the government approved the mission, with public announcements following that March. Here is where the human story begins, and it explains everything that follows. The man running the Space Research Institute at the time was a physicist named Roald Sagdiv. His institute had just pulled off the Vega missions, an international effort that had sent Soviet probes past Venus and on toward Halley's Comet in 1986. It was a triumph, and it had placed Sagdiv and his scientists firmly in the spotlight. According to Sagdiv himself, that spotlight created a problem. The leadership of the Soviet rocket industry resented the attention the scientists were receiving. So when the Phobos project was organized, overall control was handed not to the scientists who had conceived it, but to the ministry responsible for building the rockets. In practice, the manufacturer got to dictate terms to the customer. The people who would fly the mission no longer fully controlled how it was built, and there was one more pressure, the one that would haunt the entire story. By the Institute's own estimate, a project this complex needed 6 or 7 years to do properly. They were given 3.5. Remember that number, because it comes back. Yet, for all the rush and rivalry, this was also a hopeful project. It arrived precisely as the Soviet Union was beginning to open to the world, and it became one of the largest international science efforts the Soviets had ever attempted. Scientists from 14 countries contributed, from both sides of the Iron Curtain: Austria, Bulgaria, Hungary, Finland, France, Sweden, the United States, both German states, and institutions of the European Space Agency among them. That openness went remarkably far. In 1987, before either probe had launched, the Soviets displayed full-scale models of the Phobos spacecraft at an air and space show in France. In the final days before launch, Western visitors were invited to tour the Baikonur Cosmodrome itself, including an Apollo astronaut and a delegation from the US Air Force. The old reflexes hadn't entirely vanished. Rank-and-file soldiers were still ordered to swap their uniforms for civilian clothes when foreigners visited, to disguise the military nature of the site. But the direction was unmistakable. This was the Soviet space program trying to step into the light, which is part of what makes everything that came next so painful. Phobos 2 did not fly alone. It had a twin. The plan called for 2 identical probes, Phobos 1 and Phobos 2, launched a few days apart in July 1988, both bound for Mars. The logic was redundancy. If one failed, the other would carry the mission. 2 spacecraft, 2 chances. Phobos 1 lifted off first, on July 7th. For the first weeks, it behaved beautifully. It made its course correction, switched on an X-ray telescope, and photographed the sun, capturing well over 100 images of the solar corona and even catching a solar flare in the act. Then, on September 2nd, during a routine communication session, Phobos 1 simply didn't answer. Here's what happened, and it is one of the most quietly devastating facts in the history of spaceflight. A controller on the ground had sent the spacecraft a long string of commands, a routine package meant to keep the probe stable during an upcoming gap in communications. Somewhere in that string of code, a single character was wrong. One missing digit. Let that sit for a second. Not a hardware fault, not a collision, not a cosmic ray frying a circuit, a typo. That missing digit changed the meaning of the command. Instead of doing what it was supposed to, the code reached into the spacecraft's memory and triggered an old test program. A routine written to check the attitude control system on the ground, which, because there hadn't been enough time before launch, had never been erased from the spacecraft's memory. The test program ran, and the very last thing it did by design was switch off the attitude control system. So that is exactly what Phobos 1 did. 11 million kilometers from home, it shut off the system that kept it oriented. With nothing holding it steady, the spacecraft drifted, slowly nudged off axis by the faint constant pressure of the solar wind. Its solar panels turned away from the sun. The power faded. The batteries emptied. After weeks of trying to revive it, the Soviets declared Phobos 1 lost in early November. The mission had lost half its fleet before reaching Mars. Everything now rested on the second probe. Phobos 2 was built on a brand new platform, a full generation's leap beyond the old Venus probes. At its heart sat a ring-shaped instrument compartment atop a powerful propulsion unit fed by 8 fuel tanks. That propulsion design was so good, it would later live on as a rocket stage called Fregat, which still flies today. But the most important part of Phobos 2 for our story isn't the engine, it's the brain. The spacecraft was controlled by 3 identical onboard computers, working on a principle that sounds almost democratic. For any decision, the 3 computers would effectively vote, and the spacecraft would do whatever at least 2 of the 3 agreed on. The logic was sound. If a stray cosmic ray flipped a bit and made one computer briefly malfunction, the other 2 would outvote it. 3 brains, majority rules, no single point of failure. Hold on to that idea. The mission plan was extraordinary. Phobos 2 would enter a wide orbit around Mars, then gradually tighten it until it circled in step with the moon Phobos itself, eventually flying in formation just 35 kilometers above the surface. Then came the part that made this mission unlike anything before it. Once it had mapped the moon, Phobos 2 was supposed to descend until it hovered just 50 meters above the surface. Not landing, hovering. Landing on Phobos is nearly impossible because the moon's gravity is so feeble that a hard touchdown would simply send a craft bouncing back into space. While hovering, it would fire a laser at the surface, vaporizing a tiny puff of soil into a glowing cloud, then read the light from that cloud to determine exactly what the moon was made of, a way to taste a world without ever touching it. Finally, it would release landers. One designed to hop across the surface on spring-loaded legs, another built to fire a small harpoon into the ground to anchor itself to a moon that barely wanted to hold anything at all. To point its cameras at Phobos, the spacecraft had to turn its body, and turning its body meant swinging its main antenna away from Earth. Every close look at the moon required the probe to stop looking at home. It had done this before, more than once, without trouble. Just file that away. Phobos 2 launched on July 12, 1988. 5 days behind its doomed twin. Almost immediately, it began to show the strain of the rush it had been built in. Remember the 3.5 years versus the 6 or 7 the scientists said they needed. This is where that shortfall started to bite. During the long cruise to Mars, things began to fail. By the time Phobos 2